1.1 What is physics? Humans have always been curious about the world around them. The night sky with its bright celestial objects has fascinated humans since time immemorial. The regular repetitions of the day and night, the annual cycle of seasons, the eclipses, the tides, the volcanoes, the rainbow have always been a source of wonder. The world has an astonishing variety of materials and a bewildering diversity of life and behavior. The inquiring and imaginative human mind has responded to the wonder and awe of nature in different ways. One kind of response from the earliest times has been to observe the physical environment carefully. Look for any meaningful patterns and relations in natural phenomena, and build and use new tools to interact with nature. This human endeavor led, in course of time, to modern science and technology. The word science originates from the Latin verb scientia, meaning to know. The Sanskrit word vijnan and the Arabic word ilm convey similar meaning, namely knowledge. Science, in a broad sense, is as old as human species. The early civilizations of Egypt, India, China, Greece, Mesopotamia and many others made vital contributions to its progress. From the 16th century onwards, great strides were made in science in Europe. By the middle of the 20th century, science had become a truly international enterprise, with many cultures and countries contributing to its rapid growth. What is science and what is the so-called scientific method? Science is a systematic attempt to understand natural phenomena in as much detail and depth as possible, and use the knowledge so gained to predict, modify and control phenomena. Science is exploring, experimenting and predicting from what we see around us. The curiosity to learn about the world, unraveling the secrets of nature is the first step towards the discovery of science. The scientific method involves several interconnected steps: systematic observations, controlled experiments. Qualitative in Chapter 1 Physical World 1.1 What is physics? 1.2 Scope and excitement of physics 1.3 Physics, Technology and Society 1.4 Fundamental Forces in Nature 1.5 Nature of Physical Law Summary Exercises. Physics 2 Quantitative Reasoning, Mathematical Modeling, Prediction and Verification or Falsification of Theories. Speculation and conjecture also have a place in science, but ultimately, a scientific theory, to be acceptable, must be verified by relevant observations or experiments. There is much philosophical debate about the nature and method of science that we need not discuss here. The interplay of theory and observation or experiment is basic to the progress of science. Science is ever dynamic. There is no final theory in science and no unquestioned authority among scientists. As observations improve in detail and precision or experiments yield new results, theories must account for them, if necessary, by introducing modifications. Sometimes the modifications may not be drastic and may lie within the framework of existing theory. For example, when Johannes Kepler (1571–1630) examined the extensive data on planetary motion collected by Tycho Brahe (1546–1601), the planetary circular orbits in heliocentric theory sun at the center of the solar system imagined by Nicholas Copernicus 1473–1543, had to be replaced by elliptical orbits to fit the data better. Occasionally, however, the existing theory is simply unable to explain new observations. This causes a major upheaval in science. In the beginning of the 20th century, it was realized that Newtonian mechanics, till then a very successful theory, could not explain some of the most basic features of atomic phenomena. Similarly, the then accepted wave picture of light failed to explain the photoelectric effect properly. This led to the development of a radically new theory, quantum mechanics, to deal with atomic and molecular phenomena. Just as a new experiment may suggest an alternative theoretical model, a theoretical advance may suggest what to look for in some experiments. The result of experiment of scattering of alpha particles by gold foil, in 1911 by Ernest Rutherford 1871-1937, established the nuclear model of the atom, which then became the basis of the quantum theory of hydrogen atom given in 1913 by Niels Bohr 1885-1962. On the other hand, the concept of antiparticle was first introduced theoretically by Paul Dirac 1902–1984 and 1930 and confirmed 2 years later by the experimental discovery of positron anti-electron by Carl Anderson. Physics is a basic discipline in the category of natural sciences, which also includes other disciplines like chemistry and biology. The word physics comes from a Greek word meaning nature. Its Sanskrit equivalent is bodhiki, that is used to refer to the study of the physical world. A precise definition of this discipline is neither possible nor necessary. We can broadly describe physics as a study of the basic laws of nature and their manifestation in different natural phenomena. The scope of physics is described briefly in the next section. Here we remark on two principal thrusts in physics: unification and reduction. In physics, we attempt to explain diverse physical phenomena in terms of a few concepts and laws. The effort is to see the physical world as manifestation of some universal laws in different domains and conditions. For example, the same law of gravitation given by Newton describes the fall of an apple to the ground, the motion of the moon around the earth and the motion of planets around the sun. Similarly, the basic laws of electromagnetism, Maxwell's equations, govern all electric and magnetic phenomena. The attempts to unify fundamental forces of nature section 1.4 reflect this same quest for unification. A related effort is to derive the properties of a bigger, more complex, system from the properties and interactions of its constituent simpler parts. This approach is called reductionism and is at the heart of physics. For example, the subject of thermodynamics, developed in the 19th century, deals with bulk systems in terms of macroscopic quantities such as temperature, internal energy, entropy, etc. Subsequently, the subjects of kinetic theory and statistical mechanics interpreted these quantities in terms of the properties of the molecular constituents of the bulk system. In particular, the temperature was seen to be related to the average kinetic energy of molecules of the system. 1.2 Scope and excitement of physics. We can get some idea of the scope of physics by looking at its various subdisciplines. Basically, there are two domains of interest, macroscopic and microscopic. The macroscopic domain includes phenomena at the laboratory, terrestrial and astronomical scales. The microscopic domain includes atomic, molecular and nuclear. Physical world. 3 Ampere and Faraday, and encapsulated by Maxwell in his famous set of equations, the motion of a current-carrying conductor in a magnetic field. The response of a circuit to an AC voltage signal, the working of an antenna, the propagation of radio waves in the ionosphere, etc., are problems of electrodynamics. Optics deals with the phenomena involving light, the working of telescopes and microscopes, colors exhibited by thin films, etc., are topics in optics. Thermodynamics, in contrast to mechanics, does not deal with the motion of bodies as a whole. Rather, it deals with systems in macroscopic equilibrium and is concerned with changes in internal energy, temperature, entropy, etc., of the system through external work and transfer of heat. The efficiency of heat engines and refrigerators, the direction of a physical, or you can now see that the scope of physics is truly vast. It covers a tremendous range of magnitude of physical quantities like length, mass, time, energy, etc. At one end, it studies phenomena at the very small scale of length 10-14 meters or even less involving electrons, protons, etc. At the other end, it deals with astronomical phenomena at the scale of galaxies or even the entire universe whose extent is of the order of 1026 meters. The two length scales differ by a factor of 1040 or even more. The range of time scales can be obtained by dividing the length scales by the speed of light, 10-22s to 1018s. The range of masses goes from, say, 10-30 kg mass of an electron to 1055 kilograms mass of known observable universe. Terrestrial phenomena lie somewhere in the middle of this range. Figure 1.1 Theory and experiment go hand in hand in physics and help each other's progress. The alpha scattering experiments of Rutherford gave the nuclear model of the atom. Recently, the domain intermediate between the macroscopic and the microscopic, the so-called mesoscopic physics, dealing with a few tens or hundreds of atoms, has emerged as an exciting field of research. Phenomena. Classical physics deals mainly with macroscopic phenomena and includes subjects like mechanics, electrodynamics, optics and thermodynamics. Mechanics, founded on Newton's laws of motion and the law of gravitation, is concerned with the motion or equilibrium of particles, rigid and deformable bodies, and general systems of particles. The propulsion of a rocket by a jet of ejecting gases, propagation of water waves or sound waves in air, the equilibrium of a bent rod under a load, etc., are problems of mechanics. Electrodynamics deals with electric and magnetic phenomena associated with charged and magnetic bodies. Its basic laws were given by Coulomb, Ørsted, chemical process, etc., are problems of interest in thermodynamics. The microscopic domain of physics deals with the constitution and structure of matter at the minute scales of atoms and nuclei and even lower scales of length and their interaction with different probes such as electrons, photons and other elementary particles. Classical physics is inadequate to handle this domain and quantum theory is currently accepted as the proper framework for explaining microscopic phenomena. Overall, the edifice of physics is beautiful and imposing, and you will appreciate it more as you pursue the subject. Physics. For physics is exciting in many ways. To some people the excitement comes from the elegance and universality of its basic theories. From the fact that a few basic concepts and laws can explain phenomena covering a large range of magnitude of physical quantities. To some others, the challenge in carrying out imaginative new experiments to unlock the secrets of nature, to verify or refute theories, is thrilling. Applied physics is equally demanding. Application and exploitation of physical laws to make useful devices is the most interesting and exciting part and requires great ingenuity and persistence of effort. What lies behind the phenomenal progress of physics in the last few centuries? Great progress usually accompanies changes in our basic perceptions. First, it was realized that for scientific progress, only qualitative thinking, though no doubt important, is not enough. Quantitative measurement is central to the growth of science, especially physics, because the laws of nature happen to be expressible in precise mathematical equations. The second most important insight was that the basic laws of physics are universal. The same laws apply in widely different contexts. Lastly, the strategy of approximation turned out to be very successful. Most observed phenomena in daily life are rather complicated manifestations of the basic laws. Scientists recognize the importance of extracting the essential features of a phenomenon from its less significant aspects. It is not practical to take into account all the complexities of a phenomenon in one go. A good strategy is to focus first on the essential features, discover the basic principles and then introduce corrections to build a more refined theory of the phenomenon. For example, a stone and a feather dropped from the same height do not reach the ground at the same time. The reason is that the essential aspect of the phenomenon, namely free fall under gravity, is complicated by the presence of air resistance. To get the law of free fall under gravity, it is better to create a situation wherein the air resistance is negligible. We can, for example, let the stone and the feather fall through a long evacuated tube. In that case, the two objects will fall almost at the same rate, giving the basic law that acceleration due to gravity is independent of the mass of the object. With the basic law thus found, we can go back to the feather, introduce corrections due to air resistance, modify the existing theory and try to build a more realistic hypothesis, axioms and models. One should not think that everything can be proved with physics and mathematics. All physics, and also mathematics, is based on assumptions, each of which is variously called a hypothesis or axiom or postulate, etc. For example, the universal law of gravitation proposed by Newton is an assumption or hypothesis, which he proposed out of his ingenuity. Before him, there were several observations, experiments and data, on the motion of planets around the Sun, motion of the Moon around the Earth, pendulums, bodies falling towards the Earth, etc. Each of these required a separate explanation, which was more or less qualitative. What the universal law of gravitation says is that if we assume that any two bodies in the universe attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, then we can explain all these observations in one stroke. It not only explains these phenomena, it also allows us to predict the results of future experiments. A hypothesis is a supposition without assuming that it is true. It would not be fair to ask anybody to prove a universal law of gravitation, because it cannot be proved. It can be verified and substantiated by experiments and observations. An axiom is a self-evident truth while a model is a theory proposed to explain observed phenomena. But you need not worry at this stage about the nuances in using these words. For example, next year you will learn about Bohr's model of hydrogen atom, in which Bohr assumed that an electron in the hydrogen atom follows certain rules postulates. Why did he do that? There was a large amount of spectroscopic data before him which no other theory could explain. So Bohr said that if we assume that an atom behaves in such a manner, we can explain all these things at once. Einstein's special theory of relativity is also based on two postulates: the constancy of the speed of electromagnetic radiation and the validity of physical laws in all inertial frame of reference. It would not be wise to ask somebody to prove that the speed of light in vacuum is constant, independent of the source or observer. In mathematics too, we need axioms and hypotheses at every stage. Euclid's statement that parallel lines never meet is a hypothesis. This means that if we assume this statement, we can explain several properties of straight lines and two- or three-dimensional figures made out of them. But if you don't assume it, you are free to use a different axiom and get a new geometry, as has indeed happened in the past few centuries and decades. Physical World 5 Table 1.1 Some physicists from different countries of the world and their major contributions. Theory of objects falling to the Earth under gravity. 1.3 Physics, Technology and Society. The connection between physics, technology and society can be seen in many examples. The discipline of thermodynamics arose from the need to understand and improve the working of heat engines. The steam engine, as we know, is inseparable from the Industrial Revolution in England in the 18th century, which had great impact on the course of human civilization. Sometimes technology gives rise to new physics, at other times physics generates new technology. An example of the latter is the wireless communication technology that followed the discovery of the basic laws of electricity and magnetism in the 19th century. The applications of physics are not always easy to foresee. As late as 1933, the great physicist Ernest Rutherford had dismissed the possibility of tapping energy from atoms. But only a few years later, in 1938, Hahn and Meitner discovered the phenomenon of neutron-induced fission of uranium, which would serve as the basis of nuclear power reactors and nuclear weapons. Yet another important example of physics giving rise to technology is the silicon chip that triggered the computer revolution in the last 3 decades of the 20th century. A most significant area to which physics has and will contribute is the development of alternative energy resources. The fossil fuels of the planet are dwindling fast and there is an urgent need to discover new and affordable sources of energy. Considerable progress has already been made in this direction, for example, in conversion of solar energy, geothermal energy, etc., into electricity, but much more is still to be accomplished. Table 1.1 lists some of the great physicists, their major contribution and the country of origin. You will appreciate from this table the multicultural, international character of the scientific endeavor. Table 1.2 lists some important technologies and the principles of physics they are based on. Obviously, these tables are not exhaustive. We urge you to try to add many names and items to these tables with the help of your teachers, good books and websites on science. You will find that this exercise is very educative and also great fun, and, assuredly, it will never end. The progress of science is unstoppable. Physics is the study of nature and natural phenomena. Physicists try to discover the rules that are operating in nature, on the basis of observations, experimentation and analysis. Physics deals with certain basic rules, laws governing the natural world. What is the nature name? Major contribution. Discovery. Country of origin. Archimedes. Principle of buoyancy. Principle of the lever. Greece. Galileo Galilei. Law of inertia. Italy. Christian Huygens. Wave theory of light. Holland. Isaac Newton. Universal law of gravitation. Laws of motion. UK. Reflecting telescope. Michael Faraday. Laws of electromagnetic induction. UK. James Clerk Maxwell. Electromagnetic theory, Leiden, UK. Electromagnetic wave. Heinrich Rudolf Hertz. Generation of electromagnetic waves. Germany. J.C. Bose. Ultra-short radio waves. India, WK. Röntgen. X-rays. Germany. J.J. Thomson. Electron, UK. Marie Sklodowska-Curie. Discovery of radium and polonium. Studies on Poland. Natural radioactivity. Albert Einstein. Explanation of photoelectric effect, Germany. Theory of relativity. Physics 6 sections 1.4 and 1.5 contain several ideas that you may not grasp fully in your first reading. However, we advise you to read them carefully to develop a feel for some basic aspects of physics. These are some of the areas which continue to occupy the physicists today. At physical laws, we shall now discuss the nature of fundamental forces and the laws that govern the diverse phenomena of the physical world. 1.4 Fundamental forces in nature. We all have an intuitive notion of force. In our experience, force is needed to push, carry or throw objects, deform or break them. We also experience the impact of forces on us, like when a moving object hits us or we are in a merry-go-round. Going from this intuitive notion to the proper scientific concept of force is not a trivial matter. Early thinkers like Aristotle had wrong ideas about it. The correct notion of force was arrived at by Isaac Newton in his famous laws of motion. He also gave an explicit form for the force for gravitational attraction between two bodies. We shall learn these matters in subsequent chapters. In the macroscopic world, besides the gravitational force, we encounter several kinds of forces. Muscular force, contact forces between bodies, friction, which is also a contact force parallel to the surfaces in contact. The forces exerted by compressed or elongated springs and taut strings and ropes. Tension, the force of buoyancy and viscous force when solids are in. Victor Francis Hess. Cosmic radiation. Austria. R.A. Millikan. Measurement of electronic charge. USA. Ernest Rutherford. Nuclear model of atom. New Zealand. Niels Bohr. Quantum model of hydrogen atom. Denmark. C.V. Raman. Inelastic scattering of light by molecules. India. Louis Victor de Broglie. Wave nature of matter. France. M.N. Saha. Thermal ionization. India. S.N. Bose. Quantum statistics. India. Wolfgang Pauli. Exclusion principle. Austria. Enrico Fermi. Controlled nuclear fission. Italy. Werner Heisenberg. Quantum mechanics, uncertainty principle. Germany. Paul Dirac. Relativistic theory of electron, UK. Quantum statistics. Edwin Hubble. Expanding universe. USA. Ernest Orlando Lawrence. Cyclotron. USA. James Chadwick. Neutron. UK. Hideki Yukawa. Theory of nuclear forces. Japan. Homi Jehangir Babha. Cascade process of cosmic radiation. India. Lev Davidovich Landau. Theory of condensed matter, liquid helium. Russia. S. Chandrasekhar Limit, structure and evolution. India. Of stars. John Bardeen. Transistors, theory of superconductivity. USA. Ch. Towns Maser, Laser USA Abdus Salam Unification of Weakened Electromagnetic Pakistan Interactions Name Major Contribution Discovery Country of Origin Physical World 7 Contact with fluids, the force due to pressure of a fluid, the force due to surface tension of a liquid, and so on. There are also forces involving charged and magnetic bodies. In the microscopic domain again, we have electric and magnetic forces, nuclear forces involving protons and neutrons, interatomic and intermolecular forces, etc. We shall get familiar with some of these forces in later parts of this course. A great insight of the 20th century physics is that these different forces occurring in different contexts actually arise from only a small number of fundamental forces in nature. For example, the elastic spring force arises due to the net attraction-repulsion between the neighboring atoms of the spring when the spring is elongated compressed. This net attraction-repulsion can be traced to the unbalanced sum of electric forces between the charged constituents of the atoms. In principle, this means that the laws for derived forces such as spring force, friction are not independent of the laws of fundamental forces in nature. The origin of these derived forces is, however, very complex, at the present stage of our understanding. We know of 4 fundamental forces in nature, which are described in brief here. Table 1.2 Link between technology and physics. Technology. Scientific principle S. Steam engine. Laws of thermodynamics. Nuclear reactor. Controlled nuclear fission. Radio and television. Generation, propagation and detection of electromagnetic waves. Computers. Digital logic. Lasers. Light amplification by stimulated emission of radiation. Production of ultra-high magnetic superconductivity fields. Rocket propulsion. Newton's laws of motion. Electric generator. Faraday's laws of electromagnetic induction. Hydroelectric power. Conversion of gravitational potential energy into electrical energy. Aeroplane. Bernoulli's principle in fluid dynamics. Particle accelerators. Motion of charged particles in electromagnetic fields. Sonar. Reflection of ultrasonic waves. Optical fibers. Total internal reflection of light. Non-reflecting coatings. Thin film. Optical interference. Electron microscope. Wave. Nature of electrons. Photocell. Photoelectric effect. Fusion test reactor. Tokamak. Magnetic confinement of plasma. Giant metrowave. Radio detection of cosmic radio waves. Telescope. GMRT. Bose-Einstein condensate. Trapping and cooling of atoms by laser beams and magnetic fields. 1 Gravitational force. The gravitational force is the force of mutual attraction between any two objects by virtue of their masses. It is a universal force. Every object experiences this force due to every other object in the universe. All objects on the Earth, for example, experience the force of gravity due to the Earth, in particular. Gravity governs the motion of the Moon and artificial satellites around the Earth, motion of the Earth and planets around the Sun, and, of course, the motion of bodies falling to the Earth. It plays a key role in the large-scale phenomena of the universe, such as formation and evolution of stars, galaxies and galactic clusters. 2 Electromagnetic force. Electromagnetic force is the force between charged particles. In the simpler case when charges are at rest, the force is given by Coulomb's law, attractive for unlike charges and repulsive for like charges. Charges in motion produce magnetic effects and a magnetic field gives rise to a force on a moving charge. Electric and magnetic effects are, in general, inseparable, hence the name electromagnetic force. Like the gravitational force, electromagnetic force acts over large distances and does not need any intervening medium. It is enormously strong compared to gravity. The electric force between two protons, for example, is 1036 times the gravitational force between them, for any fixed distance. Matter, as we know, consists of elementary charged constituents like electrons and protons. Since the electromagnetic force is so much stronger than the gravitational force, it dominates all phenomena at atomic and molecular scales. The other two forces, as we shall see, operate only at nuclear scales. Thus it is mainly the electromagnetic force that governs the structure of atoms and molecules, the dynamics of chemical reactions and the mechanical, thermal and other properties of materials. It underlies the macroscopic forces like tension, friction, normal force, spring force, etc. Gravity is always attractive, while electromagnetic force can be attractive or repulsive. Another way of putting it is that mass comes only in one variety. There is no negative mass, but charge comes in two varieties, positive and negative charge. This is what makes all the difference. Matter is mostly electrically neutral, net charge is zero. Thus, electric force is largely zero and gravitational force dominates terrestrial phenomena. Electric force manifests itself in atmosphere where the atoms are ionized, and that leads to lightning. Albert Einstein 1879–1955. Albert Einstein, born in Ulm, Germany in 1879, is universally regarded as one of the greatest physicists of all time. His astonishing scientific career began with the publication of 3 path-breaking papers in 1905. In the first paper, he introduced the notion of light quanta, now called photons, and used it to explain the features of photoelectric effect that the classical wave theory of radiation could not account for. In the second paper, he developed a theory of Brownian motion that was confirmed experimentally a few years later and provided a convincing evidence of the atomic picture of matter. The third paper gave birth to the special theory of relativity that made Einstein a legend in his own lifetime. In the next decade, he explored the consequences of his new theory, which included, among other things, the mass-energy equivalence enshrined in his famous equation EMC2. He also created the general version of relativity, the general theory of relativity, which is the modern theory of gravitation. Some of Einstein's most significant later contributions are the notion of stimulated emission introduced in an alternative derivation of Planck's blackbody radiation law, static model of the universe which started modern cosmology, quantum statistics of a gas of massive bosons, and a critical analysis of the foundations of quantum mechanics. The year 2005 was declared as International Year of Physics, in recognition of Einstein's monumental contribution to physics, in year 1905, describing revolutionary scientific ideas that have since influenced all of modern physics. Physical World 9. If we reflect a little, the enormous strength of the electromagnetic force compared to gravity is evident in our daily life. When we hold a book in our hand, we are balancing the gravitational force on the book due to the huge mass of the Earth by the normal force provided by our hand. The latter is nothing but the net electromagnetic force between the charged constituents of our hand and the book, at the surface in contact. If electromagnetic force were not intrinsically so much stronger than gravity, the hand of the strongest man would crumble under the weight of a feather, indeed. To be consistent, in that circumstance, we ourselves would crumble under our own weight. 1, 4, 3 strong nuclear force. The strong nuclear force binds protons and neutrons in a nucleus. It is evident that without some attractive force, a nucleus will be unstable due to the electric repulsion between its protons. This attractive force cannot be gravitational since force of gravity is negligible compared to the electric force. A new basic force must, therefore, be invoked. The strong nuclear force is the strongest of all fundamental forces, about 100 times the electromagnetic force in strength. It is charge independent and acts equally between a proton and a proton, a neutron and a neutron, and a proton and a neutron. Its range is, however, extremely small, of about nuclear dimensions 10-15 m. It is responsible for the stability of nuclei. The electron, it must be noted, does not experience this force. Recent developments have, however, indicated that protons and neutrons are built out of still more elementary constituents called quarks. 1. 4. Weak nuclear force. The weak nuclear force appears only in certain nuclear processes such as the Greek letter beta decay of a nucleus. In Greek letter beta decay, the nucleus emits an electron and an uncharged particle called neutrino. The weak nuclear force is not as weak as the gravitational force, but much weaker than the strong nuclear and electromagnetic forces. The range of weak nuclear force is exceedingly small, of the order of 10-16 meters. 1, 4, 5. Towards unification of forces. We remarked in section 1.1 that unification is a basic quest in physics. Great advances in physics often amount to unification of different. Satyendranath Bose 1894–1974. Satyendranath Bose, born in Calcutta in 1894, is among the great Indian physicists who made a fundamental contribution to the advance of science in the 20th century. An outstanding student throughout, Bose started his career in 1916 as a lecturer in physics in Calcutta University. 5 years later he joined Dhaka University. Here in 1924, in a brilliant flash of insight, Bose gave a new derivation of Planck's law, treating radiation as a gas of photons and employing new statistical methods of counting of photon states. He wrote a short paper on the subject and sent it to Einstein, who immediately recognized its great significance, translated it in German and forwarded it for publication. Einstein then applied the same method to a gas of molecules. The key new conceptual ingredient in Bose's work was that the particles were regarded as indistinguishable. A radical departure from the assumption that underlies the classical Maxwell-Boltzmann statistics. It was soon realized that the new Bose-Einstein statistics was applicable to particles with integer spins. And a new quantum statistics, Fermi-Dirac statistics, was needed for particles with half-integer spins, satisfying Pauli's exclusion principle. Particles with integer spins are now known as bosons in honor of Bose. An important consequence of Bose-Einstein statistics is that a gas of molecules below a certain temperature will undergo a phase transition to a state where a large fraction of atoms populate the same lowest energy state. Some 70 years were to pass before the pioneering ideas of Bose, developed further by Einstein, were dramatically confirmed in the observation of a new state of matter in a dilute gas of ultracold alkali atoms, the Bose-Einstein condensate. Physics 10 Theories and Domains. Newton unified terrestrial and celestial domains under a common law of gravitation. The experimental discoveries of Ørsted and Faraday showed that electric and magnetic phenomena are in general inseparable. Maxwell unified electromagnetism and optics with the discovery that light is an electromagnetic wave. Einstein attempted to unify gravity and electromagnetism but could not succeed in this venture, but this did not deter physicists from zealously pursuing the goal of unification of forces. Recent decades have seen much progress on this front. The electromagnetic and the weak nuclear force have now been unified and are seen as aspects of a single electroweak force. What this unification actually means cannot be explained here. Attempts have been and are being made to unify the electroweak and the strong force and even to unify the gravitational force with the rest of the fundamental forces. Many of these ideas are still speculative and inconclusive. Table 1.4 summarizes some of the milestones in the progress towards unification of forces in nature. 1.5 Nature of physical laws. Physicists explore the universe. Their investigations, based on scientific processes, range from particles that are smaller than atoms in size to stars that are very far away. In addition to finding the facts by observation and experimentation, physicists attempt to discover the laws that summarize often as mathematical equations these facts. In any physical phenomenon governed by different forces, several quantities may change with time. A remarkable fact is that some special physical quantities, however, remain constant in time. They are the conserved quantities of nature. Understanding these conservation principles is very important to describe the observed phenomena quantitatively. For motion under an external conservative force, the total mechanical energy, that is the sum of kinetic and potential energy of a body, is a constant. The familiar example is the free fall of an object under gravity. Both the kinetic energy of the object and its potential energy change continuously with time, but the sum remains fixed. If the object is released from rest. The initial Table 1.4 Progress in unification of different forces domains in nature. Table 1.3 Fundamental forces of nature. Name relative range operates among strength gravitational force 10-39 infinite all objects in the universe weak nuclear force 10-13 very short subnuclear some elementary particles size 10-16 m particularly electron and neutrino electromagnetic force 10-2 infinite charged particles strong nuclear force 1 short nuclear nucleons heavier size 10-15 m elementary particles 2018 1 Physical world 11 Potential energy is completely converted into the kinetic energy of the object just before it hits the ground. This law restricted for a conservative force should not be confused with the general law of conservation of energy of an isolated system, which is the basis of the first law of thermodynamics. The concept of energy is central to physics and the expressions for energy can be written for every physical system. When all forms of energy, e.g., heat, mechanical energy, electrical energy, etc., are counted, it turns out that energy is conserved. The general law of conservation of energy is true for all forces and for any kind of transformation between different forms of energy. In the falling object example, if you include the effect of air resistance during the fall and see the situation after the object hits the ground and stays there, the total mechanical energy is obviously not conserved. The general law of energy conservation, however, is still applicable. The initial potential energy of the stone gets transformed into other forms of energy, heat and sound. Ultimately, sound after it is absorbed becomes heat. The total energy of the system stone plus the surroundings remains unchanged. The law of conservation of energy is thought to be valid across all domains of nature, from the microscopic to the macroscopic. It is routinely applied in the analysis of atomic, nuclear and elementary particle processes. At the other end, all kinds of violent phenomena occur in the universe all the time. Yet the total energy of the universe, the most ideal isolated system possible, is believed to remain unchanged. Until the advent of Einstein's theory of relativity, the law of conservation of mass was regarded as another basic conservation law of nature, since matter was thought to be indestructible. It was and still is an important principle used, for example, in the analysis of chemical reactions. A chemical reaction is basically a rearrangement of atoms among different molecules. If the total binding energy of the reacting molecules is less than the total binding energy of the product molecules, the difference appears as heat and the reaction is exothermic. The opposite is true for energy-absorbing endothermic reactions. However, since the atoms are merely rearranged but not destroyed, the total mass of the reactants is the same as the total mass of the products in a chemical reaction. The changes in the binding energy are too small to be measured as changes in mass. According to Einstein's theory, mass m is equivalent to energy E given by the relation E/2, where c is speed of light in vacuum. In a nuclear process, mass gets converted to energy or vice versa. This is the energy which is released in a nuclear power generation and nuclear explosions. Sir C.V. Raman 1888–1970 Chandrasekhara Venkata Raman was born on November 7, 1888 in Thiruvananthapuram. He finished his schooling by the age of 11. He graduated from Presidency College, Madras. After finishing his education he joined financial services of the Indian government. While in Kolkata, he started working on his area of interest at Indian Association for Cultivation of Science founded by Dr. Mahendralal Sarkar. During his evening hours, his area of interest included vibrations, variety of musical instruments, ultrasonics, diffraction and so on. In 1917 he was offered professorship at Calcutta University. In 1924 he was elected Fellow of the Royal Society of London and received Nobel Prize in Physics in 1930 for his discovery, now known as Raman effect. The Raman effect deals with scattering of light by molecules of a medium when they are excited to vibrational energy levels. This work opened totally new avenues for research for years to come. He spent his later years at Bangalore, first at Indian Institute of Science and then at Raman Research Institute. His work has inspired generation of young students. Physics 12 Energy is a scalar quantity, but all conserved quantities are not necessarily scalars. The total linear momentum and the total angular momentum, both vectors of an isolated system, are also conserved quantities. These laws can be derived from Newton's laws of motion in mechanics, but their validity goes beyond mechanics. They are the basic conservation laws of nature in all domains, even in those where Newton's laws may not be valid. Besides their great simplicity and generality, the conservation laws of nature are very useful in practice too. It often happens that we cannot solve the full dynamics of a complex problem involving different particles and forces. The conservation laws can still provide useful results. For example, we may not know the complicated forces that act during a collision of two automobiles, yet momentum conservation law enables us to bypass the complications and predict or rule out possible outcomes of the collision. In nuclear and elementary particle phenomena also, the conservation laws are important tools of analysis. Indeed, using the conservation laws of energy and momentum for Greek letter beta decay, Wolfgang Pauli 1900–1958 correctly predicted in 1931 the existence of a new particle now called neutrino emitted in Greek letter beta decay along with the electron. Conservation laws have a deep connection with symmetries of nature that you will explore in more advanced courses in physics. For example, an important observation is that the laws of nature do not change with time. If you perform an experiment in your laboratory today and repeat the same experiment on the same objects under identical conditions after a year, the results are bound to be the same. It turns out that this symmetry of nature with respect to translation, that is displacement in time, is equivalent to the law of conservation of energy. Likewise, space is homogeneous and there is no intrinsically preferred location in the universe. To put it more clearly, the laws of nature are the same everywhere in the universe. Caution: the phenomena may differ from place to place because of differing conditions at different locations. For example, the acceleration due to gravity at the Moon is 1/6 that at the Earth, but the law of gravitation is the same both on the Moon and the Earth. This symmetry of the laws of nature with respect to translation in space gives rise to conservation of linear momentum. In the same way, isotropy of space, no intrinsically preferred direction in space, underlies the law of conservation of angular momentum. The conservation laws of charge and other attributes of elementary particles can also be related to certain abstract symmetries. Symmetries of space and time and other abstract symmetries play a central role in modern theories of fundamental forces in nature. See Chapter 7 Conservation Laws in Physics. Conservation of energy, momentum, angular momentum, charge, etc. are considered to be fundamental laws in physics. At this moment, there are many such conservation laws. Apart from the above four, there are others which mostly deal with quantities which have been introduced in nuclear and particle physics. Some of the conserved quantities are called spin, baryon number, strangeness, hypercharge, etc., but you need not worry about them. A conservation law is a hypothesis, based on observations and experiments. It is important to remember that a conservation law cannot be proved. It can be verified, or disproved, by experiments. An experiment whose result is in conformity with the law verifies or substantiates the law. It does not prove the law. On the other hand, a single experiment whose result goes against the law is enough to disprove it. It would be wrong to ask somebody to prove the law of conservation of energy. This law is an outcome of our experience over several centuries. And it has been found to be valid in all experiments, in mechanics, thermodynamics, electromagnetism, optics, atomic and nuclear physics, or any other area. Some students feel that they can prove the conservation of mechanical energy from a body falling under gravity by adding the kinetic and potential energies at a point and showing that it turns out to be constant. As pointed out above, this is only a verification of the law, not its proof. Physical World 13 Summary 1. Physics deals with the study of the basic laws of nature and their manifestation in different phenomena. The basic laws of physics are universal and apply in widely different contexts and conditions too. The scope of physics is wide, covering a tremendous range of magnitude of physical quantities. 3. Physics and technology are related to each other. Sometimes technology gives rise to new physics, at other times physics generates new technology. Both have direct impact on society. 4. There are 4 fundamental forces in nature that govern the diverse phenomena of the macroscopic and the microscopic world. These are the gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Unification of different forces domains in nature is a basic quest in physics. 5. The physical quantities that remain unchanged in a process are called conserved quantities. Some of the general conservation laws in nature include the laws of conservation of mass, energy, linear momentum, angular momentum, charge, parity, etc. Some conservation laws are true for one fundamental force but not for the other 6. Conservation laws have a deep connection with symmetries of nature. Symmetries of space and time, and other types of symmetries play a central role in modern theories of fundamental forces in nature. Exercises. Note for the student: the exercises given here are meant to enhance your awareness about the issues surrounding science, technology and society, and to encourage you to think and formulate your views about them. The questions may not have clear-cut objective answers. Note for the teacher: the exercises given here are not for the purpose of a formal examination. 1.1 Some of the most profound statements on the nature of science have come from Albert Einstein, one of the greatest scientists of all time. What do you think did Einstein mean when he said, "The most incomprehensible thing about the world is that it is comprehensible"? 1.2 Every great physical theory starts as a heresy and ends as a dogma. Give some examples from the history of science of the validity of this incisive remark. 1.3 Politics is the art of the possible. Similarly, science is the art of the soluble. Explain this beautiful aphorism on the nature and practice of science. 1.4 Though India now has a large base in science and technology, which is fast expanding, it is still a long way from realizing its potential of becoming a world leader in science. Name some important factors, which in your view have hindered the advancement of science in India. 1.5 No physicist has ever seen an electron, yet, all physicists believe in the existence of electrons. An intelligent but superstitious man advances this analogy to argue that ghosts exist even though no one has seen one. How will you refute his argument? 1.6 The shells of crabs found around a particular coastal location in Japan seem mostly to resemble the legendary face of a samurai. Given below are 2 explanations of this observed fact. Which of these strikes you as a scientific explanation? A tragic sea accident several centuries ago drowned a young samurai. As a tribute to his bravery, nature through its inscrutable ways immortalized his face by imprinting it on the crab shells in that area. Physics 14b After the sea tragedy, fishermen in that area, in a gesture of honor to their dead hero, let free any crab shell caught by them which accidentally had a shape resembling the face of a samurai. Consequently, the particular shape of the crab shell survived longer and therefore in course of time the shape was genetically propagated. This is an example of evolution by artificial selection. Note, this interesting illustration taken from Carl Sagan's The Cosmos highlights the fact that often strange and inexplicable facts which on the first sight appear supernatural actually turn out to have simple scientific explanations. Try to think out other examples of this kind. 1.7 The Industrial Revolution in England and Western Europe more than 2 centuries ago was triggered by some key scientific and technological advances. What were these advances? 1.8 It is often said that the world is witnessing now a second industrial revolution, which will transform the society as radically as did the first. List some key contemporary areas of science and technology, which are responsible for this revolution. 1.9 Write in about 1,000 words a fiction piece based on your speculation on the science and technology of the 22nd century. 1.10 Attempt to formulate your moral views on the practice of science. Imagine yourself stumbling upon a discovery, which has great academic interest but is certain to have nothing but dangerous consequences for the human society. How, if at all, will you resolve your dilemma? 1.11 Science, like any knowledge, can be put to good or bad use, depending on the user. Given below are some of the applications of science. Formulate your views on whether the particular application is good, bad or something that cannot be so clearly categorized. A mass vaccination against smallpox to curb and finally eradicate this disease from the population. This has already been successfully done in India. B. Television for eradication of illiteracy and for mass communication of news and ideas. C. Prenatal sex determination. D. Computers for increasing work efficiency. E. Putting artificial satellites into orbits around the Earth. F. Development of nuclear weapons. G. Development of new and powerful techniques of chemical and biological warfare. H. Purification of water for drinking. I. Plastic surgery. J. Cloning. 1.12 India has had a long and unbroken tradition of great scholarship in mathematics, astronomy, linguistics, logic and ethics. Yet, in parallel with this, several superstitious and obscurantistic attitudes and practices flourished in our society and unfortunately continue even today among many educated people too. How will you use your knowledge of science to develop strategies to counter these attitudes? 1.13 Though the law gives women equal status in India, many people hold unscientific views on a woman's innate nature, capacity and intelligence, and in practice give them a secondary status and role. Demolish this view using scientific arguments, and by quoting examples of great women in science and other spheres, and persuade yourself and others that, given equal opportunity, women are on par with men. 1.14 It is more important to have beauty in the equations of physics than to have them agree with experiments. The great British physicist P.A.M. Dirac held this view. Criticize this statement. Look out for some equations and results in this book which strike you as beautiful. 1.15 Though the statement quoted above may be disputed, most physicists do have a feeling that the great laws of physics are at once simple and beautiful. Some of the notable physicists, besides Dirac, who have articulated this feeling, are Einstein, Bohr, Heisenberg, Chandrasekhar and Feynman. You are urged to make special efforts to get Physical World 15 access to the general books and writings buddies and other great masters of physics. See the bibliography at the end of this book. Their writings are truly inspiring. 1.16 Textbooks on science may give you a wrong impression that studying science is dry and all too serious and that scientists are absent-minded introverts who never laugh or grin. This image of science and scientists is patently false. Scientists, like any other group of humans, have their share of humorists, and many had led their lives with a great sense of fun and adventure, even as they seriously pursued their scientific work. Two great physicists of this genre are Gamow and Feynman. You will enjoy reading their books listed in the bibliography. 2018 1. Chapter 2 Units and Measurement 2.1 Introduction Measurement of any physical quantity involves comparison with a certain basic, arbitrarily chosen, internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number or numerical measure accompanied by a unit. Although the number of physical quantities appears to be very large, we need only a limited number of units for expressing all the physical quantities, since they are interrelated with one another. The units for the fundamental or base quantities are called fundamental or base units. The units of all other physical quantities can be expressed as combinations of the base units. Such units obtained for the derived quantities are called derived units. A complete set of these units, both the base units and derived units, is known as the system of units. 2.2 The international system of units. In earlier times, scientists of different countries were using different systems of units for measurement. Three such systems, the CGS, the FPS or British system and the MK system, were in use extensively till recently. The base units for length, mass and time in these systems were as follows. In CGS system they were centimeter, gram and second respectively. In FPS system they were foot, pound and second respectively. In MK system they were meter, kilogram and second respectively. The system of units which is at present internationally accepted for measurement is the System International de Unites, French for International System of Units, abbreviated as SI. The SI, with standard scheme of symbols, units and abbreviations, was developed and recommended by General Conference on Weights and Measures in 1971 for 2.1 Introduction. 2.2 The International System of Units. 2.3 Measurement of length. 2.4 Measurement of mass. 2.5 Measurement of time. 2.6 Accuracy, precision of instruments and errors in measurement. 2.7 Significant figures. 2.8 Dimensions of physical quantities. 2.9 Dimensional formulae and dimensional equations. 2.10 Dimensional analysis and its application. Summary exercises. Additional exercises. International usage in scientific, technical, industrial and commercial work. Because SI units use decimal system, conversions within the system are quite simple and convenient. We shall follow the SI units in this book. In SI, there are 7 base units as given in Table 2.1. Besides the 7 base units, there are 2 more units that are defined for a plane angled as the ratio of length of arc ds to the radius r and b solid angled as the ratio of the intercepted area of the spherical surface, described about the apex O as the center, to the square of its radius r, as shown in Fig. 2.1 and b respectively. The unit for plane angle is radian with the symbol rad and the unit for the solid angle is steradian with the symbol senior. Both these are dimensionless quantities. Table 2.1 SI base quantities and units. Units and measurement. 17 The values mentioned here need not be remembered or asked in a test. They are given here only to indicate the extent of accuracy to which they are measured. With progress in technology, the measuring techniques get improved, leading to measurements with greater precision. The definitions of base units are revised to keep up with this progress. At B Figure 2.1 Description of a plane angled and B solid angled. Base SI units. Quantity name symbol definition length meter m. The meter is the length of the path traveled by light in vacuum during a time interval of 1/299, 792, 458 of a second. 1983 Mass kilogram kg. The kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at International Bureau of Weights and Measures. At Severs, near Paris, France. 1889 times second s. The second is the duration of 9, 192, 631, 770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. 1967 Electric ampere. A. The ampere is that constant current which, if maintained in current two straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 × 10⁷ Newton per meter of length. 1948 Thermokelvin. K. The Kelvin is the fraction 1/273.16 of the thermodynamic dynamic temperature of the triple point of water. 1967 Temperature amount of mole. The mole is the amount of substance of a system, which contains substance as many elementary entities as there are atoms in 0.012 kg of carbon-12. 1971 Luminous candela. CD. The candela is the luminous intensity, in a given intensity direction, of a source that emits monochromatic radiation of frequency 540 × 1012 Hz and that has a radiant intensity in the direction of 1683 watt per steradian. 1979 Physics 18 Table 2.2 Some units retained for general use though outside SI. Note that when mole is used, the elementary entities must be specified. These entities may be atoms, molecules, ions, electrons, other particles or specified groups of such particles. We employ units for some physical quantities that can be derived from the 7 base units Appendix A6. Some derived units in terms of the SI base units are given in Appendix A6.1, some SI derived units are given special names Appendix A6.2 and some derived SI units make use of these units with special names and the 7 base units Appendix A6.3. These are given in Appendix A6.2 and A6.3 for your ready reference. Other units retained for general use are given in Table 2.2. Common SI prefixes and symbols for multiples and submultiples are given in Appendix A2, General Guidelines for Using Symbols for Physical Quantities. Chemical elements and nuclides are given in Appendix A7 and those for SI units and some other units are given in Appendix A8 for your guidance and ready reference. 2.3 Measurement of length. You are already familiar with some direct methods for the measurement of length. For example, a meter scale is used for lengths from 10-3 meters to 102 meters. A vernier calipers is used for lengths to an accuracy of 10-4 meters. A screw gauge and a spherometer can be used to measure lengths as less as to 10-5 meters. To measure lengths beyond these ranges, we make use of some special indirect methods. 2, 3. 1. Measurement of large distances. Large distances such as the distance of a planet or a star from the Earth cannot be measured directly with a meter scale. An important method in such cases is the parallax method. When you hold a pencil in front of you against some specific point on the background, a wall, and look at the pencil first through your left eye A closing the right eye and then look at the pencil through your right eye B closing the left eye, you would notice that the position of the pencil seems to change with respect to the point on the wall. This is called parallax. The distance between the 2 points of observation is called the basis. In this example, the basis is the distance between the eyes. To measure the distance d of a faraway planet S by the parallax method, we observe it from 2 different positions, observatories A and B on the Earth, separated by distance ABB at the same time as shown in Fig. 2.2. We measure the angle between the 2 directions along which the planet is viewed at these 2 points. The ASB in Figure 2.2 represented by symbol Greek letter theta is called the parallax angle or parallactic angle, as the planet is very far away, 1, BD, and therefore, Greek letter theta is very small. Then we approximately take AB as an arc of length B of a circle with center at S and the distance D as units and measurement 19 TTTT the radius SBS so that ABBD Greek letter theta where Greek letter theta is in radians. dB Greek letter theta 2.1 Having determined E, we can employ a similar method to determine the size or angular diameter of the planet. If D is the diameter of the planet and Greek letter alpha the angular size of the planet, the angle subtended by D at the Earth We have Greek letter alpha DD 2.2. The angle Greek letter alpha can be measured from the same location on the Earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through the telescope. Since d is known, the diameter d of the planet can be determined using EC 2.2. Example 2.1. Calculate the angle of a 10-degree b 1 minute of arc or arcmin and c 1 second of arc or arc second in radians. Use 3602 Greek letter pi rad. 1060 and 160. Answer: we have 3602 Greek letter pi rad 10 Greek letter pi 180 rad 1.745 x 10-2 rad b 1061.745 x 10-2 rad 1 2.908 x 10-4 rad 2.91 x 10-4 rad c 162.908 x 10-4 rad 1 4.847 x 10-4 rad 4.85 x 10-6 rad t. Example 2.2. A man wishes to estimate the distance of a nearby tower from him. He stands at a point A in front of the tower C and spots a very distant object O in line with AC. He then walks perpendicular to AC up to B, a distance of 100 meters, and looks at O and C again, since O is very distant. The direction BO is practically the same as AO, but he finds the line of sight of C shifted from the original line of sight by an angle Greek letter theta 400. Greek letter theta is known as parallax. Estimate the distance of the tower C from his original position A. Figure 2.3. Answer: we have parallax angle Greek letter theta 400 from figure 2.3, ABAC tan Greek letter theta AC AB tan 100 meters tan 400 100 meters 0.8391 119 meters t. Example 2.3. The moon is observed from two diametrically opposite points A and B on Earth. The angle Greek letter theta subtended at the moon by the two directions of observation is 1054, given the diameter of the Earth to be about 1.276 xxxxx 107 meters. Compute the distance of the moon from the Earth. Answer: we have Greek letter theta x 31 degree 54 114 6114 64.85 10 xxx rad 3.32 x 10 2 rad, since 61 4.85 10 rad x also be AB 1.276 mx 107. Hence from EC 2.1, we have the Earth-Moon distance, dB Greek letter theta 1, 276, 10, 3, 32, 10, 7, 2, xx 83.84 10 meters xt. Example 2.4. The Sun's angular diameter is measured to be 1920. The distance d of the Sun from the Earth is 1.496 x 1011 meters. What is the diameter of the Sun? Fig. 2.2. Parallax method. Physics 20t. Answer: Sun's angular diameter Greek letter alpha 1920. XX 1924.85 10 rad 6x 9.31 10 rad 3. Sun's diameter DD Greek letter alpha 3, 119, 31, 10, 1, 496, 10, meters xxx 91.39 10 mxt 2, 3, 2. Estimation of very small distances, size of the molecule to measure a very small size, like that of a molecule 10-8 meters to 10-10 meters. We have to adopt special methods. We cannot use a screw gauge or similar instruments. Even a microscope has certain limitations. An optical microscope uses visible light to look at the system under investigation. As light has wave-like features, the resolution to which an optical microscope can be used is the wavelength of light. A detailed explanation can be found in the Class 12 physics textbook. For visible light, the range of wavelengths is from about 4000 A ring to 7000 A ring 1 angstrom 1 A ring 10 meters. Hence an optical microscope cannot resolve particles with sizes smaller than this. Instead of visible light, we can use an electron beam. Electron beams can be focused by properly designed electric and magnetic fields. The resolution of such an electron microscope is limited finally by the fact that electrons can also behave as waves. You will learn more about this in Class 12. The wavelength of an electron can be as small as a fraction of an angstrom. Such electron microscopes with a resolution of 0.6 A ring have been built. They can almost resolve atoms and molecules in a material. In recent times, tunneling microscopy has been developed, in which again the limit of resolution is better than an angstrom. It is possible to estimate the sizes of molecules. A simple method for estimating the molecular size of oleic acid is given below. Oleic acid is a soapy liquid with large molecular size of the order of 10-9 meters. The idea is to first form one molecular layer of oleic acid on water surface. We dissolve 1 cubic centimeter of oleic acid in alcohol to make a solution of 20 cubic centimeters. Then we take 1 cubic centimeter of this solution and dilute it to 20 cubic centimeters, using alcohol. So, the concentration of the solution is equal to 120-23 x cm of oleic acid cm3 of solution. Next we lightly sprinkle some lycopodium powder on the surface of water in a large trough, and we put 1 drop of this solution in the water. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. Then, We quickly measure the diameter of the thin film to get its area A. Suppose we have dropped n drops in the water, initially. We determine the approximate volume of each drop VCN3. Volume of n drops of solution NVCN3. Amount of oleic acid in the solution NV1 2020 x CN3. This solution of oleic acid spreads very fast on the surface of water and forms a very thin layer of thickness T. If this spreads to form a film of area ACN2, then the thickness of the film T, volume of the film, area of the film, or CN 2020 NVTAX 2.3. If we assume that the film has 1 molecular thickness, then this becomes the size or diameter of a molecule of oleic acid. The value of this thickness comes out to be of the order of 10-9 meters. Example 2.5. If the size of a nucleus in the range of 10-15 to 10-14 meters is scaled up to the tip of a sharp pin. What roughly is the size of an atom? Assume tip of the pin to be in the range 10-5 m to 10-4 m. Answer: the size of a nucleus is in the range of 10-15 meters and 10-14 meters. The tip of a sharp pin is taken to be in the range of 10-5 meters and 10-4 meters. Thus we are scaling up by a factor of 1010. An atom roughly of size 10-10 meters will be scaled up to a size of 1 meters. Thus a nucleus in an atom is as small in size as the tip of a sharp pin placed at the center of a sphere of radius about a meter long. T. Units and measurement 21 2, 3. 3. Range of lengths. The sizes of the objects we come across in the universe vary over a very wide range. These may vary from the size of the order of 10-14 meters of the tiny nucleus of an atom to the size of the order of 1026 meters of the extent of the observable universe. Table 2.3 gives the range and order of lengths and sizes of some of these objects. We also use certain special length units for short and large lengths. These are 1 Fermi, 1 F 10-15 meters, 1 angstrom, 1 A ring 10-10 meters, 1 astronomical unit, 1 AU. Average distance of the Sun from the Earth 1.496 x 1011 meters, 1 light year, 1 Li 9.46 x 1015 meters. Distance that light travels with velocity of 3 x 108 meters s1 in 1 year. 1 parsec 3.08 x 1016 meters. Parsec is the distance at which average radius of Earth's orbit subtends an angle of 1 arc second. 2.4 Measurement of mass. Mass is a basic property of matter. It does not depend on the temperature, pressure or location of the object in space. The SI unit of mass is kilogram/kg. The prototypes of the International Standard Kilogram supplied by the International Bureau of Weights and Measures (BIPM) are available in many other laboratories of different countries. In India, this is available at the National Physical Laboratory (NPL), New Delhi. While dealing with atoms and molecules, the kilogram is an inconvenient unit. In this case, there is an important standard unit of mass, called the Unified Atomic Mass Unit U, which has been established for expressing the mass of atoms as 1 Unified Atomic Mass Unit 1 U. 1/12 of the mass of an atom of carbon-12 isotope 612C, including the mass of electrons 1.66 x 10-27 kg. Mass of commonly available objects can be determined by a common balance like the one used in a grocery shop. Large masses in the universe like planets, stars, etc., based on Newton's law of gravitation can be measured by using gravitational methods. See Chapter 8. For measurement of small masses of atomic, subatomic particles, etc., we make use of mass spectrograph, in which radius of the trajectory is proportional to the mass of a charged particle moving in uniform electric and magnetic field. 2. 4. 1 Range of masses. The masses of the objects we come across in the universe vary over a very wide range. These may vary from tiny mass of the order of 10-30 kilograms of an electron to the huge mass of about 1055 kilograms of the known universe. Table 2.4 gives the range and order of the typical masses of various objects. Table 2.3 Range and order of lengths 2018 1. Physics 22 Table 2.4 Range and order of masses 2.5 Measurement of time. To measure any time interval we need a clock. We now use an atomic standard of time, which is based on the periodic vibrations produced in a cesium atom. This is the basis of the cesium clock, sometimes called atomic clock, used in the national standards. Such standards are available in many laboratories. In the cesium atomic clock, the second is taken as the time needed for 9, 192, 631, 770 vibrations of the radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium-133 atom. The vibrations of the cesium atom regulate the rate of this cesium atomic clock, just as the vibrations of a balance wheel regulate an ordinary wristwatch, or the vibrations of a small quartz crystal regulate a quartz wristwatch. The cesium atomic clocks are very accurate. In principle they provide portable standard, the national standard of time interval second, as well as the frequency is maintained through 4 cesium atomic clocks. A cesium atomic clock is used at the National Physical Laboratory (NPL), New Delhi, to maintain the Indian standard of time. In our country, The NPL has the responsibility of maintenance and improvement of physical standards, including that of time, frequency, etc. Note that the Indian Standard Time (ISD) is linked to this set of atomic clocks. The efficient cesium atomic clocks are so accurate that they impart the uncertainty in time realization as plus or minus 1x10-13, that is, 1 part in 1013. This implies that the uncertainty gained over time by such a device is less than 1 part in 1013. They lose or gain no more than 3 micros in 1 year. In view of the tremendous accuracy in time measurement, the SI unit of length has been expressed in terms the path length light travels in certain interval of time 1/299, 792, 458 of the second table 2.1. The time interval of events that we come across in the universe vary over a very wide range. Table 2.5 gives the range and order of some typical time intervals. You may notice that there is an interesting coincidence between the numbers appearing in tables 2.3 and 2.5. Note that the ratio of the longest and shortest lengths of objects in our universe is about 1041. Interestingly enough, the ratio of the longest and shortest time intervals associated with the events and objects in our universe is also about 1041. This number, 1041, comes up again in table 2.4, which lists typical masses of objects. The ratio of the largest and smallest masses of the objects in our universe is about 1041 too. Is this a curious coincidence between these large numbers purely accidental? 2.6 Accuracy, precision of instruments and errors in measurement. Measurement is the foundation of all experimental science and technology. The result of every measurement by any measuring instrument contains some uncertainty. This uncertainty is called error. Every calculated quantity which is based on measured values also has an error. We shall distinguish between two terms, accuracy and precision. The accuracy of a measurement is a measure of how close the measured value is to the true value of the quantity. Precision tells us to what resolution or limit the quantity is measured. The accuracy in measurement may depend on several factors, including the limit or the resolution of the measuring instrument. For example, suppose the true value of a certain length is near 3.678 centimeters, in one experiment, using a measuring instrument of resolution 0.1 centimeters. The measured value is found to be 3.5 centimeters, while in another experiment using a measuring device of greater resolution, say 0.01 centimeters, the length is determined to be 3.38 centimeters. The first measurement has more accuracy because it is units and measurement 23 closer to the true value but less precision. Its resolution is only 0.1 centimeters, while the second measurement is less accurate but more precise. Thus every measurement is approximate due to errors in measurement. In general, the errors in measurement can be broadly classified as A systematic errors and B random errors. Systematic errors. The systematic errors are those errors that tend to be in one direction, either positive or negative. Some of the sources of systematic errors are A. Instrumental errors that arise from the errors due to imperfect design or calibration of the measuring instrument. Zero error in the instrument, etc. For example, the temperature graduations of a thermometer may be inadequately calibrated. It may read 104 degrees Celsius at the boiling point of water at STP, whereas it should read 100 degrees Celsius. In a vernier calipers, the zero mark of vernier scale may not coincide with the zero mark of the main scale, or simply an ordinary meter scale may be worn off at one end. The imperfection in experimental technique or procedure to determine the temperature of a human body. A thermometer placed under the armpit will always give a temperature lower than the actual value of the body temperature. Other external conditions such as changes in temperature, humidity, wind velocity, etc. during the experiment may systematically affect the measurement. See personal errors that arise due to an individual's bias, lack of proper setting of the apparatus, or individual's carelessness in taking observations without observing proper precautions, etc. For example, if you, by habit, always hold your head a bit too far to the right while reading the position of a needle on the scale, you will introduce an error due to parallax. Systematic errors can be minimized by improving experimental techniques, selecting better instruments, and removing personal bias as far as possible. For a given setup, these errors may be estimated to a certain extent and the necessary corrections may be applied to the readings. Random errors. The random errors are those errors which occur irregularly and hence are random with respect to Table 2.5 range and order of time intervals. Physics 24 to sign and size. These can arise due to random and unpredictable fluctuations in experimental conditions, e.g. unpredictable fluctuations in temperature, voltage supply, mechanical vibrations of experimental setups, etc., personal unbiased errors by the observer taking readings, etc. For example, when the same person repeats the same observation, it is very likely that he may get different readings every time. Least count error. The smallest value that can be measured by the measuring instrument is called its least count. All the readings or measured values are good only up to this value. The least count error is the error associated with the resolution of the instrument. For example, a vernier calipers has the least count of 0.01 centimeters. A spherometer may have a least count of 0.001 centimeters. Least count error belongs to the category of random errors but within a limited size. It occurs with both systematic and random errors. If we use a meter scale for measurement of length, it may have graduations at 1 mm division scale spacing or interval. Using instruments of higher precision, improving experimental techniques, etc., we can reduce the least count error. Repeating the observations several times and taking the arithmetic mean of all the observations, the mean value would be very close to the true value of the measured quantity. 2. 6. 1 absolute error, relative error and percentage error. Suppose the values obtained in several measurements are a 1, a 2, a 3, and the arithmetic mean of these values is taken as the best possible value of the quantity under the given conditions of measurement as a mean or 1, a 2, a 3, an n 2.4 or a mean I1 n 2.5. This is because, as explained earlier, it is reasonable to suppose that individual measurements are as likely to overestimate as to underestimate the true value of the quantity. The magnitude of the difference between the individual measurement and the true value of the quantity is called the absolute error of the measurement. This is denoted by a, in absence of any other method of knowing true value, we considered arithmetic mean as the true value. Then the errors in the individual measurement values from the true value are a 1, a 1, a mean, a 2, a 2, a mean, comma and a n. A mean the calculated above may be positive in certain cases and negative in some other cases. But absolute error will always be positive. B. The arithmetic mean of all the absolute errors is taken as the final or mean absolute error of the value of the physical quantity A. It is represented by a mean, thus, a mean or 1, a 2, a 3, an n 2.6 I1 n a I n 2.7. If we do a single measurement, the value we get may be in the range a mean plus or minus a mean, that is, a mean plus or minus a mean, or a mean, a mean, a mean, a mean 2.8. This implies that any measurement of the physical quantity A is likely to lie between a mean and a mean, a mean. See, instead of the absolute error, we often use the relative error or the percentage error of. The relative error is the ratio of the mean absolute error a mean to the mean value a mean of the quantity measured. Units and measurement 25 tt. Relative error a mean 2.9. When the relative error is expressed in percent, it is called the percentage error of. Thus, percentage error a mean x 102.10. Let us now consider an example. Example 2.62 clocks are being tested against a standard clock located in a national laboratory. At 12 hours, 0 minutes, and 0 seconds noon by the standard clock. The readings of the two clocks are, clock 1, clock 2, Monday 12 hours, 0 minutes, and 5 seconds 10 hours, 15 minutes, and 6 seconds Tuesday 12 hours, 1 minute, and 15 seconds 10 hours, 14 minutes, and 59 seconds Wednesday 11 hours, 59 minutes, and 8 seconds 10 hours, 15 minutes, and 18 seconds Thursday 12 hours, 1 minute, and 50 seconds 10 hours, 15 minutes, and 7 seconds Friday 11 hours, 59 minutes, and 15 seconds 10 hours, 14 minutes, and 53 seconds Saturday 12 hours, 1 minute, and 30 seconds 10 hours, 15 minutes, and 24 seconds Sunday 12 hours, 1 minute, and 19 seconds 10:15, 11. If you are doing an experiment that requires precision time interval measurements, which of the two clocks will you prefer? Answer. The range of variation over the 7 days of observations is 162 s for clock 1, and 31 s for clock 2. The average reading of clock 1 is much closer to the standard time than the average reading of clock 2. The important point is that a clock 0 error is not as significant for precision work as its variation, because a 0 error can always be easily corrected. Hence clock 2 is to be preferred to clock 1. Example 2.7. We measure the period of oscillation of a simple pendulum. In successive measurements, the readings turn out to be 2.63 s, 2.56 s, 2.42 s, 2.71 s and 2.80 s. Calculate the absolute errors, relative error or percentage error. Answer. The mean period of oscillation of the pendulum T2.63, 2.56, 2.42, 2.71, 2.80 s, 513.12, 5 s, 2.624 s, 2.62 s. As the periods are measured to a resolution of 0.01 s, all times are to the second decimal. It is proper to put this mean period also to the second decimal. The errors in the measurements are 2.63 s, 2.62 s, 0.01 s, 2.56 s, 2.62 s, 0.06 s, 2.42 s, 2.62 s, 0.20 s, 2.71 s, 2.62 s, 0.09 s, 2.80 s, 2.62 s, 0.18 s. Note that the errors have the same units as the quantity to be measured. The arithmetic mean of all the absolute errors. For arithmetic mean, we take only the magnitudes as mean. 0.010.060.20.090 0.18 S5 0.54 S5 0.11 S. That means the period of oscillation of the simple pendulum is 2.62 plus or minus 0.11 S. That is, it lies between 2.62 0.11 S and 2.62 to 0.11 S, or between 2.73 S and 2.51 S. As the arithmetic mean of all the absolute errors is 0.11 S, there is already an error in the tenth of a second. Hence there is no point in giving the period to a hundredth. A more correct way will be to write t2.6 plus or minus 0.1 S. Note that the last numeral 6 is unreliable, since it may be anything between 5 and 7. We indicate this by saying that the measurement has two significant figures. In this case, the two significant figures are 2, which is reliable, and 6, which has an error associated with it. You will learn more about the significant figures in section 2.7. For this example, the relative error or the percentage error is IX01, 100, 4. 2.6 T2, 6. 2 combination of errors. If we do an experiment involving several measurements, we must know how the errors in all the measurements combine. For example, Physics 26T mass density is obtained by dividing mass by the volume of the substance. If we have errors in the measurement of mass and of the sizes or dimensions, we must know what the error will be in the density of the substance. To make such estimates, we should learn how errors combine in various mathematical operations. For this, we use the following procedure. A error of a sum or a difference. Suppose two physical quantities A and B have measured values A plus or minus A, B plus or minus B respectively, where A and B are their absolute errors. We wish to find the error Z in the sum ZAB we have by addition, Z plus or minus ZA plus or minus AB plus or minus B. The maximum possible error in ZAB for the difference ZA, B, we have Z plus or minus ZA plus or minus AB plus or minus BA, B plus or minus A plus or minus B, or plus or minus Z plus or minus A plus or minus B. The maximum value of the errors E is again AB, hence the rule, when two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. Example 2.8. The temperatures of two bodies measured by a thermometer are T120 C plus or minus 0.50 C and T250 C plus or minus 0.50 C. Calculate the temperature difference in the error therein. Answer: T2 T150 C plus or minus 0.50 C 200 C plus or minus 0.50 C T30 C plus or minus 10 C. TB error of a product or a quotient. Suppose ZAB and the measured values of A and B are A plus or minus A and B plus or minus B. Then Z plus or minus ZA plus or minus AB plus or minus BAB plus or minus BA plus or minus AB plus or minus AB. Dividing LHS by Z and RHS by AB, we have 1 plus or minus EZ 1 plus or minus AA plus or minus BB plus or minus AABB. Since A and B are small, we shall ignore their product. Hence the maximum relative error is EZAABB. You can easily verify that this is true for division also. Hence the rule, when two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. How will you measure the length of a line? What a naive question. At this stage, you might say, but what if it is not a straight line? Draw a zigzag line in your copy, or on the blackboard. Well, not too difficult again. You might take a thread, place it along the line, open up the thread, and measure its length. Now imagine that you want to measure the length of a national highway, a river, the railway track between two stations, or the boundary between two states or two nations. If you take a string of length 1 meter or 100 meter, keep it along the line, shift its position every time, the arithmetic of man-hours of labor and expenses on the project is not commensurate with the outcome. Moreover, errors are bound to occur in this enormous task. There is an interesting fact about this. France and Belgium share a common international boundary, whose length mentioned in the official documents of the two countries differs substantially. Go one step beyond and imagine the coastline where land meets sea. Roads and rivers have fairly mild bends as compared to a coastline. Even so, all documents, including our school books, contain information on the length of the coastline of Gujarat or Andhra Pradesh, or the common boundary between two states, etc. Railway tickets come with the distance between stations printed on them. We have milestones all along the roads indicating the distances to various towns. So, how is it done? One has to decide how much error one can tolerate and optimize cost effectiveness. If you want smaller errors, it will involve high technology and high costs. Suffice it to say that it requires fairly advanced level of physics, mathematics, engineering and technology. It belongs to the areas of fractals, which has lately become popular in theoretical physics. Even then one doesn't know how much to rely on the figure that props up, as is clear from the story of France and Belgium. Incidentally, this story of the France-Belgium discrepancy appears on the first page of an advanced physics book on the subject of fractals and chaos. Units and measurement 27 TTTT example 2.9 The resistance RVI where V 100 plus or minus 5V and I 10 plus or minus 0.2A. Find the percentage error in R. Answer: the percentage error in V is 5 and in I it is 2. The total error in R would therefore be 527. T example 2.102 Resistors of resistances R1 100 plus or minus 3 ohm and R2 200 plus or minus 4 ohm are connected A in series, B in parallel. Find the equivalent resistance of the A series combination, B parallel combination, use for the relation RR1 R2, and for B and answer of the equivalent resistance of series combination RR1 R2 100 plus or minus 3 ohm 200 plus or minus 4 ohm 300 plus or minus 7 ohm. B the equivalent resistance of parallel combination 1212 203 RRRRR 66.7 ohm. Then from 12111 RRR we get 122212 RRRRR 221 22212 RRRRR 2 266 7 66 7 3 4 100 201.8 then 66.71.80 HM plus or minus. Here, R is expressed as 1.8 instead of 2 to keep in conformity with the rules of significant figures. TC error in case of a measured quantity raised to a power suppose ZA2. Then, ZCAAA2AA, hence, the relative error in A2 is 2 times the error in A in general. If ZAPQCR then, ZCPAAQBBRCC, hence the rule, the relative error in a physical quantity raised to the power K is the K times the relative error in the individual quantity. Example 2.11 Find the relative error in Z. If ZA4B13CD32, answer the relative error in Z is ZZ4AA13BBCC32DD. T example 2.12 The period of oscillation of a simple pendulum is TLG2 Greek letter pi. Measured value of L is 20.0 centimeters. Known to 1 millimeter accuracy and time for 100 oscillations of the pendulum is found to be 90 s using a wristwatch of 1s resolution. What is the accuracy in the determination of G? Answer: G for Greek letter pi to LT2 here, TTN and TTN. Therefore, TTTT, the errors in both L and T are the least count errors. Therefore, GGLL2TT012021900027. Thus, the percentage error in G is 100 grams G100LL2X100TT3T 2.7 significant figures as discussed above. Every measurement involves errors. Thus, the result of measurement should be reported in a way that indicates the precision of measurement. Normally, the reported result of measurement is a number that includes all digits and the number that are known reliably plus the first digit that is uncertain. The reliable digits plus Physics 28 The first uncertain digit are known as significant digits or significant figures. If we say the period of oscillation of a simple pendulum is 1.62 s, the digits 1 and 6 are reliable and certain, while the digit 2 is uncertain. Thus, the measured value has 3 significant figures. The length of an object reported after measurement to be 287.5 centimeters has 4 significant figures. The digits 2, 8, 7 are certain while the digit 5 is uncertain. Clearly, reporting the result of measurement that includes more digits than the significant digits is superfluous and also misleading since it would give a wrong idea about the precision of measurement. The rules for determining the number of significant figures can be understood from the following examples. Significant figures indicate, as already mentioned, the precision of measurement which depends on the least count of the measuring instrument. A choice of change of different units does not change the number of significant digits or figures in a measurement. This important remark makes most of the following observations clear. 1. For example, the length 2.308 centimeters has 4 significant figures. But in different units, the same value can be written as 0.02308 meters or 23.08 millimeters or 23,080 micron. All these numbers have the same number of significant figures digits 2, 3, 0, 8, namely 4. This shows that the location of decimal point is of no consequence in determining the number of significant figures. The example gives the following rules. All the non-zero digits are significant. All the zeros between two non-zero digits are significant, no matter where the decimal point is, if at all. If the number is less than 1, the 0s on the right of decimal point but to the left of the first non-zero digit are not significant. In 0.002,308, the underlined zeros are not significant. The terminal or trailing 0s in a number without a decimal point are not significant. Thus 123 meters 12,300 centimeters 123,000 millimeters has three significant figures, the trailing 0s being not significant. However, you can also see the next observation. The trailing 0s in a number with a decimal point are significant. The numbers 3.500 or 0.06900 have four significant figures each too. There can be some confusion regarding the trailing 0s. Suppose the length is reported to be 4.700 meters. It is evident that the zeros here are meant to convey the precision of measurement and are, therefore, significant. If these were not, it would be superfluous to write them explicitly. The reported measurement would have been simply 4.7 meters. Now suppose we change units, then 4.700 meters 470.0 centimeters 4,700 millimeters 0.004700 kilometers. Since the last number has trailing 0s in a number with no decimal, we would conclude erroneously from observation 1 above that the number has two significant figures, while in fact, it has four significant figures, and a mere change of units cannot change the number of significant figures. 3. To remove such ambiguities in determining the number of significant figures, the best way is to report every measurement in scientific notation in the power of 10. In this notation, every number is expressed as a x10b, where a is a number between 1 and 10, and b is any positive or negative exponent or power of 10. In order to get an approximate idea of the number, we may round off the number to 1 for a 5 and to 10 for 5, a 10. Then the number can be expressed approximately as 10b, in which the exponent or power b of 10 is called order of magnitude of the physical quantity. When only an estimate is required, the quantity is of the order of 10b. For example, the diameter of the Earth 1.28 by 107 meters is of the order of 107 meters with the order of magnitude 7. The diameter of hydrogen atom 1.06 x 10-10 m is of the order of 10-10 m, with the order of magnitude -10. Thus, the diameter of the Earth is 17 orders of magnitude larger than the hydrogen atom. It is often customary to write the decimal after the first digit. Now the confusion mentioned in above disappears. 4.700 meters 4.700 x 102 centimeters 4.700 x 103 millimeters 4.700 x 10-3 kilometers. The power of 10 is irrelevant to the determination of significant figures. However, all units and measurement 29 zeros appearing in the base number in the scientific notation are significant. Each number in this case has four significant figures. Thus, in the scientific notation, no confusion arises about the trailing 0s in the base number a. They are always significant, for the scientific notation is ideal for reporting measurement, but if this is not adopted, we use the rules adopted in the preceding example. For a number greater than 1, without any decimal, the trailing 0s are not significant. For a number with a decimal, the trailing 0s are significant. 5. The digit 0 conventionally put on the left of a decimal for a number less than 1 like 0.1250 is never significant. However, the zeros at the end of such number are significant in a measurement. 6. The multiplying or dividing factors, which are neither rounded numbers nor numbers representing measured values, are exact and have infinite number of significant digits. For example, in 2dr or s-tor, the factor 2 is an exact number and it can be written as 2.0, 2.00 or 2.0000 is required. Similarly, in ttn, n is an exact number 2, 7, 1. Rules for arithmetic operations with significant figures. The result of a calculation involving approximate measured values of quantities, that is, values with limited number of significant figures, must reflect the uncertainties in the original measured values. It cannot be more accurate than the original measured values themselves on which the result is based. In general, the final result should not have more significant figures than the original data from which it was obtained. Thus, if mass of an object is measured to be, say, 4.237 grams, 4 significant figures, and its volume is measured to be 2.51 cubic centimeters, then its density, by mere arithmetic division, is 1.6880478086 grams cm3 up to 11 decimal places. It would be clearly absurd and irrelevant to record the calculated value of density to such a precision when the measurements on which the value is based have much less precision. The following rules for arithmetic operations with significant figures ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured values. 1. In multiplication or division, the final result should retain as many significant figures as are there in the original number with the least significant figures. Thus, in the example above, density should be reported to 3 significant figures. Density 4.237 grams 2.51 centimeters 1.69 grams cm33. Similarly, If the speed of light is given as 3x 108 meters s1 significant figure and 1 year 1y 365.25 d has 3.1557 x 107 s5 significant figures. The light year is 9.47 x 1015 meters 3 significant figures to an addition or subtraction. The final result should retain as many decimal places as are there in the number with the least decimal places. For example, the sum of the numbers 436.32 grams, 227.2 grams and 0.301 grams by mere arithmetic addition, is 663.821 grams. But the least precise measurement 227.2 grams is correct to only one decimal place. The final result should, therefore, be rounded off to 663.8 grams. Similarly, the difference in length can be expressed as 0.307 meters, 0.304 meters, 0.003 meters, 3x 10-3 meters. Note that we should not use the rule 1 applicable for multiplication and division and write 664 grams as the result in the example of addition and 3.00 x 10-3 meters in the example of subtraction. They do not convey the precision of measurement properly. For addition and subtraction, the rule is in terms of decimal places. 2. 7. 2. Rounding off the uncertain digits. The result of computation with approximate numbers, which contain more than one uncertain digit, should be rounded off. The rules for rounding off numbers to the appropriate significant figures are obvious in most cases. A number 2.746 rounded off to 3 significant figures is 2.75, while the number 2.743 would be 2.74. The rule by convention is that the preceding digit is raised by 1 if the Physics 30 TT insignificant digit to be dropped. The underlying digit in this case is more than 5, and is left unchanged if the latter is less than 5. But what if the number is 2.745 in which the insignificant digit is 5? Here, the convention is that if the preceding digit is even, the insignificant digit is simply dropped and, if it is odd, the preceding digit is raised by 1. Then, the number 2.745 rounded off to 3 significant figures becomes 2.74. On the other hand, the number 2.735 rounded off to 3 significant figures becomes 2.74 since the preceding digit is odd. In any involved or complex multi-step calculation, you should retain, in intermediate steps, one digit more than the significant digits and round off to proper significant figures at the end of the calculation. Similarly, a number known to be within many significant figures, such as in 2.9979245 x 108 meters s for the speed of light in vacuum, is rounded off to an approximate value 3x 108 meters s, which is often employed in computations. Finally, remember that exact numbers that appear in formulae like 2 Greek letter pi and TLG 2 Greek letter pi, have a large infinite number of significant figures. The value of Greek letter pi 3.1415926 is known to a large number of significant figures. You may take the value as 3.142 or 3.14 for Greek letter pi, with limited number of significant figures as required in specific cases. Example 2.13 Each side of a cube is measured to be 7.203 meters. What are the total surface area and the volume of the cube to appropriate significant figures? Answer: the number of significant figures in the measured length is 4. The calculated area and the volume should therefore be rounded off to 4 significant figures. Surface area of the cube 67.232 square meters, 311.299254 square meters, 311.3 square meters. Volume of the cube 7.233 cubic meters, 373.714754 cubic meters, 373.7 cubic meters. T example 2.14 5.74 grams of a substance occupies 1.2 cubic centimeters. Express its density by keeping the significant figures in view. Answer: there are 3 significant figures in the measured mass whereas there are only 2 significant figures in the measured volume. Hence the density should be expressed to only 2 significant figures. Density 5.74 1.2 grams cm3 4.8 grams cm3. T2. 7. 3 rules for determining the uncertainty in the results of arithmetic calculations. The rules for determining the uncertainty or error in the number measured quantity in arithmetic operations can be understood from the following examples. 1. If the length and breadth of a thin rectangular sheet are measured, using a meter scale as 16.2 centimeters and 10.1 centimeters respectively, there are 3 significant figures in each measurement. It means that the length L may be written as L 16.2 plus or minus 0.1 centimeters, 16.2 centimeters plus or minus 0.6. Similarly, the breadth B may be written as B 10.1 plus or minus 0.1 centimeters, 10.1 centimeters plus or minus 1. Then, the error of the product of 2 or more experimental values. Using the combination of errors rule. will be lb 163.62 square centimeters 1.6 163.62 2.6 square centimeters. This leads us to quote the final result as lb 164 3 square centimeters. Here 3 square centimeters is the uncertainty or error in the estimation of area of rectangular sheet. 2. If a set of experimental data is specified to n significant figures, a result obtained by combining the data will also be valid to n significant figures. However, if data are subtracted, the number of significant figures can be reduced. Units and measurement 31. For example, 12.9 grams 7.06 grams, both specified to 3 significant figures, cannot properly be evaluated as 5.84 grams but only as 5.8 grams. As uncertainties in subtraction or addition combine in a different fashion, smallest number of decimal places rather than the number of significant figures in any of the number added or subtracted. 3. The relative error of a value of number specified to significant figures depends not only on n but also on the number itself. For example, the accuracy in measurement of mass 1.02 grams is plus or minus 0.01 grams, whereas another measurement 9.89 grams is also accurate to plus or minus 0.01 grams. The relative error in 1.02 grams is plus or minus 0.01 1.02 x 100 plus or minus 1. Similarly, the relative error in 9.89 grams is plus or minus 0.01 9.89 x 100 plus or minus 0.1. Finally, remember that intermediate results in a multi-step computation should be calculated to one more significant figure in every measurement than the number of digits in the least precise measurement. These should be justified by the data and then the arithmetic operations may be carried out, otherwise rounding errors can build up. For example, the reciprocal of 9.58, calculated after rounding off to the same number of significant figures 3 is 0.104, but the reciprocal of 0.104 calculated to 3 significant figures is 9.62. However, if we had written 9.58 0.1044 and then taken the reciprocal to 3 significant figures, we would have retrieved the original value of 9.58. This example justifies the idea to retain one more extra digit than the number of digits in the least precise measurement in intermediate steps of the complex multi-step calculations in order to avoid additional errors in the process of rounding off the numbers. 2.8 Dimensions of physical quantities. The nature of a physical quantity is described by its dimensions. All the physical quantities represented by derived units can be expressed in terms of some combination of 7 fundamental or base quantities. We shall call these base quantities as the 7 dimensions of the physical world, which are denoted with square brackets. Thus, length has the dimension L, mass m, time t, electric current A, thermodynamic temperature K, luminous intensity CD, and amount of substance mole. The dimensions of a physical quantity are the powers or exponents to which the base quantities are raised to represent the quantity. Note that using the square brackets round a quantity means that we are dealing with the dimensions of the quantity. In mechanics, all the physical quantities can be written in terms of the dimensions L, m and t. For example, the volume occupied by an object is expressed as the product of length, breadth and height, or 3 lengths. Hence the dimensions of volume are Lx Lx L3 L3, as the volume is independent of mass and time. It is said to possess 0 dimension in mass m degrees, 0 dimension in time t degrees and 3 dimensions in length. Similarly, force, as the product of mass and acceleration, can be expressed as force mass x acceleration mass x length time 2. The dimensions of force are mlt2 mlt2. Thus, the force has 1 dimension in mass, 1 dimension in length, and minus 2 dimensions in time. The dimensions in all other base quantities are 0. Note that in this type of representation, the magnitudes are not considered. It is the quality of the type of the physical quantity that enters. Thus, a change in velocity, initial velocity, average velocity, final velocity, and speed are all equivalent in this context. Since all these quantities can be expressed as length time, their dimensions are Lt or Lt1. 2.9 Dimensional formulae and dimensional equations. The expression which shows how and which of the base quantities represent the dimensions of a physical quantity is called the dimensional formula of the given physical quantity. For example, the dimensional formula of the volume is m degrees L3 t degrees, and that of speed or velocity is m degrees Lt1. Similarly, m degrees Lt2 is the dimensional formula of acceleration and ml3 t degrees that of mass density. An equation obtained by equating a physical quantity with its dimensional formula is called the dimensional equation of the physical. Physics 32 Quantity. Thus, the dimensional equations are the equations which represent the dimensions of a physical quantity in terms of the base quantities. For example, the dimensional equations of volume v, speed v, Force-F and mass density Greek letter Rho may be expressed as Vm0L3T0 Vm0Lt1 FMLT2 Greek letter Rho ML3T0. The dimensional equation can be obtained from the equation representing the relations between the physical quantities. The dimensional formulae of a large number and wide variety of physical quantities, derived from the equations representing the relationships among other physical quantities and expressed in terms of base quantities, are given in Appendix 9 for your guidance and ready reference. 2.10 Dimensional analysis and its applications. The recognition of concepts of dimensions, which guide the description of physical behavior, is of basic importance, as only those physical quantities can be added or subtracted which have the same dimensions. A thorough understanding of dimensional analysis helps us in deducing certain relations among different physical quantities and checking the derivation, accuracy and dimensional consistency or homogeneity of various mathematical expressions. When magnitudes of two or more physical quantities are multiplied, their units should be treated in the same manner as ordinary algebraic symbols. We can cancel identical units in the numerator and denominator. The same is true for dimensions of a physical quantity. Similarly, physical quantities represented by symbols on both sides of a mathematical equation must have the same dimensions. 2.10.1 Checking the dimensional consistency of equations. The magnitudes of physical quantities may be added together or subtracted from one another only if they have the same dimensions. In other words, we can add or subtract similar physical quantities. Thus, velocity cannot be added to force, or an electric current cannot be subtracted from the thermodynamic temperature. This simple principle, called the principle of homogeneity of dimensions in an equation, is extremely useful in checking the correctness of an equation. If the dimensions of all the terms are not same, the equation is wrong. Hence, if we derive an expression for the length or distance of an object, regardless of the symbols appearing in the original mathematical relation, when all the individual dimensions are simplified, the remaining dimension must be that of length. Similarly, if we derive an equation of speed, the dimensions on both the sides of equation, when simplified, must be of length time, or LT1. Dimensions are customarily used as a preliminary test of the consistency of an equation, when there is some doubt about the correctness of the equation. However, the dimensional consistency does not guarantee correct equations. It is uncertain to the extent of dimensionless quantities or functions. The arguments of special functions, such as the trigonometric, logarithmic and exponential functions, must be dimensionless. A pure number, ratio of similar physical quantities, such as angle is the ratio length, refractive index is the ratio speed of light and vacuum speed of light and medium, etc., has no dimensions. Now we can test the dimensional consistency or homogeneity of the equation 21200 times xvt at t for the distance x traveled by a particle or body in time t, which starts from the position x0 with an initial velocity v0 at time t0 and has uniform acceleration along the direction of motion. The dimensions of each term may be written as xl, x0, lv0, tl, t1, tl1, 2, a t2l, t2, t2l, as each term on the right-hand side of this equation has the same dimension, namely that of length, which is same as the dimension of left-hand side of the equation. Hence this equation is a dimensionally correct equation. It may be noted that a test of consistency of dimensions tells us no more and no less than a units and measurement 33 TTT test of consistency of units, but has the advantage that we need not commit ourselves to a particular choice of units, and we need not worry about conversions among multiples and submultiples of the units. It may be borne in mind that if an equation fails this consistency test, it is proved wrong, but if it passes, it is not proved right. Thus, a dimensionally correct equation need not be actually an exact correct equation, but a dimensionally wrong, incorrect or inconsistent equation must be wrong. Example 2.15 Let us consider an equation 1 2 meters vmgh2 where m is the mass of the body, v its velocity, g is the acceleration due to gravity and h is the height. Check whether this equation is dimensionally correct. Answer. The dimensions of LHS are MLT1 2 ML2 T2 ML2 T2. The dimensions of RHS are MLT2 L ML2 T2 ML2 T2. The dimensions of LHS and RHS are the same and hence the equation is dimensionally correct. Example 2.16 The SI unit of energy is jkgm2s2, that of speed v is ms1 and of acceleration is ms2. Which of the formulae for kinetic energy K given below can you rule out on the basis of dimensional arguments? M stands for the mass of the body, a km2v3 bk12 mv2 ck mod ek316 mv2 ek12 mv2 My answer. Every correct formula or equation must have the same dimensions on both sides of the equation. Also, only quantities with the same physical dimensions can be added or subtracted. The dimensions of the quantity on the right side are m2l3t3 for A, ml2t2 for B and D, mlt2 for C. The quantity on the right side of E has no proper dimension since two quantities of different dimensions have been added. Since the kinetic energy K has the dimensions of mL2T2, formulas A, C and D are ruled out. Note that dimensional arguments cannot tell which of the two, B or D, is the correct formula. For this, one must turn to the actual definition of kinetic energy, see Chapter 6. The correct formula for kinetic energy is given by B. T2, 10. To deducing relation among the physical quantities, the method of dimensions can sometimes be used to deduce relation among the physical quantities. For this we should know the dependence of the physical quantity on other quantities. Up to 3 physical quantities are linearly independent variables and consider it as a product type of the dependence. Let us take an example. Example 2.17. Consider a simple pendulum, having a bob attached to a string, that oscillates under the action of the force of gravity. Suppose that the period of oscillation of the simple pendulum depends on its length L, mass of the bob m and acceleration due to gravity g. Derive the expression for its time period using method of dimensions. Answer: the dependence of time period t on the quantities L, g and m as a product may be written as Tk60 G(IMZ), where k is dimensionless constant and x, y and z are the exponents. By considering dimensions on both sides, we have 00111 minus 21 LMT LLT MXYZ 60 YT2 IMZ. On equating the dimensions on both sides, we have XY0, minus 2Y1, and Z0, so that 11022 XYZ then, TKLG 1/2. Physics 34 Summary 1. Physics is a quantitative science, based on measurement of physical quantities. Certain physical quantities have been chosen as fundamental or base quantities such as length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. 2. Each base quantity is defined in terms of a certain basic, arbitrarily chosen but properly standardized reference standard called units such as meter, kilogram, second, ampere, Kelvin, mole and candela. The units for the fundamental or base quantities are called fundamental or base units. 3. Other physical quantities, derived from the base quantities, can be expressed as a combination of the base units and are called derived units. A complete set of units, both fundamental and derived, is called a system of units. 4. The International System of Units SI based on 7 base units is at present internationally accepted unit system and is widely used throughout the world. 5. The SI units are used in all physical measurements, for both the base quantities and the derived quantities obtained from them. Certain derived units are expressed by means of SI units with special names such as joule, newton, watt, etc. 6. The SI units have well-defined and internationally accepted unit symbols such as M for meter, kg for kilogram, S for second, A for ampere, N for newton, etc. 7. Physical measurements are usually expressed for small and large quantities in scientific notation, with powers of 10. Scientific notation and the prefixes are used to simplify measurement notation and numerical computation, giving indication to the precision of the numbers. 8. Certain general rules and guidelines must be followed for using notations for physical quantities and standard symbols for SI units. Some other units and SI prefixes for expressing properly the physical quantities and measurements. 9. In computing any physical quantity, the units for derived quantities involved in the relationship S are treated as though they were algebraic quantities till the desired units are obtained. 10. Direct and indirect methods can be used for the measurement of physical quantities. In measured quantities, while expressing the result, the accuracy and precision of measuring instruments along with errors in measurements should be taken into account. 11. In measured and computed quantities, proper significant figures only should be retained. Rules for determining the number of significant figures, carrying out arithmetic operations with them, and rounding off the uncertain digits must be followed. 12. The dimensions of base quantities and combination of these dimensions describe the nature of physical quantities. Dimensional analysis can be used to check the dimensional consistency of equations, deducing relations among the physical quantities, etc. A dimensionally consistent equation need not be actually an exact correct equation, but a dimensionally wrong or inconsistent equation must be wrong. Or, TLKG. Note that value of constant k cannot be obtained by the method of dimensions. Here it does not matter if some number multiplies the right side of this formula, because that does not affect its dimensions. Actually, K2 Greek letter pi so that T2 liters G Greek letter pi T. Dimensional analysis is very useful in deducing relations among the interdependent physical quantities. However, dimensionless constants cannot be obtained by this method. The method of dimensions can only test the dimensional validity, but not the exact relationship between physical quantities in any equation. It does not distinguish between the physical quantities having same dimensions. A number of exercises at the end of this chapter will help you develop skill in dimensional analysis. Units and measurement 35 exercises. Note, in stating numerical answers, take care of significant figures. 2.1 Fill in the blanks. The volume of a cube of side 1 cm is equal to m3b. The surface area of a solid cylinder of radius 2.0 cm and height 10.0 cm is equal to mm2c. A vehicle moving with a speed of 18 km h1 covers m1sd. The relative density of lead is 11.3. Its density is GCM3 or KGM3. 2.2 Fill in the blanks by suitable conversion of units. A 1 kg m2s2, GCM2s2b 1 meters. Lyc 3.0 meters s2 kilometers h2 dg 6.67 x 10-11 nm2 kg-2 cm3 s2 g1 2.3 a calorie is a unit of heat energy in transit and it equals about 4.2 j where 1 j 1 kg m2s2. Suppose we employ a system of units in which the unit of mass equals Greek letter alpha kg, the unit of length equals Greek letter beta m, the unit of time is Greek letter gamma s. Show that a calorie has a magnitude 4.2 Greek letter alpha minus 1 Greek letter beta minus 2 Greek letter gamma 2 in terms of the new units. 2.4 Explain this statement clearly. To call a dimensional quantity large or small is meaningless without specifying a standard for comparison. In view of this, reframe the following statements wherever necessary. Atoms are very small objects. B. A jet plane moves with great speed. C. The mass of Jupiter is very large. D. The air inside this room contains a large number of molecules. E. A proton is much more massive than an electron. F. The speed of sound is much smaller than the speed of light. 2.5 A new unit of length is chosen such that the speed of light in vacuum is unity. What is the distance between the Sun and the Earth in terms of the new unit of light? Takes 8 minutes and 20 s to cover this distance. 2.6 Which of the following is the most precise device for measuring length? A. Vernier calipers with 20 divisions on the sliding scale. B. A screw gauge of pitch 1 mm and 100 divisions on the circular scale. C. An optical instrument that can measure length to within a wavelength of light. 2.7 A student measures the thickness of a human hair by looking at it through a microscope of magnification 100. He makes 20 observations and finds that the average width of the hair in the field of view of the microscope is 3.5 mm. What is the estimate on the thickness of hair? 2.8 Answer the following. A. You are given a thread and a meter scale. How will you estimate the diameter of the thread? B. A screw gauge has a pitch of 1.0 mm and 200 divisions on the circular scale. Do you think it is possible to increase the accuracy of the screw gauge arbitrarily by increasing the number of divisions on the circular scale? C. The mean diameter of a thin brass rod is to be measured by vernier calipers. Why is a set of 100 measurements of the diameter expected to yield a more reliable estimate than a set of 5 measurements only? 2.9 The photograph of a house occupies an area of 1.75 square centimeters on a 35 mm slide. The slide is projected onto a screen, and the area of the house on the screen is 1.55 square meters. What is the linear magnification of the projector screen arrangement? 2.10 State the number of significant figures in the following. A 0.007 square meters. B 2.64 x 1024 kilograms. C 0.2370 grams. cm3. Physics 36 D 6.320 JE 6.032 NM2 F 0.00060032 square meters. 2.11 The length, breadth and thickness of a rectangular sheet of metal are 4.234 meters, 1.005 meters, and 2.01 centimeters respectively. Give the area and volume of the sheet to correct significant figures. 2.12 The mass of the box measured by a grocer's balance is 2.300 kilograms. 2 gold pieces of masses 20.15 grams and 20.17 grams are added to the box. What is the total mass of the box? B. The difference in the masses of the pieces to correct significant figures. 2.13 A physical quantity P is related to 4 observables A, B, C and D as follows. 3 2 P A B C D. The percentage errors of measurement in A, B, C and D are 1, 3, 4 and 2, respectively. What is the percentage error in the quantity P if the value of P calculated using the above relation turns out to be 3.763? To what value should you round off the result? 2.14 A book with many printing errors contains 4 different formulas for the displacement y of a particle undergoing a certain periodic motion. A y a sin 2 Greek letter pi t t b y a sin v t c y a t sin t a d y a t t t t 2 sin 2 cos 2 Greek letter pi a maximum displacement of the particle, v speed of the particle, t time period of motion. Rule out the wrong formulas on dimensional grounds. 2.15 A famous relation in physics relates moving mass m to the rest mass mo of a particle in terms of its speed v and the speed of light, c. This relation first arose as a consequence of special relativity due to Albert Einstein. A boy recalls the relation almost correctly but forgets where to put the constant c. He writes, mm 1 volt 0212. Guess where to put the missing c. 2.16 The unit of length convenient on the atomic scale is known as an angstrom and is denoted by A ring. 1 A ring 10-10 meters. The size of a hydrogen atom is about 0.5 A ring. What is the total atomic volume in M3 of a mole of hydrogen atoms? 2.171 mole of an ideal gas at standard temperature and pressure occupies 22.4 L molar volume. What is the ratio of molar volume to the atomic volume of a mole of hydrogen? Take the size of hydrogen molecule to be about 1 A ring. Why is this ratio so large? 2.18 Explain this common observation clearly. If you look out of the window of a fast-moving train, the nearby trees, houses etc. seem to move rapidly in a direction opposite to the train's motion, but the distant objects, hilltops, the moon, the stars etc. seem to be stationary. In fact, since you are aware that you are moving, these distant objects seem to move with you. 2.19 The principle of parallax in section 2.3.1 is used in the determination of distances of very distant stars. The baseline AB is the line joining the Earth's two locations 6 months apart in its orbit around the Sun. That is, the baseline is about the diameter of the Earth's orbit 3x 1011 meters. However, even the nearest stars are so distant that with such a long baseline, they show parallax only of the order of 1 inch/second of arc or so. A parsec is a convenient unit of length on the astronomical scale. It is the distance of an object that will show a parallax of 1 inch/second of arc from opposite ends of a baseline equal to the distance from the Earth to the Sun. How much is a parsec in terms of meters? Units and measurement 37.220 The nearest star to our solar system is 4.29 light-years away. How much is this distance in terms of parsecs? How much parallax would this star named Alpha Centauri show when viewed from two locations of the Earth 6 months apart in its orbit around the Sun? 2.21 Precise measurements of physical quantities are in need of science. For example, to ascertain the speed of an aircraft, one must have an accurate method to find its positions at closely separated instants of time. This was the actual motivation behind the discovery of radar in World War II. Think of different examples in modern science where precise measurements of length, time, mass etc. are needed. Also, wherever you can, give a quantitative idea of the precision needed. 2.22 Just as precise measurements are necessary in science, it is equally important to be able to make rough estimates of quantities using rudimentary ideas and common observations. Think of ways by which you can estimate the following where an estimate is difficult to obtain. Try to get an upper bound on the quantity of the total mass of rain-bearing clouds over India during the monsoon. B. The mass of an elephant. C. The wind speed during a storm. D. The number of strands of hair on your head. E. The number of air molecules in your classroom. 2.23 The Sun is a hot plasma ionized matter with its inner core at a temperature exceeding 107 K. and its outer surface at a temperature of about 6000 K. At these high temperatures, no substance remains in a solid or liquid phase. In what range do you expect the mass density of the Sun to be? In the range of densities of solids and liquids or gases. Check if your guess is correct from the following data. Mass of the Sun 2.0 x 1030 kg. Radius of the Sun 7.0 x 108 meters. 2.24 When the planet Jupiter is at a distance of 824.7 million kilometers from the Earth, its angular diameter is measured to be 35.72 inches of arc. Calculate the diameter of Jupiter. Additional exercises. 2.25 A man walking briskly in rain with speed v must slant his umbrella forward, making an angle Greek letter theta with the vertical. A student derives the following relation between Greek letter theta and v, tan Greek letter theta v, and checks that the relation has a correct limit, as v 0, Greek letter theta 0, as expected. We are assuming there is no strong wind and that the rain falls vertically for a stationary man. Do you think this relation can be correct? If not, guess the correct relation. 2.26 It is claimed that two cesium clocks, if allowed to run for 100 years, free from any disturbance, may differ by only about 0.02 s. What does this imply for the accuracy of the standard cesium clock in measuring a time interval of 1 s? 2.27 Estimate the average mass density of a sodium atom assuming its size to be about 2.5 A ring. Use the known values of Avogadro's number and the atomic mass of sodium. Compare it with the mass density of sodium in its crystalline phase, 970 kg M3. Are the two densities of the same order of magnitude? If so, why? 2.28 The unit of length convenient on the nuclear scale is the Fermi, 1f10-15 meters. Nuclear sizes obey roughly the following empirical relation, RR0A13, where R is the radius of the nucleus, A its mass number, and ρ is a constant equal to about 1.2 f. Show that the rule implies that nuclear mass density is nearly constant for different nuclei. Estimate the mass density of sodium nucleus. Compare it with the average mass density of a sodium atom obtained in exercise 2.27. 2.29 A laser is a source of very intense, monochromatic, and unidirectional beam of light. These properties of a laser light can be exploited to measure long distances. The distance of the Moon from the Earth has been already determined very precisely using a laser as a source of light. A laser light beamed at the Moon takes 2.56 s2. Physics 38 Return after reflection at the Moon's surface. How much is the radius of the lunar orbit around the Earth? 2.30 A sonar sound navigation and ranging uses ultrasonic waves to detect and locate objects underwater. In a submarine equipped with a sonar, the time delay between generation of a probe wave and the reception of its echo after reflection from an enemy submarine is found to be 77.0 s. What is the distance of the enemy submarine speed of sound in water? 1,450 meters s1 2.31 The farthest objects in our universe discovered by modern astronomers are so distant that light emitted by them takes billions of years to reach the Earth. These objects known as quasars have many puzzling features, which have not yet been satisfactorily explained. What is the distance in kilometers of a quasar from which light takes 3.0 billion years to reach us? 2.32 It is a well-known fact that during a total solar eclipse the disk of the Moon almost completely covers the disk of the Sun. From this fact and from the information you can gather from examples 2.3 and 2.4, determine the approximate diameter of the Moon. 2.33 A great physicist of this century P.A.M. Dirac loved playing with numerical values of fundamental constants of nature. This led him to an interesting observation. Dirac found that from the basic constants of atomic physics C, E, massive electron, massive proton and the gravitational constant G, he could arrive at a number with the dimension of time. Further, it was a very large number, its magnitude being close to the present estimate on the age of the universe 15 billion years. From the table of fundamental constants in this book, try to see if you too can construct this number or any other interesting number you can think of. If its coincidence with the age of the universe were significant, what would this imply for the constancy of fundamental constants? 2018 1. Chapter 3 Motion in a Straight Line 3.1 Introduction 3.2 Position Path length and displacement 3.3 Average velocity and average speed 3.4 Instantaneous velocity and speed 3.5 Acceleration 3.6 Kinematic equations for uniformly accelerated motion 3.7 Relative velocity Summary points to ponder Exercises Additional Exercises Appendix 3.1 3.1 Introduction Motion is common to everything in the universe. We walk, run and ride a bicycle. Even when we are sleeping, air moves into and out of our lungs and blood flows in arteries and veins. We see leaves falling from trees and water flowing down a dam. Automobiles and planes carry people from one place to the other. The Earth rotates once every 24 hours and revolves round the Sun once in a year. The Sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. Motion is change in position of an object with time. How does the position change with time? In this chapter, we shall learn how to describe motion. For this, we develop the concepts of velocity and acceleration. We shall confine ourselves to the study of motion of objects along a straight line, also known as rectilinear motion. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. In our discussions, we shall treat the objects in motion as point objects. This approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. In kinematics, we study ways to describe motion without going into the causes of motion. What causes motion described in this chapter and the next chapter forms the subject matter of Chapter 5. 3.2 Position, path length and displacement. Earlier you learnt that motion is change in position of an object with time. In order to specify position, we need to use a reference point and a set of axes. It is convenient to choose Physics 40 with the path of the car's motion and origin of the axis as the point from where the car started moving, that is, the car was at x0 at t0. Figure 3.1, let P, Q and R represent the positions of the car at different instants of time. Consider two cases of motion. In the first case, the car moves from O to P, then the distance moved by the car is OP 360 meters. This distance is called the path length traversed by the car. In the second case, the car moves from O to P and then moves back from P to Q during this course of motion. The path length traversed is OPPQ 360 meters 120 meters 480 meters. Path length is a scalar quantity, a quantity that has a magnitude only in no direction. See Chapter 4. Displacement. It is useful to define another quantity, displacement, as the change in position. Let x1 and x2 be the positions of an object at time t1 and t2, then its displacement, denoted by x. In time t2 t1 is given by the difference between the final and initial positions. X2, x1 we use the Greek letter delta to denote a change in a quantity. If x2, x1, x is positive, and if x2, x1, x is negative. Displacement has both magnitude and direction. Such quantities are represented by vectors. You'll read about vectors in the next chapter. Presently, we are dealing with motion along a straight line, also called rectilinear motion only. In one-dimensional motion, there are only two directions, backward and forward, upward and downward, in which an object can move, and these two directions can easily be specified by signs. For example, displacement of the car in moving from O to P is x2 x1 360 meters 0 meters 360 meters. The displacement has a magnitude of 360 meters and is directed in the positive x direction as indicated by the sign. Similarly, the displacement of the car from P to Q is 240 meters 360 meters 120 meters. The figure 3.1 x-axis, origin and positions of a car at different times. A rectangular coordinate system consisting of three mutually perpendicular axes, labeled x, y, and z axes. The point of intersection of these three axes is called origin O and serves as the reference point. The coordinates x, y, z of an object describe the position of the object with respect to this coordinate system. To measure time, we position a clock in the system. This coordinate system along with the clock constitutes a frame of reference. If one or more coordinates of an object change with time, we say that the object is in motion. Otherwise, the object is said to be at rest with respect to this frame of reference. The choice of a set of axes in a frame of reference depends upon the situation. For example, for describing motion in one dimension, we need only one axis. To describe motion in 2-3 dimensions, we need a set of 2-3 axes. Description of an event depends on the frame of reference chosen for the description. For example, when you say that a car is moving on a road, you are describing the car with respect to a frame of reference attached to you or to the ground. But with respect to a frame of reference attached with the person sitting in the car is at rest. To describe motion along a straight line, we can choose an axis, say x-axis, so that it coincides with the path of the object. We then measure the position of the object with reference to a conveniently chosen origin, say O, as shown in Fig. 3.1. Positions to the right of O are taken as positive and to the left of O, as negative. Following this convention, the position coordinates of point P and Q in Fig. 3.1 are 360 meters and 240 meters. Similarly, the position coordinate of point R is -120 meters. Path length: consider the motion of a car along a straight line. We choose the x-axis such that it coincides. Motion in a straight line. 41 negative sign indicates the direction of displacement. Thus, it is not necessary to use vector notation for discussing motion of objects in one dimension. The magnitude of displacement may or may not be equal to the path length traversed by an object. For example, for motion of the car from O to P, the path length is 360 meters and the displacement is 360 meters. In this case, the magnitude of displacement 360 meters is equal to the path length 360 meters, but consider the motion of the car from O to P and back to Q in this case. The path length 360 meters 120 meters 480 meters, however, the displacement 240 meters 0 meters 240 meters. Thus, the magnitude of displacement 240 meters is not equal to the path length 480 meters. The magnitude of a displacement for a course of motion may be 0 but the corresponding path length is not 0. For example, if the car starts from O, goes to P and then returns to O, the final position coincides with the initial position and the displacement is 0. However, the path length of this journey is OPP 360 meters 720 meters. Motion of an object can be represented by a position-time graph as you have already learned about it. Such a graph is a powerful tool to represent and analyze different aspects of motion of an object. For motion along a straight line, say x-axis, only x-coordinate varies with time and we have an xt graph. Let us first consider the simple case in which an object is stationary, e.g. a car standing still at x 40 meters. The position-time graph is a straight line parallel to the time axis, as shown in Figure 3.2 up. If an object moving along the straight line covers equal distances in equal intervals of time, it is said to be in uniform motion along a straight line. Figure 3.2b shows the position-time graph of such a motion. Figure 3.2 position-time graph of a stationary object, and be an object in uniform motion. Figure 3.3 position-time graph of a car TSXM. Physics 42. Now, let us consider the motion of a car that starts from rest at time t0s from the origin O and picks up speed till t10s and thereafter moves with uniform speed till t18s. Then the brakes are applied and the car stops at t20s and x 296 meters. The position time graph for this case is shown in Fig. 3.3. We shall refer to this graph in our discussion in the following sections. 3.3 Average velocity and average speed. When an object is in motion, its position changes with time. But how fast is the position changing with time and in what direction? To describe this, we define the quantity average velocity. Average velocity is defined as the change in position or displacement x divided by the time intervals t, in which the displacement occurs, bxxt txt 2121 3.1, where x2 and x1 are the positions of the object at time t2 and t1, respectively. Here the bar over the symbol for velocity is a standard notation used to indicate an average quantity. The SI unit for velocity is ms or ms1, although kilometers h1 is used in many everyday applications. Like displacement, average velocity is also a vector quantity, but as explained earlier, for motion in a straight line, the directional aspect of the vector can be taken care of by n signs, and we do not have to use the vector notation for velocity in this chapter. Figure 3.4. The average velocity is the slope of line p1 p2. Consider the motion of the car in Fig. 3.3. The portion of the xt graph between t0s and t8s is blown up and shown in Figure 3.4, as seen from the plot. The average velocity of the car between time t5s and t7s is 11212 sm 8.7s 57 meters 010 427. TTXXV. Geometrically, this is the slope of the straight line p1 p2 connecting the initial position 1p to the final position p2 as shown in Fig. 3.4. The average velocity can be positive or negative depending upon the sign of the displacement. It is 0 if the displacement is 0. Figure 3.5 shows the xt graphs for an object moving with positive velocity. Fig. 3.5a, moving with negative velocity. Figure 3.5b, and at rest. Figure 3.5c. Average velocity as defined above involves only the displacement of the object. We have seen earlier that the magnitude of displacement may be different from the actual path length. To describe the rate of motion over the actual path, we introduce another quantity called average speed. Average speed is defined as the total path length traveled divided by the total time interval during which the motion has taken place. Average speed total path length total time interval. 3.2 Average speed has obviously the same unit ms1 as that of velocity. But it does not tell us in what direction an object is moving. Thus, it is always positive in contrast to the average velocity, which can be positive or negative. If the motion of an object is along a straight line and in the same direction, the magnitude of displacement is equal to the total path length. In that case, the magnitude of average velocity. Figure 3.5 Position time graph for an object: A moving with positive velocity, B moving with negative velocity, and C at rest. Motion in a straight line 43t is equal to the average speed. This is not always the case, as you will see in the following example. Example 3.1 A car is moving along a straight line, say OP in Figure 3.1. It moves from O to P in 18s and returns from P to Q in 6.0s. What are the average velocity and average speed of the car in going from O to P and B from O to P and back to Q? Answer: Average velocity displacement time interval 1 360 meters 20 meters s18 sv. Average speed path length time interval 1360 meters 20 meters s18 s. Thus, in this case the average speed is equal to the magnitude of the average velocity. B in this case. 240 meters 18 6.0 s. Displacement average velocity time interval 110 milliseconds OPPQ. Path length average speed time interval t 1360 120 meters 20 meters s 24 s. Thus, in this case the average speed is not equal to the magnitude of the average velocity. This happens because the motion here involves change in direction, so that the path length is greater than the magnitude of displacement. This shows that speed is, in general, greater than the magnitude of the velocity t if the car in example 3.1 moves from O to P and comes back to O in the same time interval. Average speed is 20 meters s, but the average velocity is 0. 3.4 Instantaneous velocity and speed. The average velocity tells us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. For this, we define instantaneous velocity, or simply velocity v at an instant t. The velocity at an instant is defined as the limit of the average velocity as the time interval t becomes infinitesimally small. In other words, v lim xt t0 3.3 a ddxt 3.3b, where the symbol lim t0 stands for the operation of taking limit as tg0 of the quantity on its right. In the language of calculus, the quantity on the right-hand side of x 3.3 a is the differential coefficient of x with respect to t and is denoted by ddxt. See Appendix 3.1. It is the rate of change of position with respect to time, at that instant. We can use EC 3.3 for obtaining the value of velocity at an instant either graphically or numerically. Suppose that we want to obtain graphically the value of velocity at time t for s point P for the motion of the car represented in Fig. 3.3. The figure has been redrawn in Figure 3.6 choosing different scales to facilitate the Figure 3.6 determining velocity from position time graph. Velocity at t4s is the slope of the tangent to the graph at that instant. Physics 44 calculation. Let us take t2s centered at t4s then, by the definition of the average velocity, the slope of line p1 p2 Fig. 3.6 gives the value of average velocity over the interval 3s to 5s. Now, we decrease the value of t from 2s to 1s. Then line p1 p2 becomes q1 q2 and its slope gives the value of the average velocity over the interval 3.5s to 4.5s. In the limit t0, the line p1 p2 becomes tangent to the position time curve at the point P and the velocity at t4s is given by the slope of the tangent at that point. It is difficult to show this process graphically, but if we use numerical method to obtain the value of the velocity, the meaning of the limiting process becomes clear. For the graph shown in Figure 3.6, x 0.08 t3, Table 3.1 gives the value of xt calculated for t equal to 2.0s, 1.0s, 0.5s, 0.1s and 0.01s centered at t4.0s. The second and third columns give the value of t1 tt2 and tt2 and the fourth and the fifth columns give the corresponding values of x, that is, xt1 0.08 t13 and xt2 0.08 t23. The sixth column lists the difference xt2 xt1 and the last column gives the ratio of x and t, that is, the average velocity corresponding to the value of t listed in the first column. We see from Table 3.1 that as we decrease the value of t from 2.0s to 0.010s, the value of the average velocity approaches the limiting value 3.84 meters s1 which is the value of velocity at t4.0s, that is, the value of ddxt at t4.0s. In this manner, we can calculate velocity at each instant for motion of the car shown in Fig. 3.3. For this case, the variation of velocity with time is found to be as shown in Figure 3.7, Fig. 3.7 velocity time graph corresponding to motion shown in Figure 3.3. The graphical method for the determination of the instantaneous velocity is always not a convenient method. For this, we must carefully plot the position time graph and calculate the value of average velocity as t becomes smaller and smaller. It is easier to calculate the value of velocity at different instants if we have data of positions at different instants or exact expression for the position as a function of time. Then, we calculate xt from the data for decreasing the value of t and find the limiting value as we have done in Table 3.1 or use differential calculus for the given expression and calculate ddxt at different instants as done in the following example. Table 3.1 limiting value of xt at t4s 2018-1. Motion in a straight line 45t. Example 3.2 The position of an object moving along x-axis is given by x at bt2 where 8.5 meters, b2.5 meters s2 and t is measured in seconds. What is its velocity at t0s and t2.0s? What is the average velocity between t2.0s and t4.0s? Answer in notation of differential calculus. The velocity is vxt at bt2 bt2 dd 5.0 tms1 at t0s, d0 meters s1 and at t2.0s, b10 meters s1. 4.02.0 4.02.0 xx average velocity 1646.02.0 ab at bbx 16.02.5 15 meters sxt from Fig. 3.7. We note that during the period t10s to 18s the velocity is constant. Between period t18s to t20s, it is uniformly decreasing and during the period t0s to t10s, it is increasing. Note that for uniform motion, velocity is the same as the average velocity at all instants. Instantaneous speed or simply speed is the magnitude of velocity. For example, a velocity of 24.0 meters s1 and a velocity of 24.0 meters s1 both have an associated speed of 24.0 meters s1. It should be noted that low average speed over a finite interval of time is greater or equal to the magnitude of the average velocity. Instantaneous speed at an instant is equal to the magnitude of the instantaneous velocity at that instant. Why so? 3.5 Acceleration. The velocity of an object, in general, changes during its course of motion. How to describe this change? Should it be described as the rate of change in velocity with distance or with time? This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change of velocity with distance. but, through his studies of motion of freely falling objects and motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant, it decreases with the increasing distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration over a time interval is defined as the change of velocity divided by the time interval, 2121 v via t 3.4, where v2 and v1 are the instantaneous velocities or simply velocities at time t2 and t1. It is the average change of velocity per unit time. The SI unit of acceleration is ms2. On a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2, t2 and v1, t1. The average acceleration for velocity time graph shown in figure 3.7 for different time intervals 0s 10s, 10s 18s, and 18s 20s are 0s 10s minus 1 minus 224 0 meters s 2.4 meters s 10 0s a 10s 18s minus 1 minus 224 24 meters s 0 meters s 18 minus 10s 18s 20s minus 1 minus 20 24 meters s 12 meters s 20 18s a fig. 3.8 Acceleration is a function of time for motion represented in figure 3.3. Instantaneous acceleration is defined in the same way as the instantaneous velocity, ddt 0 volt via lim t 3.5. The acceleration at an instant is the slope of the tangent to the vt curve at that instant. For the vt curve shown in figure 3.7, we can obtain acceleration at every instant of time. The resulting t curve is shown in fig. 3.8. We see a ms2. Physics 46 that the acceleration is non-uniform over the period 0s to 10s. It is 0 between 10s and 18s and is constant with value minus 12 meters s2 between 18s and 20s. When the acceleration is uniform, obviously, it equals the average acceleration over that period. Since velocity is a quantity having both magnitude and direction, a change in velocity may involve either or both of these factors. Acceleration, therefore, may result from a change in speed magnitude, a change in direction, or changes in both. Like velocity, acceleration can also be positive, negative, or zero. Position time graphs for motion with positive, negative, and zero acceleration are shown in figs. 3.9 A, B and C, respectively. Note that the graph curves upward for positive acceleration, downward for negative acceleration, and it is a straight line for zero acceleration. As an exercise, identify in figure 3.3, the regions of the curve that correspond to these three cases. Although acceleration can vary with time, our study in this chapter will be restricted to motion with constant acceleration. In this case, the average acceleration equals the constant value of acceleration during the interval. If the velocity of an object is v at t0 and v at time t, we have a 0 volt via v via t 3.6 fig. 3.9 Position time graph for motion with a positive acceleration, b negative acceleration, and c zero acceleration. Let us see how velocity time graph looks like for some simple cases. Figure 3.10 shows velocity time graph for motion with constant acceleration for the following cases. An object is moving in a positive direction with a positive acceleration. For example, the motion of the car in figure 3.3 between t0s and t10s. B. An object is moving in positive direction with a negative acceleration. For example, motion of the car in figure 3.3 between t18s and 20s. C. An object is moving in negative direction with a negative acceleration. For example, the motion of a car moving from O in fig. 3.1 in negative x direction with increasing speed. D. An object is moving in positive direction till time t1, and then turns back with the same negative acceleration. For example, the motion of a car from point O to point Q in fig. 3.1 till time t1 with decreasing speed and turning back and moving with the same negative acceleration. An interesting feature of a velocity time graph for any moving object is that the area under the curve represents the displacement over a given time interval. A general proof of this figure 3.10 velocity time graph for motions with constant acceleration. A motion in positive direction with positive acceleration. B. Motion in positive direction with negative acceleration. C. Motion in negative direction with negative acceleration. D. Motion of an object with negative acceleration that changes direction at time t1. Between time 0 to t1, it moves in positive x direction, and between t1 and t2 it moves in the opposite direction. Motion in a straight line. 47 Statement requires use of calculus. We can, however, see that it is true for the simple case of an object moving with constant velocity u. Its velocity time graph is as shown in figure 3.11. Figure 3.11 Area under vt curve equals displacement of the object over a given time interval. The VT curve is a straight line parallel to the time axis, and the area under it between t0 and tt is the area of the rectangle of height u and base t. Therefore, area uxt at which is the displacement in this time interval. How come in this case an area is equal to a distance? Think. Note the dimensions of quantities on the two coordinate axis, and you will arrive at the answer. Note that the xt, vt, and a t graphs shown in several figures in this chapter have sharp kinks at some points, implying that the functions are not differentiable at these points. In any realistic situation, the functions will be differentiable at all points and the graphs will be smooth. What this means physically is that acceleration and velocity cannot change values abruptly at an instant. Changes are always continuous. 3.6 Kinematic equations for uniformly accelerated motion. For uniformly accelerated motion, we can derive some simple equations that relate displacement x, time taken t, initial velocity v0, final velocity v, and acceleration a. Equation 3.6 already obtained gives a relation between final and initial velocities v and v0 of an object moving with uniform acceleration a, v0 at 3.6. This relation is graphically represented in Fig. 3.12. The area under this curve is area between instant 0 and t, area of triangle ABC, area of rectangle OACT 001 volt VT VT2. Fig. 3.12. Area under VT curve for an object with uniform acceleration. As explained in the previous section, the area under VT curve represents the displacement. Therefore, the displacement x of the object is 1200 times vvt vt 3.7 but vv at t0. Therefore, 2012x at tvt or 2012x vt at 3.8. Equation 3.7 can also be written as 02 volt vx tvt 3.9. Aware 02 volt VV constant acceleration only 3.9b. Equations 3.9 and 3.9b mean that the object has undergone displacement x with an average velocity equal to the arithmetic average of the initial and final velocities. From x 3.6, tv, v0a, substituting this in x 3.9a, we get x vt vv vv a 00202222202 volt vx 3.10. Physics 48t. This equation can also be obtained by substituting the value of t from x 3.6 into x 3.8. Thus, we have obtained three important equations: 0 volt v at 2012x vt at 2202 volt vx 3.11, connecting five quantities v0, v, a, t and x. These are kinematic equations of rectilinear motion for constant acceleration. The set of x 3.11 were obtained by assuming that at t0, the position of the particle, x is 0. We can obtain a more general equation if we take the position coordinate at t0 as non-zero, say x0. Then eqs 3.11 are modified, replacing x by x, x02, 0 volt v at 20012x x vt at 3.11 b 22002 vv x x 3.11. See example 3.3. Obtain equations of motion for constant acceleration using method of calculus. Answer by definition: ddv at ttv at dt, integrating both sides. ddv at tv vt 00 at tt d0 is constant 0 vv at 0 volt v at further. ddx vt dx vdt, integrating both sides. dxxx 0 vtt d0 v at tt 00 d2001 x x vt at tx 20012 x vt at t. We can write ddddddddddvx via vtx tx or vd via dx, integrating both sides. VVX VVXX DD00220002 volt VXX 22002 VVXX. The advantage of this method is that it can be used for motion with non-uniform acceleration also. Now, we shall use these equations to some important cases. Example 3.4. A ball is thrown vertically upwards with a velocity of 20 meters s1 from the top of a multi-story building. The height of the point from where the ball is thrown is 25.0 meters from the ground. A. How high will the ball rise, and b. how long will it be before the ball hits the ground? Take g 10 meters s2. Answer A. Let us take the y-axis in the vertically upward direction with 0 at the ground, as shown in Fig. 3.13. Now a VO 20 meters s1, a g minus 10 meters s2, v 0 meters s1 if the ball rises to height y from the point of launch. Then using the equation 0220 volt v2 y, we get 0.222 minus 10 y0 solving, we get y0 20 meters. B. We can solve this part of the problem in two ways. Note carefully the method used. T. Motion in a straight line 49t. Figure 3.13. First method. In the first method, we split the path in two parts, the upward motion a to b and the downward motion b to c, and calculate the corresponding time taken t1 and t2. Since the velocity at b is 0, we have v(vo) at 0 20 10 t1 or t1 2s. This is the time in going from A to B from B, or the point of the maximum height. The ball falls freely under the acceleration due to gravity. The ball is moving in negative y direction. We use equation 2001 to y(vt) and we have y0 45 meters, y0, v0 0, a g minus 10 meters s2 0 45 1/2 minus 10 t2 2. Solving, we get t2 3s. Therefore, the total time taken by the ball before it hits the ground t1 t2 2s 3s 5s. Second method, the total time taken can also be calculated by noting the coordinates of initial and final positions of the ball with respect to the origin chosen and using equation 2001 to y(vt) at now y0 25 meters y0 meters (vo) 20 meters s1, a minus 10 ms2, t0 25 20 t1 half 10 t2 or 5 t2 20 t 25 0. Solving this quadratic equation for t, we get t5s. Note that the second method is better since we do not have to worry about the path of the motion as the motion is under constant acceleration. T example 3.5 free fall. Discuss the motion of an object under free fall. Neglect air resistance. Answer: an object released near the surface of the earth is accelerated downward under the influence of the force of gravity. The magnitude of acceleration due to gravity is represented by g. If air resistance is neglected, the object is said to be in free fall. If the height through which the object falls is small compared to the Earth's radius, g can be taken to be constant, equal to 9.8 meters s2. Free fall is thus a case of motion with uniform acceleration. We assume that the motion is in y direction, more correctly in y direction because we choose upward direction as positive. Since the acceleration due to gravity is always downward, it is in the negative direction and we have a g 9.8 meters s2. The object is released from rest at y0. Therefore, v0 0 and the equations of motion become v0 gt minus 9.8 tms1 y0 1/2 gram t2 minus 4.9 t2 meters v2 0 2 grams y minus 19.6 ym2 s2. These equations give the velocity and the distance traveled as a function of time and also the variation of velocity with distance. The variation of acceleration, velocity, and distance with time have been plotted in figure 3.14 a, b and c. A. Physics 50 TBC Figure 3.14 Motion of an object under free fall. A variation of acceleration with time. B. Variation of velocity with time. C. Variation of distance with time. T. Example 3.6 Galileo's law of odd numbers. The distances traversed during equal intervals of time, by a body falling from rest, stand to one another in the same ratio as the odd numbers beginning with unity, namely, 1, 3, 5, 7. Prove it. Answer: let us divide the time interval of motion of an object under free fall into many equal intervals Greek letter tau and find out the distances traversed during successive intervals of time. Since initial velocity is 0, we have using this equation, we can calculate the position of the object after different time intervals, 0, Greek letter tau, 2 Greek letter tau, 3 Greek letter tau, which are given in second column of table 3.2. If we take minus 1 to 2 as y0 the position coordinate after first time interval Greek letter tau, then third column gives the positions in the unit of yo. The fourth column gives the distances traversed in successives. We find that the distances are in the simple ratio 1, 3, 5, 7, 9, 11, as shown in the last column. This law was established by Galileo Galilei 1564-1642, who was the first to make quantitative studies of free fall. T. Example 3.7 Stopping distance of vehicles. When brakes are applied to a moving vehicle, the distance it travels before stopping is called stopping distance. It is an important factor for road safety and depends on the initial velocity v0 and the braking capacity, or deceleration, a, that is caused by the braking. Derive an expression for stopping distance of a vehicle in terms of vo and a. Answer: let the distance traveled by the vehicle before it stops be ds. Then, using equation of motion v2 vo 2 2x, and noting that v0, we have the stopping distance d via s0 2 to thus, the stopping distance is proportional to the square of the initial velocity. Doubling the t table 3.2 ygt 122, 2018, 1. Motion in a straight line 51 t initial velocity increases the stopping distance by a factor of 4 for the same deceleration. For the car of a particular make, the braking distance was found to be 10 meters, 20 meters, 34 meters and 50 meters corresponding to velocities of 11, 15, 20 and 25 meters s, which are nearly consistent with the above formula. Stopping distance is an important factor considered in setting speed limits, for example, in school zones. T. Example 3.8 Reaction time. When a situation demands our immediate action, it takes some time before we really respond. Reaction time is the time a person takes to observe, think and act. For example, if a person is driving and suddenly a boy appears on the road, then the time elapsed before he slams the brakes of the car is the reaction time. Reaction time depends on complexity of the situation and on an individual. You can measure your reaction time by a simple experiment. Take a ruler and ask your friend to drop it vertically through the gap between your thumb and forefinger. Fig. 3.15. After you catch it, find the distance d traveled by the ruler. In a particular case, d was found to be 21.0 centimeters. Estimate reaction time, or given d 21.0 centimeters and g 9.8 meters s2, the reaction time is t 3.7 relative velocity. You must be familiar with the experience of traveling in a train and being overtaken by another train moving in the same direction as you are. While that train must be traveling faster than you to be able to pass you, it does seem slower to you than it would be to someone standing on the ground and watching both the trains. In case both the trains have the same velocity with respect to the ground, then to you the other train would seem to be not moving at all. To understand such observations, we now introduce the concept of relative velocity. Consider two objects A and B moving uniformly with average velocities VA and VB in one dimension, say along x-axis. Unless otherwise specified, the velocities mentioned in this chapter are measured with reference to the ground. If ZA0 and XB0 are positions of objects A and B, respectively at time t0, their positions ZA_t and XB_t at time t are given by ZA_t ZA0 VA_t 3.12 XB_t XB0 VB_t 3.12b. Then, the displacement from object A to object B is given by XB_at XB_t ZA_t XB0 ZA0 VB, VA_t. 3.13 Equation 3.13 is easily interpreted. It tells us that as seen from object A, object B has a velocity VB, VA, because the displacement from A to B changes steadily by the amount VB, VA in each unit of time. We say that the velocity of object B relative to object A is VB, VA, VBA VB, VA 3.14 is similarly, velocity of object A relative to object B is VA, VB 3.14b. Fig. 3.15 Measuring the reaction time. Answer: the ruler drops under free fall, therefore, VO 0, and a g minus 9.8 meters s2. The distance traveled e and the reaction time tr are related by Physics 52. This shows VBA VAB 3.14. See, now we consider some special cases. A if VB VA, VB, VA 0. Then, from X 3.13, XBT ZA_t XB0 ZA0. Therefore, the two objects stay at a constant distance XB0 ZA0 apart, and their position time graphs are straight lines parallel to each other as shown in Fig. 3.16. The relative velocity VAB or VBA is 0 in this case. B if the VB VA is negative. One graph is steeper than the other and they meet at a common point. For example, suppose VA 20 meters s1 and ZA0 10 meters, and VB 10 meters s1, XB0 40 meters, then the time at which they meet is t3 s. Fig. 3.17. At this instant they are both at a position ZA_t XB_t 70 meters, thus, object A overtakes object B at this time. In this case, VBA 10 meters s1 20 meters s1 10 meters s1 VAB. C. Suppose VA and VB are of opposite signs. For example, if in the above example object A is moving with 20 meters s1 starting at ZA0 10 meters and object B is moving with 10 meters s1 starting at XB0 40 meters, the two objects meet at t1 s. Fig. 3.18. The velocity of B relative to A, VBA minus 1020 ms1 minus 30 meters s1 VAB. In this case, the magnitude of VBA or VAB 30 meters s1 is greater than the magnitude of velocity of A or that of B if the objects under consideration are two trains. Then for a person sitting on either of the two, the other train seems to go very fast. Note that Ek. 3.14 are valid even if A and VB represent instantaneous velocities. Example 3.92 Parallel rail tracks run north-south. Train A moves north with a speed of 54 km h1, and train B moves south with a speed of 90 km h1. What is the velocity of B with respect to A, B velocity of ground with respect to B, and C velocity of a monkey running on the roof of the train A against its motion with a velocity of 18 km h1 with respect to the train A is observed by a man standing on the ground? Answer: choose the positive direction of x-axis to be from south to north. Then, figure 3.16 position time graphs of two objects with equal velocities. Figure 3.17 position time graphs of two objects with unequal velocities, showing the time of meeting. Figure 3.18 position time graphs of two objects with velocities in opposite directions, showing the time of meeting. TST. Motion in a straight line 53 VA 54 km h1 15 meters s1 VB 90 km h1 25 meters s1 Relative velocity of B with respect to a VB, VA 40 meters s1, that is, The train B appears to A to move with a speed of 40 meters s1 from north to south. Relative velocity of ground with respect to B0 VB 25 meters s1. In C, let the velocity of the monkey with respect to ground be Vm, relative velocity of the monkey with respect to A. Vm A Vm, Va minus 18 kilometers h1 minus 5 m s1, therefore, Vm 15 5 meters s1 10 meters s1 T. Summary 1. An object is said to be in motion if its position changes with time. The position of the object can be specified with reference to a conveniently chosen origin. For motion in a straight line, position to the right of the origin is taken as positive and to the left as negative. 2. Path length is defined as the total length of the path traversed by an object. 3. Displacement is the change in position, x(x2, x1). Path length is greater or equal to the magnitude of the displacement between the same points. 4. An object is said to be in uniform motion in a straight line if its displacement is equal in equal intervals of time. Otherwise, the motion is said to be non-uniform. 5. Average velocity is the displacement divided by the time interval in which the displacement occurs, vxt on an xt graph. The average velocity over a time interval is the slope of the line connecting the initial and final positions corresponding to that interval. 6. Average speed is the ratio of total path length traversed and the corresponding time interval. The average speed of an object is greater or equal to the magnitude of the average velocity over a given time interval. 7. Instantaneous velocity or simply velocity is defined as the limit of the average velocity as the time interval t becomes infinitesimally small, d dt 0 t 0 xx v lim v lim tt. The velocity at a particular instant is equal to the slope of the tangent drawn on position time graph at that instant. 8. Average acceleration is the change in velocity divided by the time interval during which the change occurs, via t. 9. Instantaneous acceleration is defined as the limit of the average acceleration as the time interval t goes to 0, d dt 0 t 0 volt via lim tt. The acceleration of an object at a particular time is the slope of the velocity time graph at that instant of time. For uniform motion, acceleration is 0 and the xt graph is a straight line inclined to the time axis and the vt graph is a straight line. Physics 54 Parallel to the time axis. For motion with uniform acceleration, xt graph is a parabola while the vt graph is a straight line inclined to the time axis. 10. The area under the velocity time curve between times t1 and t2 is equal to the displacement of the object during that interval of time. 11. For objects in uniformly accelerated rectilinear motion, the 5 quantities, displacement x, time taken t, initial velocity v0, final velocity v and acceleration are related by a set of simple equations called kinematic equations of motion, vv0 at x vt12 at 0 2 vv2 x2 0 2 if the position of the object at time t0 is 0. If the particle starts at x0, x in above equations is replaced by x0 2018 1. Motion in a straight line 55 points to ponder 1. The path length traversed by an object between 2 points is, in general, not the same as the magnitude of displacement. The displacement depends only on the endpoints. The path length, as the name implies, depends on the actual path. In one dimension, the two quantities are equal only if the object does not change its direction during the course of motion. In all other cases, the path length is greater than the magnitude of displacement 2. In view of point 1 above, the average speed of an object is greater than or equal to the magnitude of the average velocity over a given time interval. The two are equal only if the path length is equal to the magnitude of displacement 3. The origin and the positive direction of an axis are a matter of choice. You should first specify this choice before you assign signs to quantities like displacement, velocity and acceleration. 4. If a particle is speeding up, acceleration is in the direction of velocity. If its speed is decreasing, acceleration is in the direction opposite to that of the velocity. This statement is independent of the choice of the origin and the axis. 5. The sign of acceleration does not tell us whether the particle's speed is increasing or decreasing. The sign of acceleration as mentioned in point 3 depends on the choice of the positive direction of the axis. For example, if the vertically upward direction is chosen to be the positive direction of the axis, the acceleration due to gravity is negative. If a particle is falling under gravity, this acceleration, though negative, results in increase in speed. For a particle thrown upward, the same negative acceleration of gravity results in decrease in speed. 6. The zero velocity of a particle at any instant does not necessarily imply zero acceleration at that instant. A particle may be momentarily at rest and yet have non-zero acceleration. For example, a particle thrown up has zero velocity at its uppermost point, but the acceleration at that instant continues to be the acceleration due to gravity. 7. In the kinematic equations of motion Ec 3.11, the various quantities are algebraic, that is, they may be positive or negative. The equations are applicable in all situations for one-dimensional motion with constant acceleration provided the values of different quantities are substituted in the equations with proper signs. 8. The definitions of instantaneous velocity and acceleration EQS 3.3 and 3.5 are exact and are always correct, while the kinematic equations EQ 3.11 are true only for motion in which the magnitude and the direction of acceleration are constant during the course of motion. Exercises 3.1 In which of the following examples of motion can the body be considered approximately a point object? A railway carriage moving without jerks between two stations. B. A monkey sitting on top of a man cycling smoothly on a circular track. C. A spinning cricket ball that turns sharply on hitting the ground. D. A tumbling beaker that has slipped off the edge of a table. 3.2 The position time xt graphs for two children A and B returning from their school O to their homes P and Q respectively are shown in Fig. 3.19. Choose the correct entries in the brackets below. AB lives closer to the school than BAB. AB starts from the school earlier than BAC. AB walks faster than BAD. A and B reach home at the same different time. AB overtakes BA on the road once twice. Physics 56 3.3 A woman starts from her home at 9 a.m., walks with a speed of 5 km h1 on a straight road up to her office 2.5 km away, stays at the office up to 5 p.m., and returns home by an auto with a speed of 25 km h1. Choose suitable scales and plot the xt graph of her motion. 3.4 A drunkard walking in a narrow lane takes 5 steps forward and 3 steps backward, followed again by 5 steps forward and 3 steps backward, and so on. Each step is 1 meter long and requires 1s. Plot the xt graph of his motion. Determine graphically and otherwise how long the drunkard takes to fall in a pit 13 meters away from the start. 3.5 A jet airplane traveling at the speed of 500 km h1 ejects its products of combustion at the speed of 1,500 km h1 relative to the jet plane. What is the speed of the latter with respect to an observer on the ground? 3.6 A car moving along a straight highway with speed of 126 km h1 is brought to a stop within a distance of 200 meters. What is the retardation of the car assumed uniform, and how long does it take for the car to stop? 3.72 Trains A and B of length 400 meters each are moving on two parallel tracks with a uniform speed of 72 km h1 in the same direction. With A ahead of B, the driver of B decides to overtake A and accelerates by 1 meters s2, if after 50 s. The guard of B just brushes past the driver of A. What was the original distance between them? 3.8 On a two-lane road, car A is traveling with a speed of 36 km h1. Two cars B and C approach car A in opposite directions with a speed of 54 km h1 each. At a certain instant, when the distance AB is equal to AC, both being 1 km, B decides to overtake A before C does. What minimum acceleration of car B is required to avoid an accident? 3.92 Towns A and B are connected by a regular bus service with a bus leaving in either direction every 10 minutes. A man cycling with a speed of 20 km h1 in the direction A to B notices that a bus goes past him every 18 minutes in the direction of his motion, and every 6 minutes in the opposite direction. What is the period T of the bus service and with what speed assumed constant do the buses ply on the road? 3.10 A player throws a ball upwards with an initial speed of 29.4 meters s1. A. What is the direction of acceleration during the upward motion of the ball? B. What are the velocity and acceleration of the ball at the highest point of its motion? C. Choose the x0 meters and t0 s to be the location and time of the ball at its highest point. Vertically downward direction to be the positive direction of x-axis, and give the signs of position, velocity and acceleration of the ball during its upward and downward motion. D. To what height does the ball rise and after how long does the ball return to the player's hands? Take G 9.8 meters s2 and neglect air resistance. Figure 3.19. Motion in a straight line 57 3.11 Read each statement below carefully and state with reasons and examples. If it is true or false, a particle in one-dimensional motion or with zero speed at an instant may have non-zero acceleration at that instant. B with zero speed may have non-zero velocity. C with constant speed must have zero acceleration. D with positive value of acceleration must be speeding up. 3.12 A ball is dropped from a height of 90 meters on a floor. At each collision with the floor, the ball loses 1/10 of its speed. Plot the speed-time graph of its motion between t0 to 12s. 3.13 Explain clearly, with examples, the distinction between a magnitude of displacement sometimes called distance over an interval of time, and the total length of path covered by a particle over the same interval. B. Magnitude of average velocity over an interval of time, and the average speed over the same interval. Average speed of a particle over an interval of time is defined as the total path length divided by the time interval. Show in both A and B that the second quantity is either greater than or equal to the first. When is the equality sign true? For simplicity, consider one-dimensional motion only. 3.14 A man walks on a straight road from his home to a market 2.5 kilometers away with a speed of 5 kilometers h1. Finding the market closed, he instantly turns and walks back home with a speed of 7.5 kilometers h1. What is the magnitude of average velocity? And B. Average speed of the man over the interval of time I0 to 30 minutes, 20 to 50 minutes, 30 to 40 minutes. Note, you will appreciate from this exercise why it is better to define average speed as total path length divided by time, and not as magnitude of average velocity. You would not like to tell the tired man on his return home that his average speed was 3.15 in exercises 3.13 and 3.14. We have carefully distinguished between average speed and magnitude of average velocity. No such distinction is necessary when we consider instantaneous speed and magnitude of velocity. The instantaneous speed is always equal to the magnitude of instantaneous velocity. Y 3.16. Look at the graphs at 2D Fig. 3.20 carefully and state, with reasons, which of these cannot possibly represent one-dimensional motion of a particle. Figure 3.20. Physics 58. Figure 3.24. Figure 3.21. 3.17. Figure 3.21 shows the xt plot of one-dimensional motion of a particle. Is it correct to say from the graph that the particle moves in a straight line for t, 0 and on a parabolic path for t, 0? If not, suggest a suitable physical context for this graph. 3.18. A policeman moving on a highway with a speed of 30 km h1 fires a bullet at a thief's car speeding away in the same direction with a speed of 192 km h1. If the muzzle speed of the bullet is 150 meters s1, with what speed does the bullet hit the thief's car? Note, obtain that speed which is relevant for damaging the thief's car. 3.19. Suggest a suitable physical situation for each of the following graphs. Figure 3.22, Figure 3.22. 3.20. Figure 3.23 gives the xt plot of a particle executing one-dimensional simple harmonic motion. You will learn about this motion in more detail in Chapter 14. Give the signs of position, velocity and acceleration variables of the particle at t 0.3 s, 1.2 s, 1.2 s. Figure 3.23. 3.21. Figure 3.24 gives the xt plot of a particle in one-dimensional motion. 3 different equal intervals of time are shown. In which interval is the average speed greatest, and in which is it the least? Give the sign of average velocity for each interval. Motion in a straight line. 59. 3.22. Figure 3.25 gives a speed-time graph of a particle in motion along a constant direction. 3 equal intervals of time are shown. In which interval is the average acceleration greatest in magnitude? In which interval is the average speed greatest? Choosing the positive direction as the constant direction of motion. Give the signs of v and a in the 3 intervals. What are the accelerations at the points A, B, C and D? Additional exercises. 3.23. A three-wheeler starts from rest, accelerates uniformly with 1 meters s2 on a straight road for 10 s, and then moves with uniform velocity. Plot the distance covered by the vehicle during the nth second n1, 2, 3, versus n. What do you expect this plot to be during accelerated motion, a straight line or a parabola? 3.24. A boy standing on a stationary lift open from above throws a ball upwards with the maximum initial speed he can, equal to 49 meters s1. How much time does the ball take to return to his hands if the lift starts moving up with a uniform speed of 5 meters s1 and the boy again throws the ball up with the maximum speed he can? How long does the ball take to return to his hands? 3.25. On a long horizontally moving belt. Fig. 3.26. A child runs to and fro with a speed 9 km h-1 with respect to the belt between his father and mother located 50 meters apart on the moving belt. The belt moves with a speed of 4 km h1. For an observer on a stationary platform outside, what is the speed of the child running in the direction of motion of the belt? B. Speed of the child running opposite to the direction of motion of the belt. C. Time taken by the child in A and B. Which of the answers alter if motion is viewed by one of the parents? Fig. 3.26. 3.26. 2 stones are thrown up simultaneously from the edge of a cliff 200 meters high with initial speeds of 15 meters s1 and 30 meters s1. Verify that the graph shown in Figure 3.27 correctly represents the time variation of the relative position of the second stone with respect to the first. Neglect air resistance and assume that the stones do not rebound after hitting the ground. Take g 10 meters s2. Give the equations for the linear and curved parts of the plot. Figure 3.25. Physics 60. Figure 3.27. 3.27. The speed-time graph of a particle moving along a fixed direction is shown in Fig. 3.28. Obtain the distance traversed by the particle between a t0s to 10s, bt2s to 6s. Figure 3.28. What is the average speed of the particle over the intervals in A and B? 3.28. The velocity-time graph of a particle in one-dimensional motion is shown in Fig. 3.29. Fig. 3.29 Which of the following formulae are correct for describing the motion of the particle over the time interval t1 to t2? A x t2 x t1 v t1 t2 t1 1 half a t2 t1 2 b v t2 v t1 a t2 t1 c average x t2 x t1 t2 t1 d average v t2 v t1 t2 t1 e x t2 x t1 average t2 t1 1 half average t2 t1 2 f x t2 x t1 area under the vt curve bounded by the t-axis and the dotted line shown. Motion in a straight line 61 Appendix 3.1 Elements of calculus Differential calculus using the concept of differential coefficient or derivative. We can easily define velocity and acceleration, though you will learn in detail in mathematics about derivatives. We shall introduce this concept in brief in this appendix so as to facilitate its use in describing physical quantities involved in motion. Suppose we have a quantity y whose value depends upon a single variable x, and is expressed by an equation defining y as some specific function of x. This is represented as y f x1. This relationship can be visualized by drawing a graph of function y f x regarding y and x as Cartesian coordinates, as shown in Fig. 3.30 at B. Figure 3.30 Consider the point P on the curve y f x whose coordinates are x, y and another point Q where coordinates are x x, y y. The slope of the line joining P and Q is given by x y y y x y tan Greek letter theta 2. Suppose now that the point Q moves along the curve towards P in this process. Y and x decrease and approach 0, though their ratio yx will not necessarily vanish. What happens to the line PQ as y0, x0? You can see that this line becomes a tangent to the curve at point P as shown in Fig. 3.30b. This means that tan Greek letter theta approaches the slope of the tangent at P. Denoted by m, x00 lim x y y y y m x x3. The limit of the ratio yx as x approaches 0 is called the derivative of y with respect to x and is written as di dx. It represents the slope of the tangent line to the curve yfx at the point x, y, since yfx and yfx. We can write the definition of the derivative as xxfxxfxyx lim dx d dx di 00 xxf. Given below are some elementary formulae for derivatives of functions. In these ux and vx represent arbitrary functions of x, and a and b denote constant quantities that are independent of x. Derivatives of some common functions are also listed. Physics 62 x u x u d d d a d, d d d. d d d u u x t x t x u v x v u x of d d d d d d, 2 d 1 d d, d d d u v u v u x x 15 x v x u v u d d d d d d x x x cos sin d d, d cos sin d x x x 2 d tan sec d x x x, 2 d cot cos d x x x x x x x x sec tan sec d d, 2 d cosec cot cosec d x x x x x u u n u x n n d d d d 1. d1 ln du u d e d u u. In terms of derivatives, instantaneous velocity and acceleration are defined as tx tx vt dd lim 0220 dd lim dd tvvx a ttt. Integral calculus. You are familiar with the notion of area. The formulae for areas of simple geometrical figures are also known to you. For example, the area of a rectangle is length times breadth and that of a triangle is half of the product of base and height. But how to deal with the problem of determination of area of an irregular figure? The mathematical notion of integral is necessary in connection with such problems. Let us take a concrete example. Suppose a variable force Fx acts on a particle in its motion along x-axis from x to xb. The problem is to determine the work done W by the force on the particle during the motion. This problem is discussed in detail in Chapter 6. Figure 3.31 shows the variation of Fx with x if the force were constant. Work would be simply the area Fb as shown in Fig. 3.31i, but in the general case, force is varying. Figure 3.31. Motion in a straight line 63. To calculate the area under this curve. Figure 3.312. Let us employ the following trick. Divide the interval on x-axis from a to b into a large number n of small intervals, x0 to x1, x1 to x2, x2 to x3, xn1 to xnb. The area under the curve is thus divided into n strips. Each strip is approximately a rectangle, since the variation of Fx over a strip is negligible. The area of the ith strip shown Figure 3.312 is then approximately xxfxxxfa2ii1 where x is the width of the strip which we have taken to be the same for all the strips. You may wonder whether we should put fψ1 or the mean of fψ and fψ1 into the above expression. If we take n to be very large n, it does not really matter, since then the strip will be so thin that the difference between fψ and fψ1 is vanishingly small. The total area under the curve n is NIINIIXXFAA11. The limit of this sum as n is known as the integral of Fx over x from a to b. It is given a special symbol as shown below, via dxxfa. The integral sign looks like an elongated S, reminding us that it basically is the limit of the sum of an infinite number of terms. A most significant mathematical fact is that integration is, in a sense, an inverse of differentiation. Suppose we have a function gx whose derivative is fx, that is, dxx dgxf. A function gx is known as the indefinite integral of fx and is denoted as dxx fxg. An integral with lower and upper limits is known as a definite integral. It is a number. Indefinite integral has no limits. It is a function. A fundamental theorem of mathematics states that a gbgx gdxxf be a b. As an example, suppose fx(x2) and we wish to determine the value of the definite integral from x1 to x2. The function gx whose derivative is x2 is x33. Therefore, 3731382121223x dxx3. Clearly, to evaluate definite integrals, we need to know the corresponding indefinite integrals. Some common indefinite integrals are ln1xxxxd0. This introduction to differential and integral calculus is not rigorous and is intended to convey to you the basic notions of calculus. 2018 1. Chapter 4 Motion in a Plane 4.1 Introduction. In the last chapter we developed the concepts of position, displacement, velocity and acceleration that are needed to describe the motion of an object along a straight line. We found that the directional aspect of these quantities can be taken care of by n signs, as in one dimension only two directions are possible. But in order to describe motion of an object in two dimensions, a plane or three dimensions space, we need to use vectors to describe the above-mentioned physical quantities. Therefore, it is first necessary to learn the language of vectors. What is a vector? How to add, subtract and multiply vectors? What is the result of multiplying a vector by a real number? We shall learn this to enable us to use vectors for defining velocity and acceleration in a plane. We then discuss motion of an object in a plane. As a simple case of motion in a plane, we shall discuss motion with constant acceleration and treat in detail the projectile motion. Circular motion is a familiar class of motion that has a special significance in daily life situations. We shall discuss uniform circular motion in some detail. The equations developed in this chapter for motion in a plane can be easily extended to the case of three dimensions. 4.2 Scalars and vectors. In physics, we can classify quantities as scalars or vectors. Basically, the difference is that a direction is associated with a vector but not with a scalar. A scalar quantity is a quantity with magnitude only. It is specified completely by a single number, along with the proper unit. Examples are the distance between 2 points, mass of an object, the temperature of a body and the time at which a certain event happened. The rules for combining scalars are the rules of ordinary algebra. Scalars can be added, subtracted, multiplied and divided. 4.1 Introduction. 4.2 Scalars and vectors. 4.3 Multiplication of vectors by real numbers. 4.4 Addition and subtraction of vectors. Graphical method. 4.5 Resolution of vectors. 4.6 Vector addition. Analytical method. 4.7 Motion in a plane. 4.8 Motion in a plane with constant acceleration. 4.9 Relative velocity in two dimensions. 4.10 Projectile motion. 4.11 Uniform circular motion. Summary points to ponder. Exercises. Additional exercises. Physics 66. Just as the ordinary numbers, for example, if the length and breadth of a rectangle are 1.0 meters and 0.5 meters respectively, then its perimeter is the sum of the lengths of the four sides, 1.0 meters, 0.5 meters, 1.0 meters, 0.5 meters, 3.0 meters. The length of each side is a scalar and the perimeter is also a scalar. Take another example. The maximum and minimum temperatures on a particular day are 35.6 degrees Celsius and 24.2 degrees Celsius respectively. Then, the difference between the two temperatures is 11.4 degrees Celsius. Similarly, if a uniform solid cube of aluminium of side 10 centimeters has a mass of 2.7 kilograms, then its volume is 10-3 m3 a scalar and its density is 2.7 x 103 kilograms m3 a scalar. A vector quantity is a quantity that has both a magnitude and a direction and obeys the triangle law of addition or equivalently the parallelogram law of addition. So, a vector is specified by giving its magnitude by a number and its direction. Some physical quantities that are represented by vectors are displacement, velocity, acceleration and force. To represent a vector, we use a boldface type in this book. Thus, a velocity vector can be represented by a symbol v. Since boldface is difficult to produce, when written by hand, a vector is often represented by an arrow placed over a letter, say RV. Thus, both v and rv represent the velocity vector. The magnitude of a vector is often called its absolute value, indicated by vv. Thus, a vector is represented by a boldface, e.g. by a, p, q, r, x, y, with respective magnitudes denoted by lightface a, p, q, r. x, y4, 2, 1 position and displacement vectors to describe the position of an object moving in a plane. We need to choose a convenient point, say O as origin. Let P and P be the positions of the object at time t and t, respectively. Figure 4.1a, we join O and P by a straight line. Then, OP is the position vector of the object at time t. An arrow is marked at the head of this line. It is represented by a symbol r, that is OPR. Point P is represented by another position vector, OP denoted by r. The length of the vector r represents the magnitude of the vector and its direction is the direction in which P lies as seen from O if the object moves from P to P. The vector PP with tail at P and tip at P is called the displacement vector corresponding to motion from point P at time t to point P at time t. Figure 4.1 a position and displacement vectors B displacement vector PQ and different courses of motion. It is important to note that displacement vector is the straight line joining the initial and final positions and does not depend on the actual path undertaken by the object between the two positions. For example, in figure 4.1b, given the initial and final positions as P and Q, the displacement vector is the same PQ for different paths of journey. Say PABCQ, PDQ, and PBEFQ. Therefore, the magnitude of displacement is either less or equal to the path length of an object between 2 points. This fact was emphasized in the previous chapter also while discussing motion along a straight line. 4.2 equality of vectors. Two vectors A and B are said to be equal if, and only if, they have the same magnitude and the same direction. Figure 4.2a shows two equal vectors A and B. We can easily check their equality. Shift B parallel to itself until its tail Q coincides with that of A, that is, Q coincides with O. Then, since their tips S and P also coincide, the two vectors are said to be equal. In general, equality is indicated. Addition and subtraction of scalars make sense only for quantities with same units. However, you can multiply and divide scalars of different units. In our study, vectors do not have fixed locations. So displacing a vector parallel to itself leaves the vector unchanged. Such vectors are called free vectors. However, in some physical applications, location or line of application of a vector is important. Such vectors are called localized vectors. Motion in A-plane 67 as AB. Note that in figure 4.2b, vectors A and B have the same magnitude but they are not equal because they have different directions. Even if we shift B parallel to itself so that its tail Q coincides with the tail O of A, the tip S of B does not coincide with the tip P of A. 4.3 Multiplication of vectors by real numbers. Multiplying a vector A with a positive number Greek letter lambda gives a vector whose magnitude is changed by the factor Greek letter lambda but the direction is the same as that of A, Greek letter lambda A, Greek letter lambda A if Greek letter lambda, 0. For example, if A is multiplied by 2, the resultant vector 2A is in the same direction as A and has a magnitude twice of A as shown in Fig. 4.3a. Multiplying a vector A by a negative number Greek letter lambda gives another vector whose direction is opposite to the direction of A and whose magnitude is Greek letter lambda times A. Multiplying a given vector A by negative numbers, say -1 and -1.5, gives vectors as shown in figure 4.3b. The factor Greek letter lambda by which a vector A is multiplied could be a scalar having its own physical dimension. Then, the dimension of Greek letter lambda A is the product of the dimensions of Greek letter lambda and A. For example, if we multiply a constant velocity vector by duration of time, we get a displacement vector. 4.4 Addition and subtraction of vectors. Graphical method as mentioned in section 4.2. Vectors, by definition, obey the triangle law or equivalently, the parallelogram law of addition. We shall now describe this law of addition using the graphical method. Let us consider two vectors A and B that lie in a plane as shown in Fig. 4.4a. The lengths of the line segments representing these vectors are proportional to the magnitude of the vectors. To find the sum AB, we place vector B so that its tail is at the head of the vector A, as in Fig. 4.4b. Then, we join the tail of A to the head of B. This line OQ represents a vector R, that is, the sum of the vectors A and B. Since in this procedure of vector addition, vectors are figure 4.2 a. Two equal vectors A and B. Two vectors A and B are unequal though they are of the same length. Figure 4.3 of vector A and the resultant vector after multiplying A by a positive number 2b. Vector A and resultant vectors after multiplying it by a negative number -1 and -1.5. CD figure 4.4 of vectors A and B. Vectors A and B added graphically. C vectors B and A added graphically. D. Illustrating the associative law of vector addition. Physics 68 Arranged head to tail. This graphical method is called the head-to-tail method. The two vectors and their resultant form three sides of a triangle, so this method is also known as triangle method of vector addition. If we find the resultant of BA as in figure 4.4c, the same vector R is obtained. Thus, vector addition is commutative. ABBA 4.1 The addition of vectors also obeys the associative law as illustrated in Fig. 4.4d. The result of adding vectors A and B first and then adding vector C is the same as the result of adding B and C first and then adding vector A. ABC 4.2 What is the result of adding two equal and opposite vectors? Consider two vectors A and A shown in Fig. 4.3b. Their sum is AA, since the magnitudes of the two vectors are the same, but the directions are opposite. The resultant vector has zero magnitude and is represented by 0 called a null vector or a zero vector, A0 0 0 4.3 Since the magnitude of a null vector is 0. Its direction cannot be specified. The null vector also results when we multiply a vector A by the number 0. The main properties of 0 are, A0 A Greek letter lambda 0 0 0 A0 4.4 Figure 4.5 A two vectors A and B is also shown. B subtracting vector B from vector A, the result is R2. For comparison, addition of vectors A and B, that is, R1 is also shown. What is the physical meaning of a zero vector? Consider the position and displacement vectors in a plane as shown in Fig. 4.1a. Now suppose that an object which is at P at time t, moves to P and then comes back to P then. What is its displacement? Since the initial and final positions coincide, the displacement is a null vector. Subtraction of vectors can be defined in terms of addition of vectors. We define the difference of two vectors A and B as the sum of two vectors A and B. BAB 4.5 It is shown in Figure 4.5. The vector B is added to vector A to get R2A, B. The vector R1AB is also shown in the same figure for comparison. We can also use the parallelogram method to find the sum of two vectors. Suppose we have two vectors A and B to add these vectors. We bring their tails to a common origin O as shown in Figure 4.6a. Then we draw a line from the head of A parallel to B and another line from the head of B parallel to A to complete a parallelogram OQSP. Now we join the point of the intersection of these two lines to the origin O. The resultant vector R is directed from the common origin O along the diagonal OS of the parallelogram Fig. 4.6b. In Figure 4.6c, the triangle law is used to obtain the resultant of A and B, and we see that the two methods yield the same result. Thus, the two methods are equivalent. Motion in A-plane 69T Example 4.1 Rain is falling vertically with a speed of 35 meters s1. Wind starts blowing after some time with a speed of 12 meters s1 in east to west direction. In which direction should a boy waiting at a bus stop hold his umbrella? Figure 4.7 Answer. The velocity of the rain and the wind are represented by the vectors VR and VW in Fig. 4.7 and are in the direction specified by the problem. Using the rule of vector addition, we see that the resultant of VR and VW is R as shown in the figure. The magnitude of R is RVV R2W2 35 12 meters S 37 meters S2 211. The direction Greek letter theta that R makes with the vertical is given by 12 tan 0.343 35 WRVV Greek letter theta or Greek letter theta degrees tan 10 343 19. Therefore, the boy should hold his umbrella in the vertical plane at an angle of about 19° with the vertical towards the east. T Figure 4.6 A two vectors A and B with their tails brought to a common origin B. The sum AB obtained using the parallelogram method. See the parallelogram method of vector addition is equivalent to the triangle method. 4.5 Resolution of vectors. Let A and B be any two non-zero vectors in a plane with different directions and let A be another vector in the same plane. Fig. 4.8 A can be expressed as a sum of two vectors, one obtained by multiplying A by a real number and the other obtained by multiplying B by another real number. To see this, let O and P be the tail and head of the vector A. Then, through O, draw a straight line parallel to A, and through P, a straight line parallel to B. Let them intersect at Q. Then, we have AOPOQQP 4.6. But since OQ is parallel to A, and QP is parallel to B, we can write OQ Greek letter lambda A, and QP micro B 4.7 where Greek letter lambda and micro O are real numbers. Therefore, A Greek letter lambda and micro B 4.8 Figure 4.8 A two non-collinear vectors A and B resolving a vector A in terms of vectors A and B. We say that A has been resolved into two component vectors Greek letter lambda and micro B along A and B respectively. Using this method one can resolve Physics 70 Figure 4.9 A unit vectors I, J and K lie along the X, Y, and Z axes. B A vector A is resolved into its components X and I along X and Y axes. CA1 and A2 expressed in terms of I and J. A given vector into two component vectors along a set of two vectors. All the three lie in the same plane. It is convenient to resolve a general vector along the axes of a rectangular coordinate system using vectors of unit magnitude. These are called unit vectors that we discuss now. A unit vector is a vector of unit magnitude and points in a particular direction. It has no dimension and unit. It is used to specify a direction only. Unit vectors along the x, y and z axes of a rectangular coordinate system are denoted by I, j and k, respectively, as shown in Fig. 4.9a. Since these are unit vectors, we have ijk1 4.9. These unit vectors are perpendicular to each other. In this text, they are printed in boldface with a cap to distinguish them from other vectors. Since we are dealing with motion in 2 dimensions in this chapter, we require use of only 2 unit vectors. If we multiply a unit vector, say n by a scalar, the result is a vector Greek letter lambda 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 n in general. A vector A can be written as AAN 4.10 where n is a unit vector along A. We can now resolve a vector A in terms of component vectors that lie along unit vectors I and j. Consider a vector A that lies in xy plane as shown in figure 4.9b. We draw lines from the head of A perpendicular to the coordinate axes as in Fig. 4.9b, and get vectors A1 and A2 such that A1 A2a since A1 is parallel to I and A2 is parallel to j. We have A1 axi, A2 ij 4.11 where x and I are real numbers, thus, A axi ij 4.12. This is represented in Fig. 4.9c, the quantities x and I are called x and y components of the vector A. Note that x is itself not a vector, but xi is a vector, and so is ij. Using simple trigonometry, we can express x and I in terms of the magnitude of A and the angle Greek letter theta it makes with the x-axis, x A cos Greek letter theta I A sin Greek letter theta. 4.13 as is clear from Ek. 4.13, a component of a vector can be positive, negative or zero depending on the value of Greek letter theta. Now, we have 2 ways to specify a vector A in a plane. It can be specified by I its magnitude A and the direction Greek letter theta it makes with the x-axis, or 2 its components x and I. If A and Greek letter theta are given, x and I can be obtained using Ek. 4.13, if x and I are given, A and Greek letter theta can be obtained as follows: AAX2Y22222 cos sin Greek letter theta A2 or AAX2Y2 4.14 and tan Greek letter theta AAAYXYX1 4.15. Motion in A-plane 71 TBIJBBXY. Let R be their sum. We have RABAABBXYXYIJIJ 4.19. As since vectors obey the commutative and associative laws, we can arrange and regroup the vectors in Ek. 4.19 is convenient to us. RIJABABXXYY 4.19b. Since RIJRRXY 4.20 we have XXXYY or AB, RAB 4.21. Thus, each component of the resultant vector R is the sum of the corresponding components of A and B in 3 dimensions. We have AIJKAXYZBIJKBBBXYZRABIJKRRRXYZ with RABXXXRA by YYRABZZZ 4.22. This method can be extended to addition and subtraction of any number of vectors. For example, if vectors A, B and C are given as IJKAXYZBIJKBBBXYZCIJKCCCXYZ 4.23 then a vector TAB, C has components, TABCXXXX TABCYYY 4.23b TABCZZZZ. Example 4.2. Find the magnitude and direction of the resultant of 2 vectors A and B in terms of their magnitudes and angle Greek letter theta between them. Figure 4.9d. A vector A resolved into components along x, y, and z axes. Note that angles Greek letter alpha, Greek letter beta, and Greek letter gamma are angles in space. They are between pairs of lines, which are not coplanar. So far we have considered a vector lying in an xy plane. The same procedure can be used to resolve a general vector A into 3 components along x, y, and z axes in 3 dimensions. If Greek letter alpha, Greek letter beta, and Greek letter gamma are the angles between A and the x, y, and z axis, respectively figure 4.9d, we have dxy's A cos. AA cos Greek letter alpha Greek letter beta Greek letter gamma 4.16. In general, we have xy's AAAIJK 4.16b. The magnitude of vector A is 222 xy's AAA 4.16 ca. Position vector R can be expressed as RIJKXYZ 4.17 where x, y, and z are the components of R along x, y, z axis, respectively. 4.6 Vector addition, analytical method. Although the graphical method of adding vectors helps us in visualizing the vectors and the resultant vector, it is sometimes tedious and has limited accuracy. It is much easier to add vectors by combining their respective components. Consider 2 vectors A and B in xy plane with components x, I and bx, by AIJAXY 4.18. Physics 72T Figure 4.10 Answer. Let OP and OQ represent the two vectors A and B making an angle Greek letter theta. Fig. 4.10. Then, using the parallelogram method of vector addition, OS represents the resultant vector R. RABSN is normal to OP and PM is normal to OS, from the geometry of the figure. OS2 on 2 SN2 but on OPPN AB cos Greek letter theta SNB sin Greek letter theta OS2 AB cos Greek letter theta 2B sin Greek letter theta 2 or R2A2B2 to ob cos Greek letter theta RAB to ob 2 cos 4.24 in OSN, SN OS sin R sin, and in PSN. SN PS sin Greek letter theta B sin Greek letter theta. Therefore, R sin Greek letter alpha B sin Greek letter theta or RB sin Greek letter theta Greek letter alpha 4.24 B. Similarly, PMA sin Greek letter alpha B sin Greek letter beta or AB sin Greek letter beta Greek letter alpha 4.24 C. Combining EQS 4.24b and 4.24c, we get RA sin Greek letter theta Greek letter beta Greek letter alpha B 4.24d. Using EC 4.24d, we get sin Greek letter alpha Greek letter theta BR 4.24e where R is given by EC 4.24 or sin tan cos SNB OPPN AB Greek letter theta Greek letter alpha Greek letter theta 4.24 F. Equation 4.24 gives the magnitude of the resultant and EQS 4.24e and 4.24f its direction. Equation 4.24a is known as the law of cosines and EC 4.24d is the law of sines. T. Example 4.3a motorboat is racing towards north at 25 km h and the water current in that region is 10 km h in the direction of 60 degrees east of south. Find the resultant velocity of the boat. Answer. The vector VB representing the velocity of the motorboat and the vector VC representing the water current are shown in Fig. 4.11 in directions specified by the problem. Using the parallelogram method of addition, the resultant R is obtained in the direction shown in the figure. Figure 4.11 we can obtain the magnitude of R using the law of cosine. RVBVB2C2BC2 cos 120 0 25 10 2 25 10 1 2 22 km h 2 XX to obtain the direction. We apply the law of sines. RVC sin Greek letter theta Greek letter phi or sin Greek letter phi Greek letter theta VRC sin 10 sin 120 21.8 10 3 2 21.8 0.397 XX Greek letter phi 23.4 T 4.7 Motion in a plane. In this section we shall see how to describe motion in two dimensions using vectors. Motion in a plane 73.4.7. 1 position vector and displacement. The position vector R of a particle P located in a plane with reference to the origin of an XY reference frame. Fig. 4.12 is given by RIJXY where X and Y are components of R along X, and Y axes or simply they are the coordinates of the object. A B. Figure 4.12 a position vector RB displacement R and average velocity V of a particle. Suppose that particle moves along the curve shown by the thick line and is at P at time T and P at time T. Fig. 4.12b. Then, the displacement is R 4.25 and is directed from P to P. We can write EC 4.25 inches a component form, RXYXIJIJIJXY where XXX. Y 4.26 velocity. The average velocity V of an object is the ratio of the displacement and the corresponding time interval, VRIJIJTXYTXTYT 4.27 or, X of VBIJ since VRT, the direction of the average velocity is the same as that of R. Fig. 4.12. The velocity instantaneous velocity is given by the limiting value of the average velocity as the time interval approaches 0. VRR lim TTT 0 DD 4.28. The meaning of the limiting process can be easily understood with the help of figure 4.13 A to D. In these figures, the thick line represents the path of an object, which is at P at time t. P1, P2 and P3 represent the positions of the object after times T1, T2, and T3. R1, R2, and R3 are the displacements of the object in times T1, T2, and figure 4.13 as the time interval T approaches 0, the average velocity approaches the velocity V. The direction of V is parallel to the line tangent to the path. Physics 74T3, respectively, the direction of the average velocity V is shown in figures A, B and C for 3 decreasing values of T, that is, T1, T2, and T3, T1, T2, T3, as T0, R0 and is along the tangent to the path. Fig. 4.13d. Therefore, the direction of velocity at any point on the path of an object is tangential to the path at that point and is in the direction of motion. We can express V in a component form, VRD dt lim XT y TT0 IJ 4.29 IJ lim XT lim y TT T00 or VIJIJDDDDXTYTVVXY. Where VXTVYTXYDDDD 4.30 is so, if the expressions for the coordinates x and y are known as functions of time, we can use these equations to find Vx and y. The magnitude of V is then VVVx2y2 4.30b and the direction of V is given by the angle Greek letter theta, tan 1 Greek letter theta VVVVYXYX. 4.30 CVx, y and angle Greek letter theta are shown in figure 4.14 for a velocity vector v. Acceleration. The average acceleration of an object for a time interval t moving in xy plane is the change in velocity divided by the time interval, a VIJIJTVVTVTVTXYXY 4.31 or IJXY. 4.31b. The acceleration. Instantaneous acceleration is the limiting value of the average acceleration as the time interval approaches zero, a v lim tt0 4.32 since vvv, xyij we have a ij lim vt txty00 or IJXY 4.32b where a VTXXYYDDDD 4.32c as in the case of velocity. We can understand graphically the limiting process used in defining acceleration on a graph showing the path of the object's motion. This is shown in figures 4.15 at 2D. P represents the position of the object at time t and P1, P2, P3 positions after time T1, T2, T3, respectively T1, T2, T3. The velocity vectors at points P, P1, P2, P3 are also shown in figures 4.15 a, b and c. In each case of t, v is obtained using the triangle law of vector addition. By definition, the direction of average acceleration is the same as that of v. We see that as t decreases, the direction of v changes and consequently, the direction of the acceleration changes. Finally, in the limit tg0 figure 4.15d, the average acceleration becomes the instantaneous acceleration and has the direction as shown. Figure 4.1 for the components vx and y of velocity v and the angle Greek letter theta it makes with x-axis. Note that vx v cos Greek letter theta, vy v sin Greek letter theta. In terms of x and y, a x and a y can be expressed as motion in a plane 75 txm. Note that in one dimension, the velocity and the acceleration of an object are always along the same straight line either in the same direction or in the opposite direction. However, for motion in 2 or 3 dimensions, velocity and acceleration vectors may have any angle between 0 degrees and 180 degrees between them. Example 4.4 The position of a particle is given by RIJK 3.0 T20502 T where T is in seconds and the coefficients have the proper units for R to be in meters. Find Vt entity of the particle B. Find the magnitude and direction of Vt at d1.0 s. Answer VRIJKTTTT2DDD3.02.05.03.0.0 IJ4T of EJTTDD 4.0 or 4.0 meters s2 along y direction at d1.0 s. 3.0 4.0 volt IJ its magnitude is 221,345.0 meters SV and direction is 114 tan 53 y x VV Greek letter theta degrees with x-axis. T 4.8 Motion in a plane with constant acceleration. Suppose that an object is moving in xy plane and its acceleration is constant. Over an interval of time, the average acceleration will equal this constant value. Now, let the velocity of the object be v0 at time t0 and v at time t. Then, by definition of VVVV00 TT0 or VV0 T 4.33 in terms of components, VV TXX VV TYY 4.33b. Let us now find how the position R changes with time. We follow the method used in the one-dimensional case. Let ρ and R be the position vectors of the particle at time 0 and t and let the velocities at these instants be v and v. Then, over this time interval t, the average velocity is v2. The displacement is the average velocity multiplied by the time interval, RRVV via v0000022 TTT Fig. 4.15 The average acceleration for 3 time intervals at t1, bt2, and ct3, t1, t2, t3. D in the limit tg0, the average acceleration becomes the acceleration. Physics 76 TT 21 2 TT 0 volt or RRV 00 TT 1224.34 It can be easily verified that the derivative of EC 4.34 that is ddRt gives EC 4.33 and it also satisfies the condition that at t0, R ρ. Equation 4.34 can be written in component form as xxvt at ox x0 21 2 21 20 oiyvt at t 4.34b. One immediate interpretation of EC 4.34b is that the motions in x and y directions can be treated independently of each other. That is, motion in a plane 2 dimensions can be treated as two separate simultaneous one-dimensional motions with constant acceleration along two perpendicular directions. This is an important result and is useful in analyzing motion of objects in 2 dimensions. A similar result holds for 3 dimensions. The choice of perpendicular directions is convenient in many physical situations, as we shall see in section 4.10 for projectile motion. Example 4.5. A particle starts from origin at t0 with a velocity 5.0 I circumflex ms and moves in xy plane under action of a force which produces a constant acceleration of 3.0 I 2.0 joules ms2. What is the y-coordinate of the particle at the instant its x-coordinate is 84 meters? B. What is the speed of the particle at this time? Answer from AC. 4.34. For r00, the position of the particle is given by 21.2 TTT0 r via 25.0123.02.0 TTIJ 225.01.51.0 TTTIJ. Therefore 25.01.5 times TTT 21.0 YTT given xt 84 meters, T 5.0 T 1.5 T2 84 T6s at T6s, Y 1.062 36.0 meters. Now, the velocity d5.03.02.0 dt TTR VIJ at T6s, VIJ 23. 012.0 speed 22, 123, 12, 26 meters SVT 4.9 relative velocity in 2 dimensions. The concept of relative velocity, introduced in section 3.7 for motion along a straight line, can be easily extended to include motion in a plane or in 3 dimensions. Suppose that 2 objects A and B are moving with velocities VA and VB each with respect to some common frame of reference, say ground. Then, velocity of object A relative to that of B is VAB VA, VB 4.35 A, and similarly, the velocity of object B relative to that of A is VBA VB, VA. Therefore, VAB VBA 4.35 BN, VVAB BA 4.35 C. Example 4.6. Rain is falling vertically with a speed of 35 meters s1. A woman rides a bicycle with a speed of 12 meters s1 in east to west direction. What is the direction in which she should hold her umbrella? Answer in Fig. 4.16. VR represents the velocity of rain and VB, the velocity of the bicycle the woman is riding. Both these velocities are with respect to the ground. Since the woman is riding a bicycle, the velocity of rain is experienced by Fig. 4.16. R is the velocity of rain relative to the velocity of the bicycle she is riding, that is VR BVR, VB. Motion in a plane 77. This relative velocity vector as shown in figure 4.16 makes an angle Greek letter theta with a vertical. It is given by tan 1235 0.343 Greek letter theta VBBR or Greek letter theta 19. Therefore, the woman should hold her umbrella at an angle of about 19 degrees with the vertical towards the west. Note carefully the difference between this example and the example 4.1. In example 4.1, the boy experiences the resultant vector sum of 2 velocities, while in this example, the woman experiences the velocity of rain relative to the bicycle, the vector difference of the 2 velocities. T4.10 Projectile motion is an application of the ideas developed in the previous sections. We consider the motion of a projectile. An object that is in flight after being thrown or projected is called a projectile. Such a projectile might be a football, a cricket ball, a baseball, or any other object. The motion of a projectile may be thought of as the result of 2 separate, simultaneously occurring components of motions. One component is along a horizontal direction without any acceleration and the other along the vertical direction with constant acceleration due to the force of gravity. It was Galileo who first stated this independency of the horizontal and the vertical components of projectile motion in his dialogue on the Great World Systems 1632. In our discussion, we shall assume that the air resistance has negligible effect on the motion of the projectile. Suppose that the projectile is launched with velocity v that makes an angle Greek letter theta O with the x-axis as shown in Fig. 4.17. After the object has been projected, the acceleration acting on it is that due to gravity which is directed vertically downward, a jg or x0, ig 4.36. The components of initial velocity vo are vox vo cos o voi vo sin o 4.37. If we take the initial position to be the origin of the reference frame as shown in Fig. 4.17, we have zo0, yo0. Then Ec 4.34b becomes x vox t vo cos Greek letter theta ot and y vo sin Greek letter theta ot 1/2 gt2 4.38. The components of velocity at time t can be obtained using Ec 4.33b. The x vox vo cos Greek letter theta o y vo sin Greek letter theta o gt 4.39. Equation 4.38 gives the x and y coordinates of the position of a projectile at time t in terms of 2 parameters: initial speed v and projection angle Greek letter theta o. Notice that the choice of mutually perpendicular x and y directions for the analysis of the projectile motion has resulted in a simplification. One of the components of velocity, that is x component, remains constant throughout the motion and only the y component changes, like an object in free fall in vertical direction. This is shown graphically at few instants in figure 4.18. Note that at the point of maximum height, by 0 and therefore, Greek letter theta tan 1 volt Vyx equation of path of a projectile. What is the shape of the path followed by the projectile? This can be seen by eliminating the time between the expressions for x and y as given in EC 4.38. We obtain, figure 4.17, motion of an object projected with velocity VO at angle Greek letter theta 0. Physics 78 TT 20200 tan 2 cos GYXXV Greek letter theta 4.40. Now, since g, Greek letter theta O and VO are constants, EC 4.40 is of the form YXBX2, in which I and B are constants. This is the equation of a parabola, that is, the path of the projectile is a parabola. Figure 4.18. Figure 4.18. The path of a projectile is a parabola. Time of maximum height. How much time does the projectile take to reach the maximum height? Let this time be denoted by Tm. Since at this point, y0, we have from EC 4.39, VO sin O, GTm0 or Tm VO sin O g 4.41 of the total time Tf during which the projectile is in flight can be obtained by putting y0 in EC 4.38. We get Tf2 VO sin Greek letter theta Og 4.41 bTf is known as the time of flight of the projectile. We note that Tf2 Tm, which is expected because of the symmetry of the parabolic path, maximum height of the projectile. The maximum height reached by the projectile can be calculated by substituting Ttm in EC 4.38, YHVBGGBGM000 sin 2 sin 0002 Greek letter theta or HVM0 sin 0 Greek letter theta 2 grams 4.42 horizontal range of a projectile. The horizontal distance traveled by a projectile from its initial position xy0 to the position where it passes y0 during its fall is called the horizontal range, r. It is the distance traveled during the time of flight Tf. Therefore, the range r is r VO cos Greek letter theta O Tf VO cos Greek letter theta O2 VO sin Greek letter theta Og or RVG02 sin 20 Greek letter theta 4.43. Equation 4.43 shows that for a given projection velocity VO, r is maximum when sin 2 Greek letter theta 0 is maximum, that is, when Greek letter theta 0 450. The maximum horizontal range is, therefore, RVGM02 4.43b. Example 4.7. Galileo, in his book Two New Sciences, stated that for elevations which exceed or fall short of 45 degrees by equal amounts, the ranges are equal. Prove this statement. Answer: for a projectile launched with velocity VO at an angle Greek letter theta O, the range is given by 0 sin 22 0 volt Rg Greek letter theta. Now, for angles, 45 degrees Greek letter alpha and 45 degrees Greek letter alpha, 2 Greek letter theta O is 90 degrees 2 Greek letter alpha and 90 degrees 2 Greek letter alpha, respectively. The values of sin 90 degrees 2 Greek letter alpha and sin 90 degrees 2 Greek letter alpha are the same, equal to that of cos 2 Greek letter alpha. Therefore, ranges are equal for elevations which exceed or fall short of 45 degrees by equal amounts Greek letter alpha. T. Example 4.8. A hiker stands on the edge of a cliff 490 meters above the ground and throws a stone horizontally with an initial speed of 15 meters s1. Neglecting air resistance, find the time taken by the stone to reach the ground, and the speed with which it hits the ground. Take g 9.8 meters s2. Motion in a plane 79t. Answer: we choose the origin of the x and y axis at the edge of the cliff and t0s at the instant the stone is thrown. Choose the positive direction of x-axis to be along the initial velocity and the positive direction of y-axis to be the vertically upward direction. The x and y components of the motion can be treated independently. The equations of motion are x t zo vox t y t yo voy t1 2 I t2 here, zo yo 0, voy 0, ig minus 9.8 meters s2, vox 15 meters s1. The stone hits the ground when yt 490 meters 129.8 t2. This gives t10 s. The velocity components are vx vox and y voy, gt, so that when the stone hits the ground, vox 15 meters s1 voy 0 9.8 x 10 98 meters s1. Therefore, the speed of the stone is 2.159899 meters s2 21 x if vt. Example 4.9. A cricket ball is thrown at a speed of 28 meters s1 in a direction 30 degrees above the horizontal. Calculate the maximum height, b the time taken by the ball to return to the same level, and c the distance from the thrower to the point where the ball returns to the same level. Answer: the maximum height is given by 220 sin 28 sin 30 meters 229.80 meters VHG Greek letter theta degrees XX 1414 29.8 10.0 meters B. The time taken to return to the same level is TF2 vo sin Greek letter theta OG2X 28X sin 30 degrees 9.8 28 9.8 S 2.9 S. C. The distance from the thrower to the point where the ball returns to the same level is R2 O was in 228 28 sin 60 69 meters 9.8 of G Greek letter theta XXT 4.11. Uniform circular motion: when an object follows a circular path at a constant speed, the motion of the object is called uniform circular motion. The word uniform refers to the speed, which is uniform constant throughout the motion. Suppose an object is moving with uniform speed v in a circle of radius r as shown in Fig. 4.19. Since the velocity of the object is changing continuously in direction, the object undergoes acceleration. Let us find the magnitude and the direction of this acceleration. Neglecting air resistance, what does the assumption really mean while treating the topic of projectile motion? We have stated that we assume that the air resistance has no effect on the motion of the projectile. You must understand what the statement really means. Friction, force due to viscosity, air resistance are all dissipative forces. In the presence of any of such forces opposing motion, any object will lose some part of its initial energy and consequently, momentum too. Thus, a projectile that traverses a parabolic path would certainly show deviation from its idealized trajectory in the presence of air resistance. It will not hit the ground with the same speed with which it was projected from it. In the absence of air resistance, the x component of the velocity remains constant and it is only the y component that undergoes a continuous change. However, in the presence of air resistance, both of these would get affected. That would mean that the range would be less than the one given by EC. 4.43. Maximum height attained would also be less than that predicted by EC 4.42. Can you then anticipate the change in the time of flight? In order to avoid air resistance, we will have to perform the experiment in vacuum or under low pressure, which is not easy. When we use a phrase like neglect air resistance, we imply that the change in parameters such as range, height, etc. is much smaller than their values without air resistance. The calculation without air resistance is much simpler than that with air resistance. Physics 80. Let r and r be the position vectors and v the velocities of the object when it is at point P and P as shown in Fig. 4.19. By definition, velocity at a point is along the tangent at that point in the direction of motion. The velocity vectors v and v are as shown in Figure 4.19. A 1v is obtained in Figure 4.19. A 2 using the triangle law of vector addition. Since the path is circular, v is perpendicular to r and so is v to r, therefore, v is perpendicular to r. Since average acceleration is along via vt, the average acceleration is perpendicular to r. If we place v on the line that bisects the angle between r and r, we see that it is directed towards the center of the circle. Figure 4.19b shows the same quantities for smaller time interval v and hence a is again directed towards the center. In Figure 4.19c, t0 and the average acceleration becomes the instantaneous acceleration. It is directed towards the center. Thus, we find that the acceleration of an object in uniform circular motion is always directed towards the center of the circle. Let us now find the magnitude of the acceleration. The magnitude of A is, by definition, given by a vt0t. Let the angle between position vectors r and r be Greek letter theta. Since the velocity vectors v and v are always perpendicular to the position vectors, the angle between them is also Greek letter theta. Therefore, the triangle CPP formed by the position vectors and the triangle GP formed by the velocity vectors v and v are similar. Fig. 4.19. Therefore, the ratio of the base length to side length for one of the triangles is equal to that of the other triangle. That is, VR or VR. Therefore, a VRRT00RR0TTVTVTT if T is small. Greek letter theta will also be small and then arc PP can be approximately taken to be R, RVTRTVR. T0TVR. Therefore, the centripetal acceleration AC is, Figure 4.19. Velocity and acceleration of an object in uniform circular motion. The time interval t decreases from a to c where it is 0. The acceleration is directed, at each point of the path, towards the center of the circle. In the limit t0, r becomes perpendicular to r in this limit v0 and is consequently also perpendicular to v. Therefore, the acceleration is directed towards the center, at each point of the circular path. Lim. Motion in a plane 81 TACVR VV2R 4.44. Thus, the acceleration of an object moving with speed v in a circle of radius r has a magnitude v2r and is always directed towards the center. This is why this acceleration is called centripetal acceleration, a term proposed by Newton. A thorough analysis of centripetal acceleration was first published in 1673 by the Dutch scientist Christian Huygens, 1629-1695, but it was probably known to Newton also some years earlier. Centripetal comes from a Greek term which means center-seeking. Since v and r are constant, the magnitude of the centripetal acceleration is also constant. However, the direction changes pointing always towards the center. Therefore, a centripetal acceleration is not a constant vector. We have another way of describing the velocity and the acceleration of an object in uniform circular motion. As the object moves from P to P in time t, the line CP figure 4.19 turns through an angle Greek letter theta as shown in the figure. Greek letter theta is called angular distance. We define the angular speed Greek letter omega. Greek letter omega as the time rate of change of angular displacement. Greek letter omega Greek letter theta t 4.45 now. If the distance traveled by the object during the time t is s, that is pp is s, then vst but sr Greek letter theta. Therefore, vrt Greek letter theta vr Greek letter omega 4.46. We can express centripetal acceleration ac in terms of angular speed. A vrrrrc 222 Greek letter omega 2 rc Greek letter omega 2 4.47. The time taken by an object to make one revolution is known as its time period t, and the number of revolution made in 1 second is called its frequency Greek letter nu 1t. However, during this time the distance moved by the object is s jude. Therefore, v2t 4.48 in terms of frequency Greek letter nu. We have Greek letter omega 2 v2 ac 4 Greek letter pi to Greek letter nu 2 r 4.49. Example 4.10. An insect trapped in a circular groove of radius 12 cm moves along the groove steadily and completes 7 revolutions in 100 s. O. What is the angular speed, and the linear speed of the motion? B is the acceleration vector, a constant vector. What is its magnitude? Answer. This is an example of uniform circular motion. Here are 12 centimeters. The angular speed Greek letter omega is given by Greek letter omega 2 Greek letter pi t2 Greek letter pi x 7 100 0.44 at s. The linear speed v is v Greek letter omega r 0.44 s1 x 12 centimeters 5.3 centimeters s1. The direction of velocity v is along the tangent to the circle at every point. The acceleration is directed towards the center of the circle. Since this direction changes continuously, acceleration here is not a constant vector. However, the magnitude of acceleration is constant. A Greek letter omega 2 r 0.44 s1 2 12 centimeters 2.3 centimeters s2 t 2018 1. Summary 1. Scalar quantities are quantities with magnitudes only. Examples are distance, speed, mass and temperature. 2. Vector quantities are quantities with magnitude and direction both. Examples are displacement, velocity and acceleration. They obey special rules of vector algebra. 3. A vector A multiplied by a real number Greek letter lambda is also a vector whose magnitude is Greek letter lambda times the magnitude of the vector A and whose direction is the same or opposite depending upon whether Greek letter lambda is positive or negative. 4. Two vectors A and B may be added graphically using head-to-tail method or parallelogram method. 5. Vector addition is commutative. ABBA. It also obeys the associative law. ABC 6. A null or zero vector is a vector with zero magnitude. Since the magnitude is zero, we don't have to specify its direction. It has the properties A0 A Greek letter lambda 0 0 0 A0 7. The subtraction of vector B from A is defined as the sum of A and B. A, B A B 8. A vector A can be resolved into component along two given vectors A and B lying in the same plane, A Greek letter lambda and micro b, where Greek letter lambda and micro o are real numbers. 9. A unit vector associated with a vector A has magnitude 1 and is along the vector A, NAA. The unit vectors I, J, K are vectors of unit magnitude and point in the direction of the X, Y, and Z axis, respectively in a right-handed coordinate system. 10. A vector A can be expressed as AIJAXY, where AX, AY are its components along X and Y axes. If vector A makes an angle Greek letter theta with the x-axis, then ax A cos Greek letter theta, IA sin Greek letter theta and 2 10. YXYXAAAA Greek letter theta A11. Vectors can be conveniently added using analytical method. If sum of two vectors A and B, that lie in xy plane, is R, then RIJRRXY, where RXAXBX, and RYAYBY 12. The position vector of an object in xy plane is given by RIJXY and the displacement from position R to position R is given by RRRXXYYIJXYIJ13. If an object undergoes a displacement r in time t, its average velocity is given by vrt. The velocity of an object at time t is the limiting value of the average velocity. Motion in a plane 83 as t tends to 0, vt0rrttdd. It can be written in unit vector notation as vijkvvvxyz where tzvty dd when position of an object is plotted on a coordinate system, v is always tangent to the curve representing the path of the object. 14. If the velocity of an object changes from v to v in time t, then its average acceleration is given by a vvvtt. The acceleration at any time t is the limiting value of a as t0, a vvtt0dd. In component form, we have aijkaxyz where a dvdt, a dvdt, a dvdtxxyyzz. 15. If an object is moving in a plane with constant acceleration 2x and its position vector at time t0 is ρ, then at any other time t, it will be at a point given by 21 2tto or rv and its velocity is given by v(vo)t where vo is the velocity at time t0. In component form, 2120xxxvt at t 2120 at tvv at txxxvv at t. Motion in a plane can be treated as superposition of two separate simultaneous one-dimensional motions along two perpendicular directions. 16. An object that is in flight after being projected is called a projectile. If an object is projected with initial velocity v making an angle Greek letter theta o with x-axis and if we assume its initial position to coincide with the origin of the coordinate system, then the position and velocity of the projectile at time t are given by x vo cos Greek letter theta o t y vo sin Greek letter theta o t 1 2 grams t2 vx fox vo cos Greek letter theta o vy vo sin Greek letter theta o gt. The path of a projectile is parabolic and is given by 202 tan cos o gxy x 2 volt Greek letter theta. The maximum height that a projectile attains is lim. Physics 84 HV 2 grams MOO sin 2Q. The time taken to reach this height is GVTOOM sin. The horizontal distance traveled by a projectile from its initial position to the position it passes y0 during its fall is called the range, r of the projectile. It is 2 sin 200 vrg Greek letter theta. 17. When an object follows a circular path at constant speed, the motion of the object is called uniform circular motion. The magnitude of its acceleration is acv2 or the direction of ac is always towards the center of the circle. The angular speed Greek letter omega is the rate of change of angular distance. It is related to velocity v by v. The acceleration is ac Greek letter omega to r. If d is the time period of revolution of the object in circular motion and Greek letter nu is its frequency, we have Greek letter omega to Greek letter pi Greek letter nu, v2, ac for Greek letter pi to Greek letter nu to r. 2018. 1. Points to ponder. 1. The path length traversed by an object between 2 points is, in general, not the same as the magnitude of displacement. The displacement depends only on the endpoints. The path length, as the name implies, depends on the actual path. The two quantities are equal only if the object does not change its direction during the course of motion. In all other cases, the path length is greater than the magnitude of displacement. 2. In view of point 1 above, the average speed of an object is greater than or equal to the magnitude of the average velocity over a given time interval. The two are equal only if the path length is equal to the magnitude of displacement. 3. The vector equations 4.33a and 4.34a do not involve any choice of axes. Of course, you can always resolve them along any two independent axes. 4. The kinematic equations for uniform acceleration do not apply to the case of uniform circular motion since in this case the magnitude of acceleration is constant but its direction is changing. 5. An object subjected to two velocities v1 and v2 has a resultant velocity v1 v2. Take care to distinguish it from velocity of object 1 relative to velocity of object 2, v12 v1 v2. Here v1 and v2 are velocities with reference to some common reference frame. 6. The resultant acceleration of an object in circular motion is towards the center only if the speed is constant. 7. The shape of the trajectory of the motion of an object is not determined by the acceleration alone but also depends on the initial conditions of motion, initial position and initial velocity. For example, the trajectory of an object moving under the same acceleration due to gravity can be a straight line or a parabola depending on the initial conditions. Exercises 4.1 state, for each of the following physical quantities, if it is a scalar or a vector, volume, mass, speed, acceleration, density, number of moles, velocity, angular frequency, displacement, angular velocity. 4.2 Pick out the two scalar quantities in the following list: force, angular momentum, work, current, linear momentum, electric field, average velocity, magnetic moment, relative velocity. 4.3 Pick out the only vector quantity in the following list: temperature, pressure, impulse, time, power, total path length, energy, gravitational potential, coefficient of friction, charge. 4.4 State with reasons whether the following algebraic operations with scalar and vector physical quantities are meaningful. A. Adding any two scalars. B. Adding a scalar to a vector of the same dimensions. C. Multiplying any vector by any scalar. D. Multiplying any two scalars. E. Adding any two vectors. F. Adding a component of a vector to the same vector. 4.5 Read each statement below carefully and state with reasons if it is true or false. A. The magnitude of a vector is always a scalar. B. Each component of a vector is always a scalar. C. The total path length is always equal to the magnitude of the displacement vector of a particle. D. The average speed of a particle defined as total path length divided by the time taken to cover the path is either greater or equal to the magnitude of average velocity of the particle over the same interval of time. E. Three vectors not lying in a plane can never add up to give a null vector. 4.6 Establish the following vector inequalities geometrically or otherwise. A B, a B B, a B, a B. Physics 86 Figure 4.20 C. A B, a B D, a B, a B. When does the equality sign above apply? 4.7 Given a B C D 0. Which of the following statements are correct? A, B, C, and D must each be a null vector. B. The magnitude of a C equals the magnitude of BD. C. The magnitude of A can never be greater than the sum of the magnitudes of B, C, and D. D, B, C must lie in the plane of A and D if A and D are not collinear. And in the line of A and D, if they are collinear. 4.83 Girls skating on a circular ice ground of radius 200 meters start from a point P on the edge of the ground and reach a point Q diametrically opposite to P following different paths as shown in Fig. 4.20 What is the magnitude of the displacement vector for each for which girl is this equal to the actual length of path skate? 4.9 A cyclist starts from the center O of a circular park of radius 1 km. Reaches the edge P of the park, then cycles along the circumference, and returns to the center along QO as shown in Fig. 4.21 If the round trip takes 10 minutes, what is the A net displacement, B average velocity, and C average speed of the cyclist? Fig. 4.21 4.10 On an open ground, a motorist follows a track that turns to his left by an angle of 600 after every 500 meters. Starting from a given turn, specify the displacement of the motorist at the third, sixth and eighth turn. Compare the magnitude of the displacement with the total path length covered by the motorist in each case. 4.11 A passenger arriving in a new town wishes to go from the station to a hotel located 10 kilometers away on a straight road from the station. A dishonest cabman takes him along a circuitous path 23 kilometers long and reaches the hotel in 28 minutes. What is the average speed of the taxi? B. The magnitude of average velocity. Are the two equal? 4.12 Rain is falling vertically with a speed of 30 meters s1. A woman rides a bicycle with a speed of 10 meters s1 in the north to south direction. What is the direction in which she should hold her umbrella? 4.13 A man can swim with a speed of 4.0 kilometers h in still water. How long does he take to cross a river 1.0 kilometers wide if the river flows steadily at 3.0 kilometers h and he makes his Q? Motion in a plane 87 strokes normal to the river current. How far down the river does he go when he reaches the other bank? 4.14 In a harbor. Wind is blowing at the speed of 72 kilometers h and the flag on the mast of a boat anchored in the harbor flutters along the NE direction. If the boat starts moving at a speed of 51 kilometers h to the north, what is the direction of the flag on the mast of the boat? 4.15 The ceiling of a long hall is 25 meters high. What is the maximum horizontal distance that a ball thrown with a speed of 40 meters s1 can go without hitting the ceiling of the hall? 4.16 A cricketer can throw a ball to a maximum horizontal distance of 100 meters. How much high above the ground can the cricketer throw the same ball? 4.17 A stone tied to the end of a string 80 centimeters long is whirled in a horizontal circle with a constant speed. If the stone makes 14 revolutions in 25 s, what is the magnitude and direction of acceleration of the stone? 4.18 An aircraft executes a horizontal loop of radius 1.00 kilometers with a steady speed of 900 kilometers h. Compare its centripetal acceleration with the acceleration due to gravity. 4.19 Read each statement below carefully and state with reasons if it is true or false. The net acceleration of a particle in circular motion is always along the radius of the circle towards the center. B. The velocity vector of a particle at a point is always along the tangent to the path of the particle at that point. C. The acceleration vector of a particle in uniform circular motion averaged over one cycle is a null vector. 4.20 The position of a particle is given by 23.02.04.0 megatons TRIJK where T is in seconds and the coefficients have the proper units for R to be in meters. Find the v and of the particle. B. What is the magnitude and direction of velocity of the particle at t 2.0 s? 4.21 A particle starts from the origin at t0s with a velocity of 10.0 joules ms and moves in the xy plane with a constant acceleration of 8.02.0 ij ms2. At what time is the x-coordinate of the particle? 16 meters. What is the y-coordinate of the particle at that time? b. What is the speed of the particle at the time? 4.22 I and j are unit vectors along x and y axis respectively. What is the magnitude and direction of the vectors ij and ij? What are the components of a vector a to ij3 along the directions of ij and ij? You may use graphical method. 4.23 for any arbitrary motion in space. Which of the following relations are true? A v average 1 2 vt1 vt2 b v average rt2 rt1 t2 t1 c vt v0 a t d rt r0 v0 t1 2 a t2 e average vt2 vt1 t2 t1. The average stands for average of the quantity over the time interval t1 to t2. 4.24 Read each statement below carefully and state, with reasons and examples, if it is true or false. A scalar quantity is one that is conserved in a process. B can never take negative values. C must be dimensionless. D does not vary from one point to another in space. E has the same value for observers with different orientations of axes. 4.25 An aircraft is flying at a height of 3,400 meters above the ground. If the angle subtended at a ground observation point by the aircraft positions 10.0 s apart is 30 degrees. What is the speed of the aircraft? Physics 88 Additional exercises 4.26 A vector has magnitude and direction. Does it have a location in space? Can it vary with time? Will two equal vectors A and B at different locations in space necessarily have identical physical effects? Give examples in support of your answer. 4.27 A vector has both magnitude and direction. Does it mean that anything that has magnitude and direction is necessarily a vector? The rotation of a body can be specified by the direction of the axis of rotation and the angle of rotation about the axis. Does that make any rotation a vector? 4.28 Can you associate vectors with the length of a wire bent into a loop? B. A plane area. C. A sphere. Explain. 4.29 A bullet fired at an angle of 30 degrees with the horizontal hits the ground 3.0 kilometers away. By adjusting its angle of projection, can one hope to hit a target 5.0 kilometers away? Assume the muzzle speed to be fixed, and neglect air resistance. 4.30 A fighter plane flying horizontally at an altitude of 1.5 kilometers with speed 720 kilometers h passes directly overhead an anti-aircraft gun. At what angle from the vertical should the gun be fired for the shell with muzzle speed 600 meters s1 to hit the plane? At what minimum altitude should the pilot fly the plane to avoid being hit? Take g 10 meters s2. 4.31 A cyclist is riding with a speed of 27 kilometers h as he approaches a circular turn on the road of radius 80 meters. He applies brakes and reduces his speed at the constant rate of 0.50 meters s every second. What is the magnitude and direction of the net acceleration of the cyclist on the circular turn? 4.32 Show that for a projectile the angle between the velocity and the x-axis as a function of time is given by ox0 yvg/tv1 tant. B shows that the projection angle Greek letter theta 0 for a projectile launched from the origin is given by 0r4hm1 tan where the symbols have their usual meaning. 2018 1. Chapter 5 Laws of Motion 5.1 Introduction. In the preceding chapter, our concern was to describe the motion of a particle in space quantitatively. We saw that uniform motion needs the concept of velocity alone whereas non-uniform motion requires the concept of acceleration in addition. So far, we have not asked the question as to what governs the motion of bodies. In this chapter, we turn to this basic question. Let us first guess the answer based on our common experience. To move a football at rest, someone must kick it. To throw a stone upwards, one has to give it an upward push. A breeze causes the branches of a tree to swing. A strong wind can even move heavy objects. A boat moves in a flowing river without anyone rowing it. Clearly, some external agency is needed to provide force to move a body from rest. Likewise, an external force is needed also to retard or stop motion. You can stop a ball rolling down an inclined plane by applying a force against the direction of its motion. In these examples, the external agency of force hands, wind, stream, etc. is in contact with the object. This is not always necessary. A stone released from the top of a building accelerates downward due to the gravitational pull of the earth. A bar magnet can attract an iron nail from a distance. This shows that external agencies e.g. gravitational and magnetic forces can exert force on a body even from a distance. In short, a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. The external agency may or may not be in contact with the body. So far so good, but what if a body is moving uniformly, e.g. a skater moving straight with constant speed on a horizontal ice slab is an external force required to keep a body in uniform motion. 5.1 Introduction 5.2 Aristotle's fallacy 5.3 The law of inertia 5.4 Newton's first law of motion 5.5 Newton's second law of motion 5.6 Newton's third law of motion 5.7 Conservation of momentum 5.8 Equilibrium of a particle 5.9 Common forces in mechanics 5.10 Circular motion 5.11 Solving problems in mechanics Summary points to ponder exercises Additional exercises Physics 95.2 Aristotle's fallacy The question posed above appears to be simple, however, it took ages to answer it. Indeed, the correct answer to this question given by Galileo in the 17th century was the foundation of Newtonian mechanics, which signaled the birth of modern science. The Greek thinker, Aristotle 384 BC 322 BC, held the view that if a body is moving, something external is required to keep it moving. According to this view, for example, an arrow shot from above keeps flying since the air behind the arrow keeps pushing it. The view was part of an elaborate framework of ideas developed by Aristotle on the motion of bodies in the universe. Most of the Aristotelian ideas on motion are now known to be wrong and need not concern us. For our purpose here, the Aristotelian law of motion may be phrased thus: an external force is required to keep a body in motion. Aristotelian law of motion is flawed, as we shall see, however, it is a natural view that anyone would hold from common experience. Even a small child playing with a simple non-electric toy car on the floor knows intuitively that it needs to constantly drag the string attached to the toy car with some force to keep it going. If it releases the string, it comes to rest. This experience is common to most terrestrial motion. External forces seem to be needed to keep bodies in motion. Left to themselves, all bodies eventually come to rest. What is the flaw in Aristotle's argument? The answer is, a moving toy car comes to rest because the external force of friction on the car by the floor opposes its motion. To counter this force, the child has to apply an external force on the car in the direction of motion. When the car is in uniform motion, there is no net external force acting on it. The force by the child cancels the force friction by the floor. The corollary is, if there were no friction, the child would not be required to apply any force to keep the toy car in uniform motion. The opposing forces such as friction solids and viscous forces for fluids are always present in the natural world. This explains why forces by external agencies are necessary to overcome the frictional forces to keep bodies in uniform motion. Now we understand where Aristotle went wrong. He coded this practical experience in the form of a basic argument. To get at the true law of nature for forces in motion, one has to imagine a world in which uniform motion is possible with no frictional forces opposing. This is what Galileo did. 5.3 The law of inertia Galileo studied motion of objects on an inclined plane. Objects I moving down an inclined plane accelerate, while those two moving up retard. 3 Motion on a horizontal plane is an intermediate situation. Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor retardation, that is, it should move with constant velocity. Figure 5.1 I23 Figure 5.1 Another experiment by Galileo leading to the same conclusion involves a double inclined plane. A ball released from rest on one of the planes rolls down and climbs up the other. If the planes are smooth, the final height of the ball is nearly the same as the initial height, a little less but never greater. In the ideal situation, when friction is absent, the final height of the ball is the same as its initial height. If the slope of the second plane is decreased and the experiment repeated, the ball will still reach the same height, but in doing so, it will travel a longer distance. In the limiting case, when the slope of the second plane is 0, that is a horizontal, the ball travels an infinite distance. In other words, its motion never ceases. This is, of course, an idealized situation. Figure 5.1b. Figure 5.1b The law of inertia was inferred by Galileo from observations of motion of a ball on a double inclined plane. Laws of motion 91 In practice, the ball does come to a stop after moving a finite distance on the horizontal plane, because of the opposing force of friction which can never be totally eliminated. However, if there were no friction, the ball would continue to move with a constant velocity on the horizontal plane. Galileo thus arrived at a new insight on motion that had eluded Aristotle and those who followed him. The state of rest and the state of uniform linear motion with constant velocity are equivalent. In both cases, there is no net force acting on the body. It is incorrect to assume that a net force is needed to keep a body in uniform motion. To maintain a body in uniform motion, we need to apply an external force to counter the frictional force, so that the two forces sum up to 0 net external force. To summarize, if the net external force is 0, a body at rest continues to remain at rest and a body in motion continues to move with a uniform velocity. This property of a body is called inertia. Inertia means resistance to change. A body does not change its state of rest or uniform motion, unless an external force compels it to change that state. 5.4 Newton's first law of motion. Galileo's simple, but revolutionary ideas dethroned Aristotelian mechanics. A new mechanics had to be developed. This task was ideas on motion in ancient Indian science. Ancient Indian thinkers had arrived at an elaborate system of ideas on motion. Force, the cause of motion, was thought to be of different kinds. Force due to continuous pressure Newton. As the force of wind on a sailing vessel, impact of Higgett, as when a potter's rod strikes the wheel, persistent tendency Sanskrit to move in a straight line Vega or restoration of shape in an elastic body, transmitted force by a string, rod, etc. The notion of Vega in the Vaisesika theory of motion perhaps comes closest to the concept of inertia. Vega, the tendency to move in a straight line, was thought to be opposed by contact with objects including atmosphere, a parallel to the ideas of friction and air resistance. It was correctly summarized that the different kinds of motion, translational, rotational and vibrational, of an extended body arise from only the translational motion of its constituent particles. A falling leaf in the wind may have downward motion as a whole piton and also rotational and vibrational motion Brahman. Spandan, but each particle of the leaf at an instant only has a definite small displacement. There was considerable focus in Indian thought on measurement of motion in units of length and time. It was known that the position of a particle in space can be indicated by distance measured along 3 axes. Bhaskara 1150 AD had introduced the concept of instantaneous motion Tatkaliki Gati, which anticipated the modern notion of instantaneous velocity using differential calculus. The difference between a wave and a current of water was clearly understood. A current is a motion of particles of water under gravity and fluidity, while a wave results from the transmission of vibrations of water particles. Accomplished almost single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton built on Galileo's ideas and laid the foundation of mechanics in terms of 3 laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. Every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. The state of rest or uniform linear motion both imply zero acceleration. The first law of motion can, therefore, be simply expressed as, if the net external force on a body is zero, its acceleration is zero. Acceleration can be non-zero only if there is a net external force on the body. 2 kinds of situations are encountered in the application of this law in practice. In some examples, we know that the net external force on the object is zero. In that case we can conclude that the acceleration of the object is zero. For example, a spaceship out in interstellar space, far from all other objects and with all its rockets turned off, has no net external force acting on it. Its acceleration, according to the first law, must be zero. If it is in motion, it must continue to move with a uniform velocity. Physics 92 More often, however, we do not know all the forces to begin with. In that case, if we know that an object is unaccelerated, that is, it is either at rest or in uniform linear motion, we can infer from the first law that the net external force on the object must be zero. Gravity is everywhere. For terrestrial phenomena, in particular, every object experiences gravitational force due to the Earth. Also objects in motion generally experience friction, viscous drag, etc. If then, on Earth, an object is at rest or in uniform linear motion, it is not because there are no forces acting on it, but because the various external forces cancel out, that is, at up to zero net external force. Consider a book at rest on a horizontal surface Fig 5.2 up. It is subject to 2 external forces, the force due to gravity, that is its weight W acting downward, and the upward force on the book by the table, the normal force R. R is a self-adjusting force. This is an example of the kind of situation mentioned above. The forces are not quite known fully, but the state of motion is known. We observe the book to be at rest. Therefore, we conclude from the first law that the magnitude of R equals that of W. A statement often encountered is, since WR forces cancel and, therefore, the book is at rest. This is incorrect reasoning. The correct statement is, since the book is observed to be at rest, the net external force on it must be zero, according to the first law. This implies that the Galileo Galilei, born in Pisa, Italy in 1564, was a key figure in the scientific revolution in Europe about 4 centuries ago. Galileo proposed the concept of acceleration, from experiments on motion of bodies on inclined planes or falling freely. He contradicted the Aristotelian notion that a force was required to keep a body in motion, and that heavier bodies fall faster than lighter bodies under gravity. He thus arrived at the law of inertia that was the starting point of the subsequent epical work of Isaac Newton. Galileo's discoveries in astronomy were equally revolutionary. In 1609, He designed his own telescope invented earlier in Holland and used it to make a number of startling observations: mountains and depressions on the surface of the moon, dark spots on the sun, the moons of Jupiter and the phases of Venus. He concluded that the Milky Way derived its luminosity because of a large number of stars not visible to the naked eye. In his masterpiece of scientific reasoning, Dialogue on the Two Chief World Systems, Galileo advocated the heliocentric theory of the solar system proposed by Copernicus, which eventually got universal acceptance. With Galileo came a turning point in the very method of scientific inquiry. Science was no longer merely observations of nature and inferences from them. Science meant devising and doing experiments to verify or refute theories. Science meant measurement of quantities and a search for mathematical relations between them. Not undeservedly, many regard Galileo as the father of modern science. Normal force R must be equal and opposite to the weight W. Figure 5.2. A book at rest on the table, and B. A car moving with uniform velocity. The net force is 0 in each case. Consider the motion of a car starting from rest, peaking up speed and then moving on a smooth straight road with uniform speed. Fig. 5.2b. When the car is stationary, there is no net force acting on it. During pickup, it accelerates. This must happen due to a net external force. Note, it has to be an external force. The acceleration of the car cannot be accounted for by any internal force. This might sound surprising, but it is true. The only conceivable external force along the road is the force of friction. It is the frictional force that accelerates the car as a whole. You will learn about friction in section 5.9. When the car moves with constant velocity, there is no net external force. Galileo Galilei 1564-1642. Laws of motion 93T. It relates the net external force to the acceleration of the body. Momentum of a body is defined to be the product of its mass m and velocity v, and is denoted by p. PMV 5.1. Momentum is clearly a vector quantity. The following common experiences indicate the importance of this quantity for considering the effect of force on motion. Suppose a lightweight vehicle, say a small car, and a heavyweight vehicle, say a loaded truck, are parked on a horizontal road. We all know that a much greater force is needed to push the truck than the car to bring them to the same speed and same time. Similarly, a greater opposing force is needed to stop a heavy body than a light body in the same time, if they are moving with the same speed. If two stones, one light and the other heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone than the heavy stone. The mass of a body is thus an important parameter that determines the effect of force on its motion. Speed is another important parameter to consider. A bullet fired by a gun can easily pierce human tissue before it stops, resulting in casualty. The same bullet fired with moderate speed will not cause much damage. Thus, for a given mass, the greater the speed, the greater is the opposing force needed to stop the body in a certain time. Taken together, the product of mass and velocity, that is momentum, is evidently a relevant variable of motion. The greater the change in the momentum in a given time, the greater is the force that needs to be applied. A seasoned cricketer catches a cricket ball coming in with great speed far more easily than a novice, who can hurt his hands in the act. One reason is that the cricketer allows a longer time for his hands to stop the ball. As you may have noticed, he draws in the hand backward in the act of catching the ball. Fig. 5.3. The novice, on the other hand, keeps his hands fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantly, and the property of inertia contained in the first law is evident in many situations. Suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown backward with a jerk. Why? Our feet are in touch with the floor. If there were no friction, we would remain where we were, while the floor of the bus would simply slip forward under our feet and the back of the bus would hit us. However, fortunately, there is some friction between the feet and the floor. If the start is not too sudden, that is, if the acceleration is moderate, the frictional force would be enough to accelerate our feet along with the bus. But our body is not strictly a rigid body. It is deformable, that is, it allows some relative displacement between different parts. What this means is that while our feet go with the bus, the rest of the body remains where it is due to inertia. Relative to the bus, therefore, we are thrown backward. As soon as that happens, however, the muscular forces on the rest of the body by the feet come into play to move the body along with the bus. A similar thing happens when the bus suddenly stops. Our feet stop due to the friction which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. We are thrown forward. The restoring muscular forces again come into play and bring the body to rest. Example 5.1. An astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meters s2. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. Answer: since there are no nearby stars to exert gravitational force on him and the small spaceship exerts negligible gravitational attraction on him, the net force acting on the astronaut, once he is out of the spaceship, is zero. By the first law of motion, the acceleration of the astronaut is 0 t 5.5 Newton's second law of motion. The first law refers to the simple case when the net external force on a body is zero. The second law of motion refers to the general situation when there is a net external force acting on the body. Physics 94. This hurts. The conclusion is clear. Force not only depends on the change in momentum, but also on how fast the change is brought about. The same change in momentum brought about in a shorter time needs a greater applied force. In short, the greater the rate of change of momentum, the greater is the force. Figure 5.3. Force not only depends on the change in momentum but also on how fast the change is brought about. A seasoned cricketer draws in his hands during a catch, allowing greater time for the ball to stop and hence requires a smaller force. Observations confirm that the product of mass and velocity, that is momentum, is basic to the effect of force on motion. Suppose a fixed force is applied for a certain interval of time on two bodies of different masses. Initially at rest, the lighter body picks up a greater speed than the heavier body. However, at the end of the time interval, observations show that each body acquires the same momentum. Thus the same force for the same time causes the same change in momentum for different bodies. This is a crucial clue to the second law of motion. In the preceding observations, the vector character of momentum has not been evident. In the examples so far, momentum and change in momentum both have the same direction. But this is not always the case. Suppose a stone is rotated with uniform speed in a horizontal plane by means of a string. The magnitude of momentum is fixed, but its direction changes. Fig. 5.4. A force is needed to cause this change in momentum vector. This force is provided by our hand through the string. Experience suggests that our hand needs to exert a greater force if the stone is rotated at greater speed or in a circle of smaller radius, or both. This corresponds to greater acceleration or equivalently a greater rate of change in momentum vector. This suggests that the greater the rate of change in momentum vector, the greater is the force applied. Figure 5.4. Force is necessary for changing the direction of momentum, even if its magnitude is constant. We can feel this while rotating a stone in a horizontal circle with uniform speed by means of a string. These qualitative observations led to the second law of motion expressed by Newton as follows. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Thus, if under the action of a force F for time interval t, the velocity of a body of mass m changes from v to vv, that is, its initial momentum pmv changes by mpv, according to the second law, or ktTP/pff, where k is a constant of proportionality. Taking the limit t0, the term Tp becomes the derivative or differential coefficient of p with respect to t, denoted by ddtp. Thus, laws of motion 95 tddktpf 5.2 for a body of fixed mass m. ddddddmmttpvv of 5.3, that is the second law, can also be written as fkm of 5.4, which shows that force is proportional to the product of mass m and acceleration a. The unit of force has not been defined so far. In fact, we use EC 5.4 to define the unit of force. We, therefore, have the liberty to choose any constant value for k. For simplicity, we choose k1. The second law then is a PFMTDD 5.5 in SI unit force is 1 that causes an acceleration of 1 meters s2 to a mass of 1 kilogram. This unit is known as Newton, 1 and 1 kilogram ms2. Let us note at this stage some important points about the second law. 1. In the second law, F0 implies a 0. The second law is obviously consistent with the first law. 2. The second law of motion is a vector law. It is equivalent to 3 equations. 1 for each component of the vectors, fpt max xxdd fpt may yydd mtpfdd 5.6. This means that if a force is not parallel to the velocity of the body, but makes some angle with it, it changes only the component of velocity along the direction of force. The component of velocity normal to the force remains unchanged. For example, in the motion of a projectile under the vertical gravitational force, the horizontal component of velocity remains unchanged. Fig. 5.53. The second law of motion given by EC 5.5 is applicable to a single-point particle. The force F in the law stands for the net external force on the particle and A stands for acceleration of the particle. It turns out, however, that the law in the same form applies to a rigid body or, even more generally, to a system of particles. In that case, F refers to the total external force on the system and A refers to the acceleration of the system as a whole. More precisely, I is the acceleration of the center of mass of the system, about which we shall study in detail in Chapter 7. Any internal forces in the system are not to be included in F. Figure 5.5. Acceleration at an instant is determined by the force at that instant. The moment after a stone is dropped out of an accelerated train, it has no horizontal acceleration or force, if air resistance is neglected. The stone carries no memory of its acceleration with the train a moment ago, for the second law of motion is a local relation, which means that force F at a point in space location of the particle at a certain instant of time is related to A at that point at that instant. Acceleration here and now is determined by the force here and now, not by any history of the motion of the particle. See Fig. 5.5. Example 5.2. A bullet of mass 0.04 kilograms moving with a speed of 90 meters s1 enters a heavy wooden block and is stopped after a distance of 60 centimeters. What is the average resistive force exerted by the block on the bullet? Answer. The retardation of the bullet's assumed constant is given by 2 U s 2 90 meters s 6750 meters s2 0.6xx. Physics 96 TT. The retarding force, by the second law of motion, is 0.04 kilograms x 6750 meters s2 270 and the actual resistive force, and therefore, retardation of the bullet may not be uniform. The answer therefore, only indicates the average resistive force T. Example 5.3. The motion of a particle of mass m is described by y21 2 at gt. Find the force acting on the particle. Answer. We know 21 2 y at gt now, d dy vu gtt acceleration, dtv at gt, then the force is given by ek. 5.5 F ma mg. Thus the given equation describes the motion of a particle under acceleration due to gravity and y is the position coordinate in the direction of g. T. In pulse we sometimes encounter examples where a large force acts for a very short duration, producing a finite change in momentum of the body. For example, when a ball hits a wall and bounces back, the force on the ball by the wall acts for a very short time when the two are in contact, yet the force is large enough to reverse the momentum of the ball. Often, in these situations, the force and the time duration are difficult to ascertain separately. However, the product of force and time, which is the change in momentum of a body, remains a measurable quantity. This product is called impulse force x time duration change in momentum. 5.7 A large force acting for a short time to produce a finite change in momentum is called an impulsive force. In the history of science, impulsive forces were put in a conceptually different category from ordinary forces. Newtonian mechanics has no such distinction. Impulsive force is like any other force except that it is large and acts for a short time. Example 5.4 A batsman hits back a ball straight in the direction of the bowler without changing its initial speed of 12 meters s1. If the mass of the ball is 0.15 kilograms, determine the impulse imparted to the ball. Assume linear motion of the ball. Answer. Change in momentum 0.15 x 12 minus 0.15 x 12 3.6 ns. Impulse 3.6 ns, in the direction from the batsman to the bowler. This is an example where the force on the ball by the batsman and the time of contact of the ball and the bat are difficult to know, but the impulse is readily calculated. T. 5.6 Newton's third law of motion. The second law relates the external force on a body to its acceleration. What is the origin of the external force on the body? What agency provides the external force? The simple answer in Newtonian mechanics is that the external force on a body always arises due to some other body. Consider a pair of bodies A and B. B gives rise to an external force on A. A natural question is, does A in turn give rise to an external force on B? In some examples, the answer seems clear. If you press a coiled spring, the spring is compressed by the force of your hand. The compressed spring in turn exerts a force on your hand and you can feel it, but what if the bodies are not in contact? The earth pulls a stone downwards due to gravity. Does the stone exert a force on the earth? The answer is not obvious since we hardly see the effect of the stone on the earth. The answer according to Newton is, yes, the stone does exert an equal and opposite force on the earth. We do not notice it since the earth is very massive and the effect of a small force on its motion is negligible. Thus, according to Newtonian mechanics, force never occurs singly in nature. Force is the mutual interaction between two bodies. Forces. Laws of motion 97 always occur in pairs. Further, the mutual forces between two bodies are always equal and opposite. This idea was expressed by Newton in the form of the third law of motion. To every action, there is always an equal and opposite reaction. Newton's wording of the third law is so crisp and beautiful that it has become a part of common language. For the same reason perhaps, misconceptions about the third law abound. Let us note some important points about the third law, particularly in regard to the usage of the terms, action and reaction. 1. The terms action and reaction in the third law mean nothing else but force. Using different terms for the same physical concept can sometimes be confusing. A simple and clear way of stating the third law is as follows. Forces always occur in pairs. Force on a body A by B is equal and opposite to the force on the body B by A. 2. The terms action and reaction in the third law may give a wrong impression that action comes before reaction, that is, action is the cause and reaction the effect. There is no cause-effect relation implied in the third law. The force on A by B and the force on B by A act at the same instant. By the same reasoning, any one of them may be called action and the other reaction. 3. Action and reaction forces act on different bodies, not on the same body. Consider a pair of bodies A and B according to the third law. FAB/SPA 5.8 Force on A by B, force on B by A. Thus, if we are considering the motion of any one body A or B, only one of the two forces is relevant. It is an error to add up the two forces and claim that the net force is zero. However, if you are considering the system of two bodies as a whole, FAB and SPA are internal forces of the system AB. They add up to give a null force. Internal forces in a body or a system of particles thus cancel away in pairs. This is an important fact that enables the second law to be applicable to a body or a system of particles. See Chapter 7. Isaac Newton 1642–1727. Isaac Newton was born in Woolsthorpe, England in 1642, the year Galileo died. His extraordinary mathematical ability and mechanical aptitude remained hidden from others in his school life. In 1662, he went to Cambridge for undergraduate studies. A plague epidemic in 1665 forced the university town to close and Newton had to return to his mother's farm. There, in 2 years of solitude, his dormant creativity blossomed in a deluge of fundamental discoveries in mathematics and physics, binomial theorem for negative and fractional exponents, the beginning of calculus, the inverse square law of gravitation, the spectrum of white light, and so on. Returning to Cambridge, he pursued his investigations in optics and devised a reflecting telescope. In 1684, encouraged by his friend Edmund Halley, Newton embarked on writing what was to be one of the greatest scientific works ever published, the Principia Mathematica. In it, he enunciated the three laws of motion and the universal law of gravitation, which explained all the three Kepler's laws of planetary motion. The book was packed with a host of path-breaking achievements, basic principles of fluid mechanics, mathematics of wave motion, calculation of masses of the Earth, the Sun and other planets, explanation of the precession of equinoxes, theory of tides, etc. In 1704, Newton brought out another masterpiece, Optics, that summarized his work on light and color. The scientific revolution triggered by Copernicus and steered vigorously ahead by Kepler and Galileo was brought to a grand completion by Newton. Newtonian mechanics unified terrestrial and celestial phenomena. The same mathematical equation governed the fall of an apple to the ground and the motion of the moon around the Earth. The age of reason had dawned. Physics 98T Example 5.52 Identical billiard balls strike a rigid wall with the same speed but at different angles, and get reflected without any change in speed, as shown in Fig. 5.6. What is the direction of the force on the wall due to each wall? To the ratio of the magnitudes of impulses imparted to the balls by the wall. Fig. 5.6 Answer. An instinctive answer to I might be that the force on the wall in case I is normal to the wall, while that in case B is inclined at 30 degrees to the normal. This answer is wrong. The force on the wall is normal to the wall in both cases. How to find the force on the wall? The trick is to consider the force or impulse on the ball due to the wall using the second law, and then use the third law to answer I. Let U be the speed of each ball before and after collision with the wall, and M the mass of each ball. Choose the x and y axes as shown in the figure, and consider the change in momentum of the ball in each case. Case I initial 0 times ip mu p final 0 times ip mu p impulse is the change in momentum vector. Therefore, x component of impulse 2 meters u, y component of impulse 0, impulse and force are in the same direction. Clearly, from above, the force on the ball due to the wall is normal to the wall, along the negative x direction. Using Newton's third law of motion, the force on the wall due to the ball is normal to the wall along the positive x direction. The magnitude of force cannot be ascertained since the small time taken for the collision has not been specified in the problem. Case B cos 30 initial x mu, sin 30 initial ip mu cos 30 fin x mu, sin 30 fin ip mu. Note, while px changes sign after collision, pi does not. Therefore, x component of impulse minus 2 meters u cos 30 degrees, y component of impulse 0. The direction of impulse and force is the same as in I and is normal to the wall along the negative x direction. As before, using Newton's third law, the force on the wall due to the ball is normal to the wall along the positive x direction. The ratio of the magnitudes of the impulses imparted to the balls in A and B is 2 cos 31.23 meters u mut 5.7 Conservation of momentum. The second and third laws of motion led to an important consequence, the law of conservation of momentum. Take a familiar example. A bullet is fired from a gun. If the force on the bullet by the gun is F, the force on the gun by the bullet is F, according to the third law. The two forces act for a common interval of time t. According to the second law, Fd is the change in momentum of the bullet and Fd is the change in momentum of the gun. Since initially, both are at rest, the change in momentum equals the final momentum for each. Thus if Pb is the momentum of the bullet after firing and Pg is the recoil momentum of the gun, Pg that is Pg0, that is, the total momentum of the bullet gun system is conserved. Thus in an isolated system that is a system with no external force, mutual forces between pairs of particles in the system can cause momentum change in individual particles. But since the mutual forces for each pair are equal and opposite, the momentum changes cancel in pairs and the total momentum remains unchanged. This fact is known as the law of conservation of momentum. Laws of motion 99T. The total momentum of an isolated system of interacting particles is conserved. An important example of the application of the law of conservation of momentum is the collision of two bodies. Consider two bodies A and B, with initial momentum pr and pb. The bodies collide, get apart, with final momentum pr and pb respectively. By the second law Fp pab A and Fp pb abbt, where we have taken a common interval of time for both forces, that is, the time for which the two bodies are in contact, since F fab ba by the third law, ppp par abb, that is, ppp pab ab 5.9, which shows that the total final momentum of the isolated system equals its initial momentum. Notice that this is true whether the collision is elastic or inelastic. In elastic collisions, there is a second condition that the total initial kinetic energy of the system equals the total final kinetic energy. See Chapter 6. 5.8 Equilibrium of a particle. Equilibrium of a particle in mechanics refers to the situation when the net external force on the particle is zero, according to the first law. This means that the particle is either at rest or in uniform motion. If two forces F1 and F2 act on a particle, equilibrium requires F1 F2 5.10, that is, the two forces on the particle must be equal and opposite. Equilibrium under three concurrent forces F1, F2 and F3 requires that the vector sum of the three forces is zero. F1 F2 F3 0 5.11 Equilibrium of a body requires not only translational equilibrium zero net external force but also rotational equilibrium zero net external torque, as we shall see in Chapter 7. Figure 5.7 Equilibrium under concurrent forces. In other words, the resultant of any two forces, say F1 and F2, obtained by the parallelogram law of forces, must be equal and opposite to the third force, F3. As seen in Figure 5.7, the three forces in equilibrium can be represented by the sides of a triangle with the vector arrows taken in the same sense. The result can be generalized to any number of forces. A particle is in equilibrium under the action of forces F1, F2, Fn if they can be represented by the sides of a closed n-sided polygon with arrows directed in the same sense. Equation 5.11 implies that F1x F2x F3x 0 F1y F2y F3y 0 F1z F2z F3z 0 5.12 where F1x, F1y and F1z are the components of F1 along x, y and z directions respectively. Example 5.6 See Figure 5.8. A mass of 6 kilograms is suspended by a rope of length 2 meters from the ceiling. A force of 50 N in the horizontal direction is applied at the midpoint P of the rope, as shown. What is the angle the rope makes with the vertical in equilibrium? Take G 10 meters S2, neglect the mass of the rope. ABC Figure 5.8. Physics 100 Answer Figures 5.8b and 5.8c are known as free body diagrams. Figure 5.8b is the free body diagram of W and Fig. 5.8c is the free body diagram of point P. Consider the equilibrium of the weight W clearly, T26x 1060, and consider the equilibrium of the point P under the action of three forces, the tensions T1 and T2, and the horizontal force 50N. The horizontal and vertical components of the resultant force must vanish separately, T1 cos Greek letter theta T260 and T1 sin Greek letter theta 50N, which gives that note the answer does not depend on the length of the rope assumed massless nor on the point at which the horizontal force is applied. T5.9 Common forces in mechanics. In mechanics, we encounter several kinds of forces. The gravitational force is, of course, pervasive. Every object on the Earth experiences the force of gravity due to the Earth. Gravity also governs the motion of celestial bodies. The gravitational force can act at a distance without the need of any intervening medium. All the other forces common in mechanics are contact forces. As the name suggests, a contact force on an object arises due to contact with some other object, solid or fluid. When bodies are in contact, e.g. a book resting on a table, a system of rigid bodies connected by rods, hinges and other types of supports. There are mutual contact forces for each pair of bodies satisfying the third law. The component of contact force normal to the surfaces in contact is called normal reaction. The component parallel to the surfaces in contact is called friction. Contact forces arise also when solids are in contact with fluids. For example, for a solid immersed in a fluid, there is an upward buoyant force equal to the weight of the fluid displaced. The viscous force, air resistance, etc. are also examples of contact forces. Figure 5.9. Two other common forces are tension in a string and the force due to spring. When a spring is compressed or extended by an external force, a restoring force is generated. This force is usually proportional to the compression or elongation for small displacements. The spring force F is written as Fkx, where x is the displacement and k is the force constant. The negative sign denotes that the force is opposite to the displacement from the unstretched state. For an inextensible string, the force constant is very high. The restoring force in a string is called tension. It is customary to use a constant tension T throughout the string. This assumption is true for a string of negligible mass. In Chapter 1, we learned that there are four fundamental forces in nature. Of these, the weak and strong forces appear in domains that do not concern us here. Only the gravitational and electrical forces are relevant in the context of mechanics. The different contact forces of mechanics mentioned above fundamentally arise from electrical forces. This may seem surprising. We are not considering, for simplicity, charged and magnetic bodies. For these, besides gravity, there are electrical and magnetic non-contact forces. Figure 5.9. Some examples of contact forces in mechanics. Laws of motion 101. Since we are talking of uncharged and non-magnetic bodies in mechanics, at the microscopic level, all bodies are made of charged constituents, nuclei and electrons, and the various contact forces arising due to elasticity of bodies, molecular collisions and impacts, etc., can ultimately be traced to the electrical forces between the charged constituents of different bodies. The detailed microscopic origin of these forces is, however, complex and not useful for handling problems in mechanics at the macroscopic scale. This is why they are treated as different types of forces with their characteristic properties determined empirically. 5.9.1 Friction. Let us return to the example of a body of mass m at rest on a horizontal table. The force of gravity mg is cancelled by the normal reaction force n of the table. Now suppose a force F is applied horizontally to the body. We know from experience that a small applied force may not be enough to move the body. But if the applied force F were the only external force on the body, it must move with acceleration Fm, however small. Clearly, the body remains at rest because some other force comes into play in the horizontal direction and opposes the applied force F, resulting in zero net force on the body. This force Fs parallel to the surface of the body in contact with the table is known as frictional force, or simply friction Fig. 5.10 Up. The subscript stands for static friction to distinguish it from kinetic friction Fk that we consider later. Fig. 5.10b. Note that static friction does not figure. 5.10 Static and sliding friction. A impending motion of the body is opposed by static friction. When external force exceeds the maximum limit of static friction, the body begins to move. Once the body is in motion, it is subject to sliding or kinetic friction, which opposes relative motion between the two surfaces in contact. Kinetic friction is usually less than the maximum value of static exist by itself. When there is no applied force, there is no static friction. It comes into play the moment there is an applied force. As the applied force F increases, Fs also increases, remaining equal and opposite to the applied force up to a certain limit, keeping the body at rest. Hence, it is called static friction. Static friction opposes impending motion. The term impending motion means motion that would take place but does not actually take place under the applied force, if friction were absent. We know from experience that as the applied force exceeds a certain limit, the body begins to move. It is found experimentally that the limiting value of static friction max SF is independent of the area of contact and varies with the normal force n approximately as max SSF n micro. 5.13 where micros is a constant of proportionality depending only on the nature of the surfaces in contact. The constant micros is called the coefficient of static friction. The law of static friction may thus be written as Fs micros n. 5.14 If the applied force F exceeds max SF, the body begins to slide on the surface. It is found experimentally that when relative motion has started, the frictional force decreases from the static maximum value max SF. Frictional force that opposes relative motion between surfaces in contact is called kinetic or sliding friction and is denoted by Fk. Kinetic friction, like static friction, is found to be independent of the area of contact. Further, it is nearly independent of the velocity. It satisfies a law similar to that for static friction, KKF micro 5.15, where micrit, the coefficient of kinetic friction, depends only on the surfaces in contact. As mentioned above, experiments show that micrit is less than micros. When relative motion has begun, the acceleration of a body according to the second law is F(F)km. For a body moving with constant velocity, F(F)k, if the applied force on the body is removed, its acceleration is F(km) and it eventually comes to a stop. The laws of friction given above do not have the status of fundamental laws like those for gravitational, electric and magnetic forces. They are empirical relations that are only friction. Physics 102 TT approximately true, yet they are very useful in practical calculations in mechanics. Thus, when two bodies are in contact, each experiences a contact force by the other. Friction, by definition, is the component of the contact force parallel to the surfaces in contact, which opposes impending or actual relative motion between the two surfaces. Note that it is not motion, but relative motion that the frictional force opposes. Consider a box lying in the compartment of a train that is accelerating. If the box is stationary relative to the train, it is in fact accelerating along with the train. What forces cause the acceleration of the box? Clearly, the only conceivable force in the horizontal direction is the force of friction. If there were no friction, the floor of the train would slip by and the box would remain at its initial position due to inertia and hit the backside of the train. This impending relative motion is opposed by the static friction Fs. Static friction provides the same acceleration to the box as that of the train, keeping it stationary relative to the train. Example 5.7 Determine the maximum acceleration of the train in which a box lying on its floor will remain stationary. Given that the coefficient of static friction between the box and the train's floor is 0.15, answer: since the acceleration of the box is due to the static friction, my Fs micros n micros mg, that is, a micros g a max micros g 0.15 x 10 meters s2 1.5 meters s2 t. Example 5.8 see figure 5.11. A mass of 4 kilograms rests on a horizontal plane. The plane is gradually inclined until at an angle Greek letter theta 15 degrees with the horizontal. The mass just begins to slide. What is the coefficient of static friction between the block and the surface? Figure 5.11. Answer: the forces acting on a block of mass m at rest on an inclined plane are I, the weight mg acting vertically downwards to the normal force n of the plane, on the block, and 3. the static frictional force Fs opposing the impending motion. In equilibrium, the resultant of these forces must be 0. Resolving the weight mg along the two directions shown, we have mg sin Fs, mg cos Greek letter theta n as Greek letter theta increases. The self-adjusting frictional force Fs increases until at Greek letter theta max, Fs achieves its maximum value. Max SF micros n, therefore, 10 max micros are max tan 1 micros. When Greek letter theta becomes just a little more than max, there is a small net force on the block and it begins to slide. Note that max depends only on micros and is independent of the mass of the block. For max 15 degrees, micros tan 15 degrees 0.27 t. Example 5.9 What is the acceleration of the block and trolley system shown in a fig. 5.12 If the coefficient of kinetic friction between the trolley and the surface is 0.04, what is the tension in the string? Take g 10 meters s2. Neglect the mass of the string BC. Figure 5.12 t. Laws of motion 103 is the reason why discovery of the wheel has been a major milestone in human history. Rolling friction again has a complex origin, though somewhat different from that of static and sliding friction. During rolling, the surfaces in contact get momentarily deformed a little, and this results in a finite area, not a point of the body being in contact with the surface. The net effect is that the component of the contact force parallel to the surface opposes motion. We often regard friction as something undesirable. In many situations, like in a machine with different moving parts, friction does have a negative role. It opposes relative motion and thereby dissipates power in the form of heat, etc. Lubricants are a way of reducing kinetic friction in a machine. Another way is to use ball bearings between two moving parts of a machine. Figure 5.13 Since the rolling friction between ball bearings and the surfaces in contact is very small, power dissipation is reduced. A thin cushion of air maintained between solid surfaces in relative motion is another effective way of reducing friction. Fig. 5.13 In many practical situations, however, friction is critically needed. Kinetic friction that dissipates power is nevertheless important for quickly stopping relative motion. It is made use of by brakes in machines and automobiles. Similarly, static friction is important in daily life. We are able to walk because of friction. It is impossible for a car to move on a very slippery road. On an ordinary road, the friction between the tires and the road provides the necessary external force to accelerate the car. Answer: as the string is inextensible, and the pulley is smooth, the 3 kg block and the 20 kg trolley both have same magnitude of acceleration. Applying second law to motion of the block figure 5.12b, 30t3 apply the second law to motion of the trolley fig. 5.12c, t, fk20a now fk microc n, here microc 0.04, n20 x 10 to 100 n. Thus the equation for the motion of the trolley is t 0.04 x 220 or t 820a. These equations give a 2223 meters s minus 2 0.96 meters s to n t 27.1 n. T rolling friction: a body like a ring or a sphere rolling without slipping over a horizontal plane will suffer no friction, in principle. At every instant, there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. In this ideal situation, kinetic or static friction is zero and the body should continue to roll with constant velocity. We know, in practice, this will not happen and some resistance to motion rolling friction does occur, that is, to keep the body rolling, some applied force is needed. For the same weight, rolling friction is much smaller even by 2 or 3 orders of magnitude than static or sliding friction. This figure 5.13 some ways of reducing friction of ball bearings placed between moving parts of a machine. B. Compressed cushion of air between surfaces in relative motion. Physics 104 5.10 Circular motion. We have seen in Chapter 4 that acceleration of a body moving in a circle of radius r with uniform speed v is v2r directed towards the center. According to the second law, the force Fc providing this acceleration is 2 cm VFR 5.16 where m is the mass of the body. This force directed forwards the center is called the centripetal force. For a stone rotated in a circle by a string, the centripetal force is provided by the tension in the string. The centripetal force for motion of a planet around the sun is the static friction that provides the centripetal acceleration. Static friction opposes the impending motion of the car moving away from the circle. Using equation 5.14-5.16 we get the result 2sm VFNR micro 2SSR and VRGM micro NMG, which is independent of the mass of the car. This shows that for a given value of micro s and r, there is a maximum speed of circular motion of the car possible, namely max sv micro 5.18 to b fig. 5.14 Circular motion of a car on a level road, be a bank road. Gravitational force on the planet due to the sun. For a car taking a circular turn on a horizontal road, the centripetal force is the force of friction. The circular motion of a car on a flat and bank road give interesting application of the laws of motion. Motion of a car on a level road. 3 forces act on the car. Figure 5.14 I the weight of the car. mg2 normal reaction, n3 frictional force, F as there is no acceleration in the vertical direction n, mg0 and mg 5.17 The centripetal force required for circular motion is along the surface of the road, and is provided by the component of the contact force between road and the car tires along the surface. This by definition is the frictional force. Note that at motion of a car on a bank road we can reduce the contribution of friction to the circular motion of the car if the road is bank fig. 5.14b Since there is no acceleration along the vertical direction, the net force along this direction must be zero. Hence, n cos Greek letter theta mgf sin Greek letter theta 5.19 of the centripetal force is provided by the horizontal components of n and f. N sin Greek letter theta f cos Greek letter theta 2 mvr 5.19b but fs micro. Thus to obtain v max we put sf micro. Then EQS 5.19 and 5.19b become n cos Greek letter theta mgs micro sin Greek letter theta 5.20 up. Laws of motion 105 ttn sin Greek letter theta s micro cos Greek letter theta mv2r 5.20b from EQ 5.20 we obtain smgn cos sin micro Greek letter theta substituting value of n and EQ. 5.20b we get to max ssmg sin cos mv cos sin r Greek letter theta micro Greek letter theta micro Greek letter theta or 1 to max 1 ss tan vrg tan micro Greek letter theta 5.21. Comparing this with EQ 5.18 we see that maximum possible speed of a car on a bank road is greater than that on a flat road. For micro 0 in EQ 5.21, VRG tan Greek letter theta 1/2 5.22 at this speed, frictional force is not needed at all to provide the necessary centripetal force. Driving at this speed on a bank road will cause little wear and tear of the tires. The same equation also tells you that for VO, frictional force will be up the slope and that a car can be parked only if tan Greek letter theta micros. Example 5.10 A cyclist speeding at 18 km/h on a level road takes a sharp circular turn of radius 3 meters without reducing the speed. The coefficient of static friction between the tires and the road is 0.1. Will the cyclist slip while taking the turn? Answer: on an unbanked road, Frictional force alone can provide the centripetal force needed to keep the cyclist moving on a circular turn without slipping. If the speed is too large, or if the turn is too sharp, that is of too small a radius, or both, the frictional force is not sufficient to provide the necessary centripetal force, and the cyclist slips. The condition for the cyclist not to slip is given by EC 5.18, V2 micro SRG now, R 3 meters, G 9.8 meters S2, micro 0.1. That is, micros RG 2.94 square meters S2 V 18 kilometers H 5 meters S1, that is, V2 25 square meters S2, the condition is not obeyed. The cyclist will slip while taking the circular turn T. Example 5.11. A circular racetrack of radius 300 meters is banked at an angle of 15 degrees. If the coefficient of friction between the wheels of the race car and the road is 0.2, what is the optimum speed of the race car to avoid wear and tear on its tires? And B. Maximum permissible speed to avoid slipping. Answer. On a banked road, the horizontal component of the normal force and the frictional force contribute to provide centripetal force to keep the car moving on a circular turn without slipping. At the optimum speed, the normal reactions component is enough to provide the needed centripetal force, and the frictional force is not needed. The optimum speed VO is given by EC 5.22, VO RG tan Greek letter theta 1 2 here are 300 meters, Greek letter theta 15 degrees, G 9.8 meters S2, we have VO 28.1 meters S1. The maximum permissible speed Vmax is given by EC 5.21, T 5.11. Solving problems in mechanics. The three laws of motion that you have learned in this chapter are the foundation of mechanics. You should now be able to handle a large variety of problems in mechanics. A typical problem in mechanics usually does not merely involve a single body under the action of given forces. More often, we will need to consider an assembly of different bodies exerting forces on each other. Besides, each body in the assembly experiences the force of gravity when trying to solve a problem of this type. It is useful to remember the fact that we can choose any part of the assembly and apply the laws of motion to that part, provided we include all forces on the chosen part due to the remaining parts of the assembly. We may call the chosen part of the assembly as the system and the remaining part of the assembly plus any other agencies of forces as the environment. We have followed the same Physics 106T method in solved examples. To handle a typical problem in mechanics systematically, one should use the following steps. I draw a diagram showing schematically the various parts of the assembly of bodies, the links, supports, etc. 2. Choose a convenient part of the assembly as one system. 3. Draw a separate diagram which shows this system and all the forces on the system by the remaining part of the assembly. Include also the forces on the system by other agencies. Do not include the forces on the environment by the system. A diagram of this type is known as a free body diagram. Note this does not imply that the system under consideration is without a net force. In a free body diagram, include information about forces, their magnitudes and directions that are either given or you are sure of, e.g., the direction of tension in a string along its length. The rest should be treated as unknowns to be determined using laws of motion. If necessary, follow the same procedure for another choice of the system. In doing so, employ Newton's third law, that is, if in the free body diagram of A, the force on A due to B is shown as F, then in the free body diagram of B, the force on B due to A should be shown as F. The following example illustrates the above procedure. Example 5.12. See Fig. 5.15. A wooden block of mass 2 kg rests on a soft horizontal floor. When an iron cylinder of mass 25 kg is placed on top of the block, the floor yields steadily and the block and the cylinder together go down with an acceleration of 0.1 meters s2. What is the action of the block on the floor before and B after the floor yields? Take G 10 meters s2. Identify the action-reaction pairs in the problem. Answer: the block is at rest on the floor. Its free body diagram shows two forces on the block, the force of gravitational attraction by the Earth equal to 2x 1020 n, and the normal force R of the floor on the block. By the first law, the net force on the block must be 0, that is, R 20 n. Using third law, the action of the block, that is, the force exerted on the floor by the block, is equal to 20 n and directed vertically downwards. B. The system block cylinder accelerates downwards with 0.1 meters s2. The free body diagram of the system shows two forces on the system, the force of gravity due to the Earth 270 n, and the normal force R by the floor. Note, the free body diagram of the system does not show the internal forces between the block and the cylinder. Applying the second law to the system, 270 R 27x 0.1 n i.e., R 267.3 n Fig. 5.15. By the third law, the action of the system on the floor is equal to 267.3 n vertically downward. Action-reaction pairs for A. The force of gravity 20 n on the block by the Earth's A. Action, the force of gravity on the Earth by the block reaction equal to 20 N directed upwards not shown in the figure. 2. The force on the floor by the block action, the force on the block by the floor reaction. For B, I the force of gravity 270 N on the system by the Earth's A, action, the force of gravity on the Earth by the system reaction. Equal to 270 N. Laws of motion 107 directed upwards not shown in the figure. 2. The force on the floor by the system action, the force on the system by the floor reaction. In addition, for B, the force on the block by the cylinder and the force on the cylinder by the block also constitute an action-reaction pair. The important thing to remember is that an action-reaction pair consists of mutual forces which are always equal and opposite between two bodies. Two forces on the same body which happen to be equal and opposite can never constitute an action-reaction pair. The force of gravity on the mass in A or B and the normal force on the mass by the floor are not action-reaction pairs. These forces happen to be equal and opposite for A since the mass is at rest. They are not so for case B, as seen already. The weight of the system is 270 N, while the normal force R is 267.3 Nt. The practice of drawing free body diagrams is of great help in solving problems in mechanics. It allows you to clearly define your system and consider all forces on the system due to objects that are not part of the system itself. A number of exercises in this and subsequent chapters will help you cultivate this practice. Summary 1. Aristotle's view that a force is necessary to keep a body in uniform motion is wrong. A force is necessary in practice to counter the opposing force of friction. 2. Galileo extrapolated simple observations on motion of bodies on inclined planes, and arrived at the law of inertia. Newton's first law of motion is the same law rephrased thus: every body continues to be in its state of rest or of uniform motion in a straight line, unless compelled by some external force to act otherwise. In simple terms, the first law is if external force on a body is zero, its acceleration is zero. 3. Momentum p of a body is the product of its mass m and velocity v, pmv4. Newton's second law of motion: the rate of change of momentum of a body is proportional to the applied force and takes place in the direction in which the force acts. Thus ddkkmtpf, where F is the net external force on the body and A its acceleration. We set the constant of proportionality K1 in SI units, then ddmtpf of the SI unit of force is Newton, 1 in 1 kg ms2. The second law is consistent with the first law. F0 implies a zero, be it is a vector equation, see it as applicable to a particle, and also to a body or a system of particles, provided F is the total external force on the system and A is the acceleration of the system as a whole. dF at a point at a certain instant determines A at the same point at that instant. That is, the second law is a local law. A at an instant does not depend on the history of motion. 5. Impulse is the product of force and time, which equals change in momentum. The notion of impulse is useful when a large force acts for a short time to produce a measurable change in momentum. Since the time of action of the force is very short, one can assume that there is no appreciable change in the position of the body during the action of the impulsive force. 6. Newton's third law of motion: to every action, there is always an equal and opposite reaction. Physics 108. In simple terms, the law can be stated thus: forces in nature always occur between pairs of bodies. Force on a body A by body B is equal and opposite to the force on the body B by A. Action and reaction forces are simultaneous forces. There is no cause-effect relation between action and reaction. Any of the two mutual forces can be called action and the other reaction. Action and reaction act on different bodies and so they cannot be cancelled out. The internal action and reaction forces between different parts of a body do, however, sum to zero. 7. Law of conservation of momentum: the total momentum of an isolated system of particles is conserved. The law follows from the second and third law of motion. 8. Friction: frictional force opposes impending or actual relative motion between two surfaces in contact. It is the component of the contact force along the common tangent to the surface in contact. Static friction Fs opposes impending relative motion. Kinetic friction Fk opposes actual relative motion. They are independent of the area of contact and satisfy the following approximate laws: max FFRs SS micro KFRK micro S. Coefficient of static friction and micro K coefficient of kinetic friction are constants characteristic of the pair of surfaces in contact. It is found experimentally that micro K is less than micro S. Points to ponder: 1. Force is not always in the direction of motion. Depending on the situation, F may be along V, opposite to V, normal to V, or may make some other angle with V. In every case, it is parallel to acceleration 2. If V0 at an instant, that is if a body is momentarily at rest, it does not mean that force or acceleration are necessarily zero at that instant. For example, when a ball thrown upward reaches its maximum height, v0 but the force continues to be its weight mg and the acceleration is not 0 but g. 3. Force on a body at a given time is determined by the situation at the location of the body at the time. Force is not carried by the body from its earlier history of motion. The moment after a stone is released out of an accelerated train, there is no horizontal force or acceleration on the stone, if the effects of the surrounding air are neglected. The stone then has only the vertical force of gravity 4. In the second law of motion FMA, F stands for the net force due to all material agencies external to the body. I as the effect of the force ma should not be regarded as yet another force, besides F. Laws of motion 109.5. The centripetal force should not be regarded as yet another kind of force. It is simply a name given to the force that provides inward radial acceleration to a body in circular motion. We should always look for some material force like tension, gravitational force, electrical force, friction, etc. as the centripetal force in any circular motion. 6. Static friction is a self-adjusting force up to its limit micros n Fs micros n. Do not put Fs micros n without being sure that the maximum value of static friction is coming into play. 7. The familiar equation mgr for a body on a table is true only if the body is in equilibrium. The two forces mg and r can be different, e.g. a body in an accelerated lift. The equality of mg and r has no connection with the third law. 8. The terms action and reaction in the third law of motion simply stand for simultaneous mutual forces between a pair of bodies. Unlike their meaning in ordinary language, action does not precede or cause reaction. Action and reaction act on different bodies. 9. The different terms like friction, normal reaction tension, air resistance, viscous drag, thrust, buoyancy, weight, centripetal force all stand for force in different contexts. For clarity, every force and its equivalent terms encountered in mechanics should be reduced to the phrase force on A by B. 10. For applying the second law of motion, there is no conceptual distinction between inanimate and animate objects. Inanimate objects such as a human also requires an external force to accelerate. For example, without the external force of friction, we cannot walk on the ground. 11. The objective concept of force in physics should not be confused with the subjective concept of the feeling of force. On a merry-go-round, all parts of our body are subject to an inward force, but we have a feeling of being pushed outward, the direction of impending motion. Exercises for simplicity in numerical calculations. Take G 10 meters S2 5.1. Give the magnitude and direction of the net force acting on a drop of rain falling down with a constant speed. B. A cork of mass 10 grams floating on water. C. A kite skillfully held stationary in the sky. D. A car moving with a constant velocity of 30 km/h on a rough road. E. A high-speed electron in space far from all material objects, and free of electric and magnetic fields. 5.2. A pebble of mass 0.05 kilograms is thrown vertically upwards. Give the direction and magnitude of the net force on the pebble, A. during its upward motion, B. during its downward motion, C. at the highest point where it is momentarily at rest. Do your answers change if the pebble was thrown at an angle of 45 degrees with the horizontal direction? Ignore air resistance. 5.3. Give the magnitude and direction of the net force acting on a stone of mass 0.1 kilograms, A. just after it is dropped from the window of a stationary train. B. just after it is dropped from the window of a train running at a constant velocity of 36 km/h. C. just after it is dropped from the window of a train accelerating with 1 meters S2. D. lying on the floor of a train which is accelerating with 1 meters S2, the stone being at rest relative to the train. Neglect air resistance throughout. Physics 110 5.4. One end of a string of length L is connected to a particle of mass m and the other to a small peg on a smooth horizontal table. If the particle moves in a circle with speed v, the net force on the particle directed towards the center is it. 2 liters mvt2, 3 liters mvt2, I0d is the tension in the string. Choose the correct alternative. 5.5. A constant retarding force of 50 N is applied to a body of mass 20 kilograms moving initially with a speed of 15 meters s1. How long does the body take to stop? 5.6. A constant force acting on a body of mass 3.0 kilograms changes its speed from 2.0 meters s1 to 3.5 meters s1 in 25 s. The direction of the motion of the body remains unchanged. What is the magnitude and direction of the force? 5.7. A body of mass 5 kilograms is acted upon by two perpendicular forces 8N and 6N. Give the magnitude and direction of the acceleration of the body. 5.8. The driver of a three-wheeler moving with a speed of 36 km/h sees a child standing in the middle of the road and brings his vehicle to rest in 4.0 s just in time to save the child. What is the average retarding force on the vehicle? The mass of the three-wheeler is 400 kilograms and the mass of the driver is 65 kilograms. 5.9 A cut with a liftoff mass 20,000 kg is blasted upwards with an initial acceleration of 5.0 meters s2. Calculate the initial thrust force of the blast. 5.10 A body of mass 0.40 kg moving initially with a constant speed of 10 meters s1 to the north is subject to a constant force of 8.0 and directed towards the south for 30 s. Take the instant the force is applied to be t0, the position of the body at that time to be x0, and predict its position at t-5s, 25s, 100s. 5.11 A truck starts from rest and accelerates uniformly at 2.0 meters s2. At t10s, a stone is dropped by a person standing on the top of the truck 6 meters high from the ground. What are the A velocity and B acceleration of the stone at t11s? Neglect air resistance. 5.12 A bob of mass 0.1 kg hung from the ceiling of a room by a string 2 meters long is set into oscillation. The speed of the bob at its mean position is 1 meters s1. What is the trajectory of the bob if the string is cut when the bob is at one of its extreme positions, B at its mean position? 5.13 A man of mass 70 kg stands on a weighing scale in a lift which is moving upwards with a uniform speed of 10 meters s1. B downwards with a uniform acceleration of 5 meters s2, C upwards with a uniform acceleration of 5 meters s2. What would be the readings on the scale in each case? D. What would be the reading if the lift mechanism failed and it hurtled down freely under gravity? 5.14 Figure 5.16 shows the position time graph of a particle of mass 4 kilograms. What is the force on the particle for t, 0, t, 4s, 0, t, 4s? B impulse at t0 and t4s. Consider one-dimensional motion only. Figure 5.16 5.152 bodies of masses 10 kilograms and 20 kilograms respectively kept on a smooth, horizontal surface are tied to the ends of a light string. A horizontal force F600N is applied to IA, 2B along the direction of string. What is the tension in the string in each case? Laws of motion 111 5.162 masses 8 kilograms and 12 kilograms are connected at the two ends of a light and extensible string that goes over a frictionless pulley. Find the acceleration of the masses, and the tension in the string when the masses are released. 5.17 A nucleus is at rest in the laboratory frame of reference. Show that if it disintegrates into two smaller nuclei the products must move in opposite directions. 5.18 Two billiard balls each of mass 0.05 kilograms moving in opposite directions with speed 6 meters s1 collide and rebound with the same speed. What is the impulse imparted to each ball due to the other? 5.19 A shell of mass 0.020 kilograms is fired by a gun of mass 100 kilograms. If the muzzle speed of the shell is 80 meters s1, what is the recoil speed of the gun? 5.20 A batsman deflects a ball by an angle of 45 degrees without changing its initial speed, which is equal to 54 km/h. What is the impulse imparted to the ball? Mass of the ball is 0.15 kilograms. 5.21 A stone of mass 0.25 kilograms tied to the end of a string is whirled round in a circle of radius 1.5 meters with a speed of 40 rev/min in a horizontal plane. What is the tension in the string? What is the maximum speed with which the stone can be whirled around if the string can withstand a maximum tension of 205.22 if? In exercise 5.21, the speed of the stone is increased beyond the maximum permissible value, and the string breaks suddenly. Which of the following correctly describes the trajectory of the stone after the string breaks? A. The stone moves radially outwards. B. The stone flies off tangentially from the instant the string breaks. C. The stone flies off at an angle with the tangent whose magnitude depends on the speed of the particle. 5.23 Explain why a horse cannot pull a cart and run in empty space. B. Passengers are thrown forward from their seats when a speeding bus stops suddenly. C. It is easier to pull a lawnmower than to push it. D. A cricketer moves his hands backwards while holding a catch. Additional exercises 5.24 Figure 5.17 shows the position time graph of a body of mass 0.04 kilograms. Suggest a suitable physical context for this motion. What is the time between two consecutive impulses received by the body? What is the magnitude of each impulse? Fig. 5.17 5.25 Figure 5.18 shows a man standing stationary with respect to a horizontal conveyor belt that is accelerating with 1 meters s2. What is the net force on the man if the coefficient of static friction between the man's shoes and the belt is 0.2? Up to what acceleration of the belt can the man continue to be stationary relative to the belt mass of the man? 65 kilograms. Fig. 5.18. Physics 112 Figure 5.19 5.26 A stone of mass m tied to the end of a string revolves in a vertical circle of radius r. The net forces at the lowest and highest points of the circle directed vertically downwards are. Choose the correct alternative. Lowest point, highest point A mgt1 mgt2 b mgt1 mg, t2 c mgt1 mv21 r mg, T2M V21 RDMG T1M V21 RMG T2M V21 RT1 and V1 denote the tension and speed at the lowest point. T2 and V2 denote corresponding values at the highest point. 5.27 A helicopter of mass 1000 kilograms rises with a vertical acceleration of 15 meters s2. The crew and the passengers weigh 300 kilograms. Give the magnitude and direction of the force on the floor by the crew and passengers. B. Action of the rotor of the helicopter on the surrounding air. C. Force on the helicopter due to the surrounding air. 5.28 A stream of water flowing horizontally with a speed of 15 meters s1 gushes out of a tube of cross-sectional area 10 square meters, and hits a vertical wall nearby. What is the force exerted on the wall by the impact of water, assuming it does not rebound? 5.29 10 1 rupee coins are put on top of each other on a table. Each coin has a mass and give the magnitude and direction of the force on the seventh coin counted from the bottom due to all the coins on its top. B. The force on the seventh coin by the eighth coin. C. The reaction of the sixth coin on the seventh coin. 5.30 An aircraft executes a horizontal loop at a speed of 720 km/h with its wings banked at 15 degrees. What is the radius of the loop? 5.31 A train runs along an unbanked circular track of radius 30 meters at a speed of 54 km/h. The mass of the train is 106 kilograms. What provides the centripetal force required for this purpose? The engine or the rails? What is the angle of banking required to prevent wearing out of the rail? 5.32 A block of mass 25 kilograms is raised by a 50-kilogram man in two different ways as shown in Fig. 5.19 What is the action on the floor by the man in the two cases if the floor yields to a normal force of 700 N? Which mode should the man adopt to lift the block without the floor yielding? Laws of motion 113 5.33 A monkey of mass 40 kilograms climbs on a rope. Figure 5.20 which can stand a maximum tension of 600 N. In which of the following cases will the rope break? The monkey A climbs up with an acceleration of 6 meters s2. B climbs down with an acceleration of 4 meters s2. C climbs up with a uniform speed of 5 meters s1. D falls down the rope nearly freely under gravity. Ignore the mass of the rope. 5.34 Two bodies A and B of masses 5 kilograms and 10 kilograms in contact with each other rest on a table against a rigid wall. Fig. 5.21 The coefficient of friction between the bodies and the table is 0.15. A force of 200 N is applied horizontally to A. What are the reaction of the partition B? The action-reaction forces between A and B. What happens when the wall is removed? Does the answer to be change? When the bodies are in motion, ignore the difference between micros and micro. 5.35 A block of mass 15 kilograms is placed on a long trolley. The coefficient of static friction between the block and the trolley is 0.18. The trolley accelerates from rest with 0.5 meters s2 for 20 s and then moves with uniform velocity. Discuss the motion of the block as viewed by a stationary observer on the ground. Be an observer moving with the trolley. 5.36 The rear side of a truck is open and a box of 40 kilograms mass is placed 5 meters away from the open end as shown in Fig. 5.22 The coefficient of friction between the box and the surface below it is 0.15. On a straight road, the truck starts from rest and accelerates with 2 meters s2. At what distance from the starting point does the box fall off the truck? Ignore the size of the box. 5.37 A disc revolves with a speed of 3313 revmin, and has a radius of 15 centimeters. Two coins are placed at 4 centimeters and 14 centimeters away from the center of the record. If the coefficient of friction between the coins and the record is 0.15, which of the coins will revolve with the record? 5.38 You may have seen in a circus a motorcyclist driving in vertical loops inside a death well hollow spherical chamber with holes, so the spectators can watch from outside. Explain clearly why the motorcyclist does not drop down when he is at the uppermost point, with no support from below. What is the minimum speed required at the uppermost position to perform a vertical loop if the radius of the chamber is 25 meters? 5.39 A 70 kilograms man stands in contact against the inner wall of a hollow cylindrical drum of radius 3 meters rotating about its vertical axis with 200 rev minimum. The coefficient of friction between the wall and his clothing is 0.15. What is the minimum rotational speed of the cylinder to enable the man to remain stuck to the wall without falling when the floor is suddenly removed? 5.40 A thin circular loop of radius r rotates about its vertical diameter with an angular frequency Greek letter omega. Show that a small bead on the wire loop remains at its lowermost point for Greek letter omega gr. What is the angle made by the radius vector joining the center to the bead with the vertical downward direction for Greek letter omega? 2 grams are neglect friction. Figure 5.20 Figure 5.21 Figure 5.22 Chapter 6 Work, Energy and Power 6.1 Introduction The terms work, energy and power are frequently used in everyday language. A farmer plowing the field, a construction worker carrying bricks, a student studying for a competitive examination, an artist painting a beautiful landscape, all are said to be working. In physics, however, the word work covers a definite and precise meaning. Somebody who has the capacity to work for 14-16 hours a day is said to have a large stamina or energy. We admire a long-distance runner for her stamina or energy. Energy is thus our capacity to do work. In physics too, the term energy is related to work in this sense, but as said above, the term work itself is defined much more precisely. The word power is used in everyday life with different shades of meaning. In karate or boxing we talk of powerful punches. These are delivered at a great speed. This shade of meaning is close to the meaning of the word power used in physics. We shall find that there is at best a loose correlation between the physical definitions and the physiological pictures these terms generate in our minds. The aim of this chapter is to develop an understanding of these three physical quantities. Before we proceed to this task, we need to develop a mathematical prerequisite, namely the scalar product of two vectors. 6.1. The scalar product. We have learnt about vectors and their use in Chapter 4, physical quantities like displacement, velocity, acceleration, force, etc. are vectors. We have also learnt how vectors are added or subtracted. We now need to know how vectors are multiplied. There are two ways of multiplying vectors which we shall come across. One way, known as the scalar product, gives a scalar from two vectors, and the other, known as the vector product, produces a new vector from two vectors. We shall look at the vector product in Chapter 7. Here we take up the scalar product of two vectors. The scalar product or dot product of any two vectors A and B. Denoted as AB. Read 6.1 Introduction. 6.2 Notions of work and kinetic energy. The work energy theorem. 6.3 Work. 6.4 Kinetic energy. 6.5 Work done by a variable force. 6.6 The work energy theorem for a variable force. 6.7 The concept of potential energy. 6.8 The conservation of mechanical energy. 6.9 The potential energy of a spring. 6.10 Various forms of energy. The law of conservation of energy. 6.11 Power. 6.12 Collision. Summary points to ponder. Exercises. Additional exercises. Appendix. 6.1 A dot B is defined as AB cos Greek letter theta. 6.1 where Greek letter theta is the angle between the two vectors as shown in Fig. 6.1 Since A, B and cos Greek letter theta are scalars, the dot product of A and B is a scalar quantity. Each vector, A and B, has a direction, but their scalar product does not have a direction. From X 6.1 we have AB cos Greek letter theta BA cos Greek letter theta. Geometrically, B cos Greek letter theta is the projection of B onto A in Figure 6.1 B, and A cos Greek letter theta is the projection of A onto B in Fig. 6.1 C. So, AB is the product of the magnitude of A and the component of B along A. Alternatively, it is the product of the magnitude of B and the component of A along B. Equation 6.1 shows that the scalar product follows the commutative law. ABBA scalar product obeys the distributive law. ABC ABAC further. A Greek letter lambda B Greek letter lambda AB, where Greek letter lambda is a real number. The proofs of the above equations are left to you as an exercise. For unit vectors I, J, K we have IIJJKK1 IJJKKI0 given two vectors AIJKAAXYZ BIJKBBBXYZ. Their scalar product is dot XYZXYZ AABBBABIJKIJKABABABXXYYZZ. 6.1b From the definition of scalar product and Ek. 6.1b we have IXXYYZ AAAAAA, or AAAA2x2y to z2. 6.1c Since AAAA cos 0a2 2ab0, if A and B are perpendicular. Example 6.1 Find the angle between force F345 IJK unit and displacement D543 IJK unit. Also find the projection of F on D. Answer FDXXYYZZ FD 16 unit, hence FD cos FD Greek letter theta 16 unit. Now FF2222XYZ FFFF 9 16 25 50 unit and DDD 2222XYZ DDD 25 16 9 50 unit. Cos Greek letter theta 16 16 0 32 50 50 50 Greek letter theta cos 1 0.32 Fig. 6.1 of the scalar product of two vectors A and B is a scalar. AB cos Greek letter theta BB cos Greek letter theta is the projection of B onto AC. A cos Greek letter theta is the projection of A onto B. Work, energy and power 115 U. Physics 116T to be proportional to the speed of the drop but is otherwise undetermined. Consider a drop of mass 1.00 grams falling from a height 1.00 kilometers. It hits the ground with a speed of 50.0 meters s1. What is the work done by the gravitational force? What is the work done by the unknown resistive force? Answer of the change in kinetic energy of the drop is 2102 km v1 2 10 50 53 xxx 1.25 j, where we have assumed that the drop is initially at rest. Assuming that g is a constant with a value 10 meters s2, the work done by the gravitational force is WGmgh 10 3x 10x 103 10.0 jb from the work energy theorem GRKWW, where WR is the work done by the resistive force on the raindrop. Thus WRKWG 1.25 10 8.75 j is negative T 6.3. Work as seen earlier, work is related to force and the displacement over which it acts. Consider a constant force F acting on an object of mass m. The object undergoes a displacement d in the positive x direction as shown in Fig. 6.2. Figure 6.2. An object undergoes a displacement d under the influence of the force F. 6.2. Notions of work and kinetic energy. The work energy theorem. The following relation for rectilinear motion under constant acceleration has been encountered in Chapter 3. v2u22 is 6.2, where u and v are the initial and final speeds and s the distance traversed. Multiplying both sides by m2, we have 221,122 mv mu mass F 6.2, where the last step follows from Newton's second law. We can generalize x 6.2 to 3 dimensions by employing vectors v2u22 ad here and dr acceleration and displacement vectors of the object respectively. Once again multiplying both sides by m2, we obtain 221,122 mv mu m 80 fd 6.2b. The above equation provides a motivation for the definitions of work and kinetic energy. The left side of the equation is the difference in the quantity half the mass times the square of the speed from its initial value to its final value. We call each of these quantities the kinetic energy, denoted by K. The right side is a product of the displacement and the component of the force along the displacement. This quantity is called work and is denoted by Wx 6.2. The is then Kf Kw 6.3, where K and Kf are respectively the initial and final kinetic energies of the object. Work refers to the force and the displacement over which it acts. Work is done by a force on the body over a certain displacement. Equation 6.2 is also a special case of the work energy theorem. The change in kinetic energy of a particle is equal to the work done on it by the net force. We shall generalize the above derivation to a varying force in a later section. Example 6.2. It is well known that a raindrop falls under the influence of the downward gravitational force and the opposing resistive force. The latter is known. Work, energy and power 117 T Table 6.1 Alternative units of work energy and J. Example 6.3 A cyclist comes to a skidding stop in 10 meters. During this process, the force on the cycle due to the road is 200 N and is directly opposed to the motion. A. How much work does the road do on the cycle? B. How much work does the cycle do on the road? Answer. Work done on the cycle by the road is the work done by the stopping frictional force on the cycle due to the road. The stopping force and the displacement make an angle of 180 Greek letter pi rad with each other. Thus, work done by the road, WRFD cos 200x 10x cos Greek letter pi 2000 j. It is this negative work that brings the cycle to a halt in accordance with theorem. B. From Newton's third law, an equal and opposite force acts on the road due to the cycle. Its magnitude is 200 N. However, the road undergoes no displacement. Thus, work done by cycle on the road is 0. T. The lesson of example 6.3 is that though the force on a body A exerted by the body B is always equal and opposite to that on B by A, Newton's third law, the work done on A by B is not necessarily equal and opposite to the work done on B by A. 6.4 Kinetic energy. As noted earlier, if an object of mass m has velocity v, its kinetic energy K is 2 km v 1122 volt v. 6.5 Kinetic energy is a scalar quantity. The kinetic energy of an object is a measure of the work, and the work done by the force is defined to be the product of component of the force in the direction of the displacement and the magnitude of this displacement. Thus Wf cos Greek letter theta dfd 6.4. We see that if there is no displacement, there is no work done even if the force is large. Thus, when you push hard against a rigid brick wall, the force you exert on the wall does no work. Yet your muscles are alternatively contracting and relaxing, and internal energy is being used up and you do get tired. Thus, the meaning of work in physics is different from its usage in everyday language. No work is done if the displacement is 0, as seen in the example above. A weightlifter holding a 150 kg mass steadily on his shoulder for 30 s does no work on the load during this time. 2. The force is 0. A block moving on a smooth horizontal table is not acted upon by a horizontal force since there is no friction, but may undergo a large displacement. 3. The force and displacement are mutually perpendicular. This is so since, for Greek letter theta Greek letter pi 2 rad 90 O, cos Greek letter pi 2 0. For the block moving on a smooth horizontal table, the gravitational force mg does no work since it acts at right angles to the displacement. If we assume that the moon's orbits around the Earth is perfectly circular, then the Earth's gravitational force does no work. The moon's instantaneous displacement is tangential while the Earth's force is radially inwards and Greek letter theta Greek letter pi 2. Work can be both positive and negative. If Greek letter theta is between 0 and 90 cos Greek letter theta in x 6.4 is positive. If Greek letter theta is between 90 and 180 cos Greek letter theta is negative. In many examples the frictional force opposes displacement and Greek letter theta 180. Then the work done by friction is negative cos 180 minus 1. From x 6.4 it is clear that work and energy have the same dimensions, ml2t2. The SI unit of these is Joule J, named after the famous British physicist James Prescott Joule 1811-1869. Since work and energy are so widely used as physical concepts, alternative units abound and some of these are listed in Table 6.1. Physics 118T object can do by the virtue of its motion. This notion has been intuitively known for a long time. The kinetic energy of a fast-flowing stream has been used to grind corn. Sailing ships employ the kinetic energy of the wind. Table 6.2 lists the kinetic energies for various objects. Example 6.4 in a ballistics demonstration a police officer fires a bullet of mass 50.0 grams with speed 200 meters s1. See Table 6.2 on soft plywood of thickness 2.00 centimeters. The bullet emerges with only 10 of its initial kinetic energy. What is the emergent speed of the bullet? Answer: the initial kinetic energy of the bullet is mv2 to 1000 joules. It has a final kinetic energy of 0.1 x 1100 joules if Vf is the emergent speed of the bullet. 12 mvf to 100 jkg 050 j 102 xfv 63.2 meters s1. The speed is reduced by approximately 68 not 90. T6.5 Work done by a variable force. A constant force is rare. It is the variable force, which is more commonly encountered. Figure 6.3 is a plot of a varying force in one dimension. If the displacement x is small, we can take the force Fx as approximately constant and the work done is then Wfxx. Table 6.2 Typical kinetic energies K. This is illustrated in Fig. 6.3 Adding successive rectangular areas in Figure 6.3 we get the total work done as Fixxxxfw 6.6 where the summation is from the initial positions I to the final position xf. If the displacements are allowed to approach zero, then the number of terms in the sum increases without limit, but the sum approaches a definite value equal to the area under the curve in Fig. 6.3b, then the work done is Fxxxxxifd 6.7 where lim stands for the limit of the sum when x tends to 0. Thus, for a varying force the work done can be expressed as a definite integral of force over displacement. See also Appendix 3.1. Lim x Fixxxxxf0 Figure 6.3 Work, energy and power 119T. Figure 6.3 of the shaded rectangle represents the work done by the varying force Fx, over the small displacement x, Wfxx. By adding the areas of all the rectangles we find that for x0, the area under the curve is exactly equal to the work done by Fx. Example 6.5 A woman pushes a trunk on a railway platform which has a rough surface. She applies the force of 100 N over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with distance to 50 N. The total distance through which the trunk has been moved is 20 meters. Plot the force applied by the woman and the frictional force, which is 50 N versus displacement. Calculate the work done by the two forces over 20 meters. Answer: Figure 6.4 Plot of the force F applied by the woman and the opposing frictional force F versus displacement. The plot of the applied force is shown in Figure 6.4. At x 20 meters, F 50 N 0, we are given that the frictional force F is F 50 N. It opposes motion and acts in a direction opposite to F. It is therefore shown on the negative side of the force axis. The work done by the woman is Wf area of the rectangle ABCD area of the trapezium CWFXX 110 12 100 50 10 1750 1750 J. The work done by the frictional force is Wf area of the rectangle AGWF 50 x 20 1000 J. The area on the negative side of the force axis has a negative sign. T6.6 The work energy theorem for a variable force. We are now familiar with the concepts of work and kinetic energy. To prove the work energy theorem for a variable force, we confine ourselves to one dimension. The time rate of change of kinetic energy is ddddkttmv122ddvmvtvf from Newton's second law ddxft. Thus dkfdx integrating from the initial position xi to final position xf. We have ddkfxkkxxifif where k and kf are the initial and final kinetic energies corresponding to xi and xf. or KKFXFIXXIFD 6.8 from X 6.7, it follows that KFKW 6.8 be thus, the Wee theorem is proof for a variable force. While the Wee theorem is useful in a variety of problems, it does not, in general, incorporate the complete dynamical information of Newton's second law. It is an integral form of Newton's second law. Newton's second law is the relation between acceleration and force at any instant of time. Work-energy theorem involves an integral over an interval of time. In this sense, the temporal time information contained in the statement of Newton's second law is integrated over and is. Physics 120T not available explicitly. Another observation is that Newton's second law for 2 or 3 dimensions is in vector form, whereas the work-energy theorem is in scalar form. In the scalar form, information with respect to directions contained in Newton's second law is not present. Example 6.6. A block of mass m1 kg, moving on a horizontal surface with speed v2 meters s1 enters a rough patch ranging from x 0.10 meters to x 2.01 meters. The retarding force 4 on the block in this range is inversely proportional to x over this range. FKXR for 0.1, x, 2.01 meters, 0 for x, 0.1 meters and x, 2.01 meters, where k 0.5 joules watt is the final kinetic energy and speed Vf of the block as it crosses this patch. Answer from EC. 6.8 KKKXXFI 0.1 2.01 D2.010.11 LN22 IMVKX1 LN2.010.122 IMVK2 0.5 LN 20.12 1.5 0.5 J1 SM1 to MKVFF here. Note that ln is a symbol for the natural logarithm to the base e and not the logarithm to the base 10 ln x log x 2.303 log 10x. T6.7 The concept of potential energy. The word potential suggests possibility or a capacity for action. The term potential energy brings to one's mind stored energy. A stretched bowstring possesses potential energy. When it is released, the arrow flies off at a great speed. The Earth's crust is not uniform, but has discontinuities and dislocations that are called fault lines. These fault lines in the Earth's crust are like compressed springs. They possess a large amount of potential energy. An earthquake results when these fault lines readjust. Thus, potential energy is the stored energy by virtue of the position or configuration of a body. The body left to itself releases this stored energy in the form of kinetic energy. Let us make our notion of potential energy more concrete. The gravitational force on a ball of mass m is mgg may be treated as a constant near the Earth's surface. By near we imply that the height h of the ball above the Earth's surface is very small compared to the Earth's radius h, so that we can ignore the variation of g near the Earth's surface. In what follows we have taken the upward direction to be positive. Let us raise the ball up to a height h. The work done by the external agency against the gravitational force is mgh. This work gets stored as potential energy. Gravitational potential energy of an object, as a function of the height h, is denoted by Vh, and it is the negative of work done by the gravitational force in raising the object to that height. Vh mgh. If h is taken as a variable, it is easily seen that the gravitational force F equals the negative of the derivative of Vh with respect to h. Thus, ddf Vh mgh. The negative sign indicates that the gravitational force is downward. When released, the ball comes down with an increasing speed. Just before it hits the ground, its speed is given by the kinematic relation. V22gh. This equation can be written as 21 meters V2 mgh, which shows that the gravitational potential energy of the object at height h, when the object is released, manifests itself as kinetic energy of the object on reaching the ground. Physically, the notion of potential energy is applicable only to the class of forces where work done against the force gets stored up as energy. When external constraints are removed, it manifests itself as kinetic energy. Mathematically, for simplicity, in one dimension the potential, the variation of g with height, is discussed in Chapter 8 on gravitation. Work. Energy and power 121. Energy Vx is defined if the force Fx can be written as ddVFxx. This implies that Fxx vvVxx if dd. The work done by a conservative force such as gravity depends on the initial and final positions only. In the previous chapter we have worked on examples dealing with inclined planes. If an object of mass m is released from rest, from the top of a smooth frictionless inclined plane of height h, its speed at the bottom is gh2 irrespective of the angle of inclination. Thus, at the bottom of the inclined plane it acquires a kinetic energy, mgh. If the work done or the kinetic energy did depend on other factors such as the velocity or the particular path taken by the object, the force would be called non-conservative. The dimensions of potential energy are ml2t-2 and the unit is joule J, the same as kinetic energy or work. To reiterate, the change in potential energy, for a conservative force. V is equal to the negative of the work done by the force Vfxx 6.9. In the example of the falling ball considered in this section, we saw how potential energy was converted to kinetic energy. This hints at an important principle of conservation in mechanics, which we now proceed to examine. 6.8 The conservation of mechanical energy. For simplicity, we demonstrate this important principle for one-dimensional motion. Suppose that a body undergoes displacement x under the action of a conservative force F. Then from the V theorem we have Kfxx. If the force is conservative, the potential energy function Vx can be defined such that Vfxx. The above equations imply the kV0 6.10, which means the kV. The sum of the kinetic and potential energies of the body is a constant, over the whole path, xi to xf. This means the kV xi kf Vxf 6.11. The quantity kVx is called the total mechanical energy of the system. Individually, the kinetic energy K and the potential energy Vx may vary from point to point, but the sum is a constant. The aptness of the term conservative force is now clear. Let us consider some of the definitions of a conservative force. La force Fx is conservative if it can be derived from a scalar quantity Vx by the relation given by Ek. 6.9 The three-dimensional generalization requires the use of a vector derivative, which is outside the scope of this book. The work done by the conservative force depends only on the endpoints. This can be seen from the relation Wkf kV xi Vxf, which depends on the endpoints. La third definition states that the work done by this force in a closed path is zero. This is once again apparent from Ek. 6.11 Since xi xf, thus, the principle of conservation of total mechanical energy can be stated as the total mechanical energy of a system is conserved if the forces doing work on it are conservative. The above discussion can be made more concrete by considering the example of the gravitational force once again and that of the spring force in the next section. Figure 6.5 depicts a ball of mass m being dropped from a cliff of height h. Figure 6.5 The conversion of potential energy to kinetic energy for a ball of mass m dropped from height h. Physics 122T The total mechanical energies E0, A, and A of the ball at the indicated height 0 ground level. H and H are AMGH 6.110122 HEMGH MV 6.11 BE012 MVF2 6.11 C. The constant force is a special case of a spatially dependent force Fx. Hence, the mechanical energy is conserved. Thus AE0 or 122 FMGH MV2 FVGH, a result that was obtained in section 3.7 for a freely falling body. Further, AA, which implies VGHHH2 to 6.11 D and is a familiar result from kinematics. At the height h, the energy is purely potential. It is partially converted to kinetic at height h and is fully kinetic at ground level. This illustrates the conservation of mechanical energy. Example 6.7 A bob of mass m is suspended by a light string of length L. It is imparted a horizontal velocity v at the lowest point A such that it completes a semicircular trajectory in the vertical plane, with the string becoming slack only on reaching the topmost point, C. This is shown in figure 6.6. Obtain an expression for IV, 2 the speeds at points B and C, 3 the ratio of the kinetic energies KB Kc at B and C. Comment on the nature of the trajectory of the bob after it reaches the point C. Figure 6.6 Answer I. There are two external forces on the bob, gravity and a tension T in the string. The latter does no work since the displacement of the bob is always normal to the string. The potential energy of the bob is thus associated with the gravitational force only. The total mechanical energy E of the system is conserved. We take the potential energy of the system to be zero at the lowest point A. Thus, at A, EMV0212 6.12 Newton's second law, where TA is the tension in the string at A at the highest point C. The string slackens, as the tension in the string Tc becomes zero. Thus, at C2 MgLMVEC221 6.13 LMVMG2C Newton's second law 6.14, where Vc is the speed at C. From EQS 6.13 and 6.145 EMGL2, equating this to the energy at A 52220 meters MGLV or 50 volt GL2, it is clear from Ek. 6.14 gigaliters Vc at B, the energy is 122 BMVMGL, equating this to the energy at A and employing the result from I. Namely GLV 205, 112222 B0 MVMGL MV 52 meters GL. Work, energy and power 123 gigaliters VB33. The ratio of the kinetic energies at B and C is 1321212 C2 BC BMV MVKK at point C. The string becomes slack and the velocity of the bob is horizontal and to the left. If the connecting string is cut at this instant, the bob will execute a projectile motion with horizontal projection akin to a rock kicked horizontally from the edge of a cliff. Otherwise the bob will continue on its circular path and complete the revolution. T6.9 The potential energy of a spring. The spring force is an example of a variable force which is conservative. Figure 6.7 shows a block attached to a spring and resting on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The spring is light and may be treated as massless. In an ideal spring, the spring force F is proportional to x, where x is the displacement of the block from the equilibrium position. The displacement could be either positive figure 6.7b or negative figure 6.7c. This force law for the spring is called Hooke's law and is mathematically stated as F's kx. The constant k is called the spring constant. Its unit is nm1. The spring is said to be stiff if k is large and soft if k is small. Suppose that we pull the block outwards as in Fig. 6.7b, if the extension is xm. The work done by the spring force is WFXSS0xMDKXX0xMD22MXK 6.15. This expression may also be obtained by considering the area of the triangle as in Fig. 6.7d. Note that the work done by the external pulling force F is positive since it overcomes the spring force. 22MXKW 6.16 Figure 6.7 Illustration of the spring force with a block attached to the free end of the spring. The spring force F is 0 when the displacement x from the equilibrium position is 0b for the stretched spring x, 0 and F's, 0c for the compressed spring x, 0 and F's, 0d. The plot of F's versus x. The area of the shaded triangle represents the work done by the spring force. Due to the opposing signs of F's and x, this work done is negative, WKXSM22. The same is true when the spring is compressed with a displacement xc, 0. The spring force does work 22CSKXW while the Physics 124 Figure 6.8 Parabolic plots of the potential energy V and kinetic energy K of a block attached to a spring obeying Hooke's law. The two plots are complementary, one decreasing as the other increases. The total mechanical energy EKV remains constant. T external force F does work KXC22, if the block is moved from an initial displacement Psi to a final displacement XF. The work done by the spring force W is WKXXKXXXXIFIFD22226.17. Thus the work done by the spring force depends only on the endpoints. Specifically, if the block is pulled from Xi and allowed to return to Xi, WKXXKXXXIIXXIID2222206.18. The work done by the spring force in a cyclic process is 0. We have explicitly demonstrated that the spring force I is position dependent only as first stated by Hooke. F's kx, 2 does work which only depends on the initial and final positions, e.g. x 6.17. Thus, the spring force is a conservative force. We define the potential energy Vx of the spring to be 0 when block and spring system is in the equilibrium position. For an extension or compression X, the above analysis suggests that Vx kx 226.19. You may easily verify that dVdx kx, the spring force. If the block of mass m in figure 6.7 is extended to xm and released from rest, then its total mechanical energy at any arbitrary point x, where x lies between xm and xm, will be given by 222 meters Vmx kx K212121, where we have invoked the conservation of mechanical energy. This suggests that the speed and the kinetic energy will be maximum at the equilibrium position, x0, that is, 2 meters x KVM2121, where Vm is the maximum speed. Or mmxm kV. Note that Km has the dimensions of T2 and our equation is dimensionally correct. The kinetic energy gets converted to potential energy and vice versa. However, the total mechanical energy remains constant. This is graphically depicted in Figure 6.8. Example 6.8. To simulate car accidents, auto manufacturers study the collisions of moving cars with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1,000 kilograms moving with a speed 18.0 km/h on a smooth road and colliding with a horizontally mounted spring of spring constant 6.25 x 103 nm1. What is the maximum compression of the spring? Answer: at maximum compression, the kinetic energy of the car is converted entirely into the potential energy of the spring. The kinetic energy of the moving car is kmv212551013xxxk1.25x104j, where we have converted 18 km/h1 to 5 meters s1. It is useful to remember that 36 km/h1 10 meters s1. At maximum compression xm, the potential energy V of the spring is equal to the kinetic energy K of the moving car from the principle of conservation of mechanical energy. 2mx kv21. Work, energy and power 125 x 104j. We obtain xm 2.00 meters. We note that we have idealized the situation. The spring is considered to be massless. The surface has been considered to possess negligible friction. We conclude this section by making a few remarks on conservative forces. Information on time is absent from the above discussions. In the example considered above, we can calculate the compression, but not the time over which the compression occurs. A solution of Newton's second law for this system is required for temporal information too. Not all forces are conservative. Friction, for example, is a non-conservative force. The principle of conservation of energy will have to be modified in this case. This is illustrated in example 6.9. The zero of the potential energy is arbitrary. It is set according to convenience. For the spring force we took Vx0. At x0, that is the unstretched spring had zero potential energy. For the constant gravitational force mg, we took V0 on the Earth's surface. In a later chapter we shall see that for the force due to the universal law of gravitation, the zero is best defined at an infinite distance from the gravitational source. However, once the zero of the potential energy is fixed in a given discussion, it must be consistently adhered to throughout the discussion. You cannot change forces in midstream. Example 6.9. Consider example 6.8. Taking the coefficient of friction, micro, to be 0.5 and calculate the maximum compression of the spring. Answer: in presence of friction, both the spring force and the frictional force act so as to oppose the compression of the spring as shown in Fig. 6.9. We invoke the work-energy theorem, rather than the conservation of mechanical energy. The change in kinetic energy is Fig. 6.9. The force is acting on the car. KKF key 2 volt M210. The work done by the net force is 122 meters MWKX MGX micro equating we have 1122222 meters MMVKX MGX micro now micro 0.5 x 103 x 10 5 x 103 and taking G 10.0 meters S2. After rearranging the above equation we obtain the following quadratic equation in the unknown xm. 22 meters MKX MGX MV0 micro where we take the positive square root since xm is positive. Putting in numerical values we obtain xm 1.35 meters which, as expected, is less than the result in example 6.8. If the two forces on the body consist of a conservative force Fc and a non-conservative force Fnc, the conservation of mechanical energy formula will have to be modified. By the theorem FCFNCXK but FCXV hence, KVFNCXCFNCX where E is the total mechanical energy. Over the path this assumes the form FEIWNC where WNC is the total work done by the non-conservative forces over the path. Note that Physics 126 unlike the conservative force, WNC depends on the particular path I to FT 6.10 various forms of energy. The law of conservation of energy. In the previous section we have discussed mechanical energy. We have seen that it can be classified into two distinct categories, one based on motion, namely kinetic energy, the other on configuration position, namely potential energy. Energy comes in many forms which transform into one another in ways which may not often be clear to us. 6.10. Heat. We have seen that the frictional force is not a conservative force, however, work is associated with the force of friction. Example 6.5. A block of mass m sliding on a rough horizontal surface with speed v0 comes to a halt over a distance x0. The work done by the force of kinetic friction F over x0 is Fx0, by the work-energy theorem 200 meters v2Fx. If we confine our scope to mechanics, we would say that the kinetic energy of the block is lost due to the frictional force. On examination of the block and the table we would detect a slight increase in their temperatures. The work done by friction is not lost, but is transferred as heat energy. This raises the internal energy of the block and the table. In winter, in order to feel warm, we generate heat by vigorously rubbing our palms together. We shall see later that the internal energy is associated with the ceaseless, often random, motion of molecules. A quantitative idea of the transfer of heat energy is obtained by noting that 1 kilogram of water releases about 42,000 J of energy when it cools by 10 degrees Celsius. 6.10. Chemical energy. One of the greatest technical achievements of humankind occurred when we discovered how to ignite and control fire. We learned to rub two flint stones together, mechanical energy, got them to heat up and to ignite a heap of dry leaves, chemical energy, which then provided sustained warmth. A matchstick ignites into a bright flame when struck against a specially prepared chemical surface. The lighted matchstick, when applied to a firecracker, results in a spectacular display of sound and light. Chemical energy arises from the fact that the molecules participating in the chemical reaction have different binding energies. A stable chemical compound has less energy than the separated parts. A chemical reaction is basically a rearrangement of atoms. If the total energy of the reactants is more than the products of the reaction, heat is released and the reaction is said to be an exothermic reaction. If the reverse is true, heat is absorbed then the reaction is endothermic. Coal consists of carbon and a kilogram of it when burnt releases about 3x107 J of energy. Chemical energy is associated with the forces that give rise to the stability of substances. These forces bind atoms into molecules, molecules into polymeric chains, etc. The chemical energy arising from the combustion of coal, cooking gas, wood and petroleum is indispensable to our daily existence. 6.1.0.3 Electrical energy. The flow of electrical current causes bulbs to glow, fans to rotate and bells to ring. There are laws governing the attraction and repulsion of charges and currents, which we shall learn later. Energy is associated with an electric current. An urban Indian household consumes about 200 J of energy per second on an average. 6.1.0.4 The equivalence of mass and energy. Till the end of the 19th century, physicists believed that in every physical and chemical process, the mass of an isolated system is conserved. Matter might change its phase, e.g. glacial ice could melt into a gushing stream, but matter is neither created nor destroyed. Albert Einstein 1879–1955 however, showed that mass and energy are equivalent and are related by the relation EMC 26.20 where c, the speed of light in vacuum is approximately 3x108 meters s1. Thus, a staggering amount of energy is associated with a mere kilogram of matter E1x 3x108 2j 9x 1016 J. This is equivalent to the annual electrical output of a large 3000 megawatts power generating station. 6.1.0.5 Nuclear energy. The most destructive weapons made by man, the fission and fusion bombs are manifestations of work, energy and power. 127 The above equivalence of mass and energy x 6.20. On the other hand, the explanation of the life-nourishing energy output of the sun is also based on the above equation. In this case effectively 4 light hydrogen nuclei fuse to form a helium nucleus whose mass is less than the sum of the masses of the reactants. This mass difference, called the mass defect M, is the source of energy Mc2. In fission, a heavy nucleus like uranium U-23592 is split by a neutron into lighter nuclei. Once again the final mass is less than the initial mass and the mass difference translates into energy, which can be tapped to provide electrical energy as in nuclear power plants, controlled nuclear fission, or can be employed in making nuclear weapons, uncontrolled nuclear fission. Strictly, the energy E released in a chemical reaction can also be related to the mass defect MEC2. However, for a chemical reaction, this mass defect is much smaller than for a nuclear reaction. Table 6.3 lists the total energies for a variety of events and phenomena. Table 6.3 Approximate energy associated with various phenomena. Example 6.10 Examine Table 6.16.3 and express the energy required to break one bond in DNA and EV. B. The kinetic energy of an air molecule 1021 J in EV. C. The daily intake of a human adult in kilocalories. Answer. Energy required to break one bond of DNA is 2019 10 J 0.06 eV 1.6 10 J eV X note 0.1 eV 100 MeV 100 mV. B. The kinetic energy of an air molecule is 2119 10 J 0.0062 eV 1.6 10 J eV X. This is the same as 6.2 MeV. C. The average human consumption in a day is 73 10 J 2400 kcal 4.2 x 10 J kcal T. Physics 128 We point out a common misconception created by newspapers and magazines. They mention food values and calories and are just to restrict diet intake to below 2400 calories. What they should be saying is kilocalories kcal and not calories. A person consuming 2400 calories a day will soon starve to death. 1 food calorie is 1 kcal. T6.10.6 The principle of conservation of energy. We have seen that the total mechanical energy of the system is conserved if the forces doing work on it are conservative. If some of the forces involved are non-conservative, part of the mechanical energy may get transformed into other forms such as heat, light and sound. However, the total energy of an isolated system does not change, as long as one accounts for all forms of energy. Energy may be transformed from one form to another, but the total energy of an isolated system remains constant. Energy can neither be created, nor destroyed. Since the universe as a whole may be viewed as an isolated system, the total energy of the universe is constant. If one part of the universe loses energy, another part must gain an equal amount of energy. The principle of conservation of energy cannot be proved. However, no violation of this principle has been observed. The concept of conservation and transformation of energy into various forms links together various branches of physics, chemistry and life sciences. It provides a unifying, enduring element in our scientific pursuits. From engineering point of view, all electronic, communication and mechanical devices rely on some forms of energy transformation. 6.11 Power off. And it is interesting to know not only the work done on an object, but also the rate at which this work is done. We say a person is physically fit if he not only climbs 4 floors of a building but climbs them fast. Power is defined as the time rate at which work is done or energy is transferred. The average power of a force is defined as the ratio of the work W to the total time t taken. PWT. The instantaneous power is defined as the limiting value of the average power as time interval approaches 0. DDWPT 6.21 The work dW done by a force F for a displacement dr is dWF. The instantaneous power can also be expressed as ddPTF RFV 6.22 where V is the instantaneous velocity when the force is F power. Like work and energy, is a scalar quantity, its dimensions are ml2t3, in the SI, its unit is called a watt W. The watt is 1 JS1, the unit of power is named after James Watt, one of the innovators of the steam engine in the 18th century. There is another unit of power, namely the horsepower HP1 HP746W. This unit is still used to describe the output of automobiles, motorbikes, etc. We encounter the unit watt when we buy electrical goods such as bulbs, heaters and refrigerators. A 100-watt bulb which is on for 10 hours uses 1 kWh kWh of energy. 100 watt x 10 hours 1000 Wh 1 kWh kWh 103 W x 3600 s 3.6 x 106 J. Our electricity bills carry the energy consumption in units of kWh. Note that kWh is a unit of energy and not of power. Example 6.11 An elevator can carry a maximum load of 1,800 kilograms. Elevator passengers is moving up with a constant speed of 2 meters s1. The frictional force opposing the motion is 4,000 N. Determine the minimum power delivered by the motor to the elevator in watts as well as in horsepower. U. Work, energy and power. 129 Answer. The downward force on the elevator is FmgFF 1800 x 10 4000 22,000 N. The motor must supply enough power to balance this force. Hence, PFV 22,000 x 2 44,000 W 59 HPT 6.12 Collisions. In physics we study motion change in position. At the same time, we try to discover physical quantities, which do not change in a physical process. The laws of momentum and energy conservation are typical examples. In this section we shall apply these laws to a commonly encountered phenomena, namely collisions. Several games such as billiards, marbles or carom involve collisions. We shall study the collision of two masses in an idealized form. Consider two masses m1 and m2. The particle m1 is moving with speed v1I, the subscript I implying initial. We can consider m2 to be at rest. No loss of generality is involved in making such a selection. In this situation the mass m1 collides with the stationary mass m2 and this is depicted in Fig. 6.10. Figure 6.10 Collision of mass m1, with a stationary mass m2. The masses m1 and m2 fly off in different directions. We shall see that there are relationships, which connect the masses, the velocities and the angles. 6. 1, 2, 1 Elastic and inelastic collisions. In all collisions the total linear momentum is conserved. The initial momentum of the system is equal to the final momentum of the system. One can argue this as follows. When two objects collide, the mutual impulsive forces acting over the collision time t cause a change in their respective momenta. Page 1 F12t, page 2 F21t, where F12 is the force exerted on the first particle by the second particle. F21 is likewise the force exerted on the second particle by the first particle. Now from Newton's third law, F12 F21. This implies page 1 page 20 the above conclusion is true even though the forces vary in a complex fashion during the collision time t. Since the third law is true at every instant, the total impulse on the first object is equal and opposite to that on the second. On the other hand, the total kinetic energy of the system is not necessarily conserved. The impact and deformation during collision may generate heat and sound. Part of the initial kinetic energy is transformed into other forms of energy. A useful way to visualize the deformation during collision is in terms of a compressed spring. If the spring connecting the two masses regains its original shape without loss in energy, then the initial kinetic energy is equal to the final kinetic energy, but the kinetic energy during the collision time t is not constant. Such a collision is called an elastic collision. On the other hand, the deformation may not be relieved and the two bodies could move together after the collision. A collision in which the two particles move together after the collision is called a completely inelastic collision. The intermediate case where the deformation is partly relieved and some of the initial kinetic energy is lost is more common and is appropriately called an inelastic collision. 6. 1, 2. Two collisions in one dimension. Consider first a completely inelastic collision in one dimension. Then, in figure 6.10, Greek letter theta 1 Greek letter theta 2 0 m1 v1 im1 m2 vf Momentum conservation 1112 fimv mm 6.23 The loss in kinetic energy on collision is 22112112221 ifkm vmm v2 22111121122 iimm vvmm using EC 6.231 to 11121112 meters vmm me T21211212 IMM VMM which is a positive quantity as expected. Consider next inelastic collision. Using the above nomenclature with Greek letter theta 1 Greek letter theta 2 0, the momentum and kinetic energy conservation equations are m1 v1 im1 v1 fm2 v2 f 6.24222211122 if fm vm vm v 6.25 from EQS 6.24 and 6.25 it follows that 1121121 IFIFFFMVVVMVVV or 2221111 FIFIFVVVV1111 IFIFVVVV hence 211 FIFVVV 6.26 substituting this in EC 6.24, we obtain 1211112 FIMM 6.27 and 112122 IFM 6.28 thus. The unknowns V1F, V2F are obtained in terms of the knowns M1, M2, V1I. Special cases of our analysis are interesting. Case I, if the two masses are equal V1F0 V2F V1I the first mass comes to rest and pushes off the second mass with its initial speed on collision. Case 2, if one mass dominates, e.g. M2, M1 V1F V1I V2F0 the heavier mass is undisturbed while the lighter mass reverses its velocity. Example 6.12 Slowing down of neutrons. In a nuclear reactor a neutron of high speed typically 107 meters s1 must be slowed an experiment on head-on collision. In performing an experiment on collision on a horizontal surface, we face three difficulties. 1. There will be friction and bodies will not travel with uniform velocities. 2. If two bodies of different sizes collide on a table, it would be difficult to arrange them for a head-on collision unless their centers of mass are at the same height above the surface. 3. It will be fairly difficult to measure velocities of the two bodies just before and just after collision. By performing this experiment in a vertical direction, all the three difficulties vanish. Take two balls, one of which is heavier basketball, football, volleyball and the other lighter tennis ball, rubber ball, table tennis ball. First take only the heavier ball and drop it vertically from some height, say 1 meters, note to which it rises. This gives the velocities near the floor or ground, just before and just after the bounce by using 2 GH. Hence you will get the coefficient of restitution. Now take the big ball and a small ball and hold them in your hands one over the other, with the heavier ball below the lighter one, as shown here. Drop them together, taking care that they remain together while falling, and see what happens. You will find that the heavier ball rises less than when it was dropped alone, while the lighter one shoots up to about 3 meters. With practice, you will be able to hold the ball properly so that the lighter ball rises vertically up and does not fly sideways. This is head-on collision. You can try to find the best combination of balls which gives you the best effect. You can measure the masses on a standard balance. We leave it to you to think how you can determine the initial and final velocities of the balls. Work, energy and power 131 T to 103 meters S1 so that it can have a high probability of interacting with isotope 92-235U and causing it to fission. Show that a neutron can lose most of its kinetic energy in an elastic collision with a light nuclei like deuterium or carbon which has a mass of only a few times the neutron mass. The material making up the light nuclei, usually heavy water D2O or graphite, is called a moderator. Answer: the initial kinetic energy of the neutron is 2111112 IKMV while its final kinetic energy from EC 6.27 kmVMMMMVFFI111211212121 to the fractional kinetic energy lost as FKKMMMFI1111121222 while the fractional kinetic energy gained by the moderating nuclei K2FK1I is F2, 1F1 elastic collision 122124 meters mm. One can also verify this result by substituting from EC 6.28 for deuterium M2 to M1 and we obtain F119 while F289, almost 90 of the neutron's energy is transferred to deuterium. For carbon F171.6 and F228.4. In practice, however, this number is smaller since head-on collisions are rare. If the initial velocities and final velocities of both the bodies are along the same straight line, then it is called a one-dimensional collision, or head-on collision. In the case of small spherical bodies, this is possible if the direction of travel of body 1 passes through the center of body 2 which is at rest. In general, the collision is two-dimensional, where the initial velocities and the final velocities lie in a plane. 6, 1, 2, 3 collisions in 2 dimensions. Figure 6.10 also depicts the collision of a moving mass m1 with a stationary mass m2. Linear momentum is conserved in such a collision. Since momentum is a vector, this implies 3 equations for the 3 directions x, y, z. Consider the plane determined by the final velocity directions of m1 and m2 and choose it to be the xy plane. The conservation of the z component of the linear momentum implies that the entire collision is in the xy plane. The x and y component equations are m1 v1 I m1 v1 f cos Greek letter theta 1 m2 v2 f cos Greek letter theta 2 6.290 m1 v1 f sin Greek letter theta 1 m2 v2 f sin Greek letter theta 2 6.301 knows m1, m2, v1 I in most situations. There are thus 4 unknowns v1f, v2f, Greek letter theta 1 and Greek letter theta 2, and only 2 equations. If Greek letter theta 1 Greek letter theta 2 0, we regain ac. 6.24 for one-dimensional collision. If, further, the collision is elastic, 222111122111222 IFFMVMVMV 6.31, we obtain an additional equation. That still leaves us 1 equation short. At least one of the 4 unknowns, say Greek letter theta 1, must be made known for the problem to be solvable. For example, Greek letter theta 1 can be determined by moving a detector in an angular fashion from the x to the y-axis. Given m1, m2, v1I, Greek letter theta 1, we can determine v1f, v2f, Greek letter theta 2 from EQS 6.29 6.31. Example 6.13. Consider the collision depicted in Fig. 6.10 to be between 2 billiard balls with equal masses m1 m2. The first ball is called the cue while the second ball is called the target. The billiard player wants to sink the target ball in a corner pocket, which is at an angle Greek letter theta 237 degrees. Assume that the collision is elastic and that friction and rotational motion are not important. Obtain Greek letter theta 1. Answer from momentum conservation. Since the masses are equal to F1 F1 IVVV or 2121 21 IVVVV FFFF 22121 22.FFFF Physics 132 2212121 cos 37 FFFF VVVV Greek letter theta degrees 6.32. Since the collision is elastic and m1 m2, it follows from conservation of kinetic energy that 222112 IFF VVV 6.33. Comparing EQS 6.32 and 6.33, we get cos Greek letter theta 137 degrees 0 or Greek letter theta 137 degrees 90 degrees. Thus, Greek letter theta 153 degrees. This proves the following result: when 2 equal masses undergo a glancing elastic collision with one of them at rest, after the collision, they will move at right angles to each other. The matter simplifies greatly if we consider spherical masses with smooth surfaces, and assume that collision takes place only when the bodies touch each other. This is what happens in the games of marbles, carom and billiards. In our everyday world, collisions take place only when 2 bodies touch each other. But consider a comet coming from far distances to the Sun, or alpha particle coming towards a nucleus and going away in some direction. Here we have to deal with forces involving action at a distance. Such an event is called scattering. The velocities and directions in which the 2 particles go away depend on their initial velocities as well as the type of interaction between them, their masses, shapes and sizes. Summary 1. The work energy theorem states that the change in kinetic energy of a body is the work done by the net force on the body. KF net 2. A force is conservative if I work done by it on an object is path independent and depends only on the endpoint xi. Xj, or 2. The work done by the force is 0 for an arbitrary closed path taken by the object such that it returns to its initial position. 3. For a conservative force in one dimension, we may define a potential energy function Vx such that Fx Vxxd or Vvfx Ifxx Ifd4. The principle of conservation of mechanical energy states that the total mechanical energy of a body remains constant if the only forces that act on the body are conservative. 5. The gravitational potential energy of a particle of mass m at a height x about the Earth's surface is the xmgx, where the variation of g with height is ignored. 6. The elastic potential energy of a spring of force constant k and extension x is the xkx1227. The scalar or dot product of 2 vectors a and b is written as ab and is a scalar quantity given by ab cos Greek letter theta. Where Greek letter theta is the angle between a and b, it can be positive, negative or 0 depending upon the value of Greek letter theta. The scalar product of 2 vectors can be interpreted as the product of magnitude of one vector and component of the other vector along the first vector. For unit vectors, iijjkk1 and ijjkki0, scalar products obey the commutative and the distributive laws. Work, energy and power 133 points to ponder 1. The phrase calculate the work done is incomplete. We should refer or imply clearly by context to the work done by a specific force or a group of forces on a given body over a certain displacement. 2. Work done is a scalar quantity. It can be positive or negative, unlike mass and kinetic energy, which are positive scalar quantities. The work done by the friction or viscous force on a moving body is negative 3. For two bodies, the sum of the mutual forces exerted between them is 0 from Newton's third law, F12 F21 0, but the sum of the work done by the two forces need not always cancel, that is, W12 W21 is not equal to 0. However, it may sometimes be true for the work done by a force can be calculated sometimes even if the exact nature of the force is not known. This is clear from example 6.2 where the Wee theorem is used in such a situation. 5. The Wee theorem is not independent of Newton's second law. The Wee theorem may be viewed as a scalar form of the second law. The principle of conservation of mechanical energy may be viewed as a consequence of the Wee theorem for conservative forces. 6. The Wee theorem holds in all inertial frames. It can also be extended to non-inertial frames provided we include the pseudo-forces in the calculation of the net force acting on the body under consideration. 7. The potential energy of a body subjected to a conservative force is always undetermined up to a constant. For example, the point where the potential energy is 0 is a matter of choice. For the gravitational potential energy mgh, the 0 of the potential energy is chosen to be the ground. For the spring potential energy kx22, the 0 of the potential energy is the equilibrium position of the oscillating mass. 8. Every force encountered in mechanics does not have an associated potential energy. For example, work done by friction over a closed path is not 0 and no potential energy can be associated with friction. 9. During a collision, the total linear momentum is conserved at each instant of the collision. B. The kinetic energy conservation even if the collision is elastic applies after the collision is over and does not hold at every instant of the collision. In fact, the two colliding objects are deformed and may be momentarily at rest with respect to each other. Physics 134 Exercises 6.1 The sign of work done by a force on a body is important to understand. State carefully if the following quantities are positive or negative. A work done by a man in lifting a bucket out of a well by means of a rope tied to the bucket. B. Work done by gravitational force in the above case. C. Work done by friction on a body sliding down an inclined plane. D. Work done by an applied force on a body moving on a rough horizontal plane with uniform velocity. E. Work done by the resistive force of air on a vibrating pendulum and bringing it to rest. 6.2 A body of mass 2 kg initially at rest moves under the action of an applied horizontal force of 7 N on a table with coefficient of kinetic friction 0.1. Compute the A. Work done by the applied force in 10 S. B. Work done by friction in 10 S. C. Work done by the net force on the body in 10 S. D. Change in kinetic energy of the body in 10 S. And interpret your results. 6.3 Given in figure 6.11 are examples of some potential energy functions in one dimension. The total energy of the particle is indicated by a cross on the ordinate axis. In each case, specify the regions, if any, in which the particle cannot be found for the given energy. Also, indicate the minimum total energy the particle must have in each case. Think of simple physical contexts for which these potential energy shapes are relevant. Figure 6.11. Work, energy and power 135 6.4 The potential energy function for a particle executing linear simple harmonic motion is given by Vx kx22, where k is the force constant of the oscillator. For k 0.5 nm1, the graph of Vx versus x is shown in figure 6.12. Show that a particle of total energy 1j moving under this potential must turn back when it reaches x plus or minus 2 meters. 6.5 Answer the following. The casing of the rocket in flight burns up due to friction. At whose expense is the heat energy required for burning obtained? The rocket or the atmosphere? B. Comets move around the sun in highly elliptical orbits. The gravitational force on the comet due to the sun is not normal to the comet's velocity in general. Yet the work done by the gravitational force over every complete orbit of the comet is 0. Why? See an artificial satellite orbiting the Earth in very thin atmosphere loses its energy gradually due to dissipation against atmospheric resistance, however small. Why then does its speed increase progressively as it comes closer and closer to the Earth? D in Fig. 6.13 I. The man walks 2 meters carrying a mass of 15 kilograms on his hands. In figure 6.13.2, he walks the same distance pulling the rope behind him. The rope goes over a pulley, and a mass of 15 kilograms hangs at its other end. In which case is the work done greater? 6.6 Underline the correct alternative. O. When a conservative force does positive work on a body, the potential energy of a body increases, decreases, remains unaltered. B. Work done by a body against friction always results in a loss of its kinetic potential energy. See, the rate of change of total momentum of a many-particle system is proportional to the external force sum of the internal forces on the system. D. In an inelastic collision of two bodies, the quantities which do not change after the collision are the total kinetic energy, total linear momentum, total energy of the system of two bodies. 6.7 State if each of the following statements is true or false. Give reasons for your answer. In an elastic collision of two bodies, the momentum and energy of each body is conserved. B. Total energy of a system is always conserved, no matter what internal and external forces on the body are present. C. Work done in the motion of a body over a closed loop is zero for every force in nature. D. In an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. 6.8 Answer carefully, with reasons. In an elastic collision of two billiard balls, is the total kinetic energy conserved during the short time of collision of the balls, that is, when they are in contact. B. Is the total linear momentum conserved during the short time of an elastic collision of two balls. Fig. 6.13 Figure 6.12. Physics 136 C. What are the answers to A and B for an inelastic collision? D. If the potential energy of two billiard balls depends only on the separation distance between their centers, is the collision elastic or inelastic? Note, we are talking here of potential energy corresponding to the force during collision, not gravitational potential energy. 6.9 A body is initially at rest. It undergoes one-dimensional motion with constant acceleration. The power delivered to it at time t is proportional to it12 to t3 t3 to it2 6.10 A body is moving unidirectionally under the influence of a source of constant power. Its displacement in time t is proportional to it12 to t3 t3 to it2 6.11 A body constrained to move along the z-axis of a coordinate system is subject to a constant force F given by n32 kjif, where k, j, I are unit vectors along the x, y and z axis of the system respectively. What is the work done by this force in moving the body a distance of 4 meters along the z-axis? 6.12 An electron and a proton are detected in a cosmic ray experiment. The first with kinetic energy 10 keV, and the second with 100 keV. Which is faster, the electron or the proton? Obtain the ratio of their speeds. Electron mass 9.11 x 1031 kilograms, proton mass 1.67 x 10-27 kg, 1/2 1.60 x 10-19 J. 6.13 A raindrop of radius 2 mm falls from a height of 500 meters above the ground. It falls with decreasing acceleration due to viscous resistance of the air until at half its original height. It attains its maximum terminal speed, and moves with uniform speed thereafter. What is the work done by the gravitational force on the drop in the first and second half of its journey? What is the work done by the resistive force in the entire journey if its speed on reaching the ground is 10 meters s1? 6.14 A molecule in a gas container hits a horizontal wall with speed 200 meters s1 and angle 30 degrees with the normal, and rebounds with the same speed. Is momentum conserved in the collision? Is the collision elastic or inelastic? 6.15 A pump on the ground floor of a building can pump up water to fill a tank of volume 30 cubic meters in 15 minutes. If the tank is 40 meters above the ground, and the efficiency of the pump is 30, how much electric power is consumed by the pump? 6.16 Two identical ball bearings in contact with each other and resting on a frictionless table are hit head-on by another ball bearing of the same mass moving initially with a speed v. If the collision is elastic, which of the following? Figure 6.14 is a possible result after collision? Fig. 6.14. Work, energy and power 137. 6.17 The bob A of a pendulum released from 30 to the vertical hits another bob B of the same mass at rest on a table as shown in Fig. 6.15 How high does the bob A rise after the collision? Neglect the size of the bobs and assume the collision to be elastic. 6.18 The bob of a pendulum is released from a horizontal position, if the length of the pendulum is 1.5 meters. What is the speed with which the bob arrives at the lowermost point, given that it dissipated 5 of its initial energy against air resistance? 6.19 A trolley of mass 300 kilograms carrying a sandbag of 25 kilograms is moving uniformly with a speed of 27 kilometers h on a frictionless track. After a while, sand starts leaking out of a hole on the floor of the trolley at the rate of 0.05 kilograms s1. What is the speed of the trolley after the entire sandbag is empty? 6.20 A body of mass 0.5 kilograms travels in a straight line with velocity v x32 where a 5m12 s1. What is the work done by the net force during its displacement from x0 to x2 meters? 6.21 The blades of a windmill sweep out a circle of area A if the wind flows at a velocity v perpendicular to the circle. What is the mass of the air passing through it in time tb? What is the kinetic energy of the air? C. Assume that the windmill converts 25 of the wind's energy into electrical energy. and that A30 square meters, V 36 kilometers H, and the density of air is 1.2 kilograms M3. What is the electrical power produced? 6.22. A person trying to lose weight either lifts a 10 kilogram mass, 1,000 times, to a height of 0.5 meters each time. Assume that the potential energy lost each time she lowers the mass is dissipated, and how much work does she do against the gravitational force? B. That supplies 3.8 x 107 J of energy per kilogram, which is converted to mechanical energy with a 20 efficiency rate. How much fat will the Dieter use up? 6.23. A family uses 8 kilowatts of power. A direct solar energy is incident on the horizontal surface at an average rate of 200 W per square meter. If 20 of this energy can be converted to useful electrical energy, how large an area is needed to supply 8 kilowatts? B. Compare this area to that of the roof of a typical house. Additional exercises. 6.24. A bullet of mass 0.012 kilograms and horizontal speed 70 meters S1 strikes a block of wood of mass 0.4 kilograms and instantly comes to rest with respect to the block. The block is suspended from the ceiling by means of thin wires. Calculate the height to which the block rises. Also, estimate the amount of heat produced in the block. 6.25. Two inclined frictionless tracks, one gradual and the other steep, meet at A from where two stones are allowed to slide down from rest, one on each track. Fig. 6.16. Will the stones reach the bottom at the same time? Will they reach there with the same speed? Explain. Given Greek letter theta 1 300, Greek letter theta 2 600, and h 10 meters, what are the speeds and times taken by the two stones? Fig. 6.16. Figure 6.15. Physics 138. 6.26. A 1 kilogram block situated on a rough incline is connected to a spring of spring constant 100 Nm1 as shown in Fig. 6.17. The block is released from rest with the spring in the unstretched position. The block moves 10 centimeters down the incline before coming to rest. Find the coefficient of friction between the block and the incline. Assume that the spring has a negligible mass and the pulley is frictionless. Figure 6.17. 6.27. A bolt of mass 0.3 kilograms falls from the ceiling of an elevator moving down with an uniform speed of 7 meters S1. It hits the floor of the elevator length of the elevator 3 meters and does not rebound. What is the heat produced by the impact? Would your answer be different if the elevator were stationary? 6.28. A trolley of mass 200 kilograms moves with a uniform speed of 36 kilometers h on a frictionless track. A child of mass 20 kilograms runs on the trolley from one end to the other 10 meters away with a speed of 4 meters S1 relative to the trolley in a direction opposite to its motion, and jumps out of the trolley. What is the final speed of the trolley? How much has the trolley moved from the time the child begins to run? 6.29. Which of the following potential energy curves in Fig. 6.18 cannot possibly describe the elastic collision of two billiard balls? Here R is the distance between centers of the balls. Figure 6.18. 6.30 Consider the decay of a free neutron at rest, and GPE. Work, energy and power. 139 show that the two-body decay of this type must necessarily give an electron of fixed energy n. Therefore, cannot account for the observed continuous energy distribution in the Greek letter beta decay of a neutron or a nucleus. Fig. 6.19. Figure 6.19 note, the simple result of this exercise was one among the several arguments advanced by W. Pauli to predict the existence of a third particle and the decay products of Greek letter beta decay. This particle is known as neutrino. We now know that it is a particle of intrinsic spin 1/2 like E, P or N, but is neutral, and either massless or having an extremely small mass compared to the mass of electron, and which interacts very weakly with matter. The correct decay process of neutron is, and GPE Greek letter nu 2018 1. Physics 140 Appendix 6.1, Power consumption in walking. The table below lists the approximate power expended by an adult human of mass 60 kilograms. Table 6. For approximate power consumption, mechanical work must not be confused with the everyday usage of the term work. A woman standing with a very heavy load on her head may get very tired, but no mechanical work is involved. That is not to say that mechanical work cannot be estimated in ordinary human activity. Consider a person walking with constant speed v0. The mechanical work he does may be estimated simply with the help of the work-energy theorem. Assume the major work done in walking is due to the acceleration and deceleration of the legs with each stride. See Fig. 6.20. B. Neglect air resistance. C. Neglect the small work done in lifting the legs against gravity. D. Neglect the swinging of hands etc. as is common in walking. As we can see in Figure 6.20, in each stride the leg is brought from rest to a speed, approximately equal to the speed of walking, and then brought to rest again. Figure 6.20, an illustration of a single stride in walking. While the first leg is maximally off the ground, the second leg is on the ground and vice versa. The work done by one leg in each stride is 20 liters Vm by the work energy theorem. Here ml is the mass of the leg. Note 220 liters Vm energy is expended by one set of leg muscles to bring the foot from rest to speed V0, while an additional 220 liters Vm is expended by a complementary set of leg muscles to bring the foot to rest from speed V0. Hence work done by both legs in one stride is study figure 6.20 carefully. 20 liters SVMW to 6.34 assuming ml 10 kilograms and slow running of a 9-minute mile, which translates to 3 meters S1 in SI units. We obtain W's 180 J stride. If we take a stride to be 2 meters long, the person covers 1.5 strides per second at his speed of 3 meters S1. Thus the power expended 270 W. We must bear in mind that this is a lower estimate and several avenues of power loss, e.g. swinging of hands, air resistance, etc. have been ignored. The interesting point is that we did not worry about the forces involved. The forces, mainly friction and those exerted on the leg by the muscles of the rest of the body, are hard to estimate. Static friction does no work, and we bypass the impossible task of estimating the work done by the muscles by taking recourse to the work energy theorem. We can also see the advantage of a wheel. The wheel permits smooth locomotion without the continuous starting and stopping in mammalian locomotion. Chapter 7, Systems of Particles and Rotational Motion. 7.1 Introduction. In the earlier chapters we primarily considered the motion of a single particle. A particle is ideally represented as a point mass having no size. We applied the results of our study even to the motion of bodies of finite size. Assuming that motion of such bodies can be described in terms of the motion of a particle, any real body which we encounter in daily life has a finite size. In dealing with the motion of extended bodies of finite size, often the idealized model of a particle is inadequate. In this chapter we shall try to go beyond this inadequacy. We shall attempt to build an understanding of the motion of extended bodies. An extended body, in the first place, is a system of particles. We shall begin with the consideration of motion of the system as a whole. The center of mass of a system of particles will be a key concept here. We shall discuss the motion of the center of mass of a system of particles and usefulness of this concept in understanding the motion of extended bodies. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with a perfectly definite and unchanging shape. The distances between all pairs of particles of such a body do not change. It is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of forces. But in many situations the deformations are negligible. In a number of situations involving bodies such as wheels, tops, steel beams, molecules and planets on the other hand, we can ignore that they warp, twist out of shape, bend or vibrate and treat them as rigid. 7.1. What kind of motion can a rigid body have? Let us try to explore this question by taking some examples of the motion of rigid bodies. Let us begin with the rectangular. 7.1 Introduction. 7.2 Center of mass. 7.3 Motion of center of mass. 7.4 Linear momentum of a system of particles. 7.5 Vector product of two vectors. 7.6 Angular velocity and its relation with linear velocity. 7.7 Torque and angular momentum. 7.8 Equilibrium of a rigid body. 7.9 Moment of inertia. 7.10 Theorems of perpendicular and parallel axes. 7.11 Kinematics of rotational motion about a fixed axis. 7.12 Dynamics of rotational motion about a fixed axis. 7.13 Angular momentum in case of rotation about a fixed axis. 7.14 Rolling motion. Summary points to ponder. Exercises. Additional exercises. 142 Physics block. Sliding down an inclined plane without any sidewise movement. The block is taken as a rigid body. Its motion down the plane is such that all the particles of the body are moving together, that is, they have the same velocity at any instant of time. The rigid body here is in pure translational motion. Figure 7.1. In pure translational motion at any instant of time, all particles of the body have the same velocity. Consider now the rolling motion of a solid metallic or wooden cylinder down the same inclined plane. Fig. 7.2. The rigid body in this problem, namely the cylinder, shifts from the top to the bottom of the inclined plane, and thus, seems to have translational motion. But as figure 7.2 shows, all its particles are not moving with the same velocity at any instant. The body, therefore, is not in pure translational motion. Its motion is translational plus something else. In order to understand what this something else is, let us take a rigid body so constrained that it cannot have translational motion. The most common way to constrain a rigid body so that it does not have translational motion is to fix it along a straight line. The only possible motion of such a rigid body is rotation. The line or fixed axis about which the body is rotating is its axis of rotation. If you look around, you will come across many examples of rotation about an axis: a ceiling fan, a potter's wheel, a giant wheel in a fair, a merry-go-round, and so on. Figure 7.3a and b. A b. Figure 7.3 rotation about a fixed axis. A ceiling fan. B. A potter's wheel. Let us try to understand what rotation is. What characterizes rotation? You may notice that in rotation of a rigid body about a fixed axis, figure 7.1, translational sliding motion of a block down an inclined plane. Any point like P1 or P2 of the block moves with the same velocity at any instant of time. Fig. 7.2, rolling motion of a cylinder. It is not pure translational motion. Points P1, P2, P3 and P4 have different velocities shown by arrows at any instant of time. In fact, the velocity of the point of contact P3 is 0 at any instant, if the cylinder rolls without slipping. Systems of particles and rotational motion. 143. Every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. Figure 7.4 shows the rotational motion of a rigid body about a fixed axis, the z-axis of the frame of reference. Let P1 be a particle of the rigid body, arbitrarily chosen and at a distance r1 from fixed axis. The particle P1 describes a circle of radius r1 with its center c1 on the fixed axis. The circle lies in a plane perpendicular to the axis. The figure also shows another particle P2 of the rigid body. P2 is at a distance r2 from the fixed axis. The particle P2 moves in a circle of radius r2 and with center c2 on the axis. This circle, 2, lies in a plane perpendicular to the axis. Note that the circles described by P1 and P2 lie in different planes. Both these planes, however, are perpendicular to the fixed axis. For any particle on the axis like P3, R0, any such particle remains stationary while the body rotates. This is expected since the axis of rotation is fixed. Figure 7.5. A spinning top. The point of contact of the top with the ground, its tip O, is fixed. Fig. 7.5b. An oscillating table fan with rotating blades. The pivot of the fan, point O, is fixed. The blades of the fan are under rotational motion, whereas the axis of rotation of the fan blades is oscillating. Figure 7.4. A rigid body rotation about the z-axis. Each point of the body such as P1 or P2 describes a circle with its center C1 or C2 on the axis of rotation. The radius of the circle R1 or R2 is the perpendicular distance of the point P1 or P2 from the axis. A point on the axis like P3 remains stationary. Axis of oscillation. Axis of rotation from blades. In some examples of rotation, however, the axis may not be fixed. A prominent example of this kind of rotation is a top spinning in place. Figure 7.5a. We assume that the top does not slip from place to place and so does not have translational motion. We know from experience that the axis of such a spinning top moves around the vertical through its point of contact with the ground, sweeping out a cone as shown in Fig. 7.5a. This movement of the axis of the top around the vertical is termed precession. Note, the point of contact of the top with ground is fixed. The axis of rotation of the top at any instant passes through the point of contact. Another simple example of this kind of rotation is the oscillating table fan or a pedestal fan. Figure 7.5b. You may have observed that the 144 physics axis of rotation of such a fan has an oscillating sidewise movement in a horizontal plane about the vertical through the point at which the axis is pivoted. Point O in Fig. 7.5b. While the fan rotates and its axis moves sidewise, this point is fixed. Thus, in more general cases of rotation, such as the rotation of a top or a pedestal fan, one point and not one line of the rigid body is fixed. In this case the axis is not fixed, though it always passes through the fixed point. In our study, however, we mostly deal with the simpler and special case of rotation in which one line it is. The axis is fixed. Thus, for us rotation will be about a fixed axis only unless stated otherwise. The rolling motion of a cylinder down an inclined plane is a combination of rotation about a fixed axis and translation. Thus, the something else in the case of rolling motion which we referred to earlier as rotational motion. You will find figure 7.6a and b instructive from this point of view. Both these figures show motion of the same body along identical translational trajectory. In one case, figure 7.6a, the motion is a pure translation. In the other case, figure 7.6b, it is a combination of translation and rotation. You may try to reproduce the two types of motion shown. Using a rigid object like a heavy book, we now recapitulate the most important observations of the present section. The motion of a rigid body which is not pivoted or fixed in some way is either a pure translation or a combination of translation and rotation. The motion of a rigid body which is pivoted or fixed in some way is rotation. The rotation may be about an axis that is fixed, e.g. a ceiling fan or moving, e.g. an oscillating table fan. Figure 7.5b. We shall, in the present chapter, consider rotational motion about a fixed axis only. 7.2 Center of mass. We shall first see what the center of mass of a system of particles is and then discuss its significance. For simplicity we shall start with a two-particle system. We shall take the line joining the two particles to be the x-axis. Figure 7.7 Let the distances of the two particles be x1 and x2 respectively from some origin O. Let m1 and m2 be respectively the masses of the two. Fig. 7.6 A motion of a rigid body which is pure translation. Figure 7.6b Motion of a rigid body which is a combination of translation and rotation. Figure 7.6a and 7.6b illustrate different motions of the same body. Note P is an arbitrary point of the body, O is the center of mass of the body, which is defined in the next section. Suffice to say here that the trajectories of O are the translational trajectories tr1 and tr2 of the body. The positions O and P at three different instants of time are shown by O1, O2, and O3, and P1, P2 and P3, respectively, in both figs. 7.6a and b. As seen from figure 7.6a, at any instant the velocities of any particles like O and P of a body are the same in pure translation. Notice, in this case the orientation of OP, that is the angle OP makes with a fixed direction, say the horizontal, remains the same, that is, Greek letter alpha 1 Greek letter alpha 2 Greek letter alpha 3. Figure 7.6b illustrates a case of combination of translation and rotation. In this case, at any instance the velocities of O and P differ. Also, Greek letter alpha 1, Greek letter alpha 2 and may 3 all be different. Systems of particles and rotational motion. 145 particles. The center of mass of the system is that point C which is at a distance x from O, where x is given by 11212 meters xm x xmm 7.1 in ek. 7.1. X can be regarded as the mass-weighted mean of x1 and x2. If the two particles have the same mass m1 m2 m, then 121222 m xm xxxxm. Thus, for two particles of equal mass the center of mass lies exactly midway between them. If we have n particles of masses m1, m2, mn respectively, along a straight line taken as the x-axis, then by definition the position of the center of the mass of the system of particles is given by xm 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 mm xm mm xm nnii 11221211. 7.2 Where x1, x2, xn are the distances of the particles from the origin, x is also measured from the same origin. The symbol the Greek letter sigma denotes summation, in this case over n particles. The sum mm is the total mass of the system. Suppose that we have three particles, not lying in a straight line. We may define x and y axes in the plane in which the particles lie and represent the positions of the three particles by coordinates x1, y1, x2, y2 and x3, y3 respectively. Let the masses of the three particles be m1, m2 and m3 respectively. The center of mass C of the system of the three particles is defined and located by the coordinates x, y given by 112233123 meters xm xm x xm mm 7.3 a 112233123 meters ym ym y ym mm 7.3 b for the particles of equal mass mm1 m2 m3. 1231233 meters xxxxxxxxm 1231233 meters ym. Thus, for three particles of equal mass, the center of mass coincides with the centroid of the triangle formed by the particles. Results of EQS 7.3a and 7.3b are generalized easily to a system of n particles, not necessarily lying in a plane, but distributed in space. The center of mass of such a system is at x, y, z, where I am x xm 7.4 I am y y m 7.4 b and I am z z m 7.4 c. Here m is the total mass of the system. The index I runs from 1 to n, m is the mass of the ith particle and the position of the ith particle is given by xi, y, z. EQS 7.4a, 7.4b and 7.4c can be combined into one equation using the notation of position vectors. Let ir be the position vector of the ith particle and r be the position vector of the center of mass, III9YZRIJK and XYZRIJK. Then IMMRR 7.4d. The sum on the right-hand side is a vector sum. Note the economy of expressions we achieve by use of vectors. If the origin of the frame of reference, the coordinate system, is chosen to be the center of mass, then 0 IMR for the given system of particles. A rigid body, such as a meter stick or a flywheel, is a system of closely packed particles. EQS 7.4a, 7.4b. 7.4c and 7.4d are therefore applicable to a rigid body. The number of particles, atoms or molecules in such a body is so large that it is impossible to carry out the summations over individual particles in these equations. Since the spacing of the particles is 146 physics small, we can treat the body as a continuous distribution of mass. We subdivide the body into n small elements of mass, m1, m2, mn. The ith element μ is taken to be located about the points I, y, z. The coordinates of the center of mass are then approximately given by I m x m y m z x y z m m m. As we make n bigger and bigger and each μ smaller and smaller, these expressions become exact. In that case, we denote the sums over I by integrals. Thus, mm mxx mid, myy mid and mzz mid. Here m is the total mass of the body. The coordinates of the center of mass now are xm xmy my mz mz m111 ddd. And 7.5 of the vector expression equivalent to these three scalar expressions is rr1 mmd 7.5b if we choose the center of mass as the origin of our coordinate system, r0 that is, r0 dm or xmy mz mdd 0 7.6. Often we have to calculate the center of mass of homogeneous bodies of regular shapes like rings, disks, spheres, rods etc. By a homogeneous body we mean a body with uniformly distributed mass. By using symmetry consideration, we can easily show that the centers of mass of these bodies lie at their geometric centers. Let us consider a thin rod, whose width and breadth in case the cross-section of the rod is rectangular or radius in case the cross-section of the rod is cylindrical is much smaller than its length. Taking the origin to be at the geometric center of the rod and x-axis to be along the length of the rod, we can say that on account of reflection symmetry, for every element dm of the rod at x, there is an element of the same mass dm located at x fig. 7.8. The net contribution of every such pair to the integral and hence the integral itself is 0. From x 7.6, the point for which the integral itself is 0, is the center of mass. Thus, the center of mass of a homogeneous thin rod coincides with its geometric center. This can be understood on the basis of reflection symmetry. The same symmetry argument will apply to homogeneous rings, disks, spheres, or even thick rods of circular or rectangular cross-section. For all such bodies you will realize that for every element dm at a point x, y, z one can always take an element of the same mass at the point x, y, z. In other words, the origin is a point of reflection symmetry for these bodies. As a result, the integrals in x 7.5 all are 0. This means that for all the above bodies, their center of mass coincides with their geometric center. Example 7.1. Find the center of mass of three particles at the vertices of an equilateral triangle. The masses of the particles are 100 grams, 150 grams, and 200 grams respectively. Each side of the equilateral triangle is 0.5 meters long. Answer figure 7.9. Figure 7.8. Determining the cm of a thin rod U. Systems of particles and rotational motion 147 UU with the x and y axes chosen as shown in Fig. 7.9. The coordinates of points O, A and B forming the equilateral triangle are respectively 0, 0, 0.5, 0, 0.25, 0.253. Let the masses 100 grams, 150 grams and 200 grams be located at O, A and B respectively. Then 112233123 meters xm 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 mm 100 0 150 0.5 200 0.25 grams m100 150 200 g75 50 125 5 meters mm 450 450 18 100 0 150 0 200 0.25 3 grams m 450 grams y53 31 meters mm 459 33. The center of mass, C, is shown in the figure. Note that it is not the geometric center of the triangle OB. YT. Example 7.2. Find the center of mass of a triangular lamina. Answer. The lamina LMN may be subdivided into narrow strips each parallel to the base MN as shown in Fig. 7.10. Figure 7.10. By symmetry each strip has its center of mass at its midpoint. If we join the midpoints of all the strips we get the median LP. The center of mass of the triangle as a whole therefore has to lie on the median LP. Similarly, we can argue that it lies on the median MQ in number. This means the center of mass lies on the point of concurrence of the medians. That is on the centroid G of the triangle T. Example 7.3. Find the center of mass of a uniform L-shaped lamina, a thin flat plate with dimensions as shown. The mass of the lamina is 3 kilograms. Answer. Choosing the x and y axes as shown in Figure 7.11. We have the coordinates of the vertices of the L-shaped lamina as given in the figure. We can think of the L shape to consist of 3 squares each of length 1 meter. The mass of each square is 1 kilogram, since the lamina is uniform. The centers of mass C1, C2 and C3 of the squares are, by symmetry, their geometric centers and have coordinates 1 2, 1 2, 3 2, 1 2, 1 2, 3 2 respectively. We take the masses of the squares to be concentrated at these points. The center of mass of the whole L shape X, Y is the center of mass of these mass points. Fig. 7.11 hence 112132112 kilograms m 111 kilogram x 5 meters 6112112 kilograms m 5 meters 111 kilogram 6 y. The center of mass of the L shape lies on the line OD. We could have guessed this without calculations. Can you tell why? Suppose the 3 squares that make up the L-shaped lamina. 148 Physics of Figure 7.11 had different masses. How will you then determine the center of mass of the lamina? T 7.3 Motion of center of mass equipped with the definition of the center of mass. We are now in a position to discuss its physical importance for a system of n particles. We may rewrite X 7.4d as 1122, IINNMMMMRRRRR 7.7. Differentiating the two sides of the equation with respect to time we get 1212 dddd. DDDNNMMMMTTTDTRRRR or 1122, NNMMMMVVVV 7.8 where 11 ddTVR is the velocity of the first particle, 22 ddTVR is the velocity of the second particle, etc. And ddTVR is the velocity of the center of mass. Note that we assume the masses m1, m2, etc. do not change in time. We have therefore treated them as constants in differentiating the equations with respect to time. Differentiating x 7.8 with respect to time, we obtain 1212 dddd, ddddnnmmmmtttvvvv or 1122. NNMMMMA 7.9 where 11 ddt of v is the acceleration of the first particle, 22 ddt of v is the acceleration of the second particle, etc. And ddtav is the acceleration of the center of mass of the system of particles. Now, from Newton's second law, the force acting on the first particle is given by 111 meter F up. The force acting on the second particle is given by 222 meters F and so on. X 7.9 may be written as 12 NMAFFF 7.10. Thus, the total mass of a system of particles times the acceleration of its center of mass is the vector sum of all the forces acting on the system of particles. Note when we talk of the force 1F on the first particle, it is not a single force, but the vector sum of all the forces on the first particle, likewise for the second particle, etc. Among these forces on each particle there will be external forces exerted by bodies outside the system and also internal forces exerted by the particles on one another. We know from Newton's third law that these internal forces occur in equal and opposite pairs and in the sum of forces of X. 7.10. Their contribution is 0, only the external forces contribute to the equation. We can then rewrite X 7.10 as X may F 7.11 where X represents the sum of all external forces acting on the particles of the system. X 7.11 states that the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied at that point. Notice, to determine the motion of the center of mass no knowledge of internal forces of the system of particles is required. For this purpose we need to know only the external forces. To obtain X 7.11 we did not need to specify the nature of the system of particles. The system may be a collection of particles in which there may be all kinds of internal motions. Or it may be a rigid body which has either pure translational motion or a combination of translational and rotational motion. Whatever is the system and the motion of its individual particles, the center of mass moves according to X. 7.11. Instead of treating extended bodies as single particles as we have done in earlier chapters, we can now treat them as systems of particles. We can obtain the translational component of their motion, that is the motion of the center of mass of the system, by taking the mass of the whole system to be concentrated at the center of mass and all the external forces on the system to be acting at the center of mass. This is the procedure that we followed earlier in analyzing forces on bodies and solving systems of particles and rotational motion. 149 problems without explicitly outlining and justifying the procedure. We now realize that in earlier studies we assumed, without saying so, that rotational motion and/or internal motion of the particles were either absent or negligible. We no longer need to do this. We have not only found the justification of the procedure we followed earlier, but we also have found how to describe and separate the translational motion of one a rigid body which may be rotating as well, or to a system of particles with all kinds of internal motion. Figure 7.12 The center of mass of the fragments of the projectile continues along the same parabolic path which it would have followed if there were no explosion. Figure 7.12 is a good illustration of X 7.11. A projectile, following the usual parabolic trajectory, explodes into fragments midway in air. The forces leading to the explosion are internal forces. They contribute nothing to the motion of the center of mass. The total external force, namely, the force of gravity acting on the body, is the same before and after the explosion. The center of mass under the influence of the external force continues, therefore, along the same parabolic trajectory as it would have followed if there were no explosion. 7.4 Linear momentum of a system of particles. Let us recall that the linear momentum of a particle is defined as mpv 7.12. Let us also recall that Newton's second law written in symbolic form for a single particle is ddtpf 7.13, where F is the force on the particle. Let us consider a system of n particles with masses m1, m2, mn respectively and velocities 1, 2, and v respectively. The particles may be interacting and have external forces acting on them. The linear momentum of the first particle is 1 meter v, of the second particle is 2 meters v, and so on. For the system of n particles, the linear momentum of the system is defined to be the vector sum of all individual particles of the system, 1, 2. NPPP page 1122, NNMMMVVV 7.14. Comparing this with X 7.8 MPV 7.15. Thus, the total momentum of a system of particles is equal to the product of the total mass of the system and the velocity of its center of mass. Differentiating X 7.15 with respect to time, DDDDMMTTPVA 7.16. Comparing X 7.16 and X 7.11, DDXPF 7.17. This is a statement of Newton's second law of motion extended to a system of particles. Suppose now, that the sum of external forces acting on a system of particles is 0, then from X 7.17 or D0 dTPP constant 7.18. Thus, when the total external force acting on a system of particles is 0, the total linear momentum of the system is constant. This is the law of conservation of the total linear momentum of a system of particles, because of X 7.15. This also means that when the total external force on the system is 0, the velocity of the center of mass remains constant. We assume throughout the discussion on systems of particles in this chapter that the total mass of the system remains constant. Note that on account of the internal forces, that is, the forces exerted by the particles on one another, the individual particles may have 150 physics complicated trajectories. Yet, if the total external force acting on the system is 0, the center of mass moves with a constant velocity, that is, moves uniformly in a straight line like a free particle. The vector X 7.18 is equivalent to three scalar equations, Pxc1, Pc2 and Pzc3. 7.18b. Here Px, Pi and Pc are the components of the total linear momentum vector P along the x, y and z axes respectively. C1, C2 and C3 are constants. A B. Figure 7.13. A heavy nucleus radium Ra splits into a lighter nucleus radon Rn and an alpha particle nucleus of helium atom. The Cm of the system is in uniform motion. B. The same splitting of the heavy nucleus radium Ra with the center of mass at rest. The two product particles fly back to back. As an example, let us consider the radioactive decay of a moving unstable particle, like the nucleus of radium. A radium nucleus disintegrates into a nucleus of radon and an alpha particle. The forces leading to the decay are internal to the system and the external forces on the system are negligible. So the total linear momentum of the system is the same before and after decay, the two particles produced in the decay. The radon nucleus and the alpha particle move in different directions in such a way that their center of mass moves along the same path along which the original decaying radium nucleus was moving. Fig. 7.13. If we observe the decay from the frame of reference in which the center of mass is at rest, the motion of the particles involved in the decay looks particularly simple. The product particles move back to back with their center of mass remaining at rest as shown in Figure 7.13b. In many problems on the system of particles, as in the above radioactive decay problem, it is convenient to work in the center of mass frame rather than in the laboratory frame of reference. In astronomy, binary double stars is a common occurrence. If there are no external forces, the center of mass of a double star moves like a free particle, as shown in Figure 7.14a. The trajectories of the two stars of equal mass are also shown in the figure. They look complicated. If we go to the center of mass frame, then we find that there the two stars are moving in a circle, about the center of mass, which is at rest. Note that the position of the stars have to be diametrically opposite to each other. Figure 7.14b. Thus in our frame of reference, the trajectories of the stars are a combination of a uniform motion in a straight line of the center of mass and two circular orbits of the stars about the center of mass, as can be seen from the two examples. Separating the motion of different parts of a system into motion of the center of mass and motion about the center of mass is a very useful technique that helps in understanding the motion of the system. 7.5 Vector product of two vectors. We are already familiar with vectors and their use in physics. In Chapter 6 Work, Energy, Power we defined the scalar product of two vectors. An important physical quantity, work, is defined as a scalar product of two vector quantities, force and displacement. A figure 7.14 trajectories of two stars, S1 dotted line and S2 solid line forming a binary system with their center of mass C in uniform motion. The same binary system, with the center of mass C at rest. Systems of particles and rotational motion 151. We shall now define another product of two vectors. This product is a vector. Two important quantities in the study of rotational motion, namely, moment of a force and angular momentum, are defined as vector products. Definition of vector product. A vector product of two vectors A and B is a vector C such that I magnitude of C sin of Greek letter theta where A and B are magnitudes of A and B and Greek letter theta is the angle between the two vectors. 2C is perpendicular to the plane containing A and B. 3 If we take a right-handed screw with its head lying in the plane of A and B and the screw perpendicular to this plane, and if we turn the head in the direction from A to B, then the tip of the screw advances in the direction of C. This right-handed screw rule is illustrated in figure 7.15a. Alternately, if one curls up the fingers of right hand around a line perpendicular to the plane of the vectors A and B and if the fingers are curled up in the direction from A to B, then the stretched thumb points in the direction of C, as shown in figure 7.15b of B. Figure 7.15 A rule of the right-handed screw for defining the direction of the vector product of two vectors. B. Rule of the right hand for defining the direction of the vector product. A simpler version of the right hand rule is the following. Open up your right hand palm and curl the fingers pointing from A to B. Your stretched thumb points in the direction of C. It should be remembered that there are two angles between any two vectors A and B. In figure 7.15 A or B they correspond to Greek letter theta as shown in 3600 Greek letter theta. While applying either of the above rules, the rotation should be taken through the smaller angle, 1800 between A and B. It is Greek letter theta here, because of the cross X used to denote the vector product. It is also referred to as cross product. Note that scalar product of two vectors is commutative as said earlier. ABB of the vector product, however, is not commutative, that is, XBBX the magnitude of both XB and BX is the same sin of Greek letter theta. Also, both of them are perpendicular to the plane of A and B. But the rotation of the right-handed screw in case of XB is from A to B, whereas in case of BX it is from B to A. This means the two vectors are in opposite directions. We have XABBA. Another interesting property of a vector product is its behavior under reflection. Under reflection, that is on taking the plane mirror image, we have an XXYYZZ. As a result, all the components of a vector change sign and thus, ABB. What happens to XB under reflection? XBXABB. Thus, XB does not change sign under reflection. Both scalar and vector products are distributive with respect to vector addition. Thus, BC. We may write CXB in the component form. For this we first need to obtain some elementary cross products. IX00 is a null vector, that is, a vector with zero magnitude. This follows since magnitude of X is 2 sin 00 degrees. 152 Physics U. From this follow the results I, XXXII 0 joules J0 KK0 2 XIJK. Note that the magnitude of psi j is sin 900 or 1, since I and j both have unit magnitude and the angle between them is 900. Thus, psi j is a unit vector perpendicular to the plane of I and j and related to them by the right-hand screw rule is K. Hence, the above result, you may verify similarly, XXJKIKIJ from the rule for commutation of the cross product. It follows, XXXJIKKJIIKJ. Note if IJK occurs cyclically in the above vector product relation, the vector product is positive. If IJK do not occur in cyclic order, the vector product is negative. Now, XYZXYZXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXYXY The expression for AXB can be put in a determinant form which is easy to remember. XYZ XYZ IBBB XIJK AB. Example 7.4. Find the scalar and vector products of two vectors. A3I 4 joules 5K and B2IJ 3K. Answer 34523641525. A BIJK IJK 3457521 XIJK. A BIJK Note 75 X BIJK T7.6. Angular velocity and its relation with linear velocity. In this section we shall study what is angular velocity and its role in rotational motion. We have seen that every particle of a rotating body moves in a circle. The linear velocity of the particle is related to the angular velocity. The relation between these two quantities involves a vector product which we learnt about in the last section. Let us go back to figure 7.4. As said above, in rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle. Fig. 7.16 Rotation about a fixed axis. A particle P of the rigid body rotating about the fixed z-axis moves in a circle with center C on the axis, which lies in a plane perpendicular to the axis and has its center on the axis. In figure 7.16 we redraw figure 7.4, showing a typical particle at a point P of the rigid body rotating about a fixed axis taken as the z-axis. The particle describes systems of particles and rotational motion. 153 A circle with a center C on the axis. The radius of the circle is r, the perpendicular distance of the point P from the axis. We also show the linear velocity vector v of the particle at P. It is along the tangent at P to the circle. Let P be the position of the particle after an interval of time t. Figure 7.16. The angle PCP describes the angular displacement Greek letter theta of the particle in time t. The average angular velocity of the particle over the interval t is Greek letter theta t, as t tends to 0, that is, takes smaller and smaller values. The ratio Greek letter theta t approaches a limit which is the instantaneous angular velocity dt of the particle at the position P. We denote the instantaneous angular velocity by Greek letter omega. The Greek letter omega. We know from our study of circular motion that the magnitude of linear velocity v of a particle moving in a circle is related to the angular velocity of the particle Greek letter omega by the simple relation Greek letter omega, where r is the radius of the circle. We observe that at any given instant the relation v applies to all particles of the rigid body. Thus for a particle at a perpendicular distance r from the fixed axis, the linear velocity at a given instant v is given by I over 7.19. The index I runs from 1 to n, where n is the total number of particles of the body. For particles on the axis, 0 r, and hence v Greek letter omega r is 0, thus, particles on the axis are stationary. This verifies that the axis is fixed. Note that we use the same angular velocity Greek letter omega for all the particles. We therefore refer to Greek letter omega 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 as the angular velocity of the whole body. We have characterized pure translation of a body by all parts of the body having the same velocity at any instant of time. Similarly, we may characterize pure rotation by all parts of the body having the same angular velocity at any instant of time. Note that this characterization of the rotation of a rigid body about a fixed axis is just another way of saying as in Sec. 7.1 that each particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has the center on the axis. In our discussion so far the angular velocity appears to be a scalar. In fact, it is a vector. We shall not justify this fact, but we shall accept it. For rotation about a fixed axis, the angular velocity vector lies along the axis of rotation, and points out in the direction in which a right-handed screw would advance, if the head of the screw is rotated with the body. See figure 7.17a. The magnitude of this vector is d Greek letter theta referred as above. Figure 7.17a. If the head of a right-handed screw rotates with the body, the screw advances in the direction of the angular velocity Greek letter omega Greek letter omega Greek letter omega Greek letter omega Greek letter omega. If the sense clockwise or anti-clockwise of rotation of the body changes, so does the direction of Greek letter omega Greek letter omega Greek letter omega Greek letter omega Greek letter omega. Figure 7.17b. The angular velocity vector Greek letter omega 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 is directed along the fixed axis as shown. The linear velocity of the particle at P is v Greek letter omega 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 xr. It is perpendicular to both Greek letter omega 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 and r and is directed along the tangent to the circle described by the particle. We shall now look at what the vector product Greek letter omega 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 xr corresponds to. Refer to figure 7.17b which is a part of Fig. 7.16 reproduced to show the path of the particle p. The figure shows the vector Greek letter omega 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 directed along the fixed z-axis, and also the position vector ROP of the particle at p of the rigid body with respect to the origin O. Note that the origin is chosen to be on the axis of rotation. 154 Physics now Greek letter omega 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 XR Greek letter omega 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 XOP Greek letter omega 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 XOCCP but Greek letter omega 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 XOC00000 is Greek letter omega 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 is the long OC, hence Greek letter omega 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 XR Greek letter omega 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 XCP. The vector Greek letter omega 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 XCP is perpendicular to Greek letter omega Greek letter omega Greek letter omega Greek letter omega Greek letter omega, that is, to the z-axis and also to CP, the radius of the circle described by the particle at p. It is therefore along the tangent to the circle at p. Also, the magnitude of Greek letter omega 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 XCP is Greek letter omega CP, since Greek letter omega 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 and CP are perpendicular to each other. We shall denote CP by R and not by R, as we did earlier. Thus, Greek letter omega 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 XR is a vector of magnitude and is along the tangent to the circle described by the particle at p. The linear velocity vector v at p has the same magnitude and direction. Thus, v Greek letter omega 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 XR 7.20. In fact, the relation x 7.20 holds good even for rotation of a rigid body with one point fixed, such as the rotation of the top fig. 7.6 In this case R represents the position vector of the particle with respect to the fixed point taken as the origin. We note that for rotation about a fixed axis, the direction of the vector Greek letter omega 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 does not change with time. Its magnitude may, however, change from instant to instant. For the more general rotation, both the magnitude and the direction of Greek letter omega 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 may change from instant to instant. 7.6 Angular acceleration. You may have noticed that we are developing a study of rotational motion along the lines of the study of translational motion with which we are already familiar. Analogous to the kinetic variables of linear displacement s and velocity v in translational motion, we have angular displacement Greek letter theta 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 and angular velocity Greek letter omega 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 in rotational motion. It is then natural to define in rotational motion the concept of angular acceleration, an analogy with linear acceleration defined as the time rate of change of velocity in translational motion. We define angular acceleration Greek letter alpha 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 as the time rate of change of angular velocity. Thus, d dt Greek letter omega Greek letter omega Greek letter omega Greek letter omega Greek letter alpha Greek letter alpha Greek letter alpha Greek letter alpha 7.21 If the axis of rotation is fixed, the direction of Greek letter omega 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 and hence that of Greek letter alpha 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 is fixed. In this case the vector equation reduces to a scalar equation d dt Greek letter omega Greek letter alpha 7.22 7.7 Torque and angular momentum. In this section, we shall acquaint ourselves with two physical quantities, torque and angular momentum, which are defined as vector products of two vectors. These, as we shall see, are especially important in the discussion of motion of systems of particles, particularly rigid bodies. 7.1 Moment of force torque. We have learnt that the motion of a rigid body, in general, is a combination of rotation and translation. If the body is fixed at a point or along a line, it has only rotational motion. We know that force is needed to change the translational state of a body, that is, to produce linear acceleration. We may then ask, what is the analog of force in the case of rotational motion? To look into the question in a concrete situation, let us take the example of opening or closing of a door. A door is a rigid body which can rotate about a fixed vertical axis passing through the hinges. What makes the door rotate? It is clear that unless a force is applied, the door does not rotate. But any force does not do the job. A force applied to the hinge line cannot produce any rotation at all. Whereas a force of given magnitude applied at right angles to the door at its outer edge is most effective in producing rotation. It is not the force alone, but how and where the force is applied is important in rotational motion. The rotational analog of force in linear motion is moment of force. It is also referred to as torque or couple. We shall use the words moment of force and torque interchangeably. We shall first define the moment of force for the special case of a single particle. Later on we shall extend the concept to systems of particles including rigid bodies. We shall also relate it to a change in the state of rotational motion, that is angular acceleration of a rigid body. Systems of particles and rotational motion 155 Figure 7.18 Greek letter tau 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 RXF Greek letter tau 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 is perpendicular to the plane containing R and F, and its direction is given by the right-handed screw rule. If a force acts on a single particle at a point P whose position with respect to the origin O is given by the position vector R Fig. 7.18. The moment of the force acting on the particle with respect to the origin O is defined as the vector product Greek letter tau 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 RXF 7.23. The moment of force or torque is a vector quantity. The symbol Greek letter tau 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 stands for the Greek letter tau. The magnitude of Greek letter tau 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 is Greek letter tau RF sin 7.24, where R is the magnitude of the position vector R, that is the length OP. F is the magnitude of force F and Greek letter theta is the angle between R and F as shown. Moment of force has dimensions mL2T2. Its dimensions are the same as those of work or energy. It is, however, a very different physical quantity than work. Moment of a force is a vector, while work is a scalar. The SI unit of moment of force is Newton meter nm. The magnitude of a moment of force may be written sin RF R Greek letter theta 7.24 b or sin RF of Greek letter theta 7.24 c, where R sin is the perpendicular distance of the line of action of F from the origin and sin FF Greek letter theta is the component of F in the direction perpendicular to R. Note that Greek letter tau 0 if R0, F0 R Greek letter theta 00 or 1800. Thus, the moment of the force vanishes if either the magnitude of the force is 0, or if the line of action of the force passes through the origin. One may note that since RXF is a vector product, properties of a vector product of two vectors apply to it. If the direction of F is reversed, the direction of the moment of force is reversed. If directions of both R and F are reversed, the direction of the moment of force remains the same. 7. 2 Angular momentum of a particle. Just as the moment of a force is the rotational analog of force in linear motion, the quantity angular momentum is the rotational analog of linear momentum. We shall first define angular momentum for the special case of a single particle and look at its usefulness in the context of single particle motion. We shall then extend the definition of angular momentum to systems of particles including rigid bodies. Like moment of a force, angular momentum is also a vector product. It could also be referred to as moment of linear momentum. From this term one could guess how angular momentum is defined. Consider a particle of mass m and linear momentum p at a position r relative to the origin O. The angular momentum L of the particle with respect to the origin O is defined to be LRX p 7.25. The magnitude of the angular momentum vector is sin lar p Greek letter theta 7.26, where p is the magnitude of p and Greek letter theta is the angle between r and p. We may write LRP or RP 7.26b, where RR sin is the perpendicular distance of the directional line of P from the origin and sin PP Greek letter theta is the component of P in a direction perpendicular to R. We expect the angular momentum to be 0 L0, if the linear momentum vanishes P0, if the particle is at the origin R0, or if the directional line of P passes through the origin Greek letter theta 00 or 1800. 156 Physics. The physical quantities, moment of a force and angular momentum, have an important relation between them. It is the rotational analog of the relation between force and linear momentum, for deriving the relation in the context of a single particle. We differentiate LRXP with respect to time, ddddttxLRP, applying the product rule for differentiation to the right-hand side. ddddttxXXRPRPPR. Now, the velocity of the particle is v dr dt and pmv. Because of this, d0, dmtxxrpvv as the vector product of two parallel vectors vanishes. Further, since dpdtf rprfxxddt Greek letter tau hence ddtrpx Greek letter tau or ddlt Greek letter tau 7.27. Thus, the time rate of change of the angular momentum of a particle is equal to the torque acting on it. This is the rotational analog of the equation F dp dt, which expresses Newton's second law for the translational motion of a single particle. Torque and angular momentum for a system of particles. To get the total angular momentum of a system of particles about a given point, we need to add vectorially the angular momenta of individual particles. Thus, for a system of n particles, LLLLL121, NIIN, the angular momentum of the ith particle is given by Lee re x pi, where re is the position vector of the ith particle with respect to a given origin and p v is the linear momentum of the particle. The particle has mass m and velocity v. We may write the total angular momentum of a system of particles as LLRPXIII 7.25b. This is a generalization of the definition of angular momentum EC 7.25 for a single particle to a system of particles. Using EQS 7.23 and 7.25b, we get DDDDDDLLLTTTIIII Greek letter tau 7.28. An experiment with a bicycle rim. Take a bicycle rim and extend its axle on both sides. Tie two strings at both ends A and B, as shown in the adjoining figure. Hold both the strings together in one hand such that the rim is vertical. If you leave one string, the rim will tilt. Now, keeping the rim in vertical position with both the strings in one hand, put the wheel in fast rotation around the axle with the other hand. Then leave one string, say B, from your hand, and observe what happens. The rim keeps rotating in a vertical plane and the plane of rotation turns around the string A which you are holding. We say that the axis of rotation of the rim, or equivalently its angular momentum, precesses about the string A. The rotating rim gives rise to an angular momentum. Determine the direction of this angular momentum. When you are holding the rotating rim with string A, a torque is generated. We leave it to you to find out how the torque is generated and what its direction is. The effect of the torque on the angular momentum is to make it precess around an axis perpendicular to both the angular momentum and the torque. Verify all these statements, initially after systems of particles and rotational motion. 157 UU, where Greek letter tau I is the torque acting on the ith particle. Greek letter tau IIXRF, the force phi on the ith particle, is the vector sum of external forces phi ext acting on the particle and the internal forces and diff exerted on it by the other particles of the system. We may therefore separate the contribution of the external and the internal forces to the total torque. Greek letter tau Greek letter tau Greek letter tau Greek letter tau x IIIRF is Greek letter tau 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 ext int, where Greek letter tau x IEXTIXRF and Greek letter tau int XR phi I. We shall assume not only Newton's third law of motion, that is, the forces between any two particles of the system are equal and opposite, but also that these forces are directed along the line joining the two particles. In this case, the contribution of the internal forces to the total torque on the system is zero, since the torque resulting from each action-reaction pair of forces is zero. We thus have Greek letter tau Greek letter tau Greek letter tau int 0, and therefore Greek letter tau 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 ext. Since Greek letter tau Greek letter tau Greek letter tau Greek letter tau I, it follows from EC 7.28.DDLTEXT Greek letter tau 7.28b. Thus, the time rate of the total angular momentum of a system of particles about a point taken as the origin of our frame of reference is equal to the sum of the external torques, that is, the torques due to external forces acting on the system taken about the same point. X 7.28b is the generalization of the single particle case of EC 7.23 to a system of particles. Note that when we have only one particle, there are no internal forces or torques. X 7.28b is the rotational analog of DDPFTEXT 7.17. Note that, like X 7.17, X 7.28b holds good for any system of particles, whether it is a rigid body or its individual particles have all kinds of internal motion. Conservation of angular momentum if x0, X 7.28b reduces to d0 dTl or L constant. 7.29. Thus, if the total external torque on a system of particles is zero, then the total angular momentum of the system is conserved, that is, remains constant. X 7.29 is equivalent to three scalar equations, 60 K1, by K2 and LZ K3 7.29b. Here K1, K2 and K3 are constants, 60, Li and LZ are the components of the total angular momentum vector L along the X, Y and Z axes respectively. The statement that the total angular momentum is conserved means that each of these three components is conserved. X 7.29 is the rotational analog of X 7.18, that is the conservation law of the total linear momentum for a system of particles. Like X 7.18, it has applications in many practical situations. We shall look at a few of the interesting applications later on in this chapter. Example 7.5. Find the torque of a force 7I3 joules 5K about the origin. The force acts on a particle whose position vector is ijk. Answer: here are ijk and 735 fijk. We shall use the determinant rule to find the torque Greek letter tau XRFR Greek letter tau 21210 IJKT. Example 7.6 show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. 158 Physics answer. Let the particle with velocity v be at point P at some instant t. We want to calculate the angular momentum of the particle about an arbitrary point O. Figure 7.19. The angular momentum is LRx_mv. Its magnitude is mvr sin, where Greek letter theta is the angle between r and v as shown in figure 7.19. Although the particle changes position with time, the line of direction of v remains the same, and hence OMR sin Greek letter theta is a constant. Further, the direction of L is perpendicular to the plane of r and v. It is into the page of the figure. This direction does not change with time. Thus, L remains the same in magnitude and direction and is therefore conserved. Is there any external torque on the particle? T7.8 Equilibrium of a rigid body. We are now going to concentrate on the motion of rigid bodies rather than on the motion of general systems of particles. We shall recapitulate what effect the external forces have on a rigid body. Henceforth we shall omit the adjective external because unless stated otherwise, we shall deal with only external forces and torques. The forces change the translational state of the motion of the rigid body, that is, they change its total linear momentum in accordance with X 7.17, but this is not the only effect the forces have. The total torque on the body may not vanish. Such a torque changes the rotational state of motion of the rigid body, that is, it changes the total angular momentum of a body in accordance with X 7.28b. A rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changing with time, or equivalently, the body has neither linear acceleration nor angular acceleration. This means 1. The total force, that is the vector sum of the forces, on the rigid body is 0, FFFF121. NIIN 07.30a. If the total force on the body is 0, then the total linear momentum of a body does not change with time. X 7.30a gives the condition for the translational equilibrium of a body to the total torque, that is, the vector sum of the torques on the rigid body is 0. Greek letter tau 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 121. NIIN 07.30b. If the total torque on the rigid body is 0, the total angular momentum of a body does not change with time. X 7.30b gives the condition for the rotational equilibrium of the body. One may raise a question, whether the rotational equilibrium condition X 7.30b remains valid if the origin with respect to which the torques are taken is shifted. One can show that if the translational equilibrium condition X 7.30 holds for a rigid body, then such a shift of origin does not matter, that is, the rotational equilibrium condition is independent of the location of the origin about which the torques are taken. Example 7.7 gives a proof of this result in a special case of a couple, that is, two forces acting on a rigid body in translational equilibrium. The generalization of this result to AN forces is left as an exercise. X 7.30 and X 7.30b, both, are vector equations. They are equivalent to three scalar equations each. X 7.30 corresponds to fix IN01, phi IN01 and phys IN01. 7.31 where fix, phi and phys are respectively the x, y and z components of the forces phi. Similarly, X 7.30b is equivalent to three scalar equations X IN01, IIN01 and Is IN01. 7.31b where X, I and Is are respectively the x, y and z components of the torque Greek letter tau Greek letter tau Greek letter tau I. Systems of particles and rotational motion. 159 X 7.31 and 7.31b give 6 independent conditions to be satisfied for mechanical equilibrium of a rigid body. In a number of problems all the forces acting on the body are coplanar, then we need only 3 conditions to be satisfied for mechanical equilibrium. 2 of these conditions correspond to translational equilibrium. The sum of the components of the forces along any 2 perpendicular axes in the plane must be 0. The third condition corresponds to rotational equilibrium. The sum of the components of the torques along any axis perpendicular to the plane of the forces must be 0. The conditions of equilibrium of a rigid body may be compared with those for a particle, which we considered in earlier chapters. Since consideration of rotational motion does not apply to a particle, only the conditions for translational equilibrium X 7.30 apply to a particle. Thus, for equilibrium of a particle the vector sum of all the forces on it must be 0. Since all these forces act on the single particle, they must be concurrent. Equilibrium under concurrent forces was discussed in the earlier chapters. A body may be in partial equilibrium, that is, it may be in translational equilibrium and not in rotational equilibrium, or it may be in rotational equilibrium and not in translational equilibrium. Consider a light that is of negligible mass rod AB as shown in figure 7.20 up, at the two ends A and B of which two parallel forces, both equal in magnitude and acting along same direction are applied perpendicular to the rod. Figure 7.20 let C be the midpoint of AB, CACBA the moment of the forces at A and B will both be equal in magnitude F, but opposite in sense as shown. The net moment on the rod will be 0, the system will be in rotational equilibrium, but it will not be in translational equilibrium, F0 Fig. 7.20b the force at B in figure 7.20a is reversed in figure 7.20b, thus, we have the same rod with two forces of equal magnitude but acting in opposite directions applied perpendicular to the rod. One at end A and the other at end B. Here the moments of both the forces are equal, but they are not opposite, they act in the same sense and cause anti-clockwise rotation of the rod. The total force on the body is 0, so the body is in translational equilibrium, but it is not in rotational equilibrium. Although the rod is not fixed in any way, it undergoes pure rotation, that is rotation without translation. A pair of forces of equal magnitude but acting in opposite directions with different lines of action is known as a couple or torque. A couple produces rotation without translation. When we open the lid of a bottle by turning it, our fingers are applying a couple to the lid. Fig. 7.21 Another known example is a compass needle in the Earth's magnetic field as shown in the Fig. 7.21b. The Earth's magnetic field exerts equal forces on the north and south poles. The force on the north pole is towards the north, and the force on the south pole is toward the south. Except when the needle points in the north-south direction, the two forces do not have the same line of action. Thus there is a couple acting on the needle due to the Earth's magnetic field. Figure 7.21 Our fingers apply a couple to turn the lid. 160 Physics U Figure 7.21b The Earth's magnetic field exerts equal and opposite forces on the poles of a compass needle. These two forces form a couple. Example 7.7 show that moment of a couple does not depend on the point about which you take the moments. Answer Figure 7.22 Consider a couple as shown in Figure 7.22 acting on a rigid body. The forces F and F act respectively at points B and A. These points have position vectors r1 and r2 with respect to origin. Let us take the moments of the forces about the origin. The moment of the couple sum of the moments of the two forces making the couple r1xf r2xf r2xf, r1xf r2 r1xf but r1 abr2, and hence abr2 r1. The moment of the couple, therefore, is ABXF. Clearly this is independent of the origin, the point about which we took the moments of the forces. T7.8. One principle of moments. An ideal lever is essentially a light that is of negligible mass rod pivoted at a point along its length. This point is called the fulcrum. A seesaw on the children's playground is a typical example of a lever. Two forces F1 and F2, parallel to each other and usually perpendicular to the lever, as shown here, act on the lever at distances d1 and d2 respectively from the fulcrum as shown in Fig. 7.23. Figure 7.23 The lever is a system in mechanical equilibrium. Let R be the reaction of the support at the fulcrum. R is directed opposite to the forces F1 and F2. For translational equilibrium, R F1 F2 0 For considering rotational equilibrium we take the moments about the fulcrum. The sum of moments must be 0. D1 F1 D2 F2 0 2 Normally the anti-clockwise moments are taken to be positive negative. Note R acts at the fulcrum itself and has 0 moment about the fulcrum. In the case of the lever, force F1 is usually some weight to be lifted. It is called the load and its distance from the fulcrum D1 is called the load arm. Force F2 is the effort applied to lift the load. Distance D2 of the effort from the fulcrum is the effort arm. F2 can be written as D1 F1 D2 F2 7.32 or load arm x load effort arm x effort. The above equation expresses the principle of moments for a lever. Incidentally, the ratio F1 F2 is called the mechanical advantage MA 1221 FD 7.32b if the effort arm D2 is larger than the load arm. The mechanical advantage is greater than 1. Mechanical advantage greater than 1 means that a small effort can be used to lift a large load. There are several examples of a lever around you besides the seesaw, but beam of a balance is a lever. Try to find more such. Systems of particles and rotational motion. 161 examples and identify the fulcrum, the effort and effort arm, and the load arm of the lever in each case. You may easily show that the principle of moment holds even when the parallel forces F1 and F2 are not perpendicular, but act at some angle, to the lever. 7.8. Center of gravity. Many of you may have the experience of balancing your notebook on the tip of a finger. Figure 7.24 illustrates a similar experiment that you can easily perform. Take an irregular shaped cardboard having mass m and an arrow-tipped object like a pencil. You can locate by trial and error a point G on the cardboard where it can be balanced on the tip of the pencil. The cardboard remains horizontal in this position. This point of balance is the center of gravity CG of the cardboard. The tip of the pencil provides the vertically upward force due to which the cardboard is in mechanical equilibrium. As shown in the figure 7.24, the reaction of the tip is equal and opposite to mg and hence the cardboard is in translational equilibrium. It is also in rotational equilibrium. If it were not so, due to the unbalanced torque it would tilt and fall. There are torques on the cardboard due to the forces of gravity like m1g, m2g etc., acting on the individual particles that make up the cardboard. Figure 7.24 balancing a cardboard on the tip of a pencil, the point of support, G, is the center of gravity. The CG of the cardboard is so located that the total torque on it due to the forces m1g, m2g etc. is 0. If ρ is the position vector of the ith particle of an extended body with respect to its CG, then the torque about the CG, due to the force of gravity on the particle is Greek letter tau on ρ x mg. The total gravitational torque about the CG is 0, that is Greek letter tau Gaia IMXRG 07.33. We may therefore define the CG of a body as that point where the total gravitational torque on the body is 0. We notice that in X 7.33, G is the same for all particles, and hence it comes out of the summation. This gives, since G is non-zero, μ I are 0, remember that the position vectors ρ are taken with respect to the CG now. In accordance with the reasoning given below X 7.4a and Sec 7.2, if the sum is 0, the origin must be the center of mass of the body. Thus, the center of gravity of the body coincides with the center of mass in uniform gravity or gravity-free space. We note that this is true because the body being small, G does not figure 7.25 determining the center of gravity of a body of irregular shape. The center of gravity G lies on the vertical AA1 through the point of suspension of the body A. 162 Physics UU vary from one point of the body to the other. If the body is so extended that G varies from part to part of the body, then the center of gravity and center of mass will not coincide. Basically, the two are different concepts. The center of mass has nothing to do with gravity, it depends only on the distribution of mass of the body. In Sec 7.2 we found out the position of the center of mass of several regular, homogeneous objects. Obviously the method used there gives us also the center of gravity of these bodies, if they are small enough. Figure 7.25 illustrates another way of determining the CG of an irregular shaped body like a cardboard. If you suspend the body from some point like A, the vertical line through A passes through the CG. We mark the vertical A1, we then suspend the body through other points like B and C. The intersection of the verticals gives the CG. Explain why the method works, since the body is small enough. The method allows us to determine also its center of mass. Example 7.8 A metal bar 70 cm long and 4.00 kg in mass supported on two knife edges placed 10 cm from each end. A 6.00 kg load is suspended at 30 cm from one end. Find the reactions at the knife edges. Assume the bar to be of uniform cross-section and homogeneous. Answer Fig. 7.26 Figure 7.26 shows the rod AB, the positions of the knife edges K1 and K2, the center of gravity of the rod at G and the suspended load at P. Note the weight of the rod W acts at its center of gravity G. The rod is uniform in cross-section and homogeneous, hence G is at the center of the rod. AB 70 cm, AG 35 cm. AP 30 cm, PG 5 cm, AK1 BK2 10 cm and K1 GK2 G25 cm. Also, W weight of the rod 4.00 kg and W1 suspended load 6.00 kg. R1 and R2 are the normal reactions of the support at the knife edges. For translational equilibrium of the rod, R1 R2 W1 W0 I note W1 and W act vertically down and R1 and R2 act vertically up. For considering rotational equilibrium, we take moments of the forces. A convenient point to take moments about is G. The moments of R2 and W1 are anti-clockwise v, whereas the moment of R1 is clockwise v. For rotational equilibrium, R1 K1 G W1 PG R2 K2 G02 it is given that W 4.00 grams N and W1 6.00 grams N, where G acceleration due to gravity. We take G 9.8 meters S2, with numerical values inserted, from IR1R to 4.00 grams 6.00 grams 0 or R1R to 10.00 grams N 398.00 and from 2. 0.25 R1 0.05 W1 0.25 R2 0 or R1 R2 1.2 grams N 11.76 Ni from 3 and IV, R1 54.88 N, R2 43.12 N. Thus the reactions of the support are about 55 N at K1 and 43 N at K2. T example 7.9 A 3 meters long ladder weighing 20 kilograms leans on a frictionless wall. Its feet rest on the floor 1 meters from the wall as shown in figure 7.27. Find the reaction forces of the wall and the floor. Answer figure 7.27. The ladder AB is 3 meters long. Its foot A is at distance AC 1 meters from the wall. From Systems of Particles and Rotational Motion 163 Pythagoras Theorem, BC 2 meters. The forces on the ladder are its weight W acting at its center of gravity D, reaction forces F1 and F2 of the wall and the floor respectively. Force F1 is perpendicular to the wall. Since the wall is frictionless, force F2 is resolved into two components. The normal reaction N and the force of friction F. Note that F prevents the ladder from sliding away from the wall and is therefore directed toward the wall, for translational equilibrium. Taking the forces in the vertical direction, N, W0I taking the forces in the horizontal direction. FF102 for rotational equilibrium, taking the moments of the forces about A. 12 to F12 W03 now W20 grams 20x 9.8 N 196.0 N from I N 196.0 N from 3142, 196, 0, 4, 2, 34.6 N FW from 2 134.6 N FF2 2 199.0 FFNN. The force F2 makes an angle Greek letter alpha with the horizontal, 1 tan 42. Tan 4280 N Greek letter alpha T 7.9 moment of inertia. We have already mentioned that we are developing a study of rotational motion parallel to the study of translational motion with which we are familiar. We have yet to answer one major question in this connection. What is the analog of mass in rotational motion? We shall attempt to answer this question in the present section. To keep the discussion simple, we shall consider rotation about a fixed axis only. Let us try to get an expression for the kinetic energy of a rotating body. We know that for a body rotating about a fixed axis, each particle of the body moves in a circle with linear velocity given by Ek. 7.19. Refer to figure 7.16. For a particle at a distance from the axis, the linear velocity is I or Greek letter omega. The kinetic energy of motion of this particle is 2 to 21.122 I mm Greek letter omega, where m is the mass of the particle. The total kinetic energy K of the body is then given by the sum of the kinetic energies of individual particles. 22112 NNIIIIKKMR Greek letter omega. Here N is the number of particles in the body. Note Greek letter omega is the same for all particles. Hence, taking Greek letter omega out of the sum, 22112 NIIIKM, we define a new parameter characterizing the rigid body, called the moment of inertia I, given by 21 NIIIMR 7.34. With this definition, 21.2K is 7.35. Note that the parameter I is independent of the magnitude of the angular velocity. It is a characteristic of the rigid body and the axis about which it rotates. Compare X 7.35 for the kinetic energy of a rotating body with the expression for the kinetic energy of a body in linear translational motion. 21.2 came here. M is the mass of the body and V is its velocity. We have already noted the analogy between angular velocity Greek letter omega in respect of rotational motion about a fixed axis and linear velocity V in respect of linear motion. It is then evident that the parameter, moment of inertia I, is the desired rotational analog of mass in linear motion. In rotation about a fixed axis, the moment of inertia plays a similar role as mass does in linear motion. We now apply the definition X 7.34, to calculate the moment of inertia in two simple cases. Consider a thin ring of radius r and mass m, rotating in its own plane around its center. 164 Physics with angular velocity Greek letter omega. Each mass element of the ring is at a distance r from the axis, and moves with a speed. The kinetic energy is therefore 2 to 21.122 km Greek letter omega. Comparing with X 7.35, we get IMR2 for the ring. Figure 7.28. A light rod of length L with a pair of masses rotating about an axis through the center of mass of the system and perpendicular to the rod. The total mass of the system is mb. Next, take a rigid rod of negligible mass of length L with a pair of small masses, rotating about an axis through the center of mass perpendicular to the rod. Fig. 7.28. Each mass m2 is at a distance L2 from the axis. The moment of inertia of the masses is therefore given by m2 L2 to m2 liters 2 to thus. For the pair of masses rotating about the axis through the center of mass perpendicular to the rod IML2 for table 7.1 simply gives the moment of inertia of various familiar regular shaped bodies about specific axes. The derivations of these expressions are beyond the scope of this textbook and you will study them in higher classes, as the mass of a body resists the change in its state of linear motion. It is a measure of its inertia in linear motion, similarly, as the moment of inertia about a given axis of rotation resists the change in its rotational motion. It can be regarded as a measure of rotational inertia of the body. It is a measure of the way in which different parts of the body are distributed at different distances from the axis. Unlike the mass of a body, the moment of inertia is not a fixed quantity but depends on distribution of mass about the axis of rotation, and the orientation and position of the axis of rotation with respect to the body as a whole, as a measure of the way in which the mass of a rotating rigid body is distributed with respect to the axis of rotation. We can define a new parameter, the radius of gyration. It is related to the moment of inertia and the total mass of the body. Notice from the table 7.1 that in all cases, we can write Imk2, where k has the dimension of length. For a rod, about the perpendicular axis at its midpoint, i.e., 2, 2, 12, kl 12 kl, similarly, kr2 for the circular disk about its diameter. The length k is a geometric property of a body and axis of rotation. It is called the radius of gyration. The radius of gyration of a body about an axis may be defined as the distance from the axis of a mass point whose mass is equal to the mass of the whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis. Thus, the moment of inertia of a rigid body depends on the mass of the body, its shape and size, distribution of mass about the axis of rotation, and the position and orientation of the axis of rotation. From the definition, X 7.34, we can infer that the dimensions of moments of inertia are ml2 and its SI units are kgm2. The property of this extremely important quantity I, as a measure of rotational inertia of the body, has been put to a great practical use. The machines, such as steam engine and the automobile engine, etc., that produce rotational motion have a disk with a large moment of inertia, called a flywheel. Because of its large moment of inertia, the flywheel resists the sudden increase or decrease of the speed of the vehicle. It allows a gradual change in the speed and prevents jerky motions, thereby ensuring a smooth ride for the passengers on the vehicle. 7.10 Theorems of perpendicular and parallel axes. These are two useful theorems relating to moment of inertia. We shall first discuss the theorem of perpendicular axes and its simple yet instructive application in working out the moments of inertia of some regular-shaped bodies. Systems of particles and rotational motion. 165 Table 7.1 Moments of inertia of some regular-shaped bodies about specific axes. See body axis figure I1. Thin circular perpendicular to MR2 ring. Radius R plane, at center 2 thin circular diameter MR2 2 ring, radius R3 thin rod, perpendicular to ML2 12 length L rod. At midpoint 4 circular disc, perpendicular to MR2 2 radius R disc at center 5 circular disc. Diameter MR2 4 radius R6 hollow cylinder, axis of cylinder MR2 radius R7 solid cylinder. Axis of cylinder MR2 2 radius R8 solid sphere, diameter 2 MR2 5 radius R. Theorem of perpendicular axes. This theorem is applicable to bodies which are planar. In practice this means the theorem applies to flat bodies whose thickness is very small compared to their other dimensions, e.g. length, breadth or radius. Figure 7.29 illustrates the theorem. It states that the moment of inertia of a planar body lamina about an axis perpendicular to its plane is equal to the sum of its moments of inertia about two perpendicular axes concurrent with perpendicular axis and lying in the plane of the body. 166 Physics U. Figure 7.29 Theorem of perpendicular axes applicable to a planar body. X and Y axes are two perpendicular axes in the plane and the Z-axis is perpendicular to the plane. The figure shows a planar body. An axis perpendicular to the body through a point O is taken as the Z-axis. Two mutually perpendicular axes lying in the plane of the body and concurrent with Z-axis, that is, passing through O, are taken as the X and Y axes. The theorem states that ZXUII 7.36. Let us look at the usefulness of the theorem through an example. Example 7.10 What is the moment of inertia of a disk about one of its diameters? Figure 7.30 Moment of inertia of a disk about a diameter, given its moment of inertia about the perpendicular axis through its center. Answer: we assume the moment of inertia of the disk about an axis perpendicular to it and through its center to be known. It is mr22, where m is the mass of the disk and r is its radius. Table 7.1 The disk can be considered to be a planar body. Hence the theorem of perpendicular axes is applicable to it. As shown in figure 7.30, we take three concurrent axes through the center of the disk, O, as the x, y and z-axis. X and y axes lie in the plane of the disk and z-axis is perpendicular to it. By the theorem of perpendicular axis, ZXUII now, x and y axes are along two diameters of the disk, and by symmetry the moment of inertia of the disk is the same about any diameter. hence 9II and is 2x but is mr2 so finally, 9 is 2 mr2 thus the moment of inertia of a disk about any of its diameter is mr2 T finds similarly the moment of inertia of a ring about any of its diameters. Will the theorem be applicable to a solid cylinder? Figure 7.31 The theorem of parallel axes. The Z and Z axes are two parallel axes separated by a distance a. O is the center of mass of the body. OOA. Systems of particles and rotational motion 167 UU 7, 10. 1 Theorem of parallel axes. This theorem is applicable to a body of any shape. It allows to find the moment of inertia of a body about any axis, given the moment of inertia of a body about a parallel axis through the center of mass of the body. We shall only state this theorem and not give its proof. We shall, however, apply it to a few simple situations which will be enough to convince us about the usefulness of the theorem. The theorem may be stated as follows. The moment of inertia of a body about any axis is equal to the sum of the moment of inertia of a body about a parallel axis passing through its center of mass and the product of its mass and the square of the distance between the two parallel axes. As shown in the figure 7.31, Z and Z are two parallel axes, separated by a distance a. The Z-axis passes through the center of mass O of the rigid body. Then according to the theorem of parallel axes is ma2 7.37 where is and is are the moments of inertia of a body about the Z and Z axes respectively. M is the total mass of the body and A is the perpendicular distance between the two parallel axes. Example 7.11 What is the moment of inertia of a rod of mass m, length L about an axis perpendicular to it through one end? Answer for the rod of mass m and length L, IML2 12. Using the parallel axes theorem, IML2 with the L2 we get 22 to 12 to 3 liters LMLIMM. We can check this independently since I is half the moment of inertia of a rod of mass 2m and length 2 liters about its midpoint, 22412. 12 to 3 liters MLIMXT. Example 7.12 What is the moment of inertia of a ring about a tangent to the circle of the ring? Answer The tangent to the ring in the plane of the ring is parallel to one of the diameters of the ring. The distance between these two parallel axes is r, the radius of the ring, using the parallel axes theorem, Fig. 7.32 II Mr. M. Diet and Gent 2222232 T 7.11 Kinematics of rotational motion about a fixed axis. We have already indicated the analogy between rotational motion and translational motion. For example, the angular velocity Greek letter omega 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 plays the same role in rotation as the linear velocity v in translation. We wish to take this analogy further. In doing so we shall restrict the discussion only to rotation about fixed axis. This case of motion involves only one degree of freedom, that is, needs only one independent variable to describe the motion. This in translation corresponds to linear motion. This section is limited only to kinematics. We shall turn to dynamics in later sections. We recall that for specifying the angular displacement of the rotating body we take any particle like P. Figure 7.33 of the body. Its angular displacement Greek letter theta in the plane it moves is the angular displacement of the whole body. Greek letter theta is measured from a fixed direction in the plane of motion of P, which we take to be the x-axis, chosen parallel to the x-axis. Note, as shown, the axis of rotation is the z-axis and the plane of the motion of the particle is the xy plane. Figure 7.33 also shows Greek letter theta 0, the angular displacement at t0. We also recall that the angular velocity is the time rate of change of angular displacement, Greek letter omega dt. Note since the axis of rotation is fixed. 168 Physics UU There is no need to treat angular velocity as a vector. Further, the angular acceleration, Greek letter alpha dt. The kinematical quantities in rotational motion, angular displacement Greek letter theta, angular velocity Greek letter omega and angular acceleration Greek letter alpha respectively are analogous to kinematic quantities in linear motion, displacement x, velocity v and acceleration a. We know the kinematical equations of linear motion with uniform that is constant acceleration, v0 at a 20012 at b2202 x Greek letter upsilon c where x0 initial displacement and v0 initial velocity. The word initial refers to values of the quantities at t0. The corresponding kinematic equations for rotational motion with uniform angular acceleration are 0t Greek letter omega Greek letter alpha 7.382001 tt Greek letter theta Greek letter omega Greek letter alpha 7.39 and 22002 Greek letter omega Greek letter alpha Greek letter theta 7.40 where Greek letter theta 0 initial angular displacement of the rotating body, and Greek letter omega 0 initial angular velocity of the body. Figure 7.33 specifying the angular position of a rigid body. Example 7.13 Obtain x 7.38 from first principles. Answer: the angular acceleration is uniform, hence dt constant t Greek letter omega Greek letter alpha I. Integrating this equation. Greek letter omega Greek letter alpha dtc is constant t Greek letter alpha at t0, Greek letter omega 0 given from I we get at t0, Greek letter omega c Greek letter omega 0 thus, Greek letter omega 0 is required. With the definition of Greek letter omega dt we may integrate x 7.38 to get x 7.39, this derivation and the derivation of x 7.40 is left as an exercise. Example 7.14 The angular speed of a motor wheel is increased from 1,200 revolutions per minute to 3,120 revolutions per minute in 16 seconds. What is its angular acceleration? Assuming the acceleration to be uniform to how many revolutions does the engine make during this time? Answer: I. We shall use Greek letter omega 0 at Greek letter omega 0 initial angular speed and rev s2 Greek letter pi x angular speed and rev s2 angular speed and rev min 60 s min 2 1200 rad s 60s 40 Greek letter pi rad s. Similarly Greek letter omega final angular speed and rad s2 3120 rad s 60s 2 Greek letter pi x 52 rad s 104 Greek letter pi rad s angular acceleration 0 t Greek letter omega Greek letter alpha 4 Greek letter pi rad s2. Systems of particles and rotational motion 169 The angular acceleration of the engine 4 Greek letter pi rad s2 2 The angular displacement in time t is given by 2012 t Greek letter omega Greek letter alpha 2140 16 4 16 2 Greek letter pi xxx rad 640 512 Greek letter pi rad 1152 Greek letter pi rad number of revolutions 1152 576 2 Greek letter pi t 7.12 Dynamics of rotational motion about a fixed axis Table 7.2 lists quantities associated with linear motion and their analogues in rotational motion. We have already compared kinematics of the two motions. Also, we know that in rotational motion moment of inertia and torque play the same role as mass and force respectively in linear motion. Given this we should be able to guess what the other analogues indicated in the table are. For example, we know that in linear motion, work done is given by F dx. In rotational motion about a fixed axis it should be Greek letter theta, since we already know the correspondence d dx Greek letter theta and F Greek letter tau. It is, however, necessary that these correspondences are established on sound dynamical considerations. This is what we now turn to. Before we begin, we note a simplification that arises in the case of rotational motion about a fixed axis. Since the axis is fixed, only those components of torques, which are along the direction of the fixed axis need to be considered in our discussion. Only these components can cause the body to rotate about the axis. A component of the torque perpendicular to the axis of rotation will tend to turn the axis from its position. We specifically assume that there will arise necessary forces of constraint to cancel the effect of the perpendicular components of the external torques, so that the fixed position of the axis will be maintained. The perpendicular components of the torques, therefore, need not be taken into account. This means that for our calculation of torques on a rigid body, we need to consider only those forces that lie in planes perpendicular to the axis. Forces which are parallel to the axis will give torques perpendicular to the axis and need not be taken into account. 2. We need to consider only those components of the position vectors which are perpendicular to the axis. Components of position vectors along the axis will result in torques perpendicular to the axis and need not be taken into account. Work done by a torque Fig. 7.34 Work done by a force F1 acting on a particle of a body rotating about a fixed axis. The particle describes a circular path with center C on the axis. P1 ds1 gives the displacement of the particle. Figure 7.34 shows a cross-section of a rigid body rotating about a fixed axis, which is taken as the z-axis perpendicular to the plane of the page. See Fig. 7.33. As said above, we need to consider only those forces which lie in planes perpendicular to the axis. Let F1 be one such typical force acting as shown on a particle of the body at point P1 with its line of action in a plane perpendicular to the axis. For convenience we call this to be the xy plane coincident with the plane of the page. The particle at P1 describes a circular path of radius r1 with center C on the axis, P1 r1. In time t, the point moves to the position P1, the displacement of the particle ds1, therefore, has magnitude ds1 r1 and direction tangential at P1 to the circular path as shown. Here it is the angular displacement of the particle, 11 pcp. The work done by the force on the particle is dw1 f1. ds1 f1 ds1 cos 1 f1 r1 sin 1 where Greek letter phi 1 is the angle between f1 and the tangent. at P1, and Greek letter alpha 1 is the angle between F1 and the radius vector OP1, Greek letter phi 1 Greek letter alpha 1 90 degrees. The torque due to F1 about the origin is OP1 x F1. Now OP1 OC OP1, refer to figure 7.17b, since OC is along the axis, the torque resulting from it is excluded from our consideration. The effective torque due to F1 is Greek letter tau Greek letter tau Greek letter tau 1 CP x F1. It is directed along the axis of rotation and has a magnitude Greek letter tau 1 R1 F1 sin. Therefore, dW1 Greek letter tau 1 if there are more than one forces acting on the body, the work done by all of them can be added to give the total work done on the body. Denoting the magnitudes of the torques due to the different forces as Greek letter tau 1, Greek letter tau 2 etc. 1 2 d, dW Greek letter tau Greek letter tau Greek letter theta. Remember, the forces giving rise to the torques act on different particles, but the angular displacement is the same for all the particles. Since all the torques considered are parallel to the fixed axis, the magnitude Greek letter tau of the total torque is just the algebraic sum of the magnitudes of the torques, that is, Greek letter tau and Greek letter tau 2. We, therefore, have ddW Greek letter theta 7.41. This expression gives the work done by the total external torque Greek letter tau which acts on the body rotating about a fixed axis. Its similarity with the corresponding expression dWf/ds for linear translational motion is obvious. Dividing both sides of x7.41 by dt gives ddddWp Greek letter theta Greek letter tau or p tau 7.42. This is the instantaneous power. Compare this expression for power in the case of rotational motion about a fixed axis with that of power in the case of linear motion. PFV in a perfectly rigid body there is no internal motion. The work done by external torques is therefore not dissipated and goes on to increase the kinetic energy of the body. The rate at which work is done on the body is given by x7.42. This is to be equated to the rate at which kinetic energy increases. The rate of increase of kinetic energy is ddddTIIT Greek letter omega 2222. We assume that the moment of inertia does not change with time. This means that the mass of the body does not change, the body remains rigid and also the axis does not change its position with respect to the body. Since dd, Greek letter omega we get ddTII Greek letter omega Greek letter alpha 22 equating rates of work done and of increase in kinetic energy. A Greek letter omega Greek letter alpha table 7.2 comparison of translational and rotational motion linear motion rotational motion about a fixed axis 1 displacement x angular displacement Greek letter theta 2 velocity v dx dt angular velocity Greek letter omega dt 3 acceleration a dv dt angular acceleration Greek letter alpha dt 4 mass m moment of inertia I 5 force f mod torque Greek letter tau I Greek letter alpha 6 work dWf ds work w Greek letter tau 7 kinetic energy kmv 22 kinetic energy k 228 power pfv power p tau 9 linear momentum pmv angular momentum L. Systems of particles and rotational motion 171 U. A Greek letter alpha 7.43 x 7.43 is similar to Newton's second law for linear motion expressed symbolically as F ma. Just as force produces acceleration, torque produces angular acceleration in a body. The angular acceleration is directly proportional to the applied torque and is inversely proportional to the moment of inertia of the body. In this respect, x 7.43 can be called Newton's second law for rotational motion about a fixed axis. Example 7.15 A cord of negligible mass is wound round the rim of a flywheel of mass 20 kg and radius 20 cm. A steady pull of 25 N is applied on the cord as shown in figure 7.35. The flywheel is mounted on a horizontal axle with frictionless bearings. Compute the angular acceleration of the wheel. B. Find the work done by the pull when 2 meters of the cord is unwound. C. Find also the kinetic energy of the wheel at this point. Assume that the wheel starts from rest. D. Compare answers to parts B and C. Answer Fig. 7.35 We use I Greek letter alpha Greek letter tau the torque Greek letter tau FR 25 x 0.20 nm is R 0.20 meters 5.0 nmi moment of inertia of flywheel about its axis 22 mr 220.0 0.22 x 0.4 kg and 2 Greek letter alpha angular acceleration 5.0 nm 0.4 kg and 2 12.5 s2 B work done by the pull unwinding 2 meters of the cord 25 n x 2 meters 50 jc. Let Greek letter omega be the final angular velocity. The kinetic energy gain 21 in, since the wheel starts from rest. Now, 22002, 0 Greek letter omega F Greek letter omega the angular displacement Greek letter theta length of unwound string radius of wheel 2 meters 0.2 meters 10 rad Greek letter omega 222 12 5 10 0 250 xx. Rad SD The answers are the same, that is the kinetic energy gained by the wheel work done by the force. There is no loss of energy due to friction. T7.13 Angular momentum in case of rotation about a fixed axis we have studied in section 7.7, the angular momentum of a system of particles. We already know from there that the time rate of total angular momentum of a system of particles about a point is equal to the total external torque on the system taken about the same point. When the total external torque is zero, the total angular momentum of the system is conserved. We now wish to study the angular momentum in the special case of rotation about a fixed axis. The general expression for the total angular momentum of the system of n particles is LRPXIIIN17.25b. We first consider the angular momentum of a typical particle of the rotating rigid body. We then sum up the contributions of individual particles to get L of the whole body, for a typical particle LRXP. As seen in the last section ROPOCCP figure 7.17b, with 172 physics PMV. MMXXLOCVCPV. The magnitude of the linear velocity v of the particle at P is given by v, where r is the length of CP or the perpendicular distance of P from the axis of rotation. Further, v is tangential at P to the circle which the particle describes. Using the right-hand rule one can check that CPXV is parallel to the fixed axis. The unit vector along the fixed axis chosen as the z-axis is k, hence MRMVXCPVK2 Greek letter omega k. Since Greek letter upsilon are similarly, we can check that OCXV is perpendicular to the fixed axis. Let us denote the part of L along the fixed axis, that is the z-axis, by LZ, then ZMXLCPV2 Greek letter omega k and ZMXLLOCV. We note that LZ is parallel to the fixed axis, but L is not. In general, for a particle, the angular momentum L is not along the axis of rotation. That is, for a particle, L and Greek letter omega 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 are not necessarily parallel. Compare this with the corresponding fact in translation. For a particle, P and V are always parallel to each other. For computing the total angular momentum of the whole rigid body, we add up the contribution of each particle of the body. Thus LLLOCVXI is IIM. We denote by L and ZL the components of L respectively perpendicular to the z-axis and along the z-axis. LOCVXI IIM 7.44, where m and v are respectively the mass and the velocity of the ith particle, and c is the center of the circle described by the particle, and LLKC is IIMR2 Greek letter omega micro or ZLK 7.44b. The last step follows since the perpendicular distance of the ith particle from the axis is r, and by definition the moment of inertia of the body about the axis of rotation is IM_r(I2). Note ZLLL 7.44c. The rigid bodies which we have mainly considered in this chapter are symmetric about the axis of rotation, that is, the axis of rotation is one of their symmetry axes. For such bodies, for a given OC, for every particle which has a velocity v, there is another particle of velocity v located diametrically opposite on the circle with center C described by the particle. Together such pairs will contribute 0 to L, and as a result for symmetric bodies L is 0, and hence ZLLK 7.44d. For bodies, which are not symmetric about the axis of rotation, L is not equal to LZ, and hence L does not lie along the axis of rotation. Referring to table 7.1, can you tell in which cases LLZ will not apply? Let us differentiate that. 7.44b. Since k is a fixed constant vector, we get ddddttizlk Greek letter omega micro now, ek. 7.28b states ddtl Greek letter tau Greek letter tau Greek letter tau Greek letter tau. As we have seen in the last section, only those components of the external torques which are along the axis of rotation need to be taken into account when we discuss rotation about a fixed axis. This means we can take Greek letter tau Greek letter tau Greek letter tau, since the LLL and the direction of LZ vector k is fixed. It follows that for rotation about a fixed axis, ddzt Greek letter tau lk 7.45 and d0 dtl 7.45b. Thus, for rotation about a fixed axis, the component of angular momentum perpendicular to the fixed axis is constant. As zlk, we get from x 7.45 a, ddit Greek letter omega Greek letter tau 7.45c. Systems of particles and rotational motion 173. If the moment of inertia I does not change with time, dddiitt Greek letter omega Greek letter omega Greek letter alpha, and we get from ek 7.45c, a Greek letter alpha 7.43. We have already derived this equation using the work kinetic energy rot. 7.13. Conservation of angular momentum. We are now in a position to revisit the principle of conservation of angular momentum in the context of rotation about a fixed axis. From x 7.45c, if the external torque is 0, LZ a constant 7.46 for symmetric bodies. From ek 7.44d, LZ may be replaced by L. L and LZ are respectively the magnitudes of L and LZ. This then is the required form, for fixed axis rotation, of Ek. 7.29a, which expresses the general law of conservation of angular momentum of a system of particles. Ek 7.46 applies to many situations that we come across in daily life. You may do this experiment with your friend. Sit on a swivel chair, a chair with a seat, free to rotate about a pivot with your arms folded and feet not resting on, that is, away from, the ground. Ask your friend to rotate the chair rapidly. While the chair is rotating with considerable angular speed, stretch your arms horizontally. What happens? Your angular speed is reduced. If you bring back your arms closer to your body, the angular speed increases again. This is a situation where the principle of conservation of angular momentum is applicable. If friction in the rotational mechanism is neglected, there is no external torque about the axis of rotation of the chair and hence A is constant. Stretching the arms increases I about the axis of rotation, resulting in decreasing the angular speed, Greek letter omega. Bringing the arms closer to the body has the opposite effect. A circus acrobat and a diver take advantage of this principle. Also, skaters and classical, Indian or Western, dancers performing a pirouette spinning about a tip-top on the toes of one foot display mastery over this principle. Can you explain 7.14 rolling motion? One of the most common motions observed in daily life is the rolling motion. All wheels used in transportation have rolling motion. For specificness we shall begin with the case of a disc, but the result will apply to any rolling body rolling on a level surface. We shall assume that the disc rolls without slipping. This means that at any instant of time the bottom of the disc, figure 7.36, a demonstration of conservation of angular momentum. A girl sits on a swivel chair and stretches her arms, brings her arms closer to the body. Figure 7.36b, an acrobat employing the principle of conservation of angular momentum in her performance. 174 Physics, which is in contact with the surface, is at rest on the surface. We have remarked earlier that rolling motion is a combination of rotation and translation. We know that the translational motion of a system of particles is the motion of its center of mass. Figure 7.37, the rolling motion without slipping of a disc on a level surface. Note at any instant, the point of contact P0 of the disc with the surface is at rest. The center of mass of the disc moves with velocity, vcm. The disc rotates with angular velocity about its axis, which passes through c, vcm, where r is the radius of the disc. Let vcm be the velocity of the center of mass and therefore the translational velocity of the disc. Since the center of mass of the rolling disc is at its geometric center, see figure 7.37, vcm is the velocity of c. It is parallel to the level surface. The rotational motion of the disc is about its symmetry axis, which passes through c. Thus, the velocity of any point of the disc, like p0, p1 or p2, consists of two parts. One is the translational velocity vcm and the other is the linear velocity vr on account of rotation. The magnitude of vr is vr, where Greek letter omega is the angular velocity of the rotation of the disc about the axis and r is the distance of the point from the axis, that is, from c. The velocity vr is directed perpendicular to the radius vector of the given point with respect to c in figure 7.37. The velocity of the point p2 v2 and its components vr and vcm are shown. Vr here is perpendicular to cp2. It is easy to show that vz is perpendicular to the line pop2, therefore the line passing through pon parallel to Greek letter omega, Greek letter omega, Greek letter omega, Greek letter omega, Greek letter omega is called the instantaneous axis of rotation. At po, the linear velocity, vr, due to rotation is directed exactly opposite to the translational velocity vcm. Further, the magnitude of vr here is, where r is the radius of the disc. The condition that po is instantaneously at rest requires vcm. Thus for the disc the condition for rolling without slipping is Greek letter upsilon mar 7.47. Incidentally, this means that the velocity of point p1 at the top of the disc v1 has a magnitude vcm or 2 vcm and is directed parallel to the level surface. The condition 7.47 applies to all rolling bodies. 7.14. Kinetic energy of rolling motion. Our next task will be to obtain an expression for the kinetic energy of a rolling body. The kinetic energy of a rolling body can be separated into kinetic energy of translation and kinetic energy of rotation. This is a special case of a general result for a system of particles, according to which the kinetic energy of a system of particles K can be separated into the kinetic energy of translational motion of the center of mass mv22 and kinetic energy of rotational motion about the center of mass of the system of particles K. Thus, 7.48 we assume this general result, see exercise 7.31, and apply it to the case of rolling motion. In our notation, the kinetic energy of the center of mass, that is, the kinetic energy of translation, of the rolling body is mv2 cm2, where m is the mass of the body and vcm is the center of the mass velocity. Since the motion of the rolling body about the center of mass is rotation, K represents the kinetic energy of rotation of the body, where I is the moment of inertia about the appropriate axis, which is the symmetry axis of the rolling body. The kinetic energy of a rolling body, therefore, is given by 7.49 as substituting K2 where K the corresponding radius of gyration of the body and VCMR Greek letter omega. We get our 7.49b. Systems of particles and rotational motion 175U equation 7.49b applies to any rolling body, a disk, a cylinder, a ring or a sphere. Example 7.163 bodies, a ring, a solid cylinder and a solid sphere roll down the same inclined plane without slipping. They start from rest. The radii of the bodies are identical. Which of the bodies reaches the ground with maximum velocity? Answer: we assume conservation of energy of the rolling body, that is, there is no loss of energy due to friction etc. The potential energy lost by the body in rolling down the inclined plane mgh must, therefore, be equal to kinetic energy gained. See figure 7.38. Since the bodies start from rest, the kinetic energy gained is equal to the final kinetic energy of the bodies. From X 7.49b, 2221112 kmr Greek letter upsilon, where v is the final velocity of the center of mass of the body. Equating k and mgh, figure 7.38 2221112 kmgh Greek letter upsilon or 22221 ghkr Greek letter upsilon node is independent of the mass of the rolling body, for a ring. K2R to 211 ring GH Greek letter upsilon. GH for a solid cylinder K2R to 22112 disk GH Greek letter upsilon 43 GH for a solid sphere K22R 252125 sphere GH Greek letter upsilon 107 GH. From the results obtained it is clear that among the three bodies the sphere has the greatest and the ring has the least velocity of the center of mass at the bottom of the inclined plane. Suppose the bodies have the same mass. Which body has the greatest rotational kinetic energy while reaching the bottom of the inclined plane? T summary 1. Ideally, a rigid body is one for which the distances between different particles of the body do not change, even though there are forces on them. 2. A rigid body fixed at one point or along a line can have only rotational motion. A rigid body not fixed in some way can have either pure translational motion or a combination of translational and rotational motions. 3. In rotation about a fixed axis, every particle of the rigid body moves in a circle which lies in a plane perpendicular to the axis and has its center on the axis. Every point in the rotating rigid body has the same angular velocity at any instant of time for, in pure translation, every particle of the body moves with the same velocity at any instant of time. 5. Angular velocity is a vector. Its magnitude is Greek letter omega dt and it is directed along the axis of rotation. For rotation about a fixed axis, this vector Greek letter omega 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 has a fixed direction. 176 Physics 6. The vector or cross product of two vector A and B is a vector written as AXB. The magnitude of this vector is absent and its direction is given by the right-handed screw or the right-hand rule. 7. The linear velocity of a particle of a rigid body rotating about a fixed axis is given by v Greek letter omega 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 xr, where r is the position vector of the particle with respect to an origin along the fixed axis. The relation applies even to more general rotation of a rigid body with one point fixed. In that case r is the position vector of the particle with respect to the fixed point taken as the origin. 8. The center of mass of a system of n particles is defined as the point whose position vector is rrmmii 9. Velocity of the center of mass of a system of particles is given by vpm, where p is the linear momentum of the system. The center of mass moves as if all the mass of the system is concentrated at this point and all the external forces act at it. If the total external force on the system is 0, then the total linear momentum of the system is constant. 10. The angular momentum of a system of n particles about the origin is LRPXIINI1. The torque or moment of force on a system of n particles about the origin is Greek letter tau XR phi1. The force phi acting on the nth particle includes the external as well as internal forces. Assuming Newton's third law of motion and that forces between any two particles act along the line joining the particles, we can show Greek letter tau int 0 and ddtextl Greek letter tau 11. A rigid body is in mechanical equilibrium if 1 it is in translational equilibrium, that is, the total external force on it is 0, F0I, and 2 it is in rotational equilibrium, that is, the total external torque on it is 0, Greek letter tau IIXR F0 12. The center of gravity of an extended body is that point where the total gravitational torque on the body is 0. 13. The moment of inertia of a rigid body about an axis is defined by the formula I2, where r is the perpendicular distance of the ith point of the body from the axis. The kinetic energy of rotation is 21.2 K. 14. The theorem of parallel axes, 2 allows us to determine the moment of inertia of a rigid body about an axis as the sum of the moment of inertia of the body about a parallel axis through its center of mass and the product of mass and square of the perpendicular distance between these two axes. 15. Rotation about a fixed axis is directly analogous to linear motion in respect of kinematics and dynamics. 16. For a rigid body rotating about a fixed axis, say, z-axis of rotation, LZ, where I is the moment of inertia about z-axis. In general, the angular momentum L for such a body is not along the axis of rotation. Only if the body is symmetric about the axis of rotation, L is along the axis of rotation. In that case, ZLIL Greek letter omega, the angular acceleration of a rigid body rotating about a fixed axis is given by a Greek letter tau. If the external torque Greek letter tau acting on the body is 0, the component of angular momentum about the fixed axis, say, z-axis, LZ of such a rotating body is constant. 17. For rolling motion without slipping VCM, where VCM is the velocity of translation that is of the center of mass, r is the radius and m is the mass of the body. The kinetic energy of such a rolling body is the sum of kinetic energies of translation and rotation, 221.122 cm vi Greek letter omega. Points to ponder. 1. To determine the motion of the center of mass of a system, no knowledge of internal forces of the system is required. For this purpose we need to know only the external forces on the body. 2. Separating the motion of a system of particles as the motion of the center of mass, that is, the translational motion of the system in motion about that is relative to the center of mass of the system is a useful technique in dynamics of a system of particles. One example of this technique is separating the kinetic energy of a system of particles K as the kinetic energy of the system about its center of mass K and the kinetic energy of the center of mass mv22, KKmv223. Newton's second law for finite-sized bodies or systems of particles is based in Newton's second law and also Newton's third law for particles. 4. To establish that the time rate of change of the total angular momentum of a system of particles is the total external torque in the system, we need not only Newton's second law for particles, but also Newton's third law with the provision that the forces between any two particles act along the line joining the particles. 5. The vanishing of the total external force and the vanishing of the total external torque are independent conditions. We can have one without the other. In a couple, total external force is 0, but total torque is non-zero. 6. The total torque on a system is independent of the origin if the total external force is 0. 7. The center of gravity of a body coincides with its center of mass only if the gravitational field does not vary from one part of the body to the other. 8. The angular momentum L and the angular velocity Greek letter omega 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 are not necessarily parallel vectors, however. For the simpler situations discussed in this chapter when rotation is about a fixed axis which is an axis of symmetry of the rigid body, the relation L Greek letter omega Greek letter omega Greek letter omega Greek letter omega holds good, where I is the moment of the inertia of the body about the rotation axis. Exercise of 7.1 give the location of the center of mass of a I-sphere, 2-cylinder, 3-ring, and I-cube, each of uniform mass density. Does the center of mass of a body necessarily lie inside the body? 7.2 In the HCl molecule, the separation between the nuclei of the two atoms is about 1.27 A ring 1 A ring 10 meters. Find the approximate location of the cm of the molecule, given that a chlorine atom is about 35.5 times as massive as a hydrogen atom and nearly all the mass of an atom is concentrated in its nucleus. 7.3 A child sits stationary at one end of a long trolley moving uniformly with a speed v on a smooth horizontal floor. If the child gets up and runs about on the trolley in any manner, what is the speed of the cm of the trolley child system? 7.4 Show that the area of the triangle contained between the vectors a and b is 1/2 of the magnitude of a xb. 7.5 Show that ABXC is equal in magnitude to the volume of the parallelepiped formed on the three vectors, A, B and C. 7.6 Find the components along the x, y, z axes of the angular momentum L of a particle, whose position vector is r with components x, y, z and momentum is p with components px, pi and pz. Show that if the particle moves only in the xy plane the angular momentum has only its e component. 7.72 Particles, each of mass m and speed v, travel in opposite directions along parallel lines separated by a distance d. Show that the angular momentum vector of the two-particle system is the same whatever be the point about which the angular momentum is taken. 7.8 A non-uniform bar of weight W is suspended at rest by two strings of negligible weight as shown in figure 7.39. The angles made by the strings with the vertical are 36.9 degrees and 53, x 31 degree respectively. The bar is 2 meters long. Calculate the distance d of the center of gravity of the bar from its left end. Figure 7.39. 7.9 A car weighs 1,800 kilograms. The distance between its front and back axles is 1.8 meters. Its center of gravity is 1.05 meters behind the front axle. Determine the force exerted by the level ground on each front wheel and each back wheel. 7.10 Find the moment of inertia of a sphere about a tangent to the sphere. Given the moment of inertia of the sphere about any of its diameters to be 2 mr25, where m is the mass of the sphere and r is the radius of the sphere. B. Given the moment of inertia of a disk of mass m and radius r about any of its diameters to be mr24. Find its moment of inertia about an axis normal to the disk and passing through a point on its edge. 7.11 Torques of equal magnitude are applied to a hollow cylinder and a solid sphere, both having the same mass and radius. The cylinder is free to rotate about its standard axis of symmetry, and the sphere is free to rotate about an axis passing through its center. Which of the two will acquire a greater angular speed after a given time? 7.12 A solid cylinder of mass 20 kilograms rotates about its axis with angular speed 100 rad s1. The radius of the cylinder is 0.25 meters. What is the kinetic energy associated with the rotation of the cylinder? What is the magnitude of angular momentum of the cylinder about its axis? 7.13 A child stands at the center of a turntable with his two arms outstretched. The turntable is set rotating with an angular speed of 40 rev minimum. How much is the angular speed of the child if he folds his hands back and thereby reduces his moment of inertia to 25 times the initial value assumed that the turntable rotates without friction? B. Show that the child's new kinetic energy of rotation is more than the initial kinetic energy of rotation. How do you account for this increase in kinetic energy? 7.14 A rope of negligible mass is wound round a hollow cylinder of mass 3 kilograms and radius 40 centimeters. What is the angular acceleration of the cylinder if the rope is pulled with a force of 30 N? What is the linear acceleration of the rope assumed that there is no slipping? 7.15 To maintain a rotor at a uniform angular speed of 200 rad s1, an engine needs to transmit a torque of 180 Nm. What is the power required by the engine? Note: uniform angular velocity in the absence of friction implies zero torque. In practice, applied torque is needed to counter frictional torque. Assume that the engine is 100 efficient. 7.16 From a uniform disk of radius r, a circular hole of radius r2 is cut out. The center of the hole is at r2 from the center of the original disk. Locate the center of gravity of the resulting flat body. 7.17 A meter stick is balanced on a knife edge at its center. When two coins, each of mass 5 grams, are put one on top of the other at the 12.0 centimeters mark, the stick is found to be balanced at 45.0 centimeters. What is the mass of the meter stick? 7.18 A solid sphere rolls down two different inclined planes of the same heights but different angles of inclination. A. Will it reach the bottom with the same speed in each case? B. Will it take longer to roll down one plane than the other? C. If so, which one and why? 7.19 A hoop of radius 2 meters weighs 100 kilograms. It rolls along a horizontal floor so that its center of mass has a speed of 20 centimeters s. How much work has to be done to stop it? 7.20 The oxygen molecule has a mass of 5.30 x 1026 kilograms and a moment of inertia of 1.94 x 1046 kilograms and about an axis through its center perpendicular to the lines joining the two atoms. Suppose the mean speed of such a molecule in a gas is 500 meters s and that its kinetic energy of rotation is 2/3 of its kinetic energy of translation. Find the average angular velocity of the molecule. 7.21 A solid cylinder rolls up an inclined plane of angle of inclination 30 degrees. At the bottom of the inclined plane the center of mass of the cylinder has a speed of 5 meters s. So how far will the cylinder go up the plane? B. How long will it take to return to the bottom? Additional exercise of 7.22 is shown in figure 7.40. The two sides of a step ladder BA and CA are 1.6 meters long and hinged at A. A rope to 0.5 meters is tied halfway up. A weight 40 kilograms is suspended from a point F, 1.2 meters from B along the ladder BA, assuming the floor to be frictionless and neglecting the weight of the ladder. Find the tension in the rope and forces exerted by the floor on the ladder. Take G 9.8 meters S2 hint. Consider the equilibrium of each side of the ladder separately. 180 Physics Figure 7.47.23 A man stands on a rotating platform, with his arms stretched horizontally holding a 5 kilogram weight in each hand. The angular speed of the platform is 30 revolutions per minute. The man then brings his arms close to his body with the distance of each weight from the axis changing from 90 centimeters to 20 centimeters. The moment of inertia of the man together with the platform may be taken to be constant and equal to 7.6 kilograms m2. A. What is his new angular speed? Neglect friction. B. Is kinetic energy conserved in the process? If not, from where does the change come? About 7.24. A bullet of mass 10 grams and speed 500 meters s is fired into a door and gets embedded exactly at the center of the door. The door is 1.0 meters wide and weighs 12 kilograms. It is hinged at one end and rotates about a vertical axis practically without friction. Find the angular speed of the door just after the bullet embeds into it. Hint: the moment of inertia of the door about the vertical axis at one end is ml23, 7.252 disks of moments of inertia I1 and I2 about their respective axes normal to the disk and passing through the center, and rotating with angular speeds Greek letter omega 1 and Greek letter omega 2 are brought into contact face to face with their axes of rotation coincident. A. What is the angular speed of the two-disk system? B. Show that the kinetic energy of the combined system is less than the sum of the initial kinetic energies of the two disks. How do you account for this loss in energy? Take Greek letter omega 1 Greek letter omega 2, 7.26. Prove the theorem of perpendicular axes. Hint: square of the distance of a point x, y in the xy plane from an axis through the origin and perpendicular to the plane is x2 y2. B. Prove the theorem of parallel axes. Hint: if the center of mass of a system of n particles is chosen to be the origin mi are 0. 7.27. Prove the result that the velocity v of translation of a rolling body like a ring, disk, cylinder or sphere at the bottom of an inclined plane of a height h is given by 22221 GHVKR using dynamical consideration, that is, by consideration of forces and torques. Note k is the radius of gyration of a body about its symmetry axis, and r is the radius of the body. The body starts from rest at the top of the plane 7.28. A disk rotating about its axis with angular speed O is placed lightly without any translational push on a perfectly frictionless table. The radius of the disk is r watt. Systems of particles and rotational motion. 181 are the linear velocities of the points A, B and C on the disk shown in Fig. 7.41. Will the disk roll in the direction indicated? Figure 7.41. 7.29. Explain why friction is necessary to make the disk in Fig. 7.41. Roll in the direction indicated. A. Give the direction of frictional force at B, and the sense of frictional torque, before perfect rolling begins. B. What is the force of friction after perfect rolling begins? 7.30. A solid disk and a ring, both of radius 10 centimeters, are placed on a horizontal table simultaneously, with initial angular speed equal to 10 Greek letter pi rad s1. Which of the two will start to roll earlier? The coefficient of kinetic friction is micro k 0.2. 7.31. A cylinder of mass 10 kilograms and radius 15 centimeters is rolling perfectly on a plane of inclination 30. The coefficient of static friction micro 0.25. A. How much is the force of friction acting on the cylinder? B. What is the work done against friction during rolling? C. If the inclination Greek letter theta of the plane is increased, at what value of Greek letter theta does the cylinder begin to skid, and not roll perfectly? 7.32. Read each statement below carefully and state, with reasons, if it is true or false. A. During rolling, the force of friction acts in the same direction as the direction of motion of the cm of the body. B. The instantaneous speed of the point of contact during rolling is 0. C. The instantaneous acceleration of the point of contact during rolling is 0. D. For perfect rolling motion, work done against friction is 0. E. A wheel moving down a perfectly frictionless inclined plane will undergo slipping, not rolling motion. 7.33. Separation of motion of a system of particles into motion of the center of mass and motion about the center of mass. A. Show ppvim where pi is the momentum of the ith particle of mass mi and pimivi. Note vi is the velocity of the ith particle relative to the center of mass. Also, prove using the definition of the center of mass pi 0. B. Show 2.5 kmv where k is the total kinetic energy of the system of particles. K is the total kinetic energy of the system when the particle velocities are taken with respect to the center of mass, and mv22 is the kinetic energy of the translation of the system as a whole, that is, of the center of mass motion of the system. The result has been used in Sec 7.14. C. Show LLRVXM where LXRPII is the angular momentum of the system about the center of mass with 182 physics velocities taken relative to the center of mass. Remember IIRRR. Rest of the notation is the standard notation used in the chapter. Note L and MXRV can be said to be angular momenta, respectively, about and of the center of mass of the system of particles. D. Show DDT further. Show that DDTEXTL Greek letter tau where X Greek letter tau is the sum of all external torques acting on the system about the center of mass. Hint: use the definition of center of mass and third law of motion. Assume the internal forces between any two particles act along the line joining the particles. Pluto, a dwarf planet. The International Astronomical Union (IAU) at the IAU 2006 General Assembly held on August 24, 2006, in Prague in Czech Republic, adopted a new definition of planets in our solar system. According to the new definition, Pluto is no longer a planet. This means that the solar system consists of 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. According to the IAU usage, the planet and other bodies in our solar system, except satellites, are to be defined into 3 distinct categories of celestial objects in the following way. 1. A planet is a celestial body that A is in orbit around the Sun, B has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium nearly round shape, and C has cleared the neighborhood around its orbit. 2. A dwarf planet is a celestial body that A is in orbit around the Sun, B has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium nearly round shape, C has not cleared the neighborhood around its orbit, and D is not a satellite. 3. All other objects, except satellites, orbiting the Sun, shall be referred to collectively as small solar system bodies. Unlike other 8 planets in the solar system, Pluto's orbital path overlaps with other objects than the planet Neptune. The other objects currently include most of the solar system asteroids, most of the trans-Neptunian objects TNOs, comets, and other small bodies. Pluto is a dwarf planet by the above definition and is recognized as the prototype of a new category of trans-Neptunian objects. Chapter 8 Gravitation 8.1 Introduction. Early in our lives, we become aware of the tendency of all material objects to be attracted towards the Earth. Anything thrown up falls down towards the Earth. Going uphill is a lot more tiring than going downhill. Raindrops from the clouds above fall towards the Earth, and there are many other such phenomena. Historically, it was the Italian physicist Galileo (1564–1642) who recognized the fact that all bodies, irrespective of their masses, are accelerated towards the Earth with a constant acceleration. It is said that he made a public demonstration of this fact. To find the truth, he certainly did experiments with bodies rolling down inclined planes and arrived at a value of the acceleration due to gravity which is close to the more accurate value obtained later. A seemingly unrelated phenomenon, observation of stars, planets and their motion, has been the subject of attention in many countries since the earliest of times. Observation since early times recognized stars which appeared in the sky with positions unchanged year after year. The more interesting objects are the planets which seem to have regular motions against the background of stars. The earliest recorded model for planetary motions proposed by Ptolemy about 2,000 years ago was a geocentric model in which all celestial objects, stars, the Sun and the planets, all revolved around the Earth. The only motion that was thought to be possible for celestial objects was motion in a circle. Complicated schemes of motion were put forward by Ptolemy in order to describe the observed motion of the planets. The planets were described as moving in circles with the center of the circles themselves moving in larger circles. Similar theories were also advanced by Indian astronomers some 400 years later. However, a more elegant model in which the Sun was the center around which the planets revolved, the heliocentric model, was already mentioned by Aryabhata 5th century AD in his treatise. 1,000 years later, a Polish monk named Nicholas 8.1 Introduction 8.2 Kepler's Laws 8.3 Universal Law of Gravitation 8.4 The Gravitational Constant 8.5 Acceleration due to gravity of the Earth 8.6 Acceleration due to gravity below and above the surface of Earth 8.7 Gravitational Potential Energy 8.8 Escape Speed 8.9 Earth Satellites 8.10 Energy of an Orbiting Satellite 8.11 Geostationary and Polar Satellites 8.12 Weightlessness Summary Points to Ponder Exercises Additional exercises 184 Physics BACPSS 2B2 Copernicus 1473–1543 proposed a definitive model in which the planets moved in circles around a fixed central sun. His theory was discredited by the Church, but notable amongst its supporters was Galileo, who had to face prosecution from the state for his beliefs. It was around the same time as Galileo, a nobleman called Tycho Brahe 1546–1601 hailing from Denmark, spent his entire lifetime recording observations of the planets with the naked eye. His compiled data were analyzed later by his assistant Johannes Kepler 1571–1640. He could extract from the data 3 elegant laws that now go by the name of Kepler's laws. These laws were known to Newton and enabled him to make a great scientific leap in proposing his universal law of gravitation. 8.2 Kepler's laws. The 3 laws of Kepler can be stated as follows. 1. Law of orbits. All planets move in elliptical orbits with the Sun situated at one of the foci Fig. 8.1 An ellipse traced out by a planet around the Sun. The closest point is P and the farthest point is A. P is called the perihelion and A the aphelion. The semi-major axis is half the distance AP. Figure 8.1b drawing an ellipse. A string has its ends fixed at F1 and F2. The tip of a pencil holds the string taut and is moved around of the ellipse. Figure 8.1a. This law was a deviation from the Copernican model which allowed only circular orbits. The ellipse, of which the circle is a special case, is a closed curve which can be drawn very simply as follows. Select 2 points F1 and F2, take a length of a string and fix its ends at F1 and F2 by pins. With the tip of a pencil stretch the string taut and then draw a curve by moving the pencil keeping the string taut throughout. Fig. 8.1b The closed curve you get is called an ellipse. Clearly for any point T on the ellipse, the sum of the distances from F1 and F2 is a constant. F1, F2 are called the foci. Join the points F1 and F2 and extend the line to intersect the ellipse at points P and A as shown in Fig. 8.1b. The midpoint of the line PA is the center of the ellipso and the length POAO is called the semi-major axis of the ellipse. For a circle, the two foci merge into one and the semi-major axis becomes the radius of the circle. 2. Law of areas. The line that joins any planet to the Sun sweeps equal areas in equal intervals of time. Fig. 8.2. This law comes from the observations that planets appear to move slower when they are farther from the Sun than when they are nearer. Figure 8.2 The planet P moves around the Sun in an elliptical orbit. The shaded area is the area A swept out in a small interval of time t. 3. Law of periods. The square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. Table 8.1 gives the approximate time periods of revolution of 8 planets around the Sun along with values of their semi-major axes. Refer to information given in the box on page 182. Gravitation 185T Table 8.1 Data from measurement of planetary motions given below confirm Kepler's law of periods. A semi-major axis in units of 1010 meters. T time period of revolution of the planet in years y. Q the quotient T2 a 3 in units of 1034 y 2 meters 3. Planet at TQ Mercury 5.790.24 2.95 Venus 10.80.615 3.00 Earth 15.01 2.96 Mars 22.81.88 2.98 Jupiter 77.8 11.9 3.01 Saturn 143 29.5 2.98 Uranus 287 84 2.98 Neptune 450 165 2.99 Pluto 590 248 2.99 The law of areas can be understood as a consequence of conservation of angular momentum. WHCH is valid for any central force. A central force is such that the force on the planet is along the vector joining the Sun and the planet. Let the Sun be at the origin and let the position and momentum of the planet be denoted by r and p respectively. Then the area swept out by the planet of mass m in time interval t is figure 8.2a given by a 1/2 rx vt 8.1 hence at 1/2 rx pm. Since Vpm L2 meters 8.2 where V is the velocity, L is the angular momentum equal to Rxp. For a central force, which is directed along R, L is a constant as the planet goes around, hence, At is a constant according to the last equation. This is the law of areas. Gravitation is a central force and hence the law of areas follows. Example 8.1 Let the speed of the planet at the perihelion P in Fig. 8.1 be Vp and the Sun planet distance SPBRP, relate Rp, Vp to the corresponding quantities at the aphelion Ra, Va. Will the planet take equal times to traverse Bach and CPB? Answer the magnitude of the angular momentum at P is LPMPRP Vp. Since inspection tells us that Rp and Vp are mutually perpendicular, similarly, LAMP Rava, from angular momentum conservation MPRP Vp MP Rava or VVPARRAPT since Ra, Rp, Vp, Va, the area SBAC bounded by the ellipse and the radius vectors SB and SC is larger than SBPC in Fig. 8.1. From Kepler's second law, equal areas are swept in equal times, hence the planet will take a longer time to traverse Bach than CPB. 8.3 Universal law of gravitation legend has it that observing an apple falling from a tree, Newton was inspired to arrive at an universal law of gravitation that led to an explanation of terrestrial gravitation as well as of Kepler's laws. Newton's reasoning was that the Moon revolving in an orbit of radius rm was subject to a centripetal acceleration due to Earth's gravity of magnitude 22.24 meters mmRVRT Greek letter pi 8.3 where v is the speed of the Moon related to the time period t, by the relation 2mVr. The time period t is about 27.3 days and rm was already known then to be about 3.84 x 108 meters, if we substitute these numbers in ek. 8.3. We get a value of m much smaller than the value of acceleration due to gravity g on the surface of the Earth, arising also due to Earth's gravitational attraction. Johannes Kepler 1571-1630, was a scientist of German origin. He formulated the 3 laws of planetary motion based on the painstaking observations of Tycho Brahe and co-workers. Kepler himself was an assistant to Brahe, and it took him 16 long years to arrive at the 3 planetary laws. He is also known as the founder of geometrical optics, being the first to describe what happens to light after it enters a telescope. Refer to information given in the box on page 182. Central forces. We know the time rate of change of the angular momentum of a single particle about the origin is d dt xlrf. The angular momentum of the particle is conserved. If the torque xr Greek letter tau due to the force F on it vanishes, this happens either when F is 0 or when F is a long r. We are interested in forces which satisfy the latter condition. Central forces satisfy this condition. A central force is always directed towards or away from a fixed point, that is, along the position vector of the point of application of the force with respect to the fixed point. See figure below. Further, the magnitude of a central force F depends on r, the distance of the point of application of the force from the fixed point, FFr. In the motion under a central force, the angular momentum is always conserved. 2 important results follow from this. 1. The motion of a particle under the central force is always confined to a plane. 2. The position vector of the particle with respect to the center of the force, that is the fixed point, has a constant areal velocity. In other words, the position vector sweeps out equal areas in equal times as the particle moves under the influence of the central force. Try to prove both these results. You may need to know that the areal velocity is given by d dt 1/2 rv sin Greek letter alpha. An immediate application of the above discussion can be made to the motion of a planet under the gravitational force of the Sun. For convenience, the Sun may be taken to be so heavy that it is at rest. The gravitational force of the Sun on the planet is directed towards the Sun. This force also satisfies the requirement FFr, since Fg m1 meters 2r to where m1 and m2 are respectively the masses of the planet and the Sun, and g is the universal constant of gravitation. The 2 results 1 and 2 described above, therefore, apply to the motion of the planet. In fact, the result 2 is the well-known second law of Kepler. Tr is the trajectory of the particle under the central force. At a position P, the force is directed along OP. O is the center of the force taken as the origin. In time t, the particle moves from P to P, rppsvt. The tangent PQ at P to the trajectory gives the direction of the velocity at P. The area swept in T is the area of sector Popson, or Greek letter alpha, pages 2 rv sin T2. Gravitation 187T. This clearly shows that the force due to Earth's gravity decreases with distance. If one assumes that the gravitational force due to the Earth decreases in proportion to the inverse square of the distance from the center of the Earth, we will have m Greek letter alpha 2 mr, g Greek letter alpha 2 er, and we get 2 meters mergr 3608.4 inches, agreement with the value of g 9.8 meters s2 and the value of m from Ek. 8.3. These observations led Newton to propose the following universal law of gravitation. Every body in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The quotation is essentially from Newton's famous treatise called Mathematical Principles of Natural Philosophy, Principia for short. Stated mathematically, Newton's gravitation law reads, the force F on a point mass m2 due to another point mass m1 has the magnitude 122 mmgrf. 8.5. Equation 8.5 can be expressed in vector form as 12122 mmmmggrrfrr 123 mmgrr, where g is the universal gravitational constant, r is the unit vector from m1 to m2, and rr to r1 as shown in Fig. 8.3. The gravitational force is attractive, that is, the force F is along, r the force on point mass m1 due to m2 is of course, F by Newton's third law. Thus, the gravitational force F12 on the body 1 due to 2 and F21 on the body 2 due to 1 are related as F12 F21. Before we can apply Ek 8.5 to objects under consideration, we have to be careful since the law refers to point masses, whereas we deal with extended objects which have finite size. If we have a collection of point masses, the force on any one of them is the vector sum of the gravitational forces exerted by the other point masses as shown in Figure 8.4. Figure 8.4. Gravitational force on point mass m1 is the vector sum of the gravitational forces exerted by m2, m3 and m4. The total force on m1 is 211,221 gmmrf 3121 231 gmmrr 4131 41 241 gmmrr. Example 8.23. Equal masses of mkg each are fixed at the vertices of an equilateral triangle ABC. A. What is the force acting on a mass 2 meters placed at the centroid of the triangle B? What is the force if the mass at the vertex A is double take AGBGCG 1 meters see Fig. 8.5 Answer. The angle between GC and the positive x-axis is 30 degrees and so is the angle between GB and the negative x-axis. The individual forces in vector notation are Figure 8.3. Gravitational force on M1 due to M2 is along R where the vector R is R2 R1. Capital O. 188 Physics B. Now if the mass at vertex A is doubled nt for the gravitational force between an extended object like the Earth and a point mass, Ek. 8.5 is not directly applicable. Each point mass in the extended object will exert a force on the given point mass and these forces will not all be in the same direction. We have to add up these forces vectorially for all the point masses in the extended object to get the total force. This is easily done using calculus, for two special cases. A simple law results when you do that. 1. The force of attraction between a hollow spherical shell of uniform density and a point mass situated outside is just as if the entire mass of the shell is concentrated at the center of the shell. Qualitatively this can be understood as follows. Gravitational forces caused by the various regions of the shell have components along the line joining the point mass to the center as well as along a direction perpendicular to this line. The components perpendicular to this line cancel out when summing over all regions of the shell leaving only a resultant force along the line joining the point to the center. The magnitude of this force works out to be as stated above. Newton's Principia Kepler had formulated his third law by 1619. The announcement of the underlying universal law of gravitation came about 70 years later with the publication in 1687 of Newton's masterpiece Philosophiae Naturalis Principia Mathematica. Often simply called the Principia. Around 1685, Edmund Halley, after whom the famous Halley's Comet is named, came to visit Newton at Cambridge and asked him about the nature of the trajectory of a body moving under the influence of an inverse square law. Without hesitation Newton replied that it had to be an ellipse, and further that he had worked it out long ago around 1665 when he was forced to retire to his farmhouse from Cambridge on account of a plague outbreak. Unfortunately, Newton had lost his papers. Halley prevailed upon Newton to produce his work in book form and agreed to bear the cost of publication. Newton accomplished this feat in 18 months of superhuman effort. The Principia is a singular scientific masterpiece and in the words of Lagrange it is the greatest production of the human mind. The Indian-born astrophysicist and Nobel laureate S. Chandrasekhar spent 10 years writing a treatise on the Principia. His book, Newton's Principia for the common reader, brings into sharp focus the beauty, clarity and breathtaking economy of Newton's methods. Figure 8.53 Equal masses are placed at the three vertices of the ABC. A mass 2 meters is placed at the centroid G. GA21 GMMFJ GB2 cos 30 sin 31 GMM Greek letter Omicron FIJ GC2 cos 30 sin 31 GMM Greek letter Omicron FIJ. From the principle of superposition and the law of vector addition, the resultant gravitational force 4 on 2 meters is 4 FGAFGBFGC Greek letter Omicron 30 sin 30 cos 2 22 RJI GM 0 30 sin 30 cos 2 Greek letter Omicron JIGM. Alternatively, one expects on the basis of symmetry that the resultant force ought to be 0. Gravitation 189 2. The force of attraction due to a hollow spherical shell of uniform density, on a point mass situated inside it is 0. Qualitatively, we can again understand this result. Various regions of the spherical shell attract the point mass inside it in various directions. These forces cancel each other completely. 8.4 The gravitational constant. The value of the gravitational constant G entering the universal law of gravitation can be determined experimentally, and this was first done by English scientist Henry Cavendish in 1798. The apparatus used by him is schematically shown in Figure 8.6. Figure 8.6 Schematic drawing of Cavendish's experiment. S1 and S2 are large spheres which are kept on either side, shown shades of the masses at A and B. When the big spheres are taken to the other side of the masses shown by dotted circles. The bar AB rotates a little since the torque reverses direction. The angle of rotation can be measured experimentally. The bar AB has two small lead spheres attached at its ends. The bar is suspended from a rigid support by a fine wire. Two large lead spheres are brought close to the small ones but on opposite sides as shown. The big spheres attract the nearby small ones by equal and opposite force as shown. There is no net force on the bar but only a torque which is clearly equal to F times the length of the bar, where F is the force of attraction between a big sphere and its neighboring small sphere. Due to this torque, the suspended wire gets twisted till such time as the restoring torque of the wire equals the gravitational torque. If Greek letter theta is the angle of twist of the suspended wire, the restoring torque is proportional to Greek letter theta, equal to Greek letter tau Greek letter theta. where Greek letter tau is the restoring couple per unit angle of twist. Greek letter tau can be measured independently, e.g. by applying a known torque and measuring the angle of twist. The gravitational force between the spherical balls is the same as if their masses are concentrated at their centers. Thus if d is the separation between the centers of the big and its neighboring small ball, m and n their masses, the gravitational force between the big sphere and its neighboring small ball is 2 mm FGD 8.6. If L is the length of the bar AB, then the torque arising out of F is F multiplied by L at equilibrium. This is equal to the restoring torque and hence 2 mm GLD. Greek letter tau, Greek letter theta 8.7. Observation of Greek letter theta thus enables one to calculate G from this equation. Since Cavendish's experiment, the measurement of G has been refined and the currently accepted value is G 6.67 x 1011 nm 2 kg 2 8.8.5 acceleration due to gravity of the Earth. The Earth can be imagined to be a sphere made of a large number of concentric spherical shells with the smallest one at the center and the largest one at its surface. A point outside the Earth is obviously outside all the shells, thus, all the shells exert a gravitational force at the point outside just as if their masses are concentrated at their common center according to the results stated in section 8.3. The total mass of all the shells combined is just the mass of the Earth, hence, at a point outside the Earth, the gravitational force is just as if its entire mass of the Earth is concentrated at its center. For a point inside the Earth, the situation is different. This is illustrated in figure 8.7. 190 Physics Figure 8.7. The mass m is in a mine located at a depth d below the surface of the Earth of mass m and radius r. We treat the Earth to be spherically symmetric. Again, consider the Earth to be made up of concentric shells as before and a point mass m situated at a distance r from the center. The point P lies outside the sphere of radius r. For the shells of radius greater than r, the point P lies inside. Hence, according to results stated in the last section, they exert no gravitational force on mass m kept at P. The shells with radius r make up a sphere of radius r for which the point P lies on the surface. This smaller sphere therefore exerts a force on a mass m at P as if its mass Mr is concentrated at the center. Thus the force on the mass m at P has a magnitude r2 gmmfr 8.9. We assume that the entire Earth is of uniform density and hence its mass is 3e43 mr. Greek letter pi, Greek letter rho, where m is the mass of the Earth, 3 is its radius, and Greek letter rho is the density. On the other hand, the mass of the sphere Mr of radius r is 34.3 r, Greek letter pi, Greek letter rho, and hence e3 egmmr 8.10 if the mass m is situated on the surface of Earth. Then r and the gravitational force on it is, from Ek 8.10 to EEMMFGR 8.11. The acceleration experienced by the mass m, which is usually denoted by the symbol g, is related to F by Newton's second law by relation Fmg. Thus 2 EEGMFGMR 8.12 acceleration g is readily measurable. R is a known quantity. The measurement of g by Cavendish's experiment or otherwise, combined with knowledge of g and r, enables one to estimate me from Ek. 8.12. This is the reason why there is a popular statement regarding Cavendish. Cavendish weighed the Earth. 8.6 Acceleration due to gravity below and above the surface of Earth. Consider a point mass m at a height h above the surface of the Earth as shown in Fig. 8.8. The radius of the Earth is denoted by r, since this point is outside the Earth. Fig. 8.8 g at a height h above the surface of the Earth. Its distance from the center of the Earth is r h. If Fh denoted the magnitude of the force on the point mass m, we get from Ek 8.5 to EEGMMFHRH 8.13 the acceleration experienced by the point mass is FHMGH, and we get Mr. Gravitation 191 to EEGMFHGHMRH 8.14. This is clearly less than the value of g on the surface of Earth. 2.EEGMGR4 AR. We can expand the RHS of Ek. 8.14 22211 EEGMGHGHRRHR for 1 EHR, using binomial expression, GHGH12. 8.15 Equation 8.15 thus tells us that for small heights h above the value of g decreases by a factor 1 2.AR. Now, consider a point mass m at a depth d below the surface of the Earth. Figure 8.8b, so that its distance from the center of the Earth is ERD as shown in the figure. The Earth can be thought of as being composed of a smaller sphere of radius r, d, and a spherical shell of thickness d. The force on m due to the outer shell of thickness d is 0 because the result quoted in the previous section. As far as the smaller sphere of radius r, d is concerned, the point mass is outside it and hence according to the result quoted earlier. The force due to this smaller sphere is just as if the entire mass of the smaller sphere is concentrated at the center. If m is the mass of the smaller sphere, then ms m r d3 r3 8.16 since mass of a sphere is proportional to b cube of its radius. Figure 8.8 bg at a depth d. In this case only the smaller sphere of radius rad contributes to g. Thus the force on the point mass is Fdg m's Emery, d2 8.17 substituting for m's from above. We get Fdg me Emery, d3 8.18 and hence the acceleration due to gravity at a depth d. GdFdm is 3 EEGMFdGdRdmr1 EERdGgdRr 8.19 thus. As we go down below Earth's surface, the acceleration due to gravity decreases by a factor 1.r. The remarkable thing about acceleration due to Earth's gravity is that it is maximum on its surface, decreasing whether you go up or down. 8.7 Gravitational potential energy. We had discussed earlier the notion of potential energy as being the energy stored in the body at its given position. If the position of the particle changes on account of forces acting on it, then the change in its potential energy is just the amount of work done on the body by the force. As we had discussed earlier, forces for which the work done is independent of the path are the conservative forces. The force of gravity is a conservative force and we can calculate the potential energy of a body arising out of this force, called the gravitational potential energy. Consider points close to the surface of Earth, at distances from the surface much smaller than the radius of the Earth. In such cases, the force of gravity is practically a constant equal to mg, directed towards the center of the Earth. If we consider a point at a height h1 from the surface of the Earth and another point vertically above it at a height h2 from the surface, the work done in lifting the particle of mass m from the first to the second position is denoted by W12 force x displacement mgh2 h1 8.20 msme. 192 Physics T. If we associate a potential energy WH at a point at a height h above the surface such that WH-mgh-wo 8.21 where wo constant, then it is clear that W12 WH2 WH1 8.2 to the work done in moving the particle is just the difference of potential energy between its final and initial positions. Observe that the constant wo cancels out in ek. 8.22. Setting h0 in the last equation, we get WH0 wo h0 means points on the surface of the Earth. Thus, wo is the potential energy on the surface of the Earth, if we consider points at arbitrary distance from the surface of the Earth. The result just derived is not valid since the assumption that the gravitational force mg is a constant is no longer valid. However, from our discussion we know that a point outside the Earth, the force of gravitation on a particle directed towards the center of the Earth is 2 EgMMFr 8.23 where m e mass of Earth, m mass of the particle and r its distance from the center of the Earth. If we now calculate the work done in lifting a particle from r1 to r to r2, r1 along a vertical path, we get instead of ek 8.20 WGMMRRR 12212 DGMMRE1121 8.24 in place of ek 8.21, we can thus associate a potential energy WR at a distance r, such that E1, GMMWR WR 8.25 valid for r, so that once again W12 WR2 WR1. Setting r infinity in the last equation, we get WR infinity W1, thus, W1 is the potential energy at infinity. One should note that only the difference of potential energy between 2 points has a definite meaning from EQS. 8.22 and 8.24, one conventionally sets W1 equal to 0, so that the potential energy at a point is just the amount of work done in displacing the particle from infinity to that point. We have calculated the potential energy at a point of a particle due to gravitational forces on it due to the Earth and it is proportional to the mass of the particle. The gravitational potential due to the gravitational force of the Earth is defined as the potential energy of a particle of unit mass at that point. From the earlier discussion, we learned that the gravitational potential energy associated with two particles of masses m1 and m2 separated by a distance r is given by 12 gmmvr. If we choose v0 as r, it should be noted that an isolated system of particles will have the total potential energy that equals the sum of energies given by the above equation for all possible pairs of its constituent particles. This is an example of the application of the superposition principle. Example 8.3. Find the potential energy of a system of 4 particles placed at the vertices of a square of side L. Also obtain the potential at the center of the square. Answer: consider 4 masses each of mass m at the corners of a square of side L. See Fig. 8.9. We have 4 mass pairs at distance L and 2 diagonal pairs at distance 2 liters, hence 2 G4 2 meters GMWRLL. Fig. 8.9. Gravitation 193 TLMG 22.5.412122. The gravitational potential at the center of the square r 2 liters 2 is LMG2 RU4. T8.8 escape speed. If a stone is thrown by hand, we see it falls back to the earth. Of course, using machines we can shoot an object with much greater speeds and with greater and greater initial speed. The object scales higher and higher heights. A natural query that arises in our mind is the following: can we throw an object with such high initial speeds that it does not fall back to the Earth? The principle of conservation of energy helps us to answer this question. Suppose the object did reach infinity and that its speed there was Vf. The energy of an object is the sum of potential and kinetic energy, as before. W1 denotes the gravitational potential energy of the object at infinity. The total energy of the projectile at infinity then is 212 FMVEW 8.26 if the object was thrown initially with a speed v from a point at a distance h from the center of the Earth radius of the Earth. Its energy initially was 2112 EEIEGMMEHRMVWHR 8.27 by the principle of energy conservation EQS. 8.26 and 8.27 must be equal, hence 2222 FEEMVMVGMMHR 8.28. The RHS is a positive quantity with a minimum value 0, hence so must be the LHS. Thus, an object can reach infinity as long as the I is such that 202 IEMVGMMHR 8.29, the minimum value of VI, corresponds to the case when the LHS of EC 8.29 equals 0. Thus, the minimum speed required for an object to reach infinity, that is, escape from the Earth, corresponds to 2 minutes 12 EIEGMMMVHR 8.30 if the object is thrown from the surface of the Earth. H0, and we get min 2 EIEGMVR 8.31 using the relation 2 EIGMR. We get min 2 IFGR 8.32 using the value of G and E, numerically V min 11.2 km s. This is called the escape speed, sometimes loosely called the escape velocity. Equation 8.32 applies equally well to an object thrown from the surface of the Moon with g replaced by the acceleration due to Moon's gravity on its surface and replaced by the radius of the Moon. Both are smaller than their values on Earth, and the escape speed for the Moon turns out to be 2.3 km s, about 5 times smaller. This is the reason that Moon has no atmosphere. Gas molecules if formed on the surface of the Moon having velocities larger than this will escape the gravitational pull of the Moon. Example 8.42 Uniform solid spheres of equal radii r, but mass m and 4m have a center-to-center separation 6r, as shown in Fig. 8.10. The two spheres are held fixed. A projectile of mass m is projected from the surface of the sphere of mass m directly towards the center of the second sphere. Obtain an expression for the minimum speed v of the projectile so that it reaches the surface of the second sphere. Figure 8.10 Answer: the projectile is acted upon by two mutually opposing gravitational forces of the two 194 physics spheres. The neutral point NC. Figure 8.10 is defined as the position where the two forces cancel each other exactly. If on R, we have 22 r 6 meters mgr mg 4 6r, r2 4 r2 6r, r plus or minus 2 r r2 r 6r. The neutral point r6r does not concern us in this example. Thus on r2r, it is sufficient to project the particle with a speed which would enable it to reach n thereafter. The greater gravitational pull of 4m would suffice. The mechanical energy at the surface of m is rmmgrmmgvme2I5421. At the neutral point n, the speed approaches 0. The mechanical energy at n is purely potential. rmmgrmmgen442. From the principle of conservation of mechanical energy 1242 volt GMR 25 or 21542 RMGVT8. To notice that the speed of the projectile is 0 at n, but is non-zero when it strikes the heavier sphere 4m. The calculation of this speed is left as an exercise to the students. 8.9 Earth satellites. Earth satellites are objects which revolve around the Earth. Their motion is very similar to the motion of planets around the Sun, and hence Kepler's laws of planetary motion are equally applicable to them. In particular, their orbits around the Earth are circular or elliptic. Moon is the only natural satellite of the Earth with a near-circular orbit with a time period of approximately 27.3 days, which is also roughly equal to the rotational period of the Moon about its own axis. Since 1957, advances in technology have enabled many countries including India to launch artificial Earth satellites for practical use in fields like telecommunication, geophysics and meteorology. We will consider a satellite in a circular orbit of a distance r(h) from the center of the Earth, where r radius of the Earth. If m is the mass of the satellite and v its speed, the centripetal force required for this orbit is F centripetal 2 EMVRH 8.33 directed towards the center. This centripetal force is provided by the gravitational force, which is F gravitation 2 EEGMMRH 8.34, where m is the mass of the Earth. Equating RHS of EQS 8.33 and 8.34 and cancelling out m, we get 2 EEGMVRH 8.35, thus v decreases as h increases. From equation 8.35, the speed v for h0 is 20 E of hgmrgr 8.36, where we have used the relation g2 EGMR. In every orbit, the satellite traverses a distance to Greek letter pi h with speed v. Its time period t therefore is 322 EERHRHTBGM Greek letter pi 8.37 on substitution of value of v from ek. 8.35, squaring both sides of ek 8.37, we get E2k H3 where k4 Greek letter pi to GME 8.38 which is Kepler's law of periods, as applied to motion of satellites around the Earth. For a satellite very close to the surface of Earth h can be neglected in comparison to re and ek. 8.38, hence, for such satellites, t is 2, where 0 to ETR 8.39 if we substitute the numerical values g 9.8 meters s2 and re 6,400 kilometers, we get 606.410 9.8 t Greek letter pi xs which is approximately 85 minutes. Gravitation 195 TTT Example 8.5 The planet Mars has two moons, Phobos and Deimos I. Phobos has a period 7 hours, 39 minutes and an orbital radius of 9.4 x 103 kilometers. Calculate the mass of Mars to assume that Earth and Mars move in circular orbits around the Sun, with the Martian orbit being 1.52 times the orbital radius of the Earth. What is the length of the Martian year and days? Answer I. We employ ek 8.38 with the Sun's mass replaced by the Martian mass mmTGMR 2 meters 423 Greek letter pi mmGRT 4232 Greek letter pi xxxxxxx 43.146.6710 459 60 11 223 18 9 410 M43.146.67 4.59 610 25 meters xxxxxxx 23 18 9 410 6.48 x 1023 kilograms. 2 Once again Kepler's third law comes to our aid. TTR RM2E2 MS3 ES3 where RMS is the Mars-Sun distance and Reg is the Earth-Sun distance. TM 1.5232 x 365 684 days. We note that the orbits of all planets except Mercury, Mars and Pluto are very close to being circular. For example, the ratio of the semi-minor to semi-major axis for our Earth is via 0.99986 t. Example 8.6 Weighing the Earth, you are given the following data, G 9.81 ms2. Re 6.37 x 106 meters, the distance to the Moon R 3.84 x 108 meters and the time period of the Moon's revolution is 27.3 days. Obtain the mass of the Earth ME in 2 different ways. Answer from ek 8.12 we have GRGM2EEXXX 9.81 6.3710 6.6710 6 to 11 5.97 x 1024 kilograms. The Moon is a satellite of the Earth, from the derivation of Kepler's third law see ek. 8.38 mGRT 3224 Greek letter pi 2324 TGRME Greek letter pi xxxxxxxxxxx 43.143.143.84 10 6.67 10 27.324 60 63 24 11 2x 6.02 10 24 kilograms. Both methods yield almost the same answer, the difference between them being less than 1. T. Example 8.7 Express the constant k of ek. 8.38 inches days in kilometers, given K10-13 S2 M3, the Moon is at a distance of 3.84 x 105 kilometers from the Earth. Obtain its time period of revolution in days. Answer given K10-13 S2 M3 10 D1 kilometers XX 13 2233 24 60 61 1001.33 x 10-14 D2 kilometers 3 using ek. 8.38 and the given value of k, the time period of the Moon is T2 1.33 x 1014 3.84 x 105 3t 27.3 dt. Note that ek. 8.38 also holds for elliptical orbits if we replace Rh by the semi-major axis of the ellipse. The Earth will then be at one of the foci of this ellipse. 8.10 Energy of an orbiting satellite using ek. 8.35 The kinetic energy of the satellite in a circular orbit with speed v is 21.2 kemvi2 eegmmrh. 8.40 Refer to information given in the box on page 182. 196 Physics T. Considering gravitational potential energy at infinity to be zero, the potential energy at distance REH from the center of the Earth is EEGMMPERH 8.41 The KE is positive whereas the PE is negative, however. In magnitude the KE is half the PE, so that the total E is 2 EEGMMEKEPERH 8.42 The total energy of an circularly orbiting satellite is thus negative. With the potential energy being negative but twice as magnitude of the positive kinetic energy, when the orbit of a satellite becomes elliptic. Both the KE and PE vary from point to point. The total energy which remains constant is negative as in the circular orbit case. This is what we expect. Since as we have discussed before if the total energy is positive or zero, the object escapes to infinity. Satellites are always at finite distance from the Earth and hence their energies cannot be positive or zero. Example 8.8 A 400 kg satellite is in a circular orbit of radius 2 r about the Earth. How much energy is required to transfer it to a circular orbit of radius 4 r? What are the changes in the kinetic and potential energies? Answer initially. EEIRMMGE4 while finally EEFRMMGE8. The change in the total energy is EF, EI882 EEERMRMGRMMGJ1013. 381037 481 9896 XXXXERMGE. The kinetic energy is reduced and it mimics E. Namely, KKF key 3.13 x 109 joules. The change in potential energy is twice the change in the total energy. Namely VVF, V6.25 x 109 JT 8.11. Geostationary and polar satellites. An interesting phenomenon arises if we arrange the value of REH such that T and 8.37 becomes equal to 24 hours. If the circular orbit is in the equatorial plane of the Earth, such a satellite, having the same period as the period of rotation of the Earth about its own axis, would appear stationary viewed from a point on Earth. The REH for this purpose works out to be large as compared to RE, 13224 ETGMRH Greek letter pi 8.43, and for T 24 hours, H works out to be 35,800 kilometers, which is much larger than RE. Satellites in a circular orbits around the Earth and the equatorial plane with T 24 hours are called geostationary satellites. Clearly, since the Earth rotates with the same period, the satellite would appear fixed from any point on Earth. It takes very powerful rockets to throw up a satellite to such large heights above the Earth, but this has been done in view of the several benefits of many practical applications. Figure 8.11 A polar satellite. A strip on Earth's surface shown shaded is visible from the satellite during one cycle. For the next revolution of the satellite, the Earth has rotated a little on its axis so that an adjacent strip becomes visible. It is known that electromagnetic waves above a certain frequency are not reflected from ionosphere. Radio waves used for radio broadcast, which are in the frequency range 2 MHz to 10 MHz, are below the critical frequency. They are therefore reflected by the ionosphere. Thus radio waves broadcast from an antenna can be received at points far away where the direct wave failed to reach on account of the curvature of the Earth. Waves used in television broadcast or other forms of communication have much higher frequencies and thus cannot be received beyond the line of sight. A geostationary satellite, appearing fixed above the broadcasting station, can however receive these signals and broadcast them back to a wide area on Earth. The INSAT group of satellites sent up by India are one such group of geostationary satellites widely used for telecommunications in India. Another class of satellites are called the polar satellites. Figure 8.11. These are low-altitude HL 500 to 800 km satellites, but they go around the poles of the Earth in a north-south direction, whereas the Earth rotates around its axis in an east-west direction. Since its time period is around 100 minutes, it crosses any altitude many times a day. However, since its height h above the Earth is about 500-800 km, a camera fixed on it can view only small strips of the Earth in one orbit. Adjacent strips are viewed in the next orbit, so that in effect the whole Earth can be viewed strip by strip during the entire day. These satellites can view polar and equatorial regions at close distances with good resolution. Information gathered from such satellites is extremely useful for remote sensing, meteorology, as well as for environmental studies of the Earth. 8.12 Weightlessness. Weight of an object is the force with which the Earth attracts it. We are conscious of our own weight when we stand on a surface, since the surface exerts a force opposite to our weight to keep us at rest. The same principle holds good when we measure the weight of an object by a spring balance hung from a fixed point, e.g. the ceiling. The object would fall down unless it is subject to a force opposite to gravity. This is exactly what the spring exerts on the object. This is because the spring is pulled down a little by the gravitational pull of the object, and in turn the spring exerts a force on the object vertically upwards. Now, imagine that the top end of the balance is no longer held fixed to the top ceiling of the room. Both ends of the spring as well as the object move with identical acceleration g. The spring is not stretched and does not exert any upward force on the object, which is moving down with acceleration g due to gravity. The reading India's Leap into Space. India started its space program in 1962. An Indian National Committee for Space Research was set up by the Government of India, which was superseded by the Indian Space Research Organisation ISRO in 1969. ISRO identified the role and importance of space technology in nations' development in bringing space to the service of the common man. India launched its first low-orbit satellite Aryabhata in 1975, for which the launch vehicle was provided by the erstwhile Soviet Union. ISRO started employing its indigenous launching vehicle in 1979 by sending Rohini series of satellites into space from its main launch site at Satish Dhawan Space Center, Sriharikota. Andhra Pradesh. The tremendous progress in India's space program has made ISRO one of the 6 largest space agencies in the world. ISRO develops and delivers application-specific satellite products and tools for broadcasts, communication, weather forecasts, disaster management tools, geographic information system, cartography, navigation, telemedicine, dedicated distance education satellite etc. In order to achieve complete self-reliance in these applications, cost-effective and reliable Polar Satellite Launch Vehicle PSLV was developed in early 1990s. PSLV has thus become a favored carrier for satellites of various countries, promoting unprecedented international collaboration. In 2001, the Geosynchronous Satellite Launch Vehicle GSLV was developed for launching heavier and more demanding geosynchronous communication satellites. Various research centers and autonomous institutions for remote sensing, astronomy and astrophysics, atmospheric sciences and space research are functioning under the aegis of the Department of Space, Government of India. Successive lunar Chandrayaan and interplanetary Mangalian missions along with other scientific projects has been landmark achievements of ISRO. Future endeavors of ISRO include human spaceflight projects, the development of heavy-lift launchers, reusable launch vehicles, semi-cryogenic engines, single and two-stage to-orbit SSTO and TSTO vehicles, development and use of composite materials for space application etc. In 1984 Rakesh Sharma became the first Indian to go into outer space aboard in a USSR spaceship www.isro.gov.in. 198 Physics Summary 1. Newton's law of universal gravitation states that the gravitational force of attraction between any two particles of masses m1 and m2 separated by a distance r has the magnitude Fg(m)m(r)212 where g is the universal gravitational constant, which has the value 6.672 x 10-11 nm2 kg2. 2. If we have to find the resultant gravitational force acting on the particle m due to a number of masses m1, m2, mn etc. We use the principle of superposition. Let F1, F2, Fn be the individual forces due to m1m, 2m, n each, given by the law of gravitation. From the principle of superposition each force acts independently and uninfluenced by the other bodies. The resultant force 4 is then found by vector addition for F1 F2, Fn Vin1 where the symbol Greek letter sigma stands for summation. 3. Kepler's laws of planetary motion state that all planets move in elliptical orbits with the Sun at one of the focal points be the radius vector drawn from the Sun to a planet sweeps out equal areas in equal time intervals. This follows from the fact that the force of gravitation on the planet is central and hence angular momentum is conserved. See the square of the orbital period of a planet is proportional to the cube of the semi-major axis of the elliptical orbit of the planet. The period t and radius r of the circular orbit of a planet about the Sun are related by 3224 rmgts, Greek letter pi where ms is the mass of the Sun. Most planets have nearly circular orbits about the Sun for elliptical orbits. The above equation is valid if r is replaced by the semi-major axis, a. 4. The acceleration due to gravity. At a height h above the Earth's surface 2 EEGMGHRH122 GMRHREE for h, ReGHG1202 HRGGM where 0 recorded in the spring balance is 0 since the spring is not stretched at all. If the object were a human being, he or she will not feel his weight since there is no upward force on him. Thus, when an object is in free fall, it is weightless and this phenomenon is usually called the phenomenon of weightlessness. In a satellite around the Earth, every part and parcel of the satellite has an acceleration towards the center of the Earth which is exactly the value of Earth's acceleration due to gravity at that position. Thus in the satellite everything inside it is in a state of free fall. This is just as if we were falling towards the Earth from a height. Thus, in a manned satellite, people inside experience no gravity. Gravity for us defines the vertical direction and thus for them there are no horizontal or vertical directions. All directions are the same. Pictures of astronauts floating in a satellite show this fact. Gravitation 199b at depth d below the Earth's surface is GGDGMRDRDREE11205. The gravitational force is a conservative force, and therefore a potential energy function can be defined. The gravitational potential energy associated with two particles separated by a distance r is given by RmMgV21 where V is taken to be 0 at r. The total potential energy for a system of particles is the sum of energies for all pairs of particles, with each pair represented by a term of the form given by above equation. This prescription follows from the principle of superposition. 6. If an isolated system consists of a particle of mass m moving with a speed v in the vicinity of a massive body of mass m, the total mechanical energy of the particle is given by RmMgVme21 to that is, the total mechanical energy is the sum of the kinetic and potential energies. The total energy is a constant of motion 7, if m moves in a circular orbit of radius about m, where m, the total energy of the system is a mmGe2 with the choice of the arbitrary constant in the potential energy given in the point 5, above. The total energy is negative for any bound system, that is, one in which the orbit is closed, such as an elliptical orbit. The kinetic and potential energies are a mmgk2 and mmgv8. The escape speed from the surface of the Earth is EER-mgv2 to EGR and has a value of 11.2 km s1. 9. If a particle is outside a uniform spherical shell or solid sphere with a spherically symmetric internal mass distribution, the sphere attracts the particle as though the mass of the sphere or shell were concentrated at the center of the sphere. 10. If a particle is inside a uniform spherical shell, the gravitational force on the particle is 0. If a particle is inside a homogeneous solid sphere, the force on the particle acts toward the center of the sphere. This force is exerted by the spherical mass anterior to the particle. 11. A geostationary geosynchronous communication satellite moves in a circular orbit in the equatorial plane at an approximate distance of 4.22 x 104 km from the Earth's center. 2018 1. Points to ponder. 1. In considering motion of an object under the gravitational influence of another object, the following quantities are conserved. A. Angular momentum. B. Total mechanical energy. Linear momentum is not conserved. 2. Angular momentum conservation leads to Kepler's second law, however, it is not special to the inverse square law of gravitation. It holds for any central force. 3. In Kepler's third law, see Ek 8.1 and T2 KSR3, the constant Ks is the same for all planets in circular orbits. This applies to satellites orbiting the Earth. Ek 8.384. An astronaut experiences weightlessness in a space satellite. This is not because the gravitational force is small at that location in space, it is because both the astronaut and the satellite are in free fall towards the Earth. 5. The gravitational potential energy associated with two particles separated by a distance r is given by VGMMR12 constant. The constant can be given any value. The simplest choice is to take it to be 0. With this choice VGMMR12, this choice implies that V0 is r. Choosing location of 0 of the gravitational energy is the same as choosing the arbitrary constant in the potential energy. Note that the gravitational force is not altered by the choice of this constant. 6. The total mechanical energy of an object is the sum of its kinetic energy, which is always positive, and the potential energy relative to infinity, that is, if we presume that the potential energy of the object at infinity is 0, the gravitational potential energy of an object is negative. The total energy of a satellite is -7. The commonly encountered expression mgh for the potential energy is actually an approximation to the difference in the gravitational potential energy discussed in the point 6, above. 8. Although the gravitational force between two particles is central, the force between two finite rigid bodies is not necessarily along the line joining their center of mass. For a spherically symmetric body, however, the force on a particle external to the body is as if the mass is concentrated at the center, and this force is therefore central. 9. The gravitational force on a particle inside a spherical shell is 0. However, unlike a metallic shell which shields electrical forces, the shell does not shield other bodies outside it from exerting gravitational forces on a particle inside. Gravitational shield